Welcome to the worst reaction video.
Welcome to this video, which is a compilation of my Intro to Proofs course. So this includes all 24 lecture videos in order. So like I said, in my college, this is called the Introduction to Proofwriting. That's the name of the course. It might also be called Elements of Higher Mathematics. I've seen it called that in other institutions. Discrete math, or Bridge to Higher Mathematics, or other fairly similar names.
I cannot wait to be done soon.
So you might have noticed that all of the videos on this channel, Math Major, are ad-free. And that's exactly what the Patreon helps us do. Keep these videos ad-free. What are some other things that the Patreon helps us do? Well, it helps us pay for creation of the between lecture example videos.
That's crazy.
And in the future, we would like to be able to invite other people to contribute their mathematical voice to this channel. Either by making big lecture series or by making example videos that go between my lecture videos. So before you jump into this course, if you can help us out on the Patreon, that would be great. If you can't, that's also okay. Okay, so enjoy this course. This is the first video in a series devoted to a course on introductory proofwriting. So this is generally a course that you might take when studying mathematics just after taking the calculus sequence. Perhaps you've also taken something like linear algebra. So we're essentially covering the material from this great book that I like called The Book of Proof, which is free and open source. You should be able to find it in the link below. Okay, so let's jump into it. So we'll start with the definition of a set. So we're starting pretty basic, and actually we're going to look at some mathematical structures before we start writing proofs. And that's just so that we're familiar with enough things that we can write proofs about. Okay, so a set is a collection of objects, and those objects are known as elements. And the important thing here is the elements can really be anything we'd like. They could be numbers, they could be letters, they could even be sets themselves. And so let's look at some basic examples. So this would be the set containing 3, 4, and 5. So that's a set with 3 elements, and each of the elements are numbers. You can have the set of all words in the English language. So some things inside of that set are like the and blue and tree and so on and so forth. The important thing about these two sets is they're both finite. So this one is clearly finite. It has 3 elements, but there are only finitely many words in the English language. Perhaps that number is quite large, but it is finite. We could also have the set containing 1, 2, 3, 4, 5, 6, 7, 8, so on and so forth. So we'll later call that the natural numbers, or the set containing all real numbers. And those are both infinite sets. They have infinitely many elements. So already we see 2 different types of sets. Sets containing finitely many elements, so finite sets, and sets containing infinitely many elements, infinite sets. And then a quick non-example would be the collection of all sets. So in other words, there's no set containing all sets, but that's like some higher end set theory, which we won't get to in this course.
Okay.
And so let's go back to our definition and notice that sets are made up of elements. Now we'd like a shorthand to describe this relation of being an element of a set. And that shorthand will be this symbol here. So it's kind of like an E, but I just call this the element symbol. And I think that's what most people would call it. So this we would say A is an element of capital A. So there it is there. But you could also negate this statement as well. So this says that X is not an element of the set capital A. And in fact, this symbol can be written in any direction you like. So here we have A as an element of A, like written backwards. But sometimes that might read like this. A contains the element little a. And that's just because we're reading it from left to right. Now let's look at a quick concrete example using this notation over here. So let's take our set A to be the set 1, 3, 5, 7, 9, 11, so on and so forth. So that's going to be all odd positive integers or positive whole numbers. Now let's notice we could say something like this. 1, 3, and then 121 are all elements of A. So this means that 1 is an element of A, 3 is, and 121 is as well. Well, let's notice there are some things that are not elements of A as well. So 1/2 is not an element of A, 2 is not an element of A, and 240, they are all not elements of A.
Okay.
So now let's look at some important sets which we'll see over and over again. So the first is called the empty set, and so we denote it by this symbol. Or less commonly this symbol where we've got curly braces and nothing inside. The important thing is that there's nothing inside. In fact, the empty set contains no elements at all. Then a next important set would be maybe the natural numbers. And so that includes all positive integers, 1, 2, 3, 4, 5, 6, 7, so on and so forth. Sometimes that includes 0 depending on who you ask. But I think mostly for this course we will have it not include 0, just for the sake of argument. Then we've got the integers, that's all positive and negative whole numbers, and then the number 0. So like -2, -1, 0, 1, 2, so on and so forth in both directions. The next we could have the rational numbers, so that's going to be all ratios of integers. So they're of the form p over q, where p and q are integers and q is not 0. Then you could have R, which is all real numbers. In order to carefully construct the real numbers, it's actually pretty tricky. You might learn that in a real analysis class like in the future. Then you've got the complex numbers, which are of the form a plus bi, where a and b are real numbers. And then I is, of course, the imaginary number. So when you square it, you get -1. Okay, so moving on, if we just look at finite sets for a little bit, we've got this natural thing, which is the number of elements in the finite set. And we'll call that the cardinality of a finite set. So to define it, the cardinality of a finite set is the number of elements it contains. And let's say A is a set with 5 elements, then we would write it like this. So it looks like absolute value of A equals 5, but since we're thinking of A as a set, we would read that as the cardinality of A is 5. Now I've seen other textbooks that use this number symbol, like this number symbol is a function acting on the set A, and it gives you the number of elements inside of A. So there are probably some more notations as well that you might want to look out for, depending on which textbook you're reading. So let's look at some examples of sets with different cardinalities. Let's start by noticing that the cardinality of the empty set is 0. And that's because it has 0 elements. That's the definition of the empty set. But if we take the cardinality of the set containing the empty set, we get the number 1. Because this set contains a single element. That element is the empty set. So it's a little bit tricky, but let's recall that elements of sets can be sets. So let's look at maybe a simpler one. What about 1, 2, 7, 100? So that set contains 4 elements. Well, let's look at another one. Let's make it a tricky one this time. So the cardinality of the empty set, and then the set containing the empty set, and then the set containing the empty set and the set containing the empty set. So our goal is to find the cardinality of that set. But the cardinality of that set is 3. So let's notice its 3 elements are the empty set, the set containing the empty set, and then finally this set containing both the empty set and the set containing the empty set. So we have 3 elements. So that means, like I said, its cardinality is 3. Now, what about this? What's the cardinality of the set containing the real numbers and the integers? Well, the cardinality of that is 2. So the real numbers itself is an infinite set. The integers is an infinite set, but we're not asking the cardinality of the real numbers or the cardinality of the integers. This is the cardinality of the set containing each of these 2 sets. But that's all this larger set contains, are those 2 sets. But that means that the cardinality is 2. That set has 2 elements. It just happens that each of those elements are infinite sets. Okay, so let's move on. Now we're going to look at some succinct ways to write down sets without listing all of the elements. And that's called set builder notation. And in fact, we've already used it to describe both the rational numbers and the complex numbers before. So it goes like this. So you'll have two curly braces kind of building the whole thing. And then you'll have this thing broken by a vertical line, or sometimes a colon, depending on the author. And we have it like this. On the left-hand side of the vertical line is an expression, and on the right-hand side is a rule satisfied by that expression. And this vertical line, or the colon, is the word such that. So you read this as the set containing this type of expression such that this expression satisfies a certain rule. Sometimes you do something slightly different and it goes like this. So on the left-hand side, you have the broad shape of an element, and on the right-hand side, you have specific rules that element must follow. Okay, so let's look at some examples. And we're actually going to look at some of the same sets written with set builder notation in different ways, for a couple of these at least. So let's say we've got 2 times n, where n is an integer. So that would be one way of describing a certain set. So notice we've got n as an integer over here, and then we've got 2 times n over here. That means our elements look like 2 times n, as n runs through all integers. Now, we can easily see that this means this is all even integers, and then we can list all even integers with some ... to recognize that there's some pattern here. So maybe this would be ... -6, -4, -2, 0, 2, 4, 6, ... And I think that's clear that we're listing all even integers. So what are some other ways to write this down? Well, you could write it like this. You could say we've got all elements n which come from the integers satisfying the rule that n is even. So that would be more in line with this second way of using set builder notation. Next, we could translate this phrase n is even, or maybe it's a sentence n is even, into something that looks more mathematical. It's not really more mathematical, but it's got some symbols, and that would look like this. So this would be the set containing all integers n, such that n equals 2k for some integer k. That would be another way of describing all even integers. So all even integers are most definitely multiples of 2. That's the definition of an even integer. So that's why this works. So let's look at some other examples. So let's look at the set of all real numbers x such that x squared equals 2. Okay, well that's just going to be all solutions to the equation, the polynomial equation, x squared equals 2. I think probably from a pre-calculus class we know that this is negative square root of 2 and positive square root of 2. So this is a set containing 2 elements. Now what about this? What about the set of all rational numbers x such that x squared is 2? Well, famously, the square root of 2 is not a rational number. We'll prove that later in the course, but you probably know that fact already. So that means no rational number will satisfy this, which means, in fact, we have the empty set. This is just a really fancy way of writing the empty set. So let's look at a couple more. Let's look at all integers z such that the absolute value of x is less than 3. So that means x has to be between -3 and +3, but it's not allowed to include 3. But we're also only looking at integers. So this boils down very quickly to the set -2, -1, 0, 1, and 2. If we take the absolute value of everything within that set, we get something smaller than 3 for sure. But everything outside that set, we would get something bigger than or equal to 3. So let's look at a companion to this. Let's say we've got all real numbers satisfying the inequality absolute value of x is less than 3.
Ooh, that's a
well,
lot.
now we would generally write this in interval notation, something that you probably learned in calculus or pre-calculus. And I would write this as the open interval -3 to 3. Just keeping in mind what I mean by that is the portion of the real line between -3 and 3, not including -3 or 3. So now let's look at some operations we can do between two sets. Now we're going to look at a way to take the product of two sets. So given two sets A and B, we'll define their Cartesian product by the following new set. So we'll call it A cross B, and it'll be the set of all ordered pairs A and B, where A comes from A and B comes from B.
Okay.
Now the important thing here is that A and B don't have to be the same type of set.
This might be a crazy reaction.
You could have A be the set of all real numbers, and B be the set of all vegetables in your fridge. So an example of something in A cross B here would be like the number 5 and broccoli. And then maybe something else would be like the number pi and a pie. So most of the time, both of these will be sets of numbers, but I think it's like a fun example to think about, well, what happens if they're not both sets of numbers? So here's a nice visualization, and this harkens back to thinking about this like the real plane. So let's say we've got a set A. It has two elements, U and V. And then we have a set B, which has three elements, X, Y, and Z. Then we could lay A across a horizontal axis and B across a vertical axis. And then everything in A cross B will be ordered pairs made up of elements of A and elements of B. So this would be A cross B. So for instance, U comma Z, V comma Z, U comma Y, V comma Y, U comma X, V comma X. Those are the 6 elements of A cross B. And in fact, something that we won't prove right now is that if A and B are finite, then the size of A cross B is the size of A times the size of B. Okay, so now let's look at some visualization examples of cross products. So let's start with R cross Z. I think this is a nice example. So this is living within the Cartesian coordinate plane. Notice the Cartesian coordinate plane is just R cross R, or sometimes we write R cross R as R squared. We'll see that later. So it's going to be a subset of this plane. And what subset will it be? Well, notice that each first coordinate can be any real number, whereas each second coordinate can be just any integer. So notice the x-axis is definitely a member of this set. And that's because the first coordinate is a real number x, and the second coordinate is the integer 0. Maybe I'll underline this in yellow just to show that we're graphing this in yellow. You could also maybe have this portion right here, which would be of the form, maybe we'll say y comma 1. We could have something down here, which is y comma -1, or real number comma -1. We could have something up here, which would have a second coordinate of 2. Down here would be a second coordinate of -2, and so on and so forth. So it's this infinite collection of lines. Okay, so let's look at a next one. Let's say we've got n cross n. So again, that naturally lives within the Cartesian coordinate plane, r squared, which is r cross r. So we might as well write it as a substructure of that larger structure. So notice here, all of the first coordinates are natural numbers, and all of the second coordinates are also natural numbers. So we would have like 1 comma 1, that would be an element. And then maybe 2 comma 1, 3 comma 1, 4 comma 1, 5 comma 1, 6 comma 1, and so on and so forth. We could also go this way. So this would be 1 comma 2, 1 comma 3, 1 comma 4. And as you see, we're filling in all of these points. So this is some sort of like lattice. And it's going infinitely in both directions, including like up like that. So that would be n cross n. Now let's look at another one. Let's look at maybe z cross the half open interval 1 to 3. Let's say it includes 1, but it does not include 3. So this is a substructure of the real numbers. So what would that look like? So notice all of the first coordinates are integers. All of the second coordinates are real numbers between 1 and 3. So that would be something like this. So we could go here to 1, up to here to 3, and it would be that. So this would be like 0 comma x, where x comes from 1 comma 3. But then this first coordinate can be any integer, like we pointed out. So it could be 1, 2, 3, 4. It could be -1, -2, -3, -4, so on and so forth. So pushing that out, we've got this like infinite collection of half open line segments, which are all parallel to each other like that. So that would be an example of that set.
Okay.
Okay, let's look at one more. Let's maybe look at the set 1, 2, 3 cross the set -1, 0, 1. So again, we'll put this in the Cartesian coordinate plane, but this is only going to have 9 elements based off the fact over here, which we're not proving just yet, at least. We'll prove it later. So notice the first coordinates can be either 1, 2, and 3. The second coordinates can be -1, 1,
I mean,
or
it seems
0.
quite obvious.
So here would be the fact when the second coordinate is 0, you would get those 3 points. If the second coordinate is 1, you would get those 3 points. If the second coordinate is -1, you would get those 3 points. So we get those following 9 points. So one of the important things for each of these is that we drew them all as substructures of the real plane R2 or R cross R. So that really motivates us to define what it really means to be a substructure or a subset. So let's do that. So if we've got two sets A and B, we say that A is a subset of B if every element of A is an element of B. And we'll write like this: A is a subset of B. But there is some contention among math people whether or not we should have this line down here. I'm really agnostic on it. I don't care one way or the other. But sometimes people use A as a subset of B without the line down there. And sometimes this means that B cannot just be all of A. So B has some elements that don't contain A. Or sometimes these two symbols can mean the same thing. Sometimes, if you want to really hit home that A does not contain all of the elements of B, in other words, B has some things that are not in A, you would write it like this. So A is a subset of B, but a proper subset. So you'd put a cross through that line. But all of these notations vary. So you just have to think on. But you should be able to pick up by context which the book you're reading is using. Okay, so let's look at some examples. So if we have any set A, well, we automatically know two subsets. And one of those subsets is the empty set. So the empty set is a subset of A. And the set itself is also a subset of A. Now, you might think that this means that every set has two subsets, but that's totally not true because the empty set only has itself as a subset. So, and that's because A would be equal to the empty set in this case.
Cheeky
then
bugger.
We also have this nice string of numerical subsets. So we've got the natural numbers as a subset of the integers, which is a subset of the rational numbers, which is a subset of the real numbers, which is a subset of the complex numbers. And in fact, you can push that way if you want to the quaternions and other more obscure things if you're psyched.
No thanks.
You could also maybe look at this. So the set containing -1, 0, 1 is a subset of the closed interval from 1 to, or from -1 to 1. You could also maybe look at the set Z cross R as we saw in a picture previously, and that will be a subset of R cross R, which is sometimes called R squared or R2. And now all of this really brings us into an important definition, which will fit in here, and that is the set of all subsets. And that's called the power set. So the power set of a set A is the set of all subsets of A. And we denote it with the following notation. We've got this calligraphic P of A. So we read that as the power set. That opens us up to some more examples. So the power set of the empty set is simply the set containing the empty set. So let's recall up here, if A is any set, then the empty set is a subset and that set is a subset. Well, in this case, those two overlap. Then we could have the power set of the singleton set X. So that's just a set containing a single element. We'll call it X. So that's going to be the empty set, and then the whole set, the singleton containing x. Then we can move on, maybe the power set of the set containing A and B. So that's sometimes called a doubleton, a set with two elements.
A, B, and
so
AB.
This one's a little bit more interesting. You would have the empty set, that's a subset. You would have the singleton A, the singleton B, and then the whole set A and B.
Boom.
Great. And all of this brings us to a fact that's pretty similar to the fact that we saw with the Cartesian product on the size, and that would be the size of the power set of A is 2 to the size of A, or the cardinality of the power set of A is 2 to the power of the cardinality of A. And right now this only makes sense for finite sets, but in fact you can make some meaning out of this for infinite sets if you want to maybe dive deeper. Well, let's maybe check this in these two examples, or three examples. So here we've got the empty set that contains 0 elements. 2 to the 0 is 1. The power set has exactly 1 element. What about this? This set contains 1 element, but the power set contains 2 elements. That's 2 to the 1. This set contains 2 elements, but the power set contains 1, 2, 3, 4 elements. That's 2 to the 2. So this fact seems to hold for these basic cases, but we'll prove that it holds in general later. Okay, so that's about enough for this first video. I'll leave you with some warm-up exercises. So here are 2 warm-up problems, each with a couple of parts to work on based off what we saw today. So the first is to list the elements of the following sets. So these are given in set builder notation. So first we've got all integers x such that the absolute value of 7x is less than 24. Next we've got all real numbers x such that 7x squared minus x cubed equals 12x. Finally, we've got all capital X inside the power set of the set containing 1, 2, 3 such that the cardinality of x equals 2. Then next up, we've got some subsets of the plane to sketch. So the first is everything of the form x comma x plus y, where x is a real number and y is an integer. Next, we've got the doubleton 0, 1. So the set containing 0 and 1 cross the half open interval 0 to 1, not including 1. Then next, we've got the closed interval 1 to 5 cross the set containing all ordered pairs x and y from real numbers such that x squared plus y squared equals 1. So this last one is interesting because it's 3-dimensional.
No thanks.
And that's a good place to stop. This is the second video in a series devoted to proofwriting and in fact a course that I'm teaching in proofwriting at my college. And so in the previous video we looked at the very basics of sets, and here we're going to look more at the basics of sets. And all of this is really just to give us some tools to work with so we can start writing down some proofs. So now let's start by looking at the intersection and the union of two sets. So let's say we're given sets A and B. We can define their union, which we read this as A union B, to be everything X such that X is in A or X is in B. So union is like the conjunction or. And there's a typical way to draw this or visualize this via something called a Venn diagram. So you think about this circle here being everything in A, this circle here being everything in B. So notice we're shading everything in A or everything in B, the total of A and B. Then the intersection, which we read as A intersect B, that's going to be all X such that X is in A and X is in B. So intersection is like the conjunction and. So here we've got our same picture, but now we just have this sliver between A and B. So notice everything within this sliver is in A and it's also in B. Whereas up here, we definitely have things in A and B, but we've got elements over here that are only in A and elements over here that are only in B. Then finally, we'll have the difference between two sets. And so A minus B is equal to all X that are in A, but they're not in B. And I use this slanty minus sign, but some authors use this just straight minus sign. So if you want to draw that, well, notice we've got this drawing right here. We have A and B. And over here, this shading in yellow is everything in A that's not in B. So that excludes the intersection because those elements are in A and B, but you don't want them to be in B. So let's look at some simple examples first before we look at something a little bit trickier involving maybe sets of real numbers. So let's say we've got these three sets. A, which has A, B, C in it, so little a, little B, little c, little d. Let's say capital B has C, D, E in it, and capital C has E, F, G in it. So let's calculate A intersect B. So for that, we're going to look for everything that is in both sets. So A and B are only in capital A, so we don't use those. C and D are in both, though. So A intersect B is just the doubleton C and D. Now notice we do not include E because that's only in the set B. Now let's look at B union C. So that'll be everything in B and everything in C, or everything in C. So it's a little bit tricky because naturally you kind of want to put the word and there, but it's not really as precise as we want to be. So that will include C, D, and E. So we've got C, D, and E. Those are in B. And then we go over here and look at C. Notice C also contains E. Well, we've already got that written down, so we don't need to write it down twice. And then we'll have F and G. Now there is a way of writing down E twice, something called the disjoint union, but we won't cover that just now. Now let's look at this. We've got A union B intersect C. So later we'll be able to rewrite this, maybe by distributing the union over the intersection, but we're not going to do that just yet. So let's do this maybe from inside out. So we'll do these parentheses first. So that'll be A union, and then B intersect C is simply the singleton E. That's because that's what's in common of B and C. But now let's go up and look at A, and A does not contain E. Okay, but it contains A, B, C, and D, and since we're doing a union, that's okay. So here our set is A, B, C, D, and E. We get the first four from the set A, and then the last one from our intersection. Now let's look at this set difference, A minus B. So there we're looking for everything in A that is not in B, but that clearly is just little a and little b. Now we've got another one of these. We have the Cartesian product of A and B minus C. So that's going to be the Cartesian product of A with, well, let's see, B minus C is the doubleton CD. So we've got a set containing 4 elements, Cartesian product with a set containing 2 elements. So that should give us a set containing 8 elements. And those 8 elements are ordered pairs. The first entry comes from A, and the second entry comes from this doubleton CD. So we'll have something like this. So maybe AC, BC, DC, and CC. So that comes from choosing A, B, C, and D and pairing it with C. And then we could choose each of these and pair them with D as well. That'll give us our 4 other elements. So we'll have AD, like I said, BD, like I said, CD, like I said, and DD, like I said. And for some weird reason, I put these like, maybe they're not really out of order because the order doesn't matter, but it's not the natural way that we would have written that down. I think my brain just did something weird there. So now let's look at B minus A. Well, we already calculated A minus B and saw that it was A comma B, and in fact our subtraction is not going to be commutative here. Well, normal subtraction is also not commutative. So here we're looking for everything in B that is not in A. Well, that's just going to be the singleton E. So here we've got the singleton E. So here are 4 examples of these set operations on sets of real numbers. And we'll approach these by making a bit of a picture of what's going on. I think that'll be a nice way to visualize what's happening. So let's get our real number line for this first one, and let's shade these as I'm color coding right here. So let's see, we'll need 4 numbers to make sure we know what's going on here. We'll need 0 to 1. Actually, now that I look at this, this should have been 10, although that will also work. So we've got 0, 7, 10, and 12 are the important points for this problem. Now let's shade everything between 0 and 10. I'll shade it below just so it doesn't get in the way. So we're gonna include 0 and 10, so we need closed circles. Then everything between 7 and 12. So let's color code that orange. And now we're looking for the intersection of those. So since we're looking for the intersection of those, we need numbers that are in both of those sets. Well, I think that's pretty clearly going to be everything between 7 and 10. And we're allowed to include both 7 and 10. So here we can make this nice simplification to the interval 7, 10. Now let's look at this next one. We've got the closed interval -1, 6 minus the closed interval 2 to infinity. It's closed because this infinite thing doesn't make it open on that side. It actually makes it open and closed on that side. So let's do the same thing here. Maybe we'll keep our same color coding. So we've got orange there, we have yellow here. So the important points to write here will be -1, 2, 6. So let's write -1 here, 2 here, and 6 here. And I don't really need to worry about scales. This is just to kind of get an idea of what's going on. Okay, so -1 to 6 will be this interval as I'm shading in yellow. And then let's see, 2 to infinity will be this thing that I'm shading in orange. And I'll put an arrow to say that we're going forever. And now notice we're doing the set minus here, the set difference. So we want everything in this yellow set that is not in this orange set. So that's going to include things like -1 all the way up to the number 2. But in fact, it will not include the number 2 because 2 is included in this other set. Yeah. So in the end, we get that red shaded bit, but we can rewrite this as the half open interval from -1 to 2.
Oh, my days, I got that correct.
So now let's look at this one. So here we'll have important points of -3, 0, 3, and 5. So let's see, -3, 0, 3, and 5. Again, let's color code just to keep everything consistent. And we'll have -3, 3 looks like this, whereas 0 to 5 looks like this. And now we're trying to find the union there, but notice the union is going to include everything between -3 and 5, not including the endpoints. Oh, I got my colors off a little bit, but that's okay. In fact, maybe these are better color choices because yellow and red makes orange. Okay, so putting this together, we see that we have the open interval -3 to 5. Okay, so now let's look at this next one. We have the entire real number line minus this interval from -1 to 1. So let's get -1 and 1 on this. So -1 and 1. And then we'll see that the real line will just be everything here in yellow, whereas this -1 to 1 will be this orange that I'm putting underneath. So we want to take the orange bit away from the yellow bit. So we cannot include -1, we cannot include 1, but we can include everything branching off from that. And then probably the easiest way to write this is as a disjoint union of two open intervals.
Okay.
So we'll have -infinity to -1 for this left-hand bit, union 1 to infinity. Okay, so let's keep going. Now that we know about the set difference, the next logical thing to look at is something called the complement of a set. But in order to talk about the complement of a set, we need to know what context we're working in or what universe we're working in. So I have this little remark to kind of describe what I mean by this. So depending on the context of the problem you're working in, we may want to define something called a universal set that contains every set that we might be interested in as a subset. So here are some standard examples of universal sets, although this list could be much larger. So you could have all of the numbers 0, 1, 2 up to n. That would be like a standard finite version of a universal set. You could also maybe have the set of all letters in the English alphabet, or I guess it would be the Latin alphabet. You could have the set of natural numbers, integers, rational numbers, real numbers, or complex numbers as well. And as you might imagine, you can also have like R2 or maybe Z cross R or whatever. You can really work with any universal set you want. These are just some standard examples. Okay, now that we've got that taken care of, let's suppose that we have a universal set U and A is a subset of U. So let's say for a certain class of problems we're working on, we don't need to consider anything larger than a certain universal set. Then the complement of A, sometimes you would actually say the complement of A in U, but we'll just say the complement in A, the U is understood. We'll write that as a bar, so a bar over it, and that is u minus a. But there's some different notation depending on which textbook you're looking at. You could also have a complement, so we've got that superscript c, or sometimes a prime. I bet there's more notations as well, but as I've seen, these are the most common. Okay, so let's look at some examples. So let's say we've got a universal set, which is all natural numbers, or I guess I should say all integers between 0 and 10. And then we've got a is all of the even integers in that set, and b is all of the powers of 2 in that set. So 1 is a power of 2 because it's 2 to the 0. Now let's calculate a few things. So let's calculate a complement first. So that's pretty straightforward. We have 1, 3, 5, 7, and 9. Those are all the odd numbers. That's pretty obvious. All of the complement of all of the even numbers should be all of the odd numbers. And then b complement will be, let's see, we'll start at 0, and then we get 3, 5, 6, 7, 9, and 10. So those are all of the non-powers of 2. So now let's do some combinations of this complement action with union and intersection. So let's look at the intersection of a complement and b complement. Okay, so we need to find numbers that are in both of these sets. So 1 is only in this first set, 0 is only in the second set, but 3, 5, 7, and 9 are in both of them. So 3, 5, 7, and 9. Now let's do something a little different. Let's take a union b and then complement that. So we're taking the union before taking the complement. So let's take this union first. So we'll have 0, 1, 2, 4, 6, 8, and 10. So that's a combination of all of the even numbers and all of the powers of 2. Now let's complement that and see what we get. Notice the first thing that we're missing is 3. I guess I should say we're looking for things in our universal set that are not here. So we're missing 3, we're missing 5, 7, and 9. Now you've probably noticed that these two sets are equal to each other. And in fact, this is true for any set. And that's something that we'll prove like in the future. Okay, now let's look at another example. Let's maybe look at the example where our universal set is all real numbers. And let's do something like this. Let's find the complement of the interval between 1 and 12, including 1 and including 12. So that's pretty similar to a problem we did on the previous board. So we want everything outside of this interval. So that's going to be everything from minus infinity to 1. We're not allowed to include 1. Then we can pick back up at 12 without including it and go forever. So that would be the complement in this case. So what about this? What about the complement of the integers? Well, the complement of the integers can be written as an infinite union. So notice that the union So notice that we'll need the open interval between 0 and 1. We have to take out 0 and take out 1. But then we'll also need the open interval between 1, 2, 2, 3, and so on and so forth. And we also have to go backwards. So this would be the open interval between -1 and 0, ... So we've got this infinite union of things like that. And actually the necessity of writing this complement of integers as an infinite union brings up the next thing that we'll look at, which is indexed sets. Now we're ready to look at the notion of an index set. So how this works is we have any set I, and it's really important that we can actually have any set I as our indexing set. So this capital I, like I said, will be called our indexing set. And then for any element little I in capital I, there is some set that we can attach to that element, and we'll call that set A sub I. Okay, so the logical thing to do would be to talk about intersections and unions over these indexing sets. And the notation for that goes like this. So this would be the intersection over all I of the A sub I. And this is all x such that x is an A sub I for all
I can't really pause this for too long,
I.
so I won't be able to upload
So you can think of a for all conditional as being like a bunch of ands stringed together. And so this could in fact be like some sort of continuous and state. So x is in A1 and A2 and A3 and A4, so on and so forth. But the important thing here is that I doesn't have to be a discrete set. It can be a continuous set, like for example, the real number. And then the the union over all I in I of AI is all x such that x is in AI for some I in I. So it only has to be in one of them. It could be in 1, 2, or 3. It could be in all of them, but it only has to be in one of them in order to be in the union. So let's look at some examples. So let's start with I being natural numbers. That's kind of a classic indexing set. And then a sub I is all of the numbers between I and I squared. So notice that a sub 1 is going to be everything between 1 and 1 squared. Well, that's just the number 1. Notice that a2 will be everything between 2 and 2 squared. Well, that'll be 2, 3, and 4. A sub 3 will be everything between 3 and 3 squared, so that'll be everything between 3 and 9. Well, now we can immediately see that the intersection here will be empty. And we'll write it like this. So the intersection from I equals 1 to infinity of a sub I is the empty set. So when you've got an indexing set of the natural numbers, it's kind of classic to write the intersection like this. I equals 1 to infinity instead of like over all I in the natural numbers, although either one would be correct. And we see that's the empty set because there's no single number that's in all of those sets. In fact, the number 1 is only in A1. It's not in any of the others. And then what about the union? Well, I think it's pretty clear here that the union is just going to be all natural numbers. And that's because the number I is in A sub I. So let's say we want 45. Well, 45 is going to be in A sub 45. It's going to be in something else, but it will be in A sub 45. So that allows us to get all of our natural numbers. Now let's look at our second example. So we've got I as the integers, and then A sub I is the open interval from negative I to I. Actually, I'm going to change this a little bit. Let's change this to the open interval between I minus 1 and I. I think that's a little bit more interesting, and it'll go back to a previous example. So now maybe let's look at a couple of examples. So a sub 1 will be the open interval between 0 and 1. A sub negative 3 will be the open interval from negative 4 to negative 3. And again here, if you take the intersection, so the intersection from I equals minus infinity to infinity of a sub I, that's still the empty set. And that's because these in fact don't overlap at all. But what about the union? So the union over all I and z, and I'd like to point out that if you're working with an indexing set of the integers, it's kind of similarly typical to write our indexed union as intersection in one of these two ways, but both of them are fairly typical. Okay, so the union here will in fact be R minus the integers. And I think that's pretty clear just by the structure of how this is going. Well, you can have a finite indexing set as well. What if our indexing set is the set 1, 2, 3? Then we've got 3 sets A1, A2, and A3. So let's notice in this case, the union from I equals 1 to 3 of AI, well, that'll just be the union of those 3 sets. I think that's going to give us the numbers 1, 2, 3, 4, 5, 6, 7, stop. So all of those numbers right there. And then we've got one last example where we've got a continuous indexing set, which is the closed interval 0 to 1. I'm actually going to do that more properly on a clean board. So now we're going to look at our example where we have a continuous indexing set. Here the indexing set is all real numbers between 0 and 1. And typically, if you have a concrete continuous indexing set, you'll use alpha as your indexer. Now, if you're working abstractly, you'll generally use the I, although it's not right or wrong to do either. Okay, so for some real number between 0 and 1, we'll define a sub alpha to be the rectangle alpha comma 2 cross product with 0 comma alpha. And so like I said, this is going to be all real numbers between 0 and 1. Those are our possible values of alpha. Okay, so let's write down a couple of these sets and then we'll make some pictures. So probably most interestingly is to look at A0 and A1 because those are the endpoints. So notice that A0 will be 0, 2 cross 0, 0. But 0, 0, the closed interval, is just going to be the singleton 0. So we have 0, 2 cross the singleton 0. Now let's maybe look at A1. So that's going to be 1, 2 cross 0, 1. So there we've got a nice kind of biggish rectangle. Then let's look at something in the middle. We may look at some more things in the middle, but let's look at A1 half. So that's going to be the closed interval half 2 cross the closed interval 0, half. Okay, so now that we've got those written down, let's look at a bit of a picture. So along the x-axis, we need everything between 0 and 2. So let's maybe put 1 here and 2 here. Then along the y-axis, we'll just need things between 0 and 1. I won't keep my scale constrained here, but I think that's okay. Okay, so now let's color code this a little bit. So let's say that A0 will be drawn in yellow. So all of the x coordinates go between 0 and 2, but all of the y coordinates are just simply the number 0. So that means we've got this line segment here that's along the x-axis or along the horizontal axis. So that's our A0 set right there. It's that line segment. Now let's look at A half. So that's going to be a rectangle. Notice the x values are between half and 2, and the y values are between 0 and half. So let's go to y equals half right here, x equals half right here, and we're allowed to have this rectangle. So that right there would be our A1 half. Next up, let's draw A1. So A1, all of the x coordinates can be between 1 and 2, so just between 1 and 2, and then all of the y coordinates are between 0 and 1. So that'll be something like this. So there's a nice picture of A1. And then maybe to fill in just a little bit, let's calculate A3/4, and then maybe as a bit of an exercise, you could do A1/4 or some more of them if you'd like to. So A3/4, all of the x coordinates are between 3/4 and 2, whereas all of the y coordinates are between 0 and 3/4. Let's maybe make this in this nice magenta color. So let's see, between 3/4 and 2, those are our x values. So 3/4 is about there, and 0 and 3/4, so those are all of our y values. So we've got a rectangle that looks something like this. Okay, nice. So I'd say it'd probably be a nice exercise to play around with this some more. I think this makes some nice pictures. Okay, so now let's look at some bigger ideas before we leave you with some warm-up exercises. So now we're going to look at a few bigger ideas. The first is the well-ordering principle. So that says that every non-empty set of positive integers has a least element. And this should be quite clear. So notice if we try to make a non-empty set of positive integers like 3, 4, 7, 1001, it most definitely naturally has a least element. In this case, it's 3. This is not true over the real numbers or even over the rational numbers, though, if you take positive rational numbers. Let's consider the set of positive rational numbers: 1, 1/2, 1/3, 1/4, 1/5, so on and so forth. So all of the reciprocals of natural numbers. This does not have a least element. You can always find one of these fractions that's smaller than anything else that you want. So something that follows from the well-ordering principle is called the division algorithm. And that says for all integers a and b, there are unique integers q and r such that a equals b times q plus r, and r is between 0 and b. It's allowed to be 0 but not allowed to be b. So this is your typical division with remainder that you learn in grade school. So for instance, 14 is equal to 4 times 3 plus 2. So if you divide 14 by 4, you get a quotient of 3 and a remainder of. So that's what's going on there. And so I'll maybe like start the sketch of the proof of that up at the top here, but we won't really finish it off. We'll do the proof of that a little bit more carefully later. So let's say we fix A and B, and now we're going to consider the following set. And that set will be made up of everything of the form a minus b times x, as x ranges through all integers, and then we'll take that set and then intersect it with all non-negative integers. So in other words, this thing right here has to be bigger than or equal to 0. Now we'll call that set S. And so maybe the step number 1 here is to show that S is non-empty. Well, clearly S is a set of natural numbers. Well, not exactly. It could include 0, and we're not taking 0 to be a natural number, but the well-ordering principle is satisfied by the positive or non-negative integers. So that's okay. So S is not the empty set. You can check that fairly easily. When we do the proof carefully, we will do that. Then next, we'll take the minimum element of S to be R and let Q be the corresponding x that makes that r. But then let's notice that we'll have r is equal to b minus, or is equal to a minus b times q, which gives us this equation down there. Now we just have to check that r is the correct size and the uniqueness. But like I said, we'll do that more carefully later when we're into our proofwriting part. Okay, so finally I want to talk about something called Russell's paradox, which is related to this fact that the collection of all sets is not a set. So it's going to consider the following collection of objects, and that will be A. And it's made up of all sets X such that X is not an element of its set of itself. So notice that A is non-empty. We can find things inside of A for sure. Notice the empty set is an element of A. That's because the empty set is a set and it doesn't contain anything. So that means it cannot contain itself. Then a bunch of other stuff is inside A as well. In fact, all maybe typical sets are inside of A. Like Z is an element of A. So Z contains all integers, but it doesn't contain the set of all integers. But can we find something not inside A? And we can, but it's kind of a crazy object. So notice if we set the set B equal to this kind of infinite collection of empty boxes, then this B is definitely inside of itself. Notice it's right there inside of itself. But since it's an element of itself, that means that B is not an element of A. So now that really brings us to the following natural question, and that is A an element of itself? Okay, so let's see. So case number one. So case number one is yes, A is an element of itself. But notice in order to be inside of A, you're not allowed to be an element of yourself. So being an element of yourself implies that you are in fact not an element of yourself if you're this whole set A. Okay, so now let's look at case two. So case one is impossible because it brings us to this contradiction. Notice we've got these two feuding ideas. So case number two will be no. But if it's not an element of itself, then by the definition of A here, it means it is an element of itself. But again, that's another contradiction. But that means we can't determine if A is an element of itself. And like I said, this is a paradox, but this is a paradox that's connected to the collection of all sets not being a set. And so while we're doing really, really basic ideas of sets right now, we're not doing this like higher end set theory in this course. Okay, so I think I'm gonna leave everyone with some warm-up exercises. So here are two nice warm-up exercises based off what we've done. So let's start with two sets A and B. They're both doubleton. A contains 1 and 2 and B contains 2 and 3.
Oh boy, I'm having
Then there are
so
these
much fun.
6 things to calculate.
So
A cross
recording.
B intersect B cross B.
Well.
The power set of A intersect the power set of B. A cross B intersect B. The power set of A union B. A cross B set minus B cross B. And then finally the power set of A union the power set of B. Then next let's simplify the following intersections or unions of indexed sets. So the intersection over all real numbers alpha of the singleton alpha cross 0, 1. And then the next is the union over all natural numbers, or sometimes you would write that as the union of I going from 1 to infinity of the closed interval from I to I plus. And that's a good place to stop. This is the third video in a series devoted to an introductory course of proofwriting. And previously we looked at the very basics of set, and now we're going to look at mathematical statements, mathematical open sentences, as well as a bit of logic. Okay, so let's look at a definition first. So a mathematical statement, or sometimes just a statement, is a sentence that is either definitely true or definitely false. And this can be a sentence written in English, or it can be a sentence written in mathematical notation. So let's look at some examples. So for this first one, it says, if a square has a side length of x, it has an area of x. So that's a true statement, just by the standard area formula for a square. Next up, we have every odd integer is 1 more than an even integer. That's also a true statement, just by the simple characterization of even and odd integers. So next up, we've got 3 that are written in mathematical notation, but we can read these as complete sentences. We have have 3030 is a natural number. In other words, 3030 is an element of the natural numbers. We have the natural numbers form a subset of integers. And next up we have 3/4 is a rational number, or 3/4 is an element of the rational numbers. And again, these are all true mathematical statements. Now for some false mathematical statements. They're still mathematical statements though, as long as you have a sentence which is definitely true or definitely false, it is a mathematical statement. So the first is the square root of 2 is a rational number. So this is false. It's well known that the square root of 2 is irrational, and we'll prove that later in the course. Next is the set of all integers is a finite set. So the set of all integers is fairly clearly an infinite set. Next up, all triangles are right triangles. Well, I can think of a lot of triangles that are not right triangles. For example, equilateral triangles, those are not right triangles. And then next, every quadratic equation has 2 real solutions. So this is also false. You could have a quadratic equation with 1 real solution, a so-called repeated root, or you could have a quadratic equation with 0 real solutions. For instance, x squared equals -1. That doesn't have any real solution. And now I won't write these on the board, but some non-examples of mathematical sentences would be something like for all integers n. So that's just a phrase. That would be the setup for a mathematical statement. Or what is the solution to x squared plus 3x equals 1? But a question is neither true nor false until you start writing down the answer, but the answer would turn into a mathematical statement. Okay, so now I want to go on to the standard strategy of naming mathematical statements. So now moving on, it's fairly typical to name mathematical statements. That sets up maybe a calculus of logic, which we'll see later. So general names occur like at the 2/3 point of the alphabet, like P, Q, and R. Further, sometimes these statements depend on variables. And in fact, if the truth of that statement depends on what the input of the variable is, it's technically not a statement anymore. It's something called an open sentence. And that's a bit more interesting when we have this variable dependence. So let's look at some examples. So let's say the statement every differentiable function is continuous. We could call that statement P. So we've named that sentence. The next, if we said Q was the statement the function f of x equals sine x is unbounded, that would be the name for that sentence. We've named that Q. Now I'd like to point out that P is most definitely true. Like in a Calculus 1 class, you learn that if a function is differentiable, then it's continuous. Q seems like it would be false because the function f of x is bound between -1 and 1. And this is actually where context matters. So if x is a real number, then this is a false statement because sine of x, like I said, is bound between -1 and 1. But if x is allowed to be a complex number, then this function is actually unbounded, and this is true. So the truth of Q depends on the context that we're working. And then here's another statement, R, and that says if P and Q are prime numbers that are 2 digits or more, so they are bigger than or equal to 11, then P to the 4th minus Q to the 4th is a multiple of 240. This is a nice, fairly elementary number theory problem. So here are some open sentences. So they become statements when we plug in values for the variable. So here we have P of x, and the statement or the open sentence is x is an even integer. So notice we cannot determine the truth or the falseness of this open sentence without plugging in a number. So notice if we plug in the number like 2,142, then we get something which is most definitely true because 2,142 is even. But if we were to plug in something like 137, we would get a false statement because now the statement reads 137 is an even integer. Now, furthermore, if we were to plug in something like 1/2, we would also get a false statement because 1/2 is not even an integer. Now let's look at another one. Let's say we have r of fg. So in this case, it's depending on 2 variables, and those variables are functions. And this open sentence says the function f is the derivative of the function g. So the truth of this will be determined once we plug functions into this. And sometimes we'll have something that's true, and sometimes we have something that's false. So let's notice if we plug in 2x plus 1 and x squared plus x, we get a true statement. That's because the derivative of x squared plus x is most definitely 2x plus 1. But if we plug in sine of x and cosine of x, we get a false statement. And that's because the derivative of cosine of x is in fact equal to negative sine of x. So we're almost there, but we're off by a sign.
I did actually know that
pretty
one.
good idea of mathematical statements, open sentences, and the like. Let's talk about how to combine two mathematical statements. Now we're going to look at some operations that we can have on mathematical statements. So there are four main ones that we want to start off with: the and statement, the or statement, the not statement, and the implication statement. So let's start off with and. So the notation is this wedge shape, and you read this as P and Q. And so in shorthand, you'd have this P wedge shape. Then we have this or, which is maybe this upside down wedge shape or this V shape. And you read this as P or Q. Then here we have this little squiggle. That's our not operator. So squiggle P will be the negation of the statement P. Now later we'll talk about how to negate complicated statements, but for now we're just going to be negating fairly simple statements. Then we've got our implication or our conditional. And so we read this as P implies Q, or sometimes if P then Q. But in fact there's lots of other ways to write this down as well, which we'll see later in the video. Okay, so let's start with some fairly simple examples. So let's say we've got three statements. P is the statement 3 is odd. So notice this is definitely a true statement. So I'll write a capital T for true. And then the second statement, Q, is 12 is odd. This is most definitely a false statement. So I'll write a capital F for false. And then finally, I've got a statement R, which is for all x, which are real numbers, the absolute value of the sine of x is less than 1. Well, that's equivalent to saying that sine of x lies between -1 and 1, as long as you have a real input. And from a trigonometry class, which you probably have in your past, that is a true statement. So now let's look at some combinations using these operators. So let's start by looking at P and Q. So we'll write this out in words. That says that 3 is odd and 12 is odd. So we could maybe simplify that a little bit to 3 and 12 are both odd. That's maybe a more natural way to write this down. But notice this is most definitely a false statement.
What?
Because for this to be true, you would need both of these numbers to be odd, but only one of them is odd. So here we have a false statement. Great. And later we'll talk about how the truth or falsehood of a mathematical statement interacts with these operations. Now let's look at this. P or Q. So that would be 3 is odd or 12 is odd.
I think that's true.
Now we could maybe write this in a more natural way as well. And that more natural way might be something like this. At least one of 3 or 12 is odd. So since 3 is odd, we're good to go because at least one of those two numbers is odd. So this is a true statement. Now let's maybe practice a negation. So maybe this is the simplest negation to practice and it's the most illuminating. So if we do not Q here, we would get the statement 12 is not odd. And since there's a word for not odd in this case, we probably want to use that, and that would be even. 12 is even. And that is a true statement. So as expected, if we negate a false statement, we get a true statement. And in fact, if we negate a true statement, we'll also get a false statement. Let's see that here. If we negate P, we'll get something like this.
There's just no way that is true.
We'll have 3 is not, but notice that's the same thing as saying that 3 is even. And like I said, that is a false statement. So the negation of a true statement is a false statement. Okay, let's look at one more real quick. Let's maybe look at P and R. So P and R would be the statement 3 is odd and for all real numbers x, so x element of real numbers, the absolute value of sine x is less than or equal to 1. So there's no natural way to combine these like we did before because they're two different types of sentences. One is about a number and one is about this function sine of x. So we would just leave the writing like this. But let's notice that this is a true statement. So it seems like when we connect a true statement And a true statement with an and statement, we get a true statement. All right, so that's good. So now I'm going to introduce something called a truth table for making like quick calculations on these logical operations. So a truth table is like an operation table, or maybe like a multiplication table for mathematical statements. But the multiplication depends on what operation we're interested in.
I've never told the truth in my life.
Like it could be the and operation, the or operation, the not operation, or as we'll see in just a bit, this implication or conditional operation. And so the idea here is we want to populate this left-hand side with all different possibilities of truth or falseness of Q and P interacting with each other, and then record the output of those operations on the right-hand side. So let's look at our and table. So we need to look at the possibilities when P is true or false. So I'll have 2 trues for P and 2 falses for P. And then here I'll alternate the truth and the falsehood of Q. And now let's notice doing that strategy allows us to combine every possibility for P with every possibility for Q. Okay. And now let's be inspired by what we saw in the logic of the sentences, those concrete examples from the last board, to fill this in. So we have a true statement and a true statement must be a true statement. We have a true statement and a false statement must be a false statement. So the and operation requires both of the statements to be true. So that means a false statement and a true statement will give us a false statement, and 2 false statements will give us a false statement. Now let's look at this other one, this or operation. So we'll fill this in the same way. We have true, true, false, false, and then we have true, false, true, false. It's a little bit trickier when you have 3 inputs, but I'll let you think about a systematic way of covering all of those. So if you have 2 true statements and you combine them with an or, you get a true statement. So that would be something like
true,
2
false,
is either an even integer or it is an odd integer. Well, it's definitely one of those, so that is a true statement. Then a true statement and a false statement combined with an or to a true statement in both ways. Notice we've got some commutativity of the operation here. And then 2 false statements will combine to give us a false. Now let's look at our not operation. So if we have a true statement, that will negate to a false statement and vice versa. If we have a false statement, that will negate to a true statement. Okay, so I think we're good to go with this. Okay. Now let's look at the implication or the conditional combination of 2 mathematical statements. So to look at conditional statements, I think our best starting strategy is to start with a statement which is a hidden conditional statement and break it down into 2 pieces. So our statement says if the integer x is a multiple of 15, then x is a multiple of 5. Let's notice that this is most definitely a true statement because every multiple of 15 is a multiple of 3 times 5, but then it's obviously a multiple of 5. So what we want to do is break this off from the if and then we'll have our 2 component statements. So let's say this is our first one, which I'll put in orange brackets, and then our second one I'll put in these purple brackets. So we'll define our orange bracketed thing to be P, and that will be the integer x is a multiple of 15. And then for the purple bracketed one, we'll define that to be our statement Q, and that'll be x is a multiple of... Okay, so now that we're done with this first example, let's look at another example that'll help us unravel like the truth table of our conditional statement. So our second example will help us build the truth table for this conditional. So let's say our statement P is the statement you pass the exam, and the statement Q is the statement you pass the class. Then the implication P implies Q, or if P then Q, reads if you pass the exam then you pass the class. Okay, so let's maybe fill the truth table in by rewriting these possibilities as sentences over here and then getting an idea for whether or not the implication is good or not. So let's look at this first one. So P is true and Q is true. So this would be something like this. You pass the exam and the class. So does that violate this implication?
I've done that many times.
Well, it does not violate this implication. You can think about this implication of this conditional as some sort of promise. And that promise is that Q will always be true as long as P is true. And that's exactly what we have here. So that means this implication here is true. Now let's look at the next one. So P is true and Q is false. And that will be you pass the exam and fail the class. So notice that's a broken promise of the P implies Q statement.
Oh,
the P implies Q statement
suck.
says that if you pass the exam, you're guaranteed to pass the class. But that does not occur in this scenario. So that tells us that this conditional would have been false. It's a broken promise. So we put a false right there. Now let's look at these others. So P is false and Q is false. So this would be you fail the exam and pass the class.
Oh, that'd be a
that
dub.
doesn't break the
That'd be a
promise
dub.
here at all. That's okay. It might seem kind of strange that false implies true should give you something true, but it does. So, and that's again because this promise is not broken. Perhaps you did really well on all your homework or all of your other stuff, so you didn't really need to pass the exam to pass the class. Okay, so let's look at this last one. False implies false. So that would be you fail the exam and the class. And again, that does not break this promise either. So you would get a true statement here. So interestingly enough here, this P implies Q statement gives you true for 3 of the outputs and false for 1 of the outputs. And the false it gives you is based off this promise breaking. As long as P is true, then Q is also true. So lastly, I'd like to write down several different wordings of this conditional statement. So there are tons of ways to write the conditional statement P implies Q. Here are a few. So the first is if P, then Q. So the first is if P, then Q. Then we could have Q if P, Q whenever P, Q provided P, whenever P, then also Q.
Got it.
P is a sufficient condition for Q. Q is a necessary condition for P. And P only if. Okay, so let's end with some warm-up problems. All right, here's a smattering of warm-up problems. So the first is to determine if the following are mathematical statements, and if they are mathematical statements, are they true? The first is the derivative of a cubic polynomial is a quadratic polynomial. Next is sets Q and R. Next is the union of R cross N with N cross R equals R cross R. Then next up, let's write the following in symbolic form, defining the component statements P, Q, R, so on and so forth if you need to. And then use our operations like P and Q, P or Q, not P, and the conditional P implies Q as needed. Okay, so first is there is a quiz on Monday or Wednesday. Next is X is in A minus B. So that's the set minus. Then next is a geometric series converges only if its common ratio R satisfies the inequality the absolute value of R is less than 1. And that's a good place to stop. This is the 4th video in a series devoted to introductory proofwriting.
Still recording?
And in the previous video, we
Absolutely
looked at
we
mathematical
are.
statements
Oh my goodness
and
me.
the very basics of logic.
Oh,
We're going to
yes, it's
continue
5
to do that
seconds ahead.
today. And we're going to
Whoopsies.
start by building up to the notion of a biconditional. And we'll do that with the first very important observation. And that is the conditional P implies Q is not the same as the conditional Q implies P. And that's pretty clear from these 2 examples that we'll go through. So the first one, we have the statement P is the function f is differentiable.
Okay.
And the statement Q is the statement the function f is continuous.
Okay.
So P implies Q here reads, if f is differentiable, then it is continuous. And that's a well-known true statement. So that's something you would learn in a first semester or a differentiable calculus class. But the statement Q implies P is not true. But let's read that statement real quick. So Q implies P would read, if a function f is continuous, then it is differentiable. But like I said, that's false. And we can see that it's false by looking at a fairly simple and fairly classic example, and that is the absolute value function. So let's consider the function f, which is defined by f of x equals the absolute value of x. And let's recall what its graph looks like. So it's this nice V shape. And that tells us that we have a point of non-differentiability given that we have this corner right there at the origin.
That is on God, bro.
Great, so that's some motivation for why P implies Q can be true, but Q implies P can be false. So that means these 2 conditionals are not logically equivalent. Let's look at another example. Let's say now we have a statement P which says the integer n is a multiple of 120.
Okay.
And then the statement Q is the integer n is a multiple of 24. So P implies Q here is also true, just as before. And that's because if you have something which is a multiple of 120, then it's a multiple of 24 times 5, because 24 times 5 is 120.
Yeah.
But if it's a multiple of 24 times 5, then it will be a multiple of 24. Now, Q implies P is not true in this case, but let's read Q implies P real quick. So that says if n is a multiple of 24, then n is a multiple of 120. But we can come up with a bunch of examples of this. Maybe the simplest example would just be n equals 24 itself. So 24 is a multiple of 24, but 24 is clearly not a multiple of 120.
So true.
Then we could have some other examples like 48, like 96, so on and so forth. Those are all multiples of 24, but they're not multiples of 120. So now we want to look at the very special case where P implies Q and Q implies P might be true, and that's called a biconditional. And we'll define it as follows. So if P implies Q and Q implies P, then we write P biconditional Q. We read this as P if and only if Q. And there are a couple of ways to write that down in English that you would write down if you're writing a proof in complete sentences. So you might write P if and only if Q, like we said. You might write P is a necessary and sufficient condition for Q. Or you might write P is equivalent to Q. Okay, so now let's see an example of this biconditional in action, and then we'll look at a truth table. So as a quick example of a biconditional statement in action, let's look at this one. We have A is even if and only if A is a multiple of 2. So in fact, this is really clearly true because that's exactly the definition of a number being even. That being said, whenever you have these if and only if or biconditional statements, then often they can be used to give some logically equivalent definitions or alternative definitions for a certain mathematical concept. Okay, so now let's look at the truth table for our biconditional. So we've got if P is true and Q is true, then P if and only if Q is true. If one of them is false, then the statement is false. But if they're both false, then the statement is true. Okay, so that's good. The next thing that we want to do is look at maybe the arithmetic or the calculus of logic operations. Now we're going to look at what I'll call the logical calculus, or the calculus of logic. And the idea behind this is we can build mathematical statements from very, very simple ones with the addition of the operator and, or, and not. So in fact, we will not need our conditional or our biconditional. We'll need to show that. So of course, we'll always use our conditional and our biconditional because it makes things simpler. But that being said, it's kind of nice to think that we only need these 3 building blocks. Okay, so let's maybe do an example first. And that will be building the exclusive OR operator. So the exclusive OR the XOR would work like this. So P exclusive OR Q should give us a truth when exactly one of P or Q is true. So they're not both allowed to be true. That would be the exclusive part of the exclusive OR. Okay, so how will we approach this? I think our best strategy will be able to write this down into kind of a bigger sentence that can be easily translated to our logical operators. Okay, so maybe something like this. So P or Q is true, but they are not both true. So that would be a first translation of the sentence that we have. Now let's see if we can translate that into symbols. So P or Q, so that would be P or Q. Good. And then what is a but? Well, a but is kind of like an and. Now connotatively it feels a little bit different, but denotatively I think it's the same thing. So we can really maybe more appropriately read this as P or Q is true and they are not both true. So let's put an and statement in there to play the role of that. And then let's write they are not both true. So for both of them to be true, we would have P and Q. And for not both of them to be true, we would have a not symbol right there. Okay, so let's check to make sure this works. And we'll check to make sure this works by building a big truth table. So we'll have inputs P and Q, and then we'll have like intermediate calculations like P or Q, and then P and Q, and then not P and Q. And then we'll have our final entry, which is our goal over here of, let's see, P or Q, and not P and Q. Great, so let's get this going. So we've got this big table. So maybe I'll put a yellow line here to separate ourselves from the inputs and the intermediate calculations. Another yellow line here to separate ourselves from the intermediate calculations and the final calculation. And then let's start maybe partitioning this off so that we can fill it up. So we'll need 4 total entries. So P can be true, true, false, false. Then we can have Q, true, false, true, false. Now let's see what we get out of this. So P or Q can be calculated like we did last time. So we'll get a true for this, a true for this, a true for this, and a false for this. And then P and Q can be, again, calculated like we did last time. So that'll give us a true when they're both true, and falses otherwise. But now we need to negate P and Q. So that just means swapping all the trues for falses and all the falses for trues in that column. That'll give us false, true, true, true. And then finally, we need to do an and conjunction between this intermediate column here and this intermediate column here. Great. So again, we want to do an and calculation between those two, and those should give us our final value. So let's see. If we have true and false, we get something that's false. If we have true and true, we get something that's true. Another true and true gives us something that's true. Another false and true gives us something that's false. And now let's say we were to kind of forget everything that's going on in the middle. So I won't really scratch this out, but let's say we forget everything that's going on in the middle and notice that we have exactly built what we wanted to. If P and Q are both true, then the output is false. If exactly one of them is true, then the output is true.
Wow,
and if they're both false, then the output is false. That's exactly our exclusive OR that we were going for. Next, we're going to take a fact that you've probably used for a long time, since probably a high school algebra class, and we're going to turn it into a logical statement. So that fact will be the product x times y is 0 if and only if x is equal to 0 or y is equal to 0. Okay, so let's put this into symbols first. We have the product xy equals 0, and then if and only if can be this nice biconditional, and then we'll have x equals 0 or y equals 0. Great. Now let's give these some names. So maybe we'll give this first one the name P. So P is the statement xy equals 0. And then maybe we'll give this one a name Q, and this one the name R.
I'm about to go toilet.
So
I think I can figure this one out.
We have
so I'm just gonna
this like more
ignore this real quick.
As P if and only if Q or R. Great. And now just for practice, let's find the truth table of this abstraction of this fact, this kind of logical abstraction of this fact. So notice in this case we have 3 inputs, P, Q, and R. So that means we'll need 8 total entries. So let's see, we'll need a P column, a Q column, and an R column. Then we'll need an intermediate calculation of Q or R. And then we'll need our final calculation of the biconditional P if and only if Q or R. So something like that. So let's build this table. Like I said, we've got this intermediate calculation of Q or R. I'll separate that from P, Q, and R with a yellow line, and then we have our final calculation, which I'll separate from the intermediate calculation with another yellow line. Now we need to break this into 8 pieces. So let's break it in half here, we'll break it in half here, here, and then we'll break each of those in half as well. So now we've got a table that we can start to fill out. Well, maybe one more thing. We'll break this into thirds for P, Q, and R. Now we need to populate these 3 columns to the left of this line with all the possible values of P, Q, and R. So let's see. We could have 4 trues for P, 4 falses for P. We could have kind of an alternating 2 trues and 2 falses for Q. Right? And then we could have just an alternating 1 true and 1 false for R. And if you look carefully, this gives all possible interactions of values of Q, P, and R. Okay, so now let's do our intermediate calculation, our Q or R. So let's see, here we'll have a true, true, here we'll have a true, here we'll have a false. It's because for an OR statement, that is only false when they're both false. Okay, and then next we'll have actually another copy of that. True, true, false, true, false. Okay, that's good. Now we want to do P if and only if Q or R. So let's link those 2 columns that we'll want to compare at this point. So that would be those 2 columns, and we're doing
Jiminy
the
crickets, that is a loss of truth.
So that means we get a truth only when the entries are the same. So here we have true, true, so that'll give us a true. True, true, that'll give us a true. True, true, that'll give us a true. But then true, false, that'll give us a false. False, true, that's a false. False, true, that's 2 falses. And then finally false, false, but that biconditional gives us a true. So next up, we'll do some calculations to show the equivalence between logical statements that may look inequivalent. Okay, so like I mentioned before, the idea behind this logical calculus is that everything should be able to be built out of and or not. And then what about conditional statements? Well, in this claim, we will show that the biconditional statement, P if and only if Q, can be built out of and or and not. And then as one of the warm-up exercises, you'll do the same thing for the conditional statement, P implies Q.
10 hours and 20 minutes.
So in fact, what we have here is P if and only if Q is logically equivalent to P and Q, or not P and not Q. So how can we prove this claim? Well, we'll do it with the truth table. So notice that there are 2 entries. So there are P and Q, 2 inputs, I should say. And then there's a few intermediates, but then we know the truth table for P if and only if Q, so we don't need to include that. So let's see, we'll have not P as one of the entries, not Q as one of the entries, P and Q as one of the entries, and then finally not P and not Q as one of the entries before our final goal, which is P and Q, or not P and not Q. Okay, so now let's use yellow lines to separate from the inputs and to separate the intermediates from the finals. And then let's start partitioning our table. So let's see, in this case we'll need 4 entries, so that's a little bit easier to work with. So let's say we've got those 4 rows, and then we'll need to partition some columns as well. So right there, right there, right there, and right there. Now we can get going. So we can have P be true, true, false, false.
Okay.
We could have Q be true, false, true, false. So let's see, not P will just be the opposite of P. So that'll give us false, false, true, true. Not Q will be false, true, false, true. Nice. Now P and Q, well, that's pretty simple. It's true, false, false, false. And then not P and not Q. So that'll be the and statement between these 2 columns. That should give us false, false, false. And then finally true down here. And now we'll finish this thing off by taking the or conjunction between these final 2 intermediate columns. So that'll give us a true value here, false,
True,
false,
true,
and then a true value there.
Bosh.
But let's notice that is exactly the same as the truth table for P if and only if Q. So we just took this biconditional and wrote it in terms of and, or, and not. So we'll finish this whole thing off by looking at some of the arithmetic rules of and, or, and not. Now we're going to look at this pretty big list of rules for calculations, if you will, with our logical arguments. So the first one is called the contrapositive. And it says that the statement P implies Q is logically equivalent to the statement not Q implies not P. This will be really important later when we start proving things, which is coming up. And then next is De Morgan's laws. That tells us how the not operator interacts with and or. And in fact, what it does is it flips an and to an or and an or to an and. So not P and Q is the same thing as not P or not Q, whereas not P or Q is the same thing as not P and not Q. Then we've got these fairly straightforward commutativity rules and associativity rules. So like P and Q is the same thing as Q and P. There's not that much that needs to be said about that. And if you have P and Q and R, that's the same thing as P and Q and R. Same thing with ORs. Then finally, there are some nice distributive properties as well. So P and Q or R is the same thing as P and Q or P and R. And then there's a similar statement where you switch the ands and the ors. Okay, so let's look at a couple of these. Maybe starting with the contrapositive, as though that's probably one of the most important. So let's build our truth table. We'll have inputs P and Q. We will need not P, we'll need not Q, and then we'll need not Q implies not P. And for good measure, we'll put P implies Q as well, although we calculated that previously. Okay, so we'll have a yellow line between the inputs and the intermediates, a yellow line between the intermediates and the outputs. Then let's get to it. So breaking our rows and our columns up. So in this case, we'll need 4 rows because we have 4 total possibilities of entries. So let's see, we could have P be true, true, false, false. Then we could have true, false, true, false. Then let's see, not P will be the opposite of P, so that's going to be false, false, true, true. And then here we'll have false, true, false, true. Great. Now let's look at not Q implies not P. So the only time that's false is when the input is true and the output is false. So let's see, that happens right here. We have not Q is true, whereas not P is false. So that's the only one that makes this conditional false. The rest of them are in fact true. But if you compare that to the truth table of P implies Q, you see that we have the same thing, giving us our logical equivalence. Okay, let's maybe do one of these De Morgan laws while we're at it. So let's get the chart on the board. Okay, so I got all the simple parts of our truth table put together, now ready to finish it off. So let's do this not P or not Q. So that means we'll compare these two columns right here, and if one of the entries is true, then the whole thing is true. So that means we'll have a false entry here, then that'll have a true entry here, a true entry here, and a true entry here. Now let's compare that to not P and Q. Well, maybe we should write down what P and Q is first. But let's just recall that P and Q will give us a true, false, 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 just based off the standard rule. So if we negate that, we'll in fact get a false, true, true, true. So that means that this operation right here, not P or not Q, is the same thing as this operation right here, not P and Q. Proving this second of the De Morgan's laws. Okay, so I'm going to leave you with some warm-ups. So here's some nice warm-up exercises. So we'd like to use truth tables to show the logical equivalence of the following statements.
Still recording.
So the first one is this distributive rule over here. So we've got the and distributes over the or as follows. P and Q or R is P and Q or P and R.
10 hours and 20
Next, we can write the implication without using the implication, just with
about
the
10
or
hours, 15 minutes, I
statement
think.
and statement. Then we've got this one that's kind of nice. It says not P if and only if Q is the same thing as P implies not Q and not Q implies P. And that's a good place to stop. This is the 5th video in a series devoted to introductory proof
Here
writing.
we go.
And today we're going to look at quantifiers. Both the universal quantifier for all, which has the symbol which is like this upside down A, and the existential quantifier there exists, which has this symbol of backwards E. So our main goal here for today will be to translate mathematical sentences into symbols using quantifiers and also negate statements involving quantifiers. And that will kind of finish this topic of logic, or this very basic logic, and in the next video we'll start writing proofs using counting strategies. Okay, so let's look at these examples. So we'll translate each of these mathematical statements into symbolic notation. Okay, so the first one says, for every integer n, 2n is even. Okay, so we would write that as, for all n in z, 2n is even. That would be a way to do that. Another thing that we could do is maybe say, for all n in z, the e of 2n, where e of x is the statement or the open sentence, x is even. Okay, so let's look at this next one. Every subset of the numbers between 1 and 10 has 10 or fewer elements. Okay, so this says for all x, which is a subset of the set containing 1 up to 10, the cardinality of x is less than or equal to 10. So that's how we would write that in symbolic notation. Now let's notice that this bit right here, x, a subset of the set containing 1 to 10, could be replaced with something involving the power set. We could say that this x is an element of the power set of this set containing 1 to 10. That's equivalent. Now let's look at this next one. There is a function whose derivative is itself. Okay, so we would say there exists an f such that f prime of x equals f of x. So there, we've got it. And of course, this is true. We can probably think of a function off the top of our heads. That would be the exponential function e to the x. Now let's look at this one. There is a subset of the natural numbers with exactly 330 elements. Okay, so we would say there exists an x, which is in the power set of the natural numbers. We could also say that it's a subset of the natural numbers like this. And then we'll have such that the cardinality of x equals 3030. Okay, so we're going to do quite a few examples here because I think it's helpful to see a lot of these. So let's get on it. So here are two more examples. So the first one says that every odd integer is one more than an even integer. So I think this is pretty clearly true, but the truth of the falsehood is not our goal here. Our goal is to rewrite it in symbols using quantifiers. So I think maybe something like this would work. For all n in z, where n is odd, there exists a k in z such that n equals 2k plus 1. So look, we've got an odd integer, and that says that this odd integer is one more than an even integer. Okay, so that's pretty good. Now let's look at this next one. If f is continuous on the closed interval a to b, f of a is negative and f of b is positive, then f of c equals 0 for some c between a and b. This is, of course, the intermediate value theorem, which you probably learned in a calculus class or maybe even a pre-calculus class. So this one's a little bit more complicated, but I think it's nice to dig into something like this. So we'll have f is continuous on the closed interval a, b. That'll be one statement. And f of a is less than 0, and f of b is bigger than 0. So that's what we have here. First of all, I maybe should have noted this first, that this is a conditional. Notice that we have if this stuff in orange brackets, then this stuff in blue brackets. So what I've done so far is I've exchanged all the stuff in orange brackets for a logically equivalent formulation using symbols. Okay, so since we have an if-then statement, this is going to turn into a conditional or an implication. So all of the stuff in orange brackets will imply that there exists a c on the open interval a to b such that f of c equals 0. So that's where our quantifier lives here, this existential quantifier, which notice up here the language was for some C between A and B. But that's equivalent to saying there exists a C between A
definitely
and
got
B
this,
such that f of C equals 0.
I have
Okay, so let's do some
certainly
more.
understood all of this.
So here's our last example before moving on to some other stuff. For all integers n bigger than or equal to 3, the equation x to the n plus y to the n equals z to the n has no solution for x, y, z, which are natural numbers. So this is, of course, the statement of Fermat's last theorem, which we know to be true. Okay, so so to rewrite this, we might do something like this. So if n is a natural number and n is bigger than or equal to 3. So that would be this thing right here. For all integers n bigger than or equal to 3, that would be something like this. That implies that for all x, y, z in n, x to the n plus y to the n is not equal to z to the n. So this reads a little bit different than it does up here in the sentence form, but it has the same information. So sometimes when translating it from a sentence like this to symbolic notation, you might have to tweak it a little bit, just based off the differences in natural English writing versus like natural logic writing. Okay, so now let's look at negating statements with quantifiers. So the rule for negating things with quantifiers is kind of similar to the rule for negating things with ands and ors. So remember, an and switches to an or, and an or switches to an and under negation. And in fact, for alls, or the universal quantifier, switches to a there exists the existential quantifier, and vice versa under this negation. So properly, we have the negation of the statement for all x, p of x, is logically equivalent to the statement there exists x, such that not p of x. And then similarly, the negation of the statement there exists x, such that q of x, is for all x, not q of x. Okay, so let's look at a couple of examples, starting with this one that says every even integer is of the form 2n, where n is an integer. So let's start by translating this into just another English statement that has the same information that will allow us to put it into symbols a little bit more easily. And that would be something like this. So for all n in z, 2n is even. Okay, good. So into symbols, we would have for all n in z, 2n is even. Okay, good. And now let's make our negation step. So let's say this magenta arrow means negate this. So I'll maybe put a negation here in blue. So that will negate to there exists an n in z such that 2n is not even. But of course, we've got a rule for not even, and that is odd. So 2n is odd. And now let's rewrite that into a sentence, and that sentence would be something like this. There is an integer n such that 2n is odd. Or maybe another way of writing this sentence would be 2n is odd for some integer n.
I disagree with that statement, actually.
These two equivalent statements, as well as this statement up here in symbols, are all false. But that's because we've negated a true statement. So the process here is not to investigate the truth or the falsehood. The process is to get some practice with negating statements. Our next thing to look at will be the negation of a conditional. So we're just going to write it down real quick, and then we'll check that it works using a truth table, which I've already prepped.
Okay.
And then we'll look at some examples, which will make it even more evident. So the negation of the statement P implies Q is the statement P and not Q. So let's build out this truth table just to convince ourselves that this is the fact. So we've got P and Q set up. Let's now do our not Q. So that means we'll change every true to a false and every false to a true. So we've got false, true, false, true. And now let's do our P and not Q. Recall that both of those need to be true in order to get a truth out. That only occurs right here. So we've got a true here, but then we have falses everywhere else because at least one of those entries is false. But now let's compare that to P implies Q. And notice it's exactly the opposite of P implies Q. Here we have false true, true false, false true, and false true. But that means that it's logically equivalent to not P implies Q. So that establishes this logical equivalence over here. Now let's look at a little bit of an example of this, and then we'll do a bigger example. So if n is odd, then n cubed is even. So this seems like it should be a true statement. And in fact, it is a true statement. It's one of the very first types of proofs that we'll do. But let's negate this conditional. In order to do that really carefully, what I'd like to do is to put it in the form P implies Q. So we'll have n is odd implies n cubed is odd. Great. So this is playing the role of P, and this is playing the role of Q. And now let's make our negation. So this magenta arrow will be our negating operator. So we should have P and not Q. So we have n is odd and n cubed is even. Which notice I just went straight to putting an and here instead of the symbol, but I think it's okay in this case. Okay, so again, we started with a statement that seems to be true, and we ended with a statement that seems to be false, which is okay. Okay, now let's do a bigger example. Now let's look at this nice big example, which actually comes from a future math class that you probably haven't taken yet called real analysis, or sometimes advanced calculus. But what we have here is the precise definition of what it means for f to be differentiable at a. So what we have is this kind of complicated statement. For all epsilon bigger than 0, there is a delta bigger than 0 such that if the absolute value of x minus a is between 0 and delta, then the absolute value of f of x minus f of a over x minus a minus some number L
I think this is the thing oleki told me not to worry about.
Okay, so our goal is to negate this, but our first step should be to
engage in this
translate it.
Lol.
So let's say this green arrow is the translation arrow. So we might have something like, for all epsilon bigger than 0, there is a delta bigger than 0, so that would be an existential. There exists a delta bigger than 0, such that if this happens, then this happens. So notice that's a conditional statement. So what we'll have is 0 is less than x minus a minus delta implies the absolute value of f of x minus f of a over x minus a minus L is less than epsilon. So we've got something like that. So probably the first thing to notice is if we have these quantifier setups, and after those quantifier setups, we have a conditional statement. I'll say this is P implies Q. So P is this inequality and Q is this inequality. So that means to do our negation, we'll need to exchange for alls for there exists and vice versa in this quantifier setup. And then we'll need to negate our conditional using the rule that we have over here. Okay, so let's do it. So we'll have something like this. There exists epsilon bigger than 0
bro, I don't
such that
I don't get this, bro.
for all delta bigger than 0, we have P and not Q. So that would be 0 is less than x minus a, which is less than delta, and the absolute value of f of x minus f of a over x minus a minus L is bigger than or equal to epsilon. So notice the negation of a less than is a greater than or equal to. Okay, now we might want to put this back into words.
Okay.
So that would go something like this. There exists epsilon bigger than 0 such that for all delta bigger than 0, 0 is less than the absolute value of x minus a, which is less than delta, and the absolute value of f of x minus f of a over x minus a minus L is bigger than or equal to epsilon. So if this up here, what we started with is the precise definition of f being differentiable at a, this down here would be the precise definition of f being non-differentiable at a. So f is not differentiable at a. So of course, some functions are differentiable and some functions are not differentiable. So in order to show that a function is not differentiable, you would show that it satisfies this definition right here. So we're going to finish this video with some rules of logical inference, and then after that I'll give you some warm-ups. Now we're going to look at some rules of logical inference. So we'll start with inferring things from the truth of the conditional P implies Q. This first inference is called modus ponens, and that says if we know P is true, then Q is true. Then the second one is called modus tollens, and that says if we know Q is false, then P is false. So let's look at a quick example of that. So here we've got our conditional. If a function f is differentiable, then it is continuous. So again, this is a well-known result from differentiable calculus that we've used several times in the past. Now let's maybe apply these two rules. So we know the function f of x equals e to the x plus x sine x is differentiable. So it is continuous. So it must be continuous. So let's say, for instance, that it's easier to test if that function is differentiable, then we get that it's continuous for free based off this larger result. Okay, so now let's look at another one. So we know the function g of x equals the floor of x. So let's recall the floor of x is like an elevator down to the closest integer. So the floor of a half is 0. The floor of 3/4 is also 0.
Yeah, I know that one.
But the floor of 1 is 1 because you don't have to go down at all. Okay, so back to this. We know that g of x equals the floor of x is not continuous. So it must be non-differentiable. So not differentiable.
Okay.
Great. Now it might be kind of tricky to straightforwardly show that this is not a differentiable function, but it's easy to show that it's not a continuous function. Now let's look at one more logical inference, and this is called elimination. And here we suppose that the or statement, P or Q, is true. And then we know that if P is false, then Q has to be true. Okay, so let's look at an example of that. So every even integer is even or odd. So I think that's pretty clear. Now let's note
that is not what that says, bossman.
That 3 is not
He can
even.
do maths, but he can't read.
So it's not even, it's not a multiple of 2. So it must be odd. Must be odd. And then this may seem kind of silly, but this either or kind of thing actually shows up quite a bit in our proof techniques moving forward. So now I'll leave you with some warm-up exercises. So here are 3 nice warm-up exercises that are based off what we just saw. So for each of them, we'd like to translate them into symbolic logic, use that translation to easily negate these statements, and then write the negation back into a sentence. So that's a nice kind of holistic practice of everything that we saw. Okay, this first one says, for every capital M bigger than 0, there is a delta bigger than 0 such that if the absolute value of x minus a is less than delta, then, I missed my then, let's get that in there, then f of x is bigger than m. I'd like to point out real quick, just as a point of interest, this is the precise definition of the limit as x goes to a of f of x equals infinity. So that's pretty cool. The next one says there is a real number a such that a times x equals x for all x in R. So of course we know exactly what that real number is. It is the real number 1. That being said, that's not what we're going for here. We'd like to do all of this stuff. Next we have the statement for every x in R, n is bigger than x for some natural number n. This is actually technically called the Archimedean principle. And that's a good place to stop.
Whatever.
This is the 6th video in a series devoted to an introductory course in proofwriting. We just finished doing some stuff with logic, and now we're going to look at counting principles. So in order to get us started with that, we need to define something called a list. So a list is an ordered sequence of objects. We'll use the notation in parentheses like this. So we have A1, A2, A3 up to AN. This is a list of length n. And maybe the third entry in this list would be A1, the second entry would be A sub 2, the nth entry would be A sub n. And I'd like to point out that we will allow repetition as we define our lists. So for example, the list A0, A1 is allowed. That repeats A 2 times. Now this is in stark contrast to sets. You don't have repeats of the same elements in sets. Now I'm going to recall something called the multiplicative principle or the multiplication principle. And I say recall not because we've done it in this course, but because you've likely seen it in the past. And that talks about how many such lists there are given the setup of the situation. So there are m1 times m2 up to mn, so that product of n numbers, such lists of length n if there are mi choices for the ith object. Okay, so let's do some examples of this setup. And the first example, we'll have like a counting tree to kind of see where this multiplication principle comes from, but then after that, we'll just apply this principle. So let's say we want to make a list of 3 objects. The first object comes from the set containing 0, 1, the second from the set containing A, B, C, and finally the third from the set containing X, Y, Z. So notice we've got 2 choices, 3 choices, 3 choices. So by the multiplication principle, there should be 2 times 3 times 3 or 18 choices. But let's just make sure that makes sense. So let's say we've started having not making any choices at all. So that'll be like our Big Bang event. The first thing that we'll do is choose whether the first entry is a 0 or a 1. So that'll give us 2 branches here. We've got our branch for 0 and our branch for 1. And at this stage, we've got 1 entry lists. And those 1 entry lists are either just 0 or 1. And now from here, we'll make a choice A, B, C, but that's 3 choices. So let's see, we'll have a choice A, B, and C. And like I said, that's for all 3 of these. So where does that leave us? So this would be maybe the choice A, B, C, and then likewise down here, the choice A, B, C. So that'll leave us with 0, comma A,
I am so
0,
understanding.
comma B, and then finally 0, comma C,
get this one.
and then same thing here, 1, comma A,
Oh, stupid.
1, B, and 1, C. And next up, we need to make our third choice, and there are 3 choices for our third choice. They come from X, Y, Z, so that's going to branch this off 3 times again. So we'll have 3 choices here, 3 choices here, and 3 choices here. And then likewise, 3 choices here, 3 choices here, and 3 choices here. And so let's say those go as X, Y, Z. Those are the choices, X, Y, Z. And then you can fill in all those other branches as well. So up here, we'll have the list 0AX, 0AY, 0AZ. And then here we'll have 0BX, 0BY, and 0BZ. Moving down, we'll have 0CX, 0CY, and 0CZ. And that's half of them so far. Then the next choice down here will be 1AX, 1AY, and 1AZ. And then I'll let you fill in the rest.
So
but I think what we can see is that we'll definitely get
page.
18 just based off of these 18 points that we get in the end. So that's kind of a nice illustration that there are 18 such lists. But from here on out, instead of making this like large tree, we'll just use this multiplication principle. Okay, let's do another example. So after that basic example, let's look at something a little bit more interesting. Let's say we're trying to choose a 4-element list, or we're trying to count the number of 4-element lists, where the first entry comes from the set containing A and B, and the remaining 3 entries come from the set 1, 2, 3, but we do not allow repetition in this case.
No repetition.
So with general lists, we do allow repetition, but sometimes we'll like to not allow repetition. Okay, so the way I like to do this is maybe put an open box for my 4 choices. Great. And now let's color code this a little bit. So maybe I'll underline this in yellow to show that my first choice comes from that set containing A, B, but then I'll underline this in magenta to show that my second, third, and fourth choices come from the set containing 1, 2, 3 without repetition. So now let's count it up. So we can choose from A or B here, so that's 2 total choices. And then we can choose from 1, 2, 3 here, that's 3 total choices. And you might say, well, here we can also choose from 1, 2, or 3. That'll be 3 more choices. But that's wrong. And that's wrong because we've already used one of the choices from 1, 2, 3 here. So for instance, let's say we chose the number 1. Then here we're only allowed to choose 2 or 3. Or if we've chosen here the number 2, we're only allowed to choose the number 1 or 3. So as you can see, we have less choices here. We have exactly 2 choices. But now we've chosen 2 elements from the set 1, 2, 3, which means we're only left with a single choice for this last bit. So let's maybe match these up. So this matches with that choice, this with that choice, and this with that choice. So putting this all together, we have 2 times 3 times 2 times 1, or 12. So there are 12 total possibilities. Okay, let's do another. So this next question is about license plates from the state where I live at the moment, which is Virginia.
Okay.
So Virginia license plates consist of 3 letters followed by 4 digits. And those digits can be between 0 and 9. Now we'd like to decide how many plates are possible. So I'll use like my boxes to indicate choosing letters or numbers.
What will that be?
So I need 7 boxes for the 3 letters and then the 4 numbers. And let's color code this again.
26,
so the first 3 are letters. So that would be this one, and this one. Whereas the remaining 4 are digits or numbers between 0 and 1. So that would be like this box, this box, this box, and this box. And notice there's no rule here about repetition, so we don't have to think too hard about that. Now we've got to choose a letter for here, here, here. How many letters are there? There are 26. So that means we get 26 choices here, 26 choices here, and 26 choices here. And then over there, we need to choose a digit
That's not 26,
between 0
boss man.
and 9. That gives us 10 possible choices. So we have 10 times 10 times 10 times 10. And then you can multiply this all up and you'll see that you get 175,760,000. And that's it. So that's far more cars than you would ever have in the state of Virginia. So now we've got a classic problem about the number of choices on a menu. So let's say a pizzeria offers 2 types of crust, 3 sauces, 2 cheeses, and 10 different toppings. And then our goal is to determine how many 4-topping pizzas are possible. Okay, so let's see. We'll have a choice for the crust, a choice for the sauce, a choice for the type of cheese, assuming that we're not going to get 2 types of cheese or 2 types of sauce, and then 4 choices for the toppings. So that means we've got these boxes to fill here. Now let's color code this. So 2 types of crust. So let's say this yellow box is our choice for crust. 3 sauces. Let's say this orange box is our choice for sauces.
Incredible
2
reaction.
cheeses. Let's say this red box is our choice for cheeses. And then finally,
I like that
10 different toppings. Let's say those are our choices for our 4 toppings that we will choose. So we have this kind of setup. Now we can apply this multiplication principle.
With blue toppings looking
there are
lovely.
2 types of crust. So there are 2 choices for this box. There are 3 sauces. So there are 3 choices for this next box. 2 cheeses, there are 2 choices for this next box, and then 10 different toppings. So for the first topping, we can choose 10 different objects. Then for the next topping, we can't choose 10 anymore because we've already chosen one. Let's just say that doubling up on a topping is not possible.
Okay.
So if you've already chosen, for example, mushrooms for your first topping, you're not allowed to choose mushrooms for the second topping.
Thank God
so
for
that means
that.
there are only 9
You're a
choices
psychopath
for the
if you
second
have
topping,
double mushrooms on your damn pizza,
8
bro.
for the third and 7 for the fourth.
Hey, I got that right.
So now we can take the product of all of those, and what we'll
like a
see
couple
is that
thousand.
there are 60,480 total pizzas. Okay, so now let's do a quick follow-up problem, and that will
That's a
be
few
how
pizzas.
many pizzas are there with 4 or less toppings? Well, we just decided that the number with 4 toppings
You just add to the 3 and 2 and the
was
1.
this 60,000. So all we need to do here is determine the number with 3 toppings, 2 toppings, 1 topping, or 0 topping, a plain cheese pizza, and then add those together. So I think we can do that without maybe doing our graph.
If you get a
just
no
motivated
topping
by what's going
pizza,
on here. So if we're choosing
you
3
fucked.
toppings, it's like filling up all of these boxes except for the last one, which means we have this product here without the 7. So that would be 2 times 3 times 2 times 10 times 9 times 8. You can multiply that up and you'll see that you get 8,640. Now let's move on to 2 topping pizzas. Then that's like filling up all of these boxes except for the last 2 because we only want 2 toppings.
What's that, 1,080?
So that means it's doing this entire product except for the 8 times 7. So we have 2 times 3 times 2 times 10 times 9. And you could multiply that up and you'll see that you get 1,080. And then how many 1 topping pizzas and how many 0 topping pizzas?
What's that shit,
So
bro?
likewise,
You
for
can
1
get,
topping pizzas, we have 2 times 3
120?
times 2 times 10, which multiplies up to 120 different pizzas.
And you got 12.
And for 0 topping pizzas, we have 2
You a bitch
times
if you get
3
20 if you get
times
them.
2, because we don't make any topping choices. And that will be 12 total pizzas. But now if we add all of this together, we need to add these 4 numbers along with this number right here for 4 toppings.
A lot of
You'll see
numbers.
that we have
Too many numbers for my liking.
70,332 total pizzas with 4 or fewer toppings. And this example actually brings us to another principle that instead of called the multiplication principle is the addition principle. So let's look at that. So now we're going to formally write down the principle that we just used, and that's called the addition principle. So let's suppose we have a finite set, we'll call it A, and it can be expressed as a disjoint union. So what I mean by that is we can write A as A1 union A2 union all the way up to AN, where AI intersect AJ is the empty set unless I is equal to J. So that means if these are not equal indices, we get this intersection is empty. Then the cardinality of A is equal to the cardinality of A1 plus the cardinality of A2 all the way up to the cardinality of AN. So let's notice that we definitely used that in the previous example. Our set A would have been all pizzas with 4 or less toppings, and we broke that down into pizzas with exactly 4, exactly 3, exactly 2, exactly 1, or 0 toppings. So let's look at our next example. We want to determine how many 5-digit multiples of 5 there are that contain exactly 19. So we can break this up into 4 disjoint possibilities. So I'll draw these in this like rectangle shape. Those possibilities depend on exactly where that single 9 happens. The single 9 could be the first entry, and then after that we have 4 more digits to choose. The single 9 could be the second digit, and then we have 1 before and 3 after to choose. The single 9 could be in the middle, or finally, the single 9 could be not quite at the end, but it could be the next to last digit. You might say, well, why can't that single digit be the last digit? And that's because these are all multiples of 5. And multiples of 5 only end in 0 and 1. So I'll shade this in right here just to collect the information that these have to be multiples of 5. So that means they end in either a 0 or a 1. So now let's see what we have here for our choices. So this is a 9. We're only supposed to have exactly 1 9. So how many choices do we have to fill in the rest? Well, we'll have 9 choices here, 9 choices here, and 9 choices here. And then 2 choices here. That's because this is allowed to be anything except for 9. So 0 through 8. This is allowed to be 0 through 8, 0 through 8. This is allowed to be 0 or 5. So in the end, we have 9 times 9 times 9 times 2. That's the number of possibilities for those two cases. Now, these other two are slightly different. So this first entry is allowed to be 1 through 8. It can't be equal to 0 because then we would have a 4-digit number instead of a 5-digit number.
That's so true.
So this can be 1 through 8. That gives us 8 possibilities. Then this can be 0 through 8, 0 through 8. So that's 9 possibilities, and then 2 possibilities. But then that's similar for each of these. We just have the product in a slightly different order. But we could write it all down as 8 times 9 times 9 times 2, 8 times 9 times 9 times 2. Okay, so in the end, how many possibilities are there? Well, there's the sum of those four numbers. But let's notice we can factor a 9 times 9 times 2 out of the whole thing. That's 81 times 2. 81 times 2 is 186. So in fact, we really have 186. And then plus 8 plus 8 plus 8, so that's 24. Plus 9, so that is
no, it's not.
33. So the final answer is 186 times 33. I'll let you do the final calculation.
That just isn't.
Okay, so now that we've looked at the addition principle and the multiplication principle,
That isn't
let's look
correct.
at the subtraction. Now we're ready to look at something called the subtraction principle. So let's say we have a finite
81 times 2 is
U. Then the cardinality of A complement is the same thing as the cardinality of U minus the cardinality of A.
How have they got that?
Let's see that counting principle in example. So our goal now
How
is
have
to
they got that one
find how
then?
many phone numbers contain at least 1 8. So let's maybe recall the shape of phone numbers, at least if you're living in the US.
Oh no.
So they look like this. You have an area code, so that would have 3 choices right here. And then you have a prefix, which is 3 more choices. And then you have the suffix, which is 4 choices.
Okay.
And I don't know the precise rules. Perhaps you're not allowed to start with a 0, but we're not going to worry about the precise rules here, just to simplify the game, and since I don't know them. So let's just assume we have 10 choices for all of these entries. Maybe post in the comments if you know what the rules are, and you can talk about what the real number is based on those rules.
Okay.
So we've got 10 choices for each of these, 10 possibilities. Okay, so I'm gonna first of all just sketch out the way that you might do this without using the subtraction principle. You could break this into the following possibilities. So we want at least 1 8, so you could break it down into exactly 1 8, exactly 2 8s, exactly 3 8s, and then so on and so forth, up to really just all 8s. But I think we can all agree that that's going to be a little bit too much work. So maybe we could do something different. And let's notice that having exactly 1 8 is disjoint from having 0 8s.
Yeah.
And in fact, it's the complement of having 0 8s. So what we can really do here is the following calculation. So all possible phone numbers minus the phone numbers without 8. So phone numbers without 8s. Notice if we were to perform this calculation, we would get exactly what we want. We would get the number of phone numbers with at least 1 8. Okay, but I think we can pretty easily calculate all possible phone numbers. We've got 10 possibilities for each of these 10 choices. So that would be 10 to the 10.
I need to do something.
But now if we're not allowing 8s, then we're allowing 0, 1, 2, 3, 4, 5, 6, 7, 9. So that'll be 9 possibilities, but we're making 10 choices. So it would be 10 to the 10 minus 9 to the 10. But you can calculate this out, and it's actually quite large. It's 6,513,215,599. So that's the number of phone numbers that contain at least 1 8. Now we're going to look at a very special case of this multiplication principle, which we actually saw in practice. And that is the notion of a K permutation. So let's look at the definition. A K permutation of an n-element set is a list of K elements from this set without repetition. Then we can easily calculate that the number of K permutations from this n-element set is, we'll use the notation P of nk, so it's the product n times n minus 1 times n minus 2 ending at n minus k plus 1. So let's talk our way through that real quick. So we're trying to make a list of length k from n element set. For our first choice, we have n possibilities. For that second choice, we have n minus 1 possibilities. That's because we've already used up one of the possibilities. For the third choice, we have n minus 2 possibilities, again, because we've used up 2 possibilities, so on and so forth. Way down here for the kth choice is n minus k plus 1 possibilities. Now, I'd like to point out that sometimes the notation is this n with an underlined k. That's called a falling power. I don't think that's in the textbook that I'm using for the course, but you might see this somewhere.
No.
And then furthermore, if k is between 0 and n, then there's like this nice, more closed formula, which is pnk is n factorial over n minus k factorial. Okay, let's look at an example. Let's say you deal 5 cards from a standard 52 card deck. Then your goal is to determine how many such dealings or how many such hands or possibilities are there that all of them are red cards or all of them are clubs. So let's recall that half of the cards are red cards.
And clubs are black.
So that means there are 26 red cards. So we're thinking about our set as our set is containing 26 cards. And then we want to choose 5 of them from that set. And so this is like taking a 5 permutation from a 26 element set. So that means we get P 26 5. So that's clearly going to be 26 times 25 times 24 times 23 times 22. Great. And then what about all clubs? So there are 4 suits in a deck and each suit has 13 cards. So that means we want to choose 5 cards from that 13 card set. So that means we want to do the number of permutations 13, 5. So that'll be 13 times 12 times 11 times 10 times 9. But then notice that these two are disjoint. If you choose all red cards, you won't choose a club because clubs are black cards. And that means that we can just use the addition rule to find out our total possibilities. So our total possibilities, like I said, will be the sum of these two numbers, which turns out to be 8,048,040. So those are how many possible dealings there are like this. Okay, so it's time to leave you with some warm-up exercises. So here are 2 nice warm-up exercises. So the first has to do with 8-digit binary strings. So those will be lists with 8 digits where each of the entries are either 0 or 1.
Oh, I thought I was going to say binary digits. 0, 1, 2, 3, 4, or 5, man.
So the first is, how many are there with no restrictions at all?
You almost got that wrong.
Second, how many of them have 0 as their second, fourth, and 7th digit? Next, how many have 0 as their second, fourth, or 7th digit? And then finally, last, how many of them contain at least one?
Well, I haven't got a Scooby-Doo boss, man.
For the last problem,
still going?
let's...
Why is it muted? Why can I not hear it? Uh-oh.
This is the 7th video in a series devoted to introductory proofwriting.
Sure.
And we're doing a couple of videos related to counting. So we just made a video on the multiplication principle, the addition principle, and the subtraction principle, as well as k permutations of n elements. And now we're ready to look at subsets of sets within elements and all of the counting that goes along with that. So let's look at our main definition for the day, and that is n choose k, or the binomial coefficient as we'll come to know it a little bit later. So if n and k are integers, then we'll define this symbol right here, which we will read, like I said, as n choose k, as the number of k element subsets of an n element set. So I think that gives you some idea for why we're using the word choose. We're choosing k things from a set of n things. And later we'll get some sort of formula for this, but we're not quite there yet. Let's start with an example where we list all of the subsets of a 4-element set. So we know there should be 16 total subsets from some things that we did earlier in the course. But now we're going to list them by the size of each subset.
My days.
Okay,
Man.
so let's start with this maybe chart right here where we have
different.
K. So this is going to be the size of the subset. Then we'll explicitly list the subsets here, and then we'll count the number of such subsets, which means we're counting the binomial coefficient for choose K. Okay, so since n and k can both be integers here, that means k can be a positive or a negative number or 0. So let's look at this maybe really boring case where k is negative. So it's -1, -2, -3, -4, so on and so forth. Well, now think about this definition right here. It's the subsets with a certain number of elements. You can't have a negative number of elements. That's impossible. So I'll just say that there are no such subsets. I'll put NA here for not applicable. Which means
0.
for choose a negative number will give us the number 0. So now what about 0 element subsets? Well, in fact, there's always a 0 element subset, and it's a unique 0 element subset, which is the empty set.
Oh my god.
And if we count up how many such there are, well, since there's the unique one, we just get the number 1. So this is really important, and this is actually true for any number, and that would be that if you take n, choose 0, you always get the number 1.
Okay.
There's always a single 0 element subset. Now let's look at 1 element subsets. But that's pretty straightforward. You just make a singleton out of every element. Remember, singletons are always going to be like the only 1 element sets by definition. So we have the set containing 1, the set containing 2, the set containing 3, and finally the set containing 4. There are exactly 4 subsets like this.
Okay.
But now if you think of an n element set, then there will always be n 1 element subsets for the same reason as this counting went here. You can just make a singleton out of every element. So in other words, we have n choose 1 is always equal to n. So at least we know those two values in general.
Yeah.
Okay, so now let's go for 2 element subsets. So I think we can make some sort of systematic choice here. Let's do the ones that contain 1 first. So we could have 1 with 2, we could have 1 with 3, or we could have 1 with 4. Those are all of the 2 element subsets containing the number 1. Next, we can have the ones containing 2, 2 with 3, or 2 with 4. We won't have 2 and 1 because we've already counted that one.
Yep.
And then finally, the one last subset would be the subset of 3, 4. So notice there are 6 such subsets. And there's not a quote-unquote obvious way to write down a formula for 2 element subsets. And so we'll wait until we do this in more generality. Okay, so now what about 3 element subsets? Well, in fact, we can do that kind of in line with 1 element subsets. But instead of thinking about which element to include, we think about which element to leave out. So we could either leave out 1, leave out 2, leave out 3, or leave out 4, and that gives us 4 choices. So if we leave out the number 1, we get 2, 3, 4.
Lithium.
If we leave out the number 2, we get 1, 3, 4. If we leave out the number 3, we get 1, 2, 4. And finally, if we leave out the number 4, we get 1, 2, 3. So it's counting just as we counted here, but instead of counting what to include, we're counting what to exclude.
Yeah.
But there are 4 choices for everything to exclude, so we've got a 4 there. And
you know what else just exploded?
How we generalized these two, we can generalize this one as well. And that would be counting how many n-1 element subsets. And there are always n-1 element subsets. We're just talking about what we're including instead of what we're excluding. So now what about 4 element subsets? Well, we've got a 4 element set. There will be a single 4 element subset, and that will be the set itself. So 1, 2, 3, 4. So we've got 1. And then we can generalize this as well very, very easily.
And choose
so how many n element subsets are there from an n element set? There will be 1, so n choose n is 1.
No way.
Now what about 5 element subsets, 6 element subsets, and so on and so forth?
Surely you can't have those.
Well, since we only have 4 elements to work with, we can never get a larger subset than a 4 element subset. So maybe we would also say that this is not applicable, or there are none. which means we get 0 such subsets all the way up there. And we could generalize this as well. N choose k is equal to 0 if k is strictly bigger than n. Or I guess if k is strictly less than 0 based off what we saw up here. So next up, what we'll do is reinvestigate this type of problem for the set 1, 2, 3, and we'll work towards a closed form of this binomial coefficient. So I misspoke on the last board. We're not going to look at subsets of 1, 2, 3. We're going to look at 3 element subsets of 1, 2, 3, 4, 5. This is right at the level where it would be too much to look where the numbers are larger, but this gives us some nice structure, like I said, towards a closed formula for n choose k. So here what I've done. I've made all 3 element subsets of 1, 2, 3, 4, 5. They're pretty easy to write out when the numbers are small like this, but any larger and it would be kind of a chore. And now we're going to build an array here. Let's notice that the number of columns in the array will be 5 choose 3. So let's maybe point that out. So number of columns. So like I said, that's going to be equal to 5 choose 3 because we're making 3 element subsets of a 5 element set. And then from there, what we'll do is build the entries of this table. And what are the entries of this table? Well, the entries of this table will be all 3 permutations of a 5 element set. So all 3 permutations, and I guess I should say of 5 objects. So of 5 objects. And then we're going to list these by 3 permutations that involve 1, 2, 3, 1, 2, 4, 1, 2, 5, so on and so forth. But the fact that we've got like a tool for doing this, we know that there's a closed formula for all 3 permutations of 5 objects. We had some notation for this. It was P of 5, 3, and that ended up being 5 times 4 times 3. Or 5 factorial over 5 minus 3 factorial. So it's a descending product of 3 terms starting at 5. Okay, so now let's fill in the rest of this table. So here we'll have all permutations of the number 1, 2, 3. So we'll have 1, 2, 3, we'll have 1, 3, 2. Those are all the ones starting with 1. Next, we'll have 2, 1, 3, 2, 3, 1. Those are all the ones starting with 2. And then finally, 3, 1, 2, or 3, 2, 1. Those are all the ones starting with 3. Now, we'll go down the line and do that for all of these. I'm not going to, in practice, fill out this whole table because it's just kind of a lot of busy work. But what we'll notice is that each of these columns has the same number of elements. So here we'll make all permutations of 1, 2, 4. So we'll have 1, 2, 4, 1, 4, 2. We'll have starting with 2, 2, 1, 4, and then 2, 4, 1. Starting with 4, we'll have 4, 1, 2, and 4, 2, 1. And then so on and so forth. But notice that each column is made up of 3 permutations of 3 objects. It's just those 3 objects vary. So that means we can count the number of rows. So the rows would be like this row, this row, this row, this row, this row, this row. The number of rows is equal to 3 factorial. That's because we're taking 3 permutations of 3 objects. But now let's notice that we can calculate the entries 2 different ways. The way that we did before, or just by multiplying the number of rows and the number of columns. And given that, we can set up this equation for 5 choose 3 and solve for 5 choose 3 as 5 times 4 times 3 over 3 factorial. And again, that's just by noticing that 5 choose 3 times 3 factorial is this object over here, and then dividing by 3 factorial. Okay, so now we could totally generalize this to have all of the k element subsets here, and then all of the permutations of the entries of the k element subsets here. So here we would have n choose k columns, and then we would have k factorial rows, and then we would have p n k total entries.
That's a lot of entries,
similar like division problem.
Oh my days.
So in the end, that brings us to the following nice closed form for n choose k. So I'll just put squiggle arrow here to say that we've just developed this. We have n choose k is equal to n times n minus 1 ending at n minus k plus 1 all over k factorial. So this descending product on the top is just this p n k. And then furthermore, let's notice that this is equal to n factorial over k factorial times n minus k factorial if k is between 0 and n. And often you're working with k values between 0 and n, so that's okay. And it's equal to 0 otherwise. And that's from reasons that we saw previously. Good, so now let's work through several examples. Now let's look at 2 examples. So the first one is fairly straightforward. Based off our definition, we want to determine how many 6-element subsets of the set containing 1, 2, 3, up to 10. So that'll just very simply, by the definition of the binomial coefficient, be 10 choose 6, which by definition is 10 times 9 times 8 times 7 times 6 times 5. So that's a descending product of 6 things on the top over 6 factorial. But I'll write that out as 6 times 5 times 4 times 3 times 2. And now let's cancel some things out. So we can cancel this 6 here with this 6 here.
Or the 2,
we can cancel 8, this 5 here with this 5 here.
And then
we can take this 4 and this
3 and the 9
and use them to cancel this 8. And then finally we can cancel this 3 with this 9 down to a 3.
Boom.
And that leaves us with 10 times 3 times 7, or in other words, 210.
Oh, thank goodness.
Okay, so now let's ratchet up the complexity a little bit and see how many 6-element subsets of the same set are there with 2 or 3 even elements. Okay, so let's break this into 2 cases. So let's break it into the case where you have 2 even elements. But if you have 2 even elements, that means that you must have 4 odd elements. Okay, so that's pretty clear, because if 2 of them are even, I guess I should say exactly 2 of them are even, then the rest of them have to be odd. But if 3 of them are even, then the rest of them being odd means that 3 of them are indeed odd. Okay, so now we'll use the multiplicative and the additive property here, or principle, I guess it was. So to choose the 2 even elements, that will be 5 choose 2. Because choosing the 2 even elements means that we're choosing 2 elements from the set containing 2, 4, 6, 8, 10, just the even numbers in here. But then choosing the 4 odd elements will be choosing 5 choose 4, because we're choosing 4 from the set 1, 3, 5, 7, 9. So again, still 5-element set that we're choosing 4 elements from. And now we take the product of these by the multiplicative principle, because we choose the even ones and we choose the odd ones, and then finding the total way of making those choices is multiplying them together. Then for 3 even, 3 odd, using the same kind of logic, we'll have 5 choose 3 for choosing the even ones, and 5 choose 3 for choosing the odd ones.
Okay.
And now all that's left to do is some arithmetic.
Okay, let's go.
So this turns into 5 times 4 over 2 factorial, which is just 2, and multiply that with 5 times 4 times 3 times 2 over 4 factorial, which is 4 times 3 times 2. Okay, so let's see this simplify. This 4 times 3 times 2 will cancel this 4 times 3 times 2. And then this 2 will cancel this 5 down to a 2. And we're left with 5 times 2 times 5, which is 50. And now let's look at this. We'll have 5 choose 3 times 5 choose 3. But that'll be 5 times 4 times 3 over 3 times 2, 3 factorial, and then squared. So that's just 5 choose 3 squared. But what do we get there? So
cancel
here, this 3 will cancel this 3. This 2 will cancel this 4 down to a 2, and we'll have 5 times 2 squared, which is 10 squared, which is 100.
Okay.
So now putting these together, we see that there are 150 total such subsets satisfying this condition. Now we've got 2 examples based on the card game poker, and these are like classic counting problems. So our first goal is to determine how many 5-card poker hands there are in general. So that means we've got to choose a 5-element set from a set that contains all of the cards in a standard card deck, which would be 52 cards. So we have 52 choose 5. So in other words, we have 52 times 53 times 52, 52 times 51 times 50 times 49 times 48 over 5 factorial. So I won't multiply that out, but we get a fairly large number of 2,598,000 and then 960.
So true.
So that's how many poker hands there are in total. So now we want to determine how many 5-card poker hands are flushes. Let's recall that flushes means that they have the same suit, and there are 4 suits, and each suit has 13 cards. So let's see, there are spades, there are hearts, there are diamonds, and there are clubs. Okay, so what we really needed to do is determine how many ways can we choose 5 spades, how many ways can we choose 5 hearts, 5 diamonds, and 5 clubs, and then really add them all together.
So true.
But choosing
This
spades
is how
will give us
everything
13
works.
choose 5, because we have to choose a 5-element subset of a 13-element set. It's just the 13-element set here is all of the spades. But it's going to be 13 choose 5 for all of these because each of the suits have the same number of cards. So we have 13 choose 5 added to itself 4 times, or just 4 times 13 choose 5.
I will not be doing this.
Being 13 times 12 times 11 times 10.
I'm going to let this guy do all the heavy lifting.
Times 4 over.
And I can do the mental maths.
Which is 5 times 4 times 3 times 2. Nominally times 1.
What can you do? Cancel the 4.
Okay, so notice I snuck the 4 in way over there. Now let's simplify these as we can. So we can take this 4
13,
times
12,
3
11,
and have
3.
it cancel this 12.
Okay.
We can take this 5 times 2 and have it cancel this 10. And in the end,
13,
we have
11,
13
9,
times
4.
11 times 9 times 4.
That's a
and
big
if you
number.
multiply that out, you'll get 5,148. So there are 5,148 total flushes, whereas there are like 2.5 million total hands. So if we were calculating probabilities, you would see that the probability of getting a flush is quite low. Okay, let's do another poker example. Okay, so next up we're going to determine how many poker hands are a full house. So that's another type of poker hand, and this type of hand has a pair and 3 of a kind. So for instance, you might have a pair of 2s and then 3 5s. Or you might have a pair of aces.
I'm pretty sure I understand this.
Queens. Okay, so by the multiplicative principle, what we need to do is determine the number of ways
big funny university words.
3 of a kind, and then also
Whereas I did it with little baby child words.
Ways to make a pair and take the product. But the important thing is that the number of ways to make a pair after making 3 of a kind is different than the number of ways to make a pair just kind of on its own. So we'll have to be careful with that. And you might say, well, does that mean that we should count this by making the 3 of a kind first and then the pair second, or vice versa? Well, in fact, it doesn't matter, and that's because of some relationships between the individual binomial coefficients, which you'll likely see on your homework exercises. So let's calculate the number of ways to choose 3 of a kind. So let's notice for each
This guy's going to knock on my door in a week's time.
So what I mean by that is that in the deck
hand me
there are 4
homework.
kings, there are 4 jacks, there are 4 aces, there are 4 5s. So we want to choose 3 of those 4. So that means building off of this, we'll have to choose 3 of a 4-element set. So let's say we want to choose 3 7s. How many ways can we choose 3 7s? Well, there are 4 choose 3 total ways. But we don't just want to, for instance, choose 3 7s or 3 9s. We just want to choose any 3 of a kind. So how many different rankings of cards are there? There are 13. So that means we'd multiply this by 13. Really, we're adding 4 choose 3 to itself
54.
13 times. And that would be for choosing 3 aces or 3 2s or 3 3s or 3 4s, so on and so forth. Okay, so that's the number of ways to choose 3 of a kind. Now, after choosing that 3 of a kind, we need to make a pair. So how can we make a pair? Well, again, there are 4 of each ranked card, and we want to choose 2 of them. So there are 4 choose 2 ways to make a pair. If we're like choosing 2 of 4 sevens.
How would you eliminate getting
but
5?
Now we can choose 2 of anything that remains. But
just 12,
how many
right?
remain? Well, there are 12 different ranks of cards that remain after making our 3 of a kind. So in the end, we need to take this product. 13 times 4 choose 3 times 12
so
times
that's like
4 choose
52
2.
times.
Then if you multiply this all out,
72.
which I won't go through the details, you can use similar strategies to what we did on previous boards. You'll get 3,744. Notice that's less than the number of flushes. And that makes a full house less likely to occur than a flush. And in fact, it is a higher ranked hand in poker.
Cool.
Okay, so now we're going to work towards some nice relations involving these binomial coefficients, and then look at some other applications. Now we're going to start looking at some of my favorite things, which are the relations between the binomial coefficients.
Ay,
So
caramba!
let's look at this nice one. In fact, this one can be used to define the binomial coefficients if we'd like to. And what it says is if we have natural numbers n and k is between 1 and n, then the binomial coefficient n plus 1 choose k is equal to n choose k minus 1 plus n choose k. Let's see why that is the case. Well, let's start with a subset A of 1 up to n plus 1. And let's assume that it has k elements. I won't write that down, but maybe I will write that down as the size of A equals k. The cardinality of A is k. Now, how many such A are there? Well, there are n plus 1 choose k. Okay, so now next up, we'll notice that A must satisfy exactly one of the following conditions. So I'll maybe put those conditions as these 2 blue dots. So n plus 1 could be an element of A. Well, that's possible because A is a subset, so that was sloppy. That should be a subset of that because A is a subset of 1 up to n plus 1. But now if A contains n plus 1, then how many such A are there? Well, it has k elements in total. If it has n plus 1 in it, then there are k minus 1 remaining choices. And you can make those choices from 1 to n. So there are n choose k minus 1 possibilities for A. But what's the other case? The other case is that n plus 1 is not in A. But that means that all of the choices for elements of A are open. We can choose k total elements. But we can only choose them from the set 1 to n because we're not allowed to choose n plus 1. So that tells us that we have n choose k possibilities left over. And that's like a nice combinatorial interpretation of this setup. Or we could also establish this with a straightforward calculation. Let's do that as well. So I'll start with the right-hand side. N choose k minus 1 plus n choose k. So n choose k minus 1 is a descending product of k minus 1 terms. So n times n minus 1 all the way down to n minus k plus 2. That would be k minus 1 factors in the numerator. And then over k minus 1 factorial. Then we're going to add that to n times n minus 1 all the way down to n minus k plus 1. That is k terms in the numerator, and then over k factorial. Next up, we'll give these two a common denominator, and we'll do that by multiplying this first one by k over k. So that leaves us with n times n minus 1 all the way down to n minus k plus 2 times k over k factorial, and then plus this n times n minus 1 all the way down to n minus k plus 1 over k factorial. Now we have a common denominator, we can put these together. But actually, let's maybe take this second term and rewrite it by putting the next to last term in. So we'll have n minus k plus 2 and n minus k plus 1. And now as we add these together, let's factor out this descending product from n to n minus k plus 2. So what does that leave us with? We'll have n times n minus 1 all the way down to n minus k plus 2. And then left over will be this k term here, and then this n minus k plus 1 term here. So we'll have k plus, because we have this plus sign here, n minus k plus 1. And then this is all over k factorial. But now let's notice that this k here cancels this k here, and we're left with n plus 1. And now we can put that n plus 1 over here at the front. So let's do that, and maybe scrub this out in total. But that leaves us a descending product of k terms in the numerator starting at n plus 1 over k factorial. In other words, we have the binomial coefficient n plus 1 choose k. So there we have it. We have two arguments for the validity of this observation. First is a straightforward calculation, like I said, and the second one is this nice combinatorial argument where we take subsets of the set containing 1 to n plus 1 and partition them into two.
Yeah, of course, man. Of course.
Okay, so now armed with this observation, I want to build something really nice, which you've probably seen before, called Pascal's triangle.
Oh yeah, I've seen that before in class. That shit was
discovered
funky as hell, bro.
To build something called Pascal's triangle. And so you might recall that this is a triangle formed from a certain rule where as you descend, you add neighbors together. Well, that's exactly what's happening here. You would add neighbors together to get the term that's below and between.
Oh, that's crazy, bruh.
So it started with just like a tree of ones, but those ones are playing either the role of something choose 0 or something choose itself. Again, those are like 0 element subsets or subsets like that are full, if you will.
Yeah.
Okay, so now we can start adding things together. So what should 2 choose 1 be? Well, 2 choose 1 is 1 choose 0 plus 1 choose 1. So that means you would add these two together to get this number right here. You would get 2. Okay, and then this is the 3 choose row. So here we have 3 choose 0 is 0, 3 choose 3 is 3. So what's 3 choose 1? Well, it's going to be the sum of these two above it, or 1 plus 2 is 3. And likewise,
that also be 3.
3 choose 2
my
will
God!
be the sum above
That
it
is
as well.
epic!
And now we can just descend
No
all
way.
the way down. So adding the 2 above it will give us 4, 6, 4. Here we'll get 5, 10, 10, 5. Here we'll get 6, 15, 20, 15, 6. Okay, so how do you read this? Well, this row right here is the 6 choose k row. And for instance, this entry right here will be 6 choose, let's see, 0, 1, 2, 3, 4. So this is the 6 choose 4 entry. So that means 6 choose 4 is 15. Okay, so now let's investigate some more things involving these binomial coefficients. Now we're going to look at my favorite defining property of binomial coefficients, and that is that the coefficient of the monomial x to the n, y to the n minus k in the binomial expansion of x plus y to the n is n choose k. And the idea behind the proof of this goes like this. So if we take x plus y to the n and write it out as x plus y times x plus y n times, then we can easily count up the way to achieve x to the k, y to the n minus k. So let's write that down. So let's say we want to achieve x to the k, y to the n minus k. So really all we have to worry about is achieving x to the k. The y to the n minus k kind of comes along for free. Okay, so how do we do that? Well, among these n factors, we choose x exactly k times. So let's write that down. So we will choose x from k of these factors. So while we're doing the big product. So maybe we choose x here, we choose x here, we skip some x's, and then we choose x again until we've chosen k x's. But how many ways can we choose k x's from this list of n total factors? Well, that's exactly the definition of binomial coefficient. So multiplying this out, we'll get n choose k times x to the k, y to the n minus k. Okay, so that leads us to the very important formula, which is a lot more powerful than it might seem initially. And that is, if we take x plus y to the n, we get the sum as k goes from 0 up to n of n choose k, x to the k, y to the n minus k. Okay, nice. Okay. And now from here we can do lots of nice sum identities really quickly. So let's do those via some examples. Let's first determine n choose 0 plus n choose 1 plus n choose 2 all the way up to n choose n. So I'll do this two different ways. I'll do it with a combinatorial approach using subsets, and I'll also use this sum formula. So let's notice that this is equal to the sum as k goes from 0 up to n of n choose k. But that's equal to the sum as k goes from 0 up to n of n choose k times x to the k, where we've evaluated x at 1. And we've not only evaluated x at 1, but we've set y equal to 1 in this initial thing. And I would say that it's common to have this formula here with y equals 1. Okay, but let's notice that this is equal to x plus 1 to the nth power evaluated at x equals 1. But that's just 1 plus 1 to the n power, or in other words, 2 to the n. So what's another interpretation of this? Well, we could interpret this by our original definition. So this would be the number of 0 element subsets plus the number of 1 element subsets all the way up to the number of n element subsets. But that's all possible types of subsets. So that should equal the total number of subsets. But the total number of subsets from a fact that we had before was 2 to the n. So that would be another interpretation. Okay, so let's do one more before we end with some warm-up exercises for you to try. Okay. And that's the sum as k goes from 0 to n of minus 1 to the k, n choose k, 7 to the n minus k times 2 to the k. Okay, nice. So this seems like it might be really difficult, but if we just think about it as probably evaluating this binomial raised to a power at some certain numbers, it shouldn't be that bad. Okay, so let's maybe put all the powers of k together. We have minus 1 to the k and 2 to the k. So this will give us the sum as k goes from 0 to infinity. We'll have n choose k minus 2 to the k and then 7 to the n minus k. And now this looks exactly like this thing over here. Wow. So this is equal to the sum as k goes from 0 to n, I should say. So that was infinity before, but that should be n. Okay. Of n choose k, x to the k, y to the n minus k, where x is equal to negative 2.
If that shit went to infinity, that'd be
but that's going to be equal to minus 2 plus 7 to the nth power based off this rule right here. But that's equal to 5 to the nth power. So that's a quick proof of kind of an identity that seems kind of gnarly. Okay, so let's end with some warm-ups for you to try. So here are 5 nice warm-up problems based off what we saw. Whew. So the first is to find the cardinality of the following set. So the set is all x and the power set of the set containing 1 to 12.
We still going strong.
The cardinality of x is equal to 6.
We still going strong.
The next is to answer how many poker hands have one pair and nothing else. Next, suppose there are 126 5-element subsets of A.
God.
What's the cardinality of A? Next,
Jesus
let's determine
Christ,
the
man.
x to the 4th y cubed from the expansion of 5x minus 2y to the 7th.
Okay.
And finally, simplify the sum as k goes from 0 to n of 6 to the k over 3 to the n times n choose k. And that's a good place to stop. This is the 8th video in a series devoted to introductory proofwriting. And we've been going through counting strategies, and we're going to continue to do that for this video as well as the next, focusing on combinatorial proofs in the next. Whereas this one, we're going to look at the inclusion-exclusion principle, as well as something called multisets. So let's start with this inclusion-exclusion principle, which very simply says that if A and B are finite sets, then the cardinality of A union B is equal to the cardinality of A plus the cardinality of B minus the cardinality of the intersection of A and B. And we can visualize this as follows. So if we've got A as this yellow set, B as this red set, then the intersection is in here like shaded in orange. And notice if we were to add the cardinality of A and the cardinality of B, we would double count the cardinality of the intersection.
That is so true.
And so in order to only single count the cardinality of the intersection, we need to subtract one copy off. So like I said, it's counted twice, but if we want to only count it once, that's why we have this subtraction of the cardinality of A intersect B there. Okay, so let's start with a fairly simple example, and that is to count the number of elements in the set 1, 2, 3, 4, up to 50 that are divisible by 2 or divisible by 7. So let's put this into the language of some sets first. So let's say that A is all in the set 1 to 50, such that n is divisible by 2. So we could write it in set builder notation like this. But notice being divisible by 2 is the same thing as being even, and we can easily enumerate the elements in this set. So we've got 2, 4, 6, 8, 10, 12, all the way up to the number 50. So the number 50 itself is, of course, even. But how many of these are there? Well, I think it's pretty easy to count up that the cardinality of A in this case is simply 25. And you can count that very easily as saying that this is 2 times 1, 2 times 2, all the way up to 2 times 25. So really just we're counting 1 to 25. So now let's look at B. So B is going to be all elements in this set, such that n is divisible by 7. So that's our definition there. Again, we can enumerate this pretty easily as well. We have 7, 14, next would be 21, then 28, then 35, then 42, and then 49. In fact, we don't need to do ... here because there's a smaller number. Okay, but let's look at this. This is 1, 2, 3, 4, 5, 6, 7 total elements. So here the cardinality of B is 7. Well, we could count that up pretty easily as well by noticing that this is 7 times 1, 7 times 2, up to 7 times 7. Now let's look at A intersect B, which we can do just by taking the elements of B which are even. Of course, that's going to be 14, 28, and 42. But that means that the cardinality of A intersect B is simply the number 3. Okay, nice. And so now in order to answer this question, we can apply this inclusion-exclusion principle. Notice that answering this question is equivalent to finding the cardinality of A union B. So using this principle, we'll have 25 plus 7 minus 3.
29!
So let's see, that'll be the same thing as 25 plus 4, which is 29. So there are 29
that was a tricky one.
Subsets. So there are 29 such elements. Now for another example. And in this example, we're going to count up how many integers are between 0 and 10 million, where they have exactly 4 digits that are equal to 1, or exactly 2 digits that are equal to 9. So let's quickly notice that this being between 0 and 10 million means that n has the following form. So it's equal to a 7-digit number. So let's write this out. So we have 1, 2, 3, 4, 5, 6, 7. And that's where we're allowing 0 to be leading digits. So we would allow something like 0, 0, 0, 0, 1, 2, 3. That would be an allowed 7-digit number in this case.
Sure
now,
thing, buddy.
often if we were just to say a 7-digit number, we would not allow a leading 0. But in this setup right here, where we have n between 0 and 10 million, we do allow leading zeros. Okay, let's also notice that 0 is not a possibility in this setup, even with leading zeros, because we must have either exactly 4 digits equal to 1 or exactly 2 digits equal to 9, which means the smallest such possible number would be 99. Okay, so now let's get counting. So let's maybe first look at the condition exactly 4 digits equal to 1, and let's count that up here next to this yellow square.
Okay.
And then we'll look at the exactly 2 digits equal to 9 with a magenta square underneath after we're done with this. Okay, so we've got 7 entries here. We want to choose exactly 4 of them to be equal to 1, so that's using a binomial coefficient. We have 7 choose 4. So like I said, this is choosing the location of the ones. Great. But then after we choose those 4 locations of a 1, we have to fill in the rest of the digits. But
no
how can we
one.
fill in the rest of those digits? Well, they can be really anything that we want, except they cannot be ones because it's saying exactly 4 ones. So that means we need to fill in 3 digits from 9 possibilities. Those 9 possibilities being 0, 2, 3, 4, 5, 6, 7, 8, 9. So in total, we have 9 cubed extra possibilities. So this would be the remaining digits. So I'll just put remaining here. Okay, good. So that's the number of ways to have numbers between 0 and 10 million where exactly 4 of the digits are equal to 1. Now let's look at this next case. Exactly 2 digits equal to 9. So I'll do that with this magenta coloring here. Okay, so we need to choose 2 of these 7 placements to be equal to 9. So that would be 7 choose 2. Then after we've chosen 2, there are 5 ones that we need to fill in, and we can fill those in with any numbers except for 9. So that means we can fill them in with the numbers 0, 1, 2, 3, 4, 5, 6, 7, 8. So there are 9 possibilities there. So we have 9 possibilities for each of the 5 remaining. So that would be 9 to the 5 total possibilities left over. Okay, so let's just point out that this is the location of the 9s, and then this right here is the remaining. So it's a little bit tricky because this is locations of 9s and we're using 9 again here, but those are playing different roles. Okay, so this would be like our set A, or the cardinality of our set A. This would be like the cardinality of our set B. And now we need to look at the cardinality of the set A intersect B. So let's put these together right here. So I'll just put yellow square plus magenta square. So that means we need to choose 4 boxes from this set to be ones. So that would be 7 choose 4 because we've got 7 empty boxes to choose. But after choosing 4 of those boxes, there are 3 remaining boxes, but we need to choose 2 of them to be 9s. So from those 3 remaining boxes, we choose 2 of them to be 9s. So let's just point out that here we're choosing the location of the ones, and here we're choosing the location of the 9s, like that. But then after that, we've used up 6 total digits. 4 of them for ones, 2 of them for 9s, which means we have 1 digit left over to fill up. But we can fill that up with any number except for 1 or 9. So that comes from the set 0, 2, 3, 4, 5, 6, 7, 8. So there are 8 total possibilities for that remaining digit. So let's put here, this is the remaining digit. Good. So now we need to use the inclusion-exclusion principle to finish this thing off. So it'll be this number here plus this number here minus that number over there. So let's just write this. So it'll be 7 choose 4 times 9 choose 3, and then plus 7 choose 2 times 9 to the 5th power, and then minus 7 choose 4 times 3 choose 2 times 8 to the 1st power. So I won't calculate that up, but you can use the formula for binomial coefficients to easily calculate that up. It's going to be a fairly large number, so you probably want to use some sort of computational device. Now, what I will say is there seems to be something fishy going on here, because what would happen if at this step right here, we first chose the location of the 9s, and then after that, chose the location of the 1s? Well, choosing the location of the 9s, we would have 7
I'm jotting this down as we speak.
And then choosing the remaining location of the 1s, we would have 5 choose 4, because we've got 4 locations to choose again. And it seems like we would get a different number, but in fact we don't get a different number because this is one of those binomial coefficient identities. So you can check that those two are the same. And in fact, there's a more general identity, which is a nice homework problem, which you might have in whatever course you're taking, and you'll definitely have in the course that I'm teaching. So now that we've done a couple of these inclusion-exclusion examples, let's move on to talk about multisets. Now we're ready to explore the notion of a multiset. So let's look at a definition. A multiset is a collection of objects which may be repeated. So this is kind of a generalization of a set and a list. It lies kind of in between a set and a list. Let's recall that objects in a list can be repeated, but the order matters in the objects of a list. Like 1, 1, 2 is thought of as being different than 1, 2, 1. Wow. Whereas in a multiset, that's not the case, as we'll see with an example. Then that repetition can be recorded in a multiset by the notion of a multiplicity. So the multiplicity of an element in a multiset is the number of times it occurs. So let's look at this very simple example, as well as some notation that we can build out of this example. So let's say we've got the multiset, which I'll call capital X. We'll use the notation where we have these square brackets. So that's different than what we used for lists, which was round brackets or parentheses, or for sets, which was curly braces. So here X is the multiset AA, B, 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 C. So there are 6 elements in this multiset. It just happens that 2 of them are equal to A and 3 of them are equal to B. So that means A has multiplicity 2, which we'll denote like this, M sub X, so X is the name of the multiset, of A equals 2. So that's the element right there. Then the multiplicity of B is 3, so that's what we would read here, and the multiplicity of C is 1, because it only occurs once. You might read this holistically as the multiplicity of B in X is 3. Now, I'd also like to point out that we could write the multiset X in a different ordering if we wanted to, and it's still the multiset X. So we could indeed write it as B, A, B, A, B, C. Yeah. So there are 2 A's, 3 B's, and a C, and that's all that matters. Furthermore, I'd like to point out that any set is a multiset. It's a multiset where everything has multiplicity 1. Okay, so since we're talking about counting, we want to move up towards counting certain multisets. And we'll start that with an example. So let's say we've got a 3-element set, and we want to find all multisets that contain elements from this 3-element set. So let's start with 0-element multisets. Well, there's only one 0-element multiset, and that's the same thing as the 0-element set, which is the empty set. Okay, now let's look at 1-element multisets. Well, 1-element multisets are just singletons, just like 1-element sets. If you only have 1 element, there's no opportunity for repetition. So here we would have 1, the multiset, the multiset 2, and the multiset 3. Of course, we could write that in curly braces because multisets and sets are the same when they have either 0 or 1 element. Now let's look at 2-element multisets. So we've got more of them here. We've got like 1, 1, 2, 2, 3, 3. So those are all of the
I
ones
really
that are
hope no
not
one's watching the
sets
whole thing.
themselves. We have repetition.
That would suck.
But we could also have 1, 2, we could have 1, 3, or we could have 2, 3. So those are all the ones that turn into sets. They do not have repetition.
Yeah.
Okay, so next up I want to introduce some notation, and this notation will help us eventually count the number of multisets.
Gotcha.
And so let's just get into writing this notation, and then we'll explain how it works. So I'll denote this multiset 1, 1 as star, star, and then bar, bar. So this means that there are 1, 2, 1s, but there is 0, 2, and 0, 3. So I'm separating the elements 1, 2, 3 by these bars right here. And so depending on the placement of the bars, that tells me how many 1s there are, how many 2s there are, and how many 3s there are.
By video 8.
So now let's look at 2, 2, the multiset 2, 2. So that would be bar, star, star. That's how we would denote that. And that's because there are 0 1s, so there's 0 stars right here. That denotes the number of 1s. There are 2 2s, and there are 0 3s. Okay, well, let's look at 3 3. So that would be bar, bar, star, star. So reading into this, since there are 0 stars in this location right here, that means there are 0 1s in the multiset. There are 0 stars in this location right here. There are 0 2s in the multiset. But there are 2 stars here.
Star bar.
That means there are 2 3s in the multiset.
Question mark?
Okay, let's move on to the next one. So 1, 2. So that would be star, bar, star, bar.
What the fuck?
So this placement right here is for the number of 1s. There's 1 of them. This placement right here is for the number of 2s. There's 1 of them. This placement right here would be for the number of 3s, but there are 0 of them, so that's left blank. Okay, so let's look at 1, 3. So that would be star, bar, bar, star. Notice the place that would count the number of 2s is empty because there are 0 2s. Okay, finally, let's look at the set 2, 3, the multiset 2, 3. So that would be bar, star, bar, star. So this spot right here that would count the number of 1s is empty. So now let's look at 3 element multisets. So let's start with 1, 1, 1.
Oh no.
And 2, 2, 2, and then 3, 3, 3. So those are all of the multisets that only contain one type of element. They all contain 3 elements, but only one type of element.
Got it.
And we could put this into the star and bar notation as follows. So this first one would be star, 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 bar, bar. So the location where we count the number of 1s has 3 stars. The location where we count the number of 2s and the number of 3s is empty. Now let's look at this next one, 2, 2, 2. So that would be bar, star, 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 bar. So where we count the number of 1s is empty, the number of 3s is empty, the number of 2s, there are 3 of them. And then finally for 3, 3, 3, we would have bar, bar, star, star, star. Again, the place where we count the number of 1s is empty, the number of 2s is empty, but the number of 3s has 3 stars. Okay, so let's get a little bit more interesting. Let's maybe look at the multiset 1, 1, 2. So that's definitely a 3-element multiset. So that would be star, star, bar, star, bar. So again, we're counting 2 1s, 1 2, and 0 3s. Okay, so let's do a couple more. We won't totally enumerate these, but we will do enough to get an idea for what's going on. What about 1 3 3? So there's a single 1, and then 0 2s, and then 2 3s. So the place where we count the number of 1s has a single star, where we count the number of 3s has 2 stars, the place where we count the number of 2s has 0 stars. So that would be the star bar diagram for 1 3 3. Now let's go ahead and look at some 4-element multisets from, like I said, the set containing 1 2 3. And I just want to be clear that this is not a full enumeration of the 3-element multisets. It might be a nice warm-up exercise for you to write down the rest of them if you'd like. Okay, so now let's look at some 4-element ones. I'll just say that there are 15 in total, and we'll be able to calculate that later, but just like I did not enumerate all of them here, I won't enumerate all of them here. I think it'd probably be a good exercise for you to as well. Okay, so let's maybe look at this one.
Is it just 3 elements and then just whack a 1, 2, and 3 on the end?
3. So that's definitely an example. So let's see. We would have 3 stars in the 1 position, then a bar, 0 stars in the 2 position, so that means there's 2 bars next to each other, and then a single star in the 3 position. So that would be the diagram for this multiset. Okay, let's look at another one. Maybe 1, 2, 3, 4. So there's a single star in the 1 position, a bar,
star, bar, star, bar, star, star,
bar, and then 2 stars in the 3 position. That's how we would count that up. So let's maybe look at 2, 2, 3, 3. So that's kind of an interesting multi-set. So it only contains elements from 1, 2, 3. It's missing 1, but then it has 2 each of 2 and 3. So that would have 0 stars in the 1 position, and then 2 stars in each of the 2 and the 3 position. So that would be our diagram there. So I said there are 15 in total. We've done 3 of them, so that means there are 12 left. Again, that would be a nice homework exercise. Okay, so now that we've kind of explored these multi-sets quite a bit, I think we can probably count up how many there are in general. Now we're ready to count k-element multisets from an n-element set.
Yikes!
That leads us to the following claim. That is, there are n plus k minus 1, choose k-element multisets from the set containing 1, 2, 3, 4 up to n, or really any n-element set. That being said, if you've got an n-element set, it might as well be equal to 1, 2, 3 up to n, especially if there's no additional structure to it. Now, some of you may like to learn extra notation. I know that when I was a student, I liked to learn extra notation. And in fact, there is notation for this number of k-element multisets.
Bonus!
And it goes like this.
No way.
So n plus k minus 1 choose k is this kind of like, I don't know the name of it, but it's this binomial coefficient where you have an extra parentheses. And furthermore, you can check this, but it's equal to n times n plus 1 all the way up to n plus k minus 1 over k factorial. But this is very, very close to a normal binomial coefficient, but instead of having a lowering factorial or a descending factorial, a falling factorial of k terms starting at n, we have what's called a rising factorial of k terms starting at n. So notice this is the product of k terms, n times n plus 1 times n plus 2 all the way up to n plus k minus 1, where we start at n. And just as we saw earlier notation for this falling product, which was k underline, there's notation for this rising product of k over line. Okay, so like I said, this is just some bonus notation for those that are interested. I know that I was super psyched about things like that when I was
I am not interested.
Okay, so let's maybe do a little bit of a proof of this claim. So let's maybe suppose that A is a k-element multiset from the set containing 1, 2 up to n. Now I'm going to introduce some notation for A. So I'll write A as follows. So it's going to be the multiset 1 to the m1, 2 to the m2, all the way up to n to the mn. So those don't really mean exponents. I'll show you what those mean, but these need to satisfy a certain rule, and that is m1 plus m2 plus all the way up to mn is equal to the number k. Okay, great. But what do I really mean by this notation? So let's be careful to sort that out over here. So the multiset, which would be like 1 cubed, 2, 4, and then 3, 2, would be the multiset where we have 3 1s, 4 2s, and 2 3s. So in other words, it would be 1, 1, 1, 2, 2, 2, 2, and then 3, 3. Okay, so that's just some shortened notation for this multiset. I don't know how common it is. I know it's like sort of common to use these exponents for repeated appearances of numbers when you're studying integer partitions. And I know something about integer partitions, so that's where I'm taking this notation. Okay, so now what we will do is take this multiset and attach it to one of these diagrams. Okay. And then we can count the number of such diagrams. And after counting the number of such diagrams, well, that'll be the number of such sets, and we'll be good to go. So what would the diagram be? Well, it'll be one of these star and bar diagrams where we have M1 stars in the 1 position, M2 stars in the 2 position, and so on and so forth. So it would look something like this. Star, 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 so a bunch of stars, and then a bar, and then a bunch of stars, and then another bar, and then that ends with a bar and a bunch of stars. So something like this.
Oh yeah, star, bar,
and
bar,
like I said, this denotes the first position, so the position of the number of ones. So that means there are M1 total stars here. Then this is the position for the number of 2s, so there are M2 stars there. And finishing off way down here, this denotes the number of n's, so there are M sub n number of stars here. So there's a really important thing to note here, and that is if we take out all of the bars, there are exactly k stars. So let's point that out. So there are exactly k stars. Great. And then how many bars are there? Well, notice the bars separate the number of 1s from the number of 2s, from the number of 3s, all the way up to the number of n's. So that means we have exactly n minus 1 bars. So let's write that down. N minus 1 bars, because there are n minus 1 places between each of the numbers. There's a spot between 1 and 2, there's a spot between 2 and 3, there's a spot between 3 and 4, there's a spot between n minus 1 and n. So now putting this together, we can see how many characters there are, and that would be the sum of these two objects. So there are exactly n plus k minus 1, like I'll say there are characters. So really we're thinking about making a word, and that word has n plus k minus 1 characters, but there are only 2 possible letters. You could have the letter which is a star and the letter which is a bar. And now we're ready to finish off our counting, and it goes like this. So from the n plus k minus 1 characters, we choose, let's see, k of them to be stars. But how many ways are there to choose k objects from n plus k minus 1 objects? Well, that's
so
exactly
many, bro.
the binomial coefficient, which we learned about in the last video.
Of course,
so
of course, of
that
course.
leads us to our result, which is there are n plus k minus 1 choose k such choices. And each of those choices gives us a new multiset.
I do remember that one.
So that counts the number of multisets. But you might worry a little bit right here, and you might worry because what if instead of choosing the location for the stars, we chose the location for the bars? Notice that we'll choose n minus 1 spots for the bars, which would give us the binomial coefficient n plus k minus 1, choose n minus 1. Well, in fact, those two are the same number. So let's put that in here. This is the same thing as n plus k minus 1, choose n
I love numbers when they're the same.
And that's from a binomial coefficient identity, which likely you saw in homework. Okay, so that clears up the proof of this result. Now let's do some examples based around this. So our first example will be to count the number of non-negative integer solutions to the equation x plus y plus z equals 17. This is an example of something called the linear Diophantine equation. So what we'll do is start with the solution, attach it to a multiset,
that sounds familiar,
and use that to come up with some sort of counting argument. We know we should attach it to a multiset because, well, of course, we're looking at examples involving multisets right now. Okay, so let's look at a solution, maybe x equals 10, and then y equals 5, z equals 2. That's most definitely a solution because 10 plus 5 plus 2 is equal to 17. Okay, so now, like I said, let's attach this to a multiset. Well, maybe we'll first attach it to one of those diagrams, and after which we'll attach it to a multiset. Well, maybe the diagram could be something like this. Star, 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 star. I'm making 10 stars, by the way. So 1, 2, 3, 4, 5, 6, 9, 10.
Okay.
And then, so this would represent the value of x. And then this line would be kind of like the plus sign. And then we'll have the value of y, which is 5. So star, star, star. So 5 stars. And then 2 stars for the value of z. And in particular, what you can think about this is having 17 stars and then choosing where to put these 2 bars. And those 2 bars will split your number into x, y, and z. But let's notice that this corresponds to the following multiset. So instead of using 1, 2, 3 here, I'll use x, y, z. So this would be the multiset x, x. Well, how many of them will have
of course,
10 of
there's
them?
10 of them.
And then y,
and 5
y,
of them.
y.
And
So
2 of
we have
them.
5
Oh my
y's.
god.
And then finally, we'll have 2 z's. Great. So let's notice that this is a 17-element multiset from a 3-element set. So that tells us how many solutions do we have? Well, we'll have 17 plus 3 minus 1. Choose 17. So just to reiterate what I just said, this is a 17-element multiset from X, Y, Z, a 3-element set. So of course that's going to be 19, choose 17, and you can work that out and it'll be 171. Now we could also use the notation that we had before over here. This is equal to 317, where we have this different type of binomial coefficient. So this would be a rising product starting at 3 for 17 total terms. And so let's see, that's going to end at 19, and then it'll be over 17 factorial. Again, that's from this like bonus notation over here. Okay, so let's look at a generalization of this example. Okay, so now, like I said, we're going to look at a generalization of that example. Let's look for all non-negative integer solutions to x1 plus x2 plus x3 up to xn equals k. Okay, so this is the same sort of idea. Okay, so let's say that we have a solution, and our solution is xi equals mi. Now we can take that solution and attach it to a multiset. The multiset would look something like this. So it would be x1, x1, and there would be exactly m1 of these. And then it would be x2, a bunch of x2s, and there would be exactly m2 of these, all the way up to xn, xn, and there would be exactly mn of these. But what is that really doing? Well, how many total entries are there in this multiset? Well, since xi equals mi is the solution, there are m1 plus m2 plus up to mn total elements in this multiset, but that's equal to k. Again, that's because this is a solution to that equation. So what are we doing here? Well, we're finding multisets with k elements from n total elements. So let's see, each of these corresponds, like I said, to a k element multiset of an n element set. That n element set is written as x1 up to xn. So we know exactly how many of those there are, and those are n plus k minus 1, choose k such solutions, because that's the same number as the number of multisets. Okay, let's do another example. Okay, so now I've got an example which actually has a nice geometric interpretation. That geometric interpretation is hard to see in higher dimensions, but it's fairly easier to see in a simple 2-dimensional case, which we'll look at. So our goal is to find all integers w, x, y, z such that
there's more than 3 letters?
W, which is less than or equal to x, which is less than or equal to y, which is less than or equal to z, which is less than or equal to 10.
Okay.
So like I said, there's a nice 2-dimensional analog
which
has a nice geometrical interpretation, and it goes like this. Let's say we want all x and y integers satisfying 0, less than or equal to x, less than or equal to y, less than or equal to 5. Well, if we were to graph all of those, we would get this nice triangular shape. So notice this kind of hypotenuse of the triangle is all of the cases where x equals y. That's allowed here. So this would be
x and y allowed.
0, 1, 2, 3, 4, 5. And then filling in the rest of it are the cases where x is less than y.
Okay.
So like I said, we get a nice triangle here. And that's in fact going to be some sort of triangular number. If we were to add all of these up, we would have something like this. 1 from this, plus 2, plus 3, plus 4, plus 5, plus 6. So we have 1 plus 2 all the way up to 6. That would be the total number here.
Okay.
But of course, we're doing this in this larger case.
Was that 21?
So you could maybe think about the three-dimensional version as some sort of tetrahedral number, right? Because okay. So let's maybe think about how we might take certain quadruples here. Well, like I said, we're going to look for x, w, x, y, z, but let's organize them in a quadruple, w, x, y, z. And what we'd like to do is assign each quadruple to a multiset. But let's do that via a couple of examples first before we get an idea of how it works. So let's look at 1, 2, 3, 4. That's definitely a quadruple that follows our rules. And let's organize this into a multiset where we have 10 total entries or 10 elements. And what these numbers are telling us is the location of the bars. So we'll have a star and then a bar after the first star, and then we'll have star, bar, star, bar, star, bar. So like I said, this is telling us the location of the bars. There's a bar after the first star, after the second star, after the third star, and after the fourth star. But after that, there are no more bars. So that means I need 6 kind of free stars here. Okay, great. So notice that this is one of those diagrams for a 10-element multiset of a how many element set? Well, I think it's going to be a 5-element set. So 5-element set. Because notice the number of bars is equal to 1 less than the total number of elements. And in fact, we can turn this into our multiset notation as follows. So it would look like 1 to the 1, 2 to the 1, 3 to the 1, 4 to the 1, and then 5 to the 6, because there are 6 copies of 5. Okay, let's look at another one. Let's say in this case we have 0, 3, 5, 10. So that would be a quadruple satisfying this inequality for sure. But let's say that 0, 3, 5, and 10 are the location of the stars. But now 0, 3, 5, and 10 will be the location of the bars. So that would turn us into the following diagram. We have a bar, and then we'll have star, 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 and then a bar. So this would be a bar in the 0th position, in the 3rd position. And now we need one in the 5th position, so that would be right there. And then we'll need one in the 10th position. So that means we need 5 stars, and then a remaining bar. Okay, good. So now which multiset does this correspond to? Well, let's see, I think it corresponds to the multiset where we have 3 2s, and then we'll have 2 3s, and then we'll have 1, 2, 3, 4, 5 4s. So that would be our multiset in this case. Okay, so let's do one more just for practice. Let's say we have 7, 9, 10, 10. Okay, so that means we have bars in the 7th location, the 9th location, and 2 bars in the 10th location. Okay, so let's see what diagram that will correspond to. So we'll have 7 stars to start off with, just to get us to the first bar. So there we have 7 stars, and then we'll have a bar, 2 stars, and then a bar. So now we have one in the 7th position and the 9th position. And then we'll have a star and 2 bars in the 10th position. That's what we have here. And then which multiset does this correspond to? Well, let's see. It's going to be 7 1s. So 1 to the 7. We'll have 2 2s. So 2 to the 2. And then a single 3. Okay, so that would be our multiset in that case. Okay, so I think we've practiced this enough. But
no,
notice
bro,
that in
what was that
all of
edit?
these cases, what it boiled down
I think I've lost it now.
was finding 10-element multisets of a 5-element set. But we know exactly how many that should be based off of our claim over here. And that is 10 plus 5 minus 1, choose 10. So that's how many total multisets there are, but since those multisets are in correspondence to these quadruples, that's how many quadruples there are. So you can do the calculation here and you'll see what you get is 1001. Okay, so we're going to do one more counting game before we finish off the video. Now we're going to look at the number of permutations of elements from a multiset. So we're going to start off with an example, which is just the number of permutations of an element from a set. And we've done this before, so this shouldn't be new. But then when we move on to a real multiset, and when I say a real multiset, I mean one that has a multiplicity larger than 1 for one of the elements, things get a little bit more interesting. So let's start with the number of permutations of the multiset MICHAEL. So that's my name. So let's notice that's a 7-element multiset where the multiplicity of each element is 1. So that might as well just be a 7-element set. But we know how many permutations there are of a 7-element set. There are simply 7 factorial. And that's by some counting exercises we did in previous videos. You can think about having 7 slots to fill, and you'll have 7 choices for this first slot, but then you've used up one of the letters. So you only have 6 for the second, 5 for the third, and so on and so forth. So you get 7 factorial. Okay. So what about the number of permutations of the multiset PENN? So of course we have to be a bit more careful here, and that's because N occurs twice. So what we'll do to start this off is to turn this multiset into a set, and when we turn it into a set, we will differentiate between the two ends with some colorings. Okay, so like I said, we're going to turn this multiset into a set, and that set will be PE, and then we'll have magenta N and then yellow N. Okay, great. So now we really have a 4-element, and now we really have a 4-element set because we're differentiating between the magenta N and the yellow N. And now looking at it like this, there should be 4 factorial or 24 permutations. And now what I'd like to do is list all 24 permutations.
Oh, for goodness sake.
Do it in a way so that when we maybe erase the colors, we're left with columns that look like the same permutation. Okay, so let's get started. So let's start with maybe just the standard spelling. So that would be PE, and then we'll have yellow N and magenta N. And then we'll have PE and then magenta N and yellow N. So that would be 2 of the 24 permutations. But if we were to erase the color here, then we would only have a single permutation of the original multiset. Okay, so now let's maybe try to do this systematically. So let's do everything starting with P first. So we have P and then E. Now let's say we have P and then N. So we'll have P yellow N and then E and then magenta N. That would be an example.
Oh my God.
P magenta N and then E and then yellow N. So that would be another such set of permutations with the colored letters that maybe collapse to the same permutation when we uncolor the letters. So now I'm going to write down all the remaining permutations on the board, and then we can work towards maybe a general way of counting this type of thing. Okay, so there's all the remaining permutations. So notice we have 24 in total, which is expected because 4 factorial is 24. And here at the moment, we're considering yellow N and magenta N to be different. But I've done this careful pairing. And that careful pairing is maybe like what we'll eventually call an equivalence relation, which will set each of these equal to each other when we erase the color. So let's see, over here we have E magenta N, P yellow N. And here we have E yellow N, P magenta N. But if we were to erase the color, that would simply be E N P N. And that's true for all of these. So let's notice in the end, we have 24, which is 4 factorial, over 2, which is the same thing as 2 factorial total possibilities. But we want to think about this not just as that number, which that number is obviously equal to 12, but how that might generalize to a larger such question. And I think maybe the best way to think about it is like this. So this would be permutations of 4 objects divided by the permutations of 2 objects. Okay, so I think maybe this leading exercise gives us an idea for how to write down the number of permutations of a k-element set where we have certain multiplicities. And so we'll write that as a claim over here, and then we'll talk our way through the truth of that claim. Okay, so here's how we can count permutations of a k-element multiset with multiplicities m1, m2 up to mr. Let's notice if those are the multiplicities, then that means the sum m1 up to mr is equal to k. So the number of such permutations is k factorial over m1 factorial, m2 factorial up to mr factorial. But there's actually a name for that, which is called a multinomial coefficient. And that multinomial coefficient is written as k choose m1, m2 up to mr. But this really only makes sense if r is bigger than or equal to 2. Because if r is equal to 1, it might look like a binomial coefficient, but the left-hand side is not a binomial coefficient. So, like I said, this is only really if r is bigger than or equal to 2 that we would use this notation of the multinomial coefficient. Okay, so here's the idea behind the proof here. So let's say we've got a k-element multiset, and that k-element multiset looks like this. x1, so a bunch of x1s. How many x1s do we have? Well, based off of this, we will have m1 x1s, and then we'll have a bunch of x2s. So how many x2s will we have? Well, we'll have m2 x2s all the way up to xr. How many of those will we have? Well, we will have mr xr's. We know we need x1s up to xr's just based off the fact that we've got that many multiplicities. So what we'll do is take this multiset and then turn it into a set by doing colorings on each of these like equal elements. So we'll color each of the x1s differently, each of the x2s differently, and so on and so forth. But we'll color them via superscripting. So we'll say like the first color, the second color, and so on and so forth. So that's going to turn into the following set. I'll call it x1, x1, 2, all the way up to x1, m1. So that would be all of the x1s. And then we'll have x2, 1, all the way up to x2, m2, all the way up to xr1, and then xr, mr. And then how many elements are in this set? Well, based off this sum, m1 to mr, we know there are k elements in this set. And now we count the total number of permutations. So the total number of permutations will be k factorial, because that's the number of k permutations of a k element set. But then a bunch of those permutations are equivalent to each other. And we can get that equivalence by just permuting each of these different colors. Okay. So how many different ways are there to permute all of these different colors of x1? Well, there are m1 different ways. So that means we have to divide by m1 factorial, because all of those will be equal to each other. And so we're like making this big multi-dimensional array, if you will. And then how many different ways are there to order these x2s? Well, there will be m2 factorial ways of ordering those x2s, all the way up to mr factorial number of different ways of ordering those xr's. So there's a sketch, and definitely just a sketch, of the proof of this claim. Okay, so now I'm going to leave you with some warm-up exercises. So I've got 3 nice warm-up exercises for you. The first is to count how many 4-digit positive integers there are with no repeated digits, or if there are repeated digits, all of the digits are odd. No. And I don't mean all of the repeated digits are odd, but all of the digits are odd.
We still going?
Next is to count how many 6-digit numbers are
You better fucking believe we still going.
5. And finally, count how many w, x, y, z integers satisfy their sum is equal to, that should be 100. And then w is bigger than or equal to 5, x is bigger than or equal to 1, and then y and z are bigger than or equal to 0. And that's a good place to stop. This is the 9th video in a series devoted to introductory proof writing. Today we're going to look at the pigeonhole principle and combinatorial proofs. So let's start with the definition, which will lead us towards the pigeonhole principle.
Okay, so this is another thing that oleki was like, you ain't gonna get this, you stupid as fuck.
Floor of x, which we'll use this following notation, as the largest integer n such that n is less than or equal to x.
Here we go!
And then as a dual to that, we'll define something called the ceiling, and we'll have similar notation, and that will be the smallest integer n such that n is bigger than or equal to x. So you can think of the floor as an elevator downstairs to the closest integer.
I know what a floor and a ceiling
is an elevator upstairs to the closest integer. So let's look at a couple of quick examples. So the floor of 2.3 is equal to 2. We go downstairs to 2. The floor of E is equal to 2. That's because E is 2.718. The floor of 2.99 is also equal to 2 because it's not quite equal to 3. And the floor of 2 is equal to 2. That's because if you're at an integer, by this definition, you don't have to go downstairs. Next up, the floor of -3/4 is -1 because that's downstairs from -3/4. Then the ceiling of 8.0001 is 9 because the ceiling says to go upstairs. So now let's look at the following fact, which is actually a generalization of the classic pigeonhole principle. So let's suppose we have n objects and we are to place those n objects in k boxes. Then at least one box contains the ceiling of n over k objects or more, and another box contains the floor of n over k objects or fewer. So let's do a quick example to see why that is true. So let's take 8 objects and let's place them into 3 boxes, and we're going to do it semi-randomly. So let's take this first object, we'll place it into this first box. And so let's draw this object occurring in this box. So there we've got it. Then maybe we'll take this second object and we'll place it in the third box. So there it is there. Then maybe this third object will be in this second box. And now let's keep going. This fourth object, let's put it in the third box. Let's say this fifth object goes back to the first box. And then maybe this sixth object goes into the last box. Okay, so there's my object there. And then let's say this next one, this 7th object, will go into our second box. And then finally, the last object, the 8th object, is placed into our first box. Okay, so now let's notice that this first and this third box both contain 3 objects. But how many is 3 in terms of 8 and 3? Well, it's going to be the ceiling of 8 over 3. So like I said, this contains the ceiling of 8 over 3 equals 3 objects. And we're guaranteed for something like this to happen by our fact over here. Well, we're really guaranteed for there to be a box with this many objects or more. But
I agree.
But in this case, we have exactly this many objects. And now let's look at what we have right here. So this has 2 objects, and 2 objects is the floor of 8 over 3. So this one has the floor of 8 over 3 or 2 objects. And we're guaranteed for a box to have that many objects or fewer, again, by this portion of our fact. Okay, so now that we've investigated this fact, let's look at the classical pigeonhole principle and then do several examples. Now we're ready to look at a special case of our general fact, which is classically known as the pigeonhole principle. So let's suppose we place n objects into k boxes. Then if n is larger than k, then at least one box contains more than one object. And towards our general statement, that's because if n is bigger than k, then n over k is strictly larger than 1. So when we take the ceiling, you get something bigger than or equal to 2. And then if n is less than k, then at least one box is empty. And that's because, again, if n is less than k, then n over k is less than 1 strictly, which means when you take the floor, you get 0. Okay, so now let's look at an example. Let's suppose we have 6 distinct integers, and they're between 0 and 9. Then we'd like to show that 2 of them must add to 9. Okay, so we've got 6 objects. Those 6 objects are the 6 integers, and we'd like to place them into less than 6 boxes. And so likely it'll be exactly 5 boxes, because for these introductory examples, you generally have one less box than objects, forcing 2 objects in a single box. Okay, so what might those boxes be? Well, there's a big hint built into this based off of the fact that we want 2 of them to add up to 9. So those boxes are based upon pairs of numbers that add up to 9. Okay, so let's get to it. So let's distribute our 6 integers among the boxes
this is
described as
this is the longest video.
So our first box will contain the numbers 0 and 9. Our second box will contain the numbers 1 and 8. Our third box, 2 and 7. Our fourth box, 3 and 6. And finally, our fifth box will contain the numbers 4 and 5. So we've got 1, 2, 3, 4, 5 boxes. We are to put 6 integers inside of these 5 boxes. So that means we're guaranteed 2 of these integers land in the same box.
That is so true.
So let's write that down. So we are guaranteed to have 2 integers in the same box. But let's notice if those 2 integers lie in the same box, then since they are distinct, they're non-equal in the same box, which means they sum to 9.
Okay.
So let's write that out. These sum to 9. And that's really all there is to it. You could write this down a little bit more carefully, but I'll maybe leave that as an exercise. We'll write down a solution to the following examples, which are a little bit more complicated, more carefully, so you can use those as a guide. Okay, let's move on. Now we're going to look at a very classic example. So a version of this example generally is inside of any proofwriting book that I've seen that covers the Pygmy
30 minutes until I can go toilet.
So let's suppose we have n plus 1 integers. I'll call them a1 up to an plus 1. And then our goal is to show that we can find 2 of those integers so that their sum or their difference is a multiple of 2n. So I've written that carefully as show that we can find I not equal to j between 1 and n plus 1 such that ai minus aj or ai plus aj is a multiple of 2n.
So true.
Okay, so how are we going to do this? Now, this being a multiple of 2n gives us motivation to divide each of these numbers by 2n and keep the remainder. And this may not seem super obvious at the moment, but as you'll see moving forward, anytime we're trying to show something as a multiple of something else, it's common to look at the remainder when dividing by that number. Okay, so anyway, let's get to it. So like I said, we want to divide each of these AIs by 2n and keep the remainder. So let's define a new set of numbers. So for all 1 less than or equal to I less than or equal to 2n, let's define Ri by the following equation. So we have AI equals 2n times Qi plus Ri, where Ri comes from the set between 0 and 2n, but it's not allowed to be 2n. Okay, so this is something called the division algorithm, which we talked about in a previous video. So let's just point out here, this is the remainder, or these are the remainders of the AI when divided by 2n. So what's nice about this is it takes a set of integers that can be really of any size, and it restricts them down to a set of integers between 0 and 2n. So that's pretty nice. Okay, so now we're going to look at 2 cases, 2 disjoint cases, I should say. So that first case will be the following. So let's suppose we have I not equal to j such that Ri is equal to Rj. Okay, nice. So that's definitely a possibility.
You know what?
And you might
Fuck
say, well,
it.
this is a
If I don't
super
get it, I don't
restrictive
get it.
possibility.
I'm gonna go piss.
Maybe it is. But we'll cover all other possibilities with case 2, which, as we'll see, will be essentially not case 1. Okay, so now what we'll do is either look at the sum or the difference. And maybe you'd like to play with it, but I think looking at the difference is maybe the obvious thing to do here. So I'll write it like this. So now let's note that AI minus AJ in this case is equal to, well, we'll write AI and AJ using this formula right here, which we've derived for them. So we have 2nqi plus ri, and then minus 2nqj plus rj. But by our assumption, ri and rj are the same. So that means when we take ri minus rj, those cancel. And thus, we can factor a 2n out of what's left over, and we have 2n times qi minus qj. So what does that mean? So we've got qi minus qj is 2n times something. So that means ai minus aj is a multiple of 2n. And now that'll bring us to our second case. So we just looked at the first case of this proof, and now we're ready to look at the second case. Let's recall the first case was there is an I not equal to j such that Ri equals Rj. We haven't used the pigeonhole principle yet, so hopefully we use that in this second case.
Oh no.
But the second case will be exactly not the condition on the first case. But luckily,
I'm not gonna get this,
am
am I?
Past of negating statements. So let's negate the setup of the first case. So we have this existential quantifier. There exists I not equal to j, so that's going to turn into a universal quantifier.
Since I don't get this, I'm just
So
gonna take some stuff downstairs.
I not equal to j.
Fuck this shit, man. This shit's difficult.
This statement is not true. So Ri is not equal to Rj. But now we've got n plus 1 numbers, R1 through Rn plus 1, that we'd like to put into n boxes, or n or less boxes, to use the pigeonhole principle. So let's figure out what those boxes are. So let's start by, we'll distribute the n plus 1 numbers, let's see, R1, R2, all the way up to Rn plus 1 into the following boxes. And those boxes are going to be all pairs of remainders after dividing by 2n that add up to 2n. So this is taking motivation from that previous example that we did. Okay, so one pair would be 0 and 2n. And I guess we're saying that we need to do summing here because we did differencing, or we did subtraction in the first case. And so that would be a pair of remainders that add up to 2n. And then next we would have 1 and 2n minus 1. And then I'm going to put a general one in here, k and 2n minus k. And then the next to last one would be n minus 1 and n plus 1. And then the final one would be n and n. But there's something that's a little bit fishy with these boxes. First of all, since these Ri's are remainders after dividing by 2n, we know they must be strictly less than 2n. They're between 0 and 2n. We can include 0, but we cannot include 2n. So that means this is an impossibility. But that's actually not a huge deal. What is a huge deal is that we have n plus 1 total boxes at the moment. But we've got n plus 1 objects, so that doesn't help us out at all. So what we'd like to do is somehow throw away one of those boxes. And indeed we can. We can throw away this last box where both of the remainders are equal to n, and that's because we have this assumption right here that the remainders are different. So that means we can scrub away that possibility, and we in fact have n boxes. So we've got n plus 1 objects to put into n boxes. That means 2 of those objects are guaranteed to be in the same box. Okay, so let's write that down a little bit more carefully. So we have I, j, and k such that Ri and Rj come from the box, or the set it would be, k and 2n minus k. And here I guess I should say I is not equal to j. Okay, so that would be like Ri and Rj coming from the same box.
Nah, man.
Okay, but now one of
this?
these is going to be k, and one of these is going to be 2n minus k. So maybe let's just, without loss of generality, assume that Ri is equal to k and Rj is equal to 2n minus k. Again, they cannot be the same by our assumption right here. Okay, so that's good. Now, since we looked at the difference before, in this case, we will look at the sum. So let's look at ai plus aj. So that's going to be 2n times qi plus ri. Let's recall that ri is equal to k by our assumption.
Yeah, of course.
And then we'll have plus 2n qj plus rj, which is 2n minus k by our assumption. But now we get some nice simplification. This k here cancels with this k here. And then everything else is a multiple of 2n, making the sum a multiple of 2n. And we can explicitly write it as the following multiple of 2n. We have 2n times qi plus qj, and then plus 1, from factoring the 2n out of this term right here. So in the end, we have ai plus aj is a multiple of 2n. So let's see. These two cases are disjoint and they make up all possibilities. In the first case, we saw that the difference of these two numbers was a multiple of 2n. In the second case, we saw that the sum of two of the numbers was a multiple of 2n. So that proves this claim up here, which was our, maybe like I said, very classic example. Okay, let's do another. Now we have what is one of my newly favorite examples for the pigeonhole principle. So let's see the setup. Let's suppose we have 101 natural numbers whose sum is 300, and we'll place all of those numbers on a circle. And then our goal is to show that we can find a consecutive sequence of these numbers whose sum is 200. Okay, so I've laid out a picture here just to get us started. So I have my circle, and I have my 101 numbers, which I have noted as A1, A2, A3, so on and so forth, up to A101. So since they're on a circle, we have A101 next to A1. That will be important moving forward. So let's see the proof here. So since we're trying to find a consecutive sequence whose sum is 200, that motivates us to look at the partial sums. So let's do that. And we'll define the sequence of partial sums. So let's consider the sequence of partial sums, which I'll write as Sm, and that's going to be A1 plus A2 ending at Am. And we can define these for all m between 1 and 101. So let's, for instance, notice that S1 is equal to A1, S2 is equal to A1 plus A2, and finally up to S101
Did he say they gotta be unique?
is the sum of all of these numbers.
Because if not, could you just have 100 ones and then
so
100?
S101 is, in fact,
Or whatever the
300.
fuck it is.
That'll be a good bit of information.
200.
So now let's take these 101 numbers and put them in 100 boxes. We just have to figure out which boxes to put them in or how to define those boxes. But the definition of those boxes is hinted towards by the fact that we have a 300 here and a 200 here. And what's common about 300 and 200? Well, they're both multiples of 100. They both end in 0, 0. So I think that gives us some motivation to define the boxes by the final 2 digits of a number. And in fact, there are 100 possibilities for the final 2 digits of a number. We've got 100 numbers, so that means we've got one more possibility of numbers than possibility of final digits. So that's really good. Okay, so now let's put these 101 numbers, and let's just write those numbers out, S1, S2, up to S101, into the 100 boxes, which are defined as, maybe, like I said, by the final 2 digits. So I'll write them like this. So my first box, I'll write as star 0, 0. We don't care what it starts with, but it ends with 0, 0. The next one will be star 0, 1. The next one will be star 0, 2. We would end with star 9, 9. So 2 of these must be in the same box. So what that means is that we have an Sn and an Sn plus k that are in the same box, but being in the same box means they are of the form star AB. In other words, they end in the same digit. Now you might say, well, why did I write Sn and Sn plus k instead of like Sn and S some other index? Well, I think it's helpful here to notice that these two will have different indices. One of the indices will be larger, so it kind of makes sense to write the larger one as an extension of the smaller one. Okay, great. Now I'd like to make a really quick observation, which I think is pretty obvious here, and that is Sn plus k is strictly bigger than Sn. And that's because we have natural numbers we're adding together here, and Sn plus k is further in this sequence of partial sums. Now let's look at the difference of Sn plus k and Sn. So let's write it like this. So let's notice that Sn plus k minus Sn is of the form star 0, 0. And that's because they end in the same 2 digits. But since they end in the same 2 digits, when we take their difference will end in 0, 0. But that actually restricts the possible values. So they cannot be the same, so they can't just be equal to 0. And we know that for sure because Sn plus k is strictly bigger than Sn. But they cannot be equal to 300 or larger than 300. They can't be bigger than or equal to 300 because the sum of all of the numbers is 300. Well, that only leaves 2 possibilities. But that means that this difference, Sn plus k minus Sn, comes from the set 100 or 200. But that's going to break us down into 2 cases. Well, if they're equal to 100 or if they're equal to 200. Let's look at this first case where they're equal to 200. That one's actually easier. Okay, so case number 1, which is Sn plus k minus Sn equals to 200. But we could rewrite that as 200 equals Sn plus k minus Sn, but by the partial sum definition of these s's, that'll end up giving us An plus 1 plus An plus 2 plus all the way up to An plus k. In other words, we have consecutive numbers along this circle that add up to 200. And I could draw them on the circle like this. Maybe An is right here, An plus 1 is right here, all the way up to An plus k is right here, and then maybe the next one might be important also, An plus k plus 1. So here what we did is we added from An plus 1 up to An plus k, and we got the number 200. Yes, but of course, that's for this first case where they sum to 200. Now we need to look at the second case where they sum to 100. So we just looked at the first case, which is when Sn plus k minus Sn was equal to 200. And in that case, we got this string of terms summed together, starting at An plus 1, ending at An plus k equaled 200, which showed that we had the right kind of consecutive sequence. But now we're going to look at the other case and show that we can get a consecutive sequence in that case as well. But let's notice if Sn plus k minus Sn equals 100, then by what we saw previously, that means that An plus 1 plus An plus 2 ending at An plus k equals 100. In other words, this sum from here to here is equal to 100. But if that sum from there to there is equal to 100 and the sum around the whole circle is equal to 300, that means the sum of the remaining stuff from here all the way around to here is equal to 200. Again, because simply 300 minus 100 is equal to 200. So we can now put that into words as follows. So we'll observe that 200 is the same thing as 300 minus 100. So I think that's pretty obvious. We can write 300 as A1 plus A2 ending at A101. And then we can write this 100 as this sum right here. So we have An plus 1 ending at An plus k. Great. But now performing that, we get the following sum. I'll maybe start it right here and then loop around. So we'll have an plus k plus 1 added all the way up to a101. So that would be from here to here. And then plus a1 all the way up to an. So we have 200 is equal to that, but that's another consecutive sum of terms along this circle. So either way you look at it, we are able to get a consecutive sequence along this circle whose sum is 200. Okay, let's look at another one. So for our last pigeonhole principle example, it's kind of geometric. I think that's nice. So let's say 9 points are placed in an isosceles right triangle with side length 1. So I've drawn the triangle here. We've like I said, we've got an isosceles right triangle, side length is 1. Then our goal is to show that 3 of them form a triangle whose area is at most 1/8. So let's maybe notice that the area of this entire triangle is 1/2. That's because it's 1/2 base times height. So that gives us motivation to split this up into 4 pieces. 4 pieces because 1/8 is 1/4 of 1/2. So furthermore, we hope that we can split this into 4 nice pieces. So let's see if we can split it into 4 pieces, all of which are isosceles right triangles. And in fact, we can. Let's split each of these into half. So we'll split each of these legs into half, and then we'll make line segments connecting them like this to the hypotenuse. Now let's note that since those are split in half, we have a length of a half here, length of a half here. This is a length of a half, and this is a length of a half. So this triangle right here that I'm shading in brown has area 1/8, and so does this one right here that I'm leaving unshaded. But that didn't split this into 4 pieces that are the same. We've got 2 triangles and 1 square. But we can split that square into 2 triangles as well. And maybe we'll split it into 2 triangles like this, although we could split it across the other diagonal as well. And now let's notice we have split this into 4 equal triangles that are all isosceles triangles with side length 1/2. Then furthermore, let's notice that we've got 4 boxes here, if you will. The boxes are triangles, and we're trying to put 9 points into each of those 4 boxes. We're guaranteed to have 3 points end up in one of these boxes. But those 3 points will make a triangle, and that triangle can at most have area of the entire triangle that it lives within. But the entire area of the triangle that it lives within is 1/8. So that's a sketch of how to do this. Now let's write it out. So maybe we would use the following words. Let's partition the triangle into 4 similar isosceles right triangles with side length 1/2 per the diagram. I think it's fair to say that we're explaining what's going on with this diagram over here. Then next, so of the 9 points, 3 are guaranteed by the pigeonhole principle, but maybe we don't need to say by the pigeonhole principle explicitly, well, especially since I'm saying it out loud here. So of the 9 points, 3 are guaranteed to be placed in the same subtriangle. So by subtriangle, I mean either this one right here, this one right here, this one right here, or this one right here. Okay, well, let's also maybe give a name to those points. So let's call them A, B, C. Great. So again, that's by the pigeonhole principle. And now we can maybe note the following. So the area of triangle ABC is less than the area of the subtriangle. The subtriangle is an isosceles right triangle with side length 1/2, and that has an area of 1/8. But now we've done exactly what we wanted to. We found 3 points that form a triangle whose area is at most 1/8. Okay, so now let's move on to some combinatorial proofs. So to put it simply, a combinatorial proof involves showing 2 expressions are equal by showing they are answers to the same counting problem. So we've done this one in a previous video, but I thought I'd do it again just because now we're talking about combinatorial proofs, officially. Okay. So let's show for all natural numbers n and k, where k lies between 1 and n, we have n plus 1 choose k, is equal to n choose k minus 1 plus n choose k. And so let's quickly recall that n plus 1 choose k is equal to the number of k element subsets of an n plus 1 element set. But we might as well write down an explicit n plus 1 element set. And I'll write 0, 1, 2, 3, ending at n. So I think that clearly has n plus 1 elements because we are including 0 here. Okay, so that's the left-hand side of this proposed equation. Now we'd like to count the number of k element subsets of 0 to n, another way to achieve the right-hand side. And we can do it as follows. So let's suppose that A is a subset of 0, 1 up to n, where the cardinality of A equals k. So in other words, it's a k element subset of our set right here. And now let's notice that there are two possibilities for A. So I'll write those down as cases. So case number 1 and case number 2. So case number 1 is that 0 is an element of A. Okay, well, so if 0 is an element of A, then we can write A as follows. It's equal to the singleton 0 disjoint union. So I'm going to introduce some notation here. We have a union with a dot there. That means disjoint union, which means these two elements will not overlap. So it'll be disjoint union A prime, where A prime is a subset of 1, 2 up to k, up to n. So it's a subset of 1 up to n. So in fact, what we're really just doing here is using the fact that 0 is an element of A, we're pulling 0 out of A, and we're seeing what's left over. So let's also note that the size of A prime now is k minus 1. And we can see that because we've taken a single element out of A prime. Okay, so that's good. So how many such A prime are there? Well, it's really easy to count because all we have to do is count k minus 1 element subsets of an n element set. So there are n choose k minus 1 such A prime. But the A prime completely determine the A in this case because we're assuming that A contains 0. Thus A, in this case when A contains 0. Okay, so let's just reiterate what we've done right here. We have A is a subset of 0 to n. In this first case, we have 0 as an element of A, which is definitely a possibility. And then we've shown that there are n choose k minus 1 such A's. So there are n choose k minus 1 subsets that contain 0. Okay, let's look at the next case. And the next case will be, well, what happens if A is not containing 0? So 0 is not an element of A. But if 0 is not an element of A, then that means that A is just plainly a subset of 1 to n. Okay, but how many elements are in A? Well, there are k elements in A. That's kind of our assumption from the very beginning. Okay, but how many such A's are there in this case? Well, that's easy to count as well because A is a k element subset of an n element set. So there are n choose k such A's. Great. But this covers all different cases. So if we have a subset of 0 to n of 0 to n, then it either contains 0 or it does not contain 0. In the case that it contains 0, there are n choose k minus 1 of them. In the case that it does not contain 0, there are n choose k of them. So we've counted the number of k element subsets of this a different way. So by definition, it's equal to n plus 1 choose k, but by this other counting procedure, it's equal to the sum of these two. So putting this all together, we have n plus 1 choose k is equal to n choose k minus 1 from case 1 plus n choose k from case 2. Okay, let's do another. Okay, so for our next one, we'll show for all natural numbers n and k, where k is between 0 and n. I guess that really makes k perhaps not a natural number, but a non-negative integer, but we'll let it slide in this case. So with that setup, we have n choose k is equal to n choose n minus k. So we're going to note that n choose k is the number of subsets of 1 to n with k elements. So maybe we'll start with a subset from the set containing 1 up to n with k elements. So that's what I'll write down here. Suppose we have A, which is a subset of 1 to n, where the number of elements of A is k. Okay, now let's notice that we have the number of elements of A complement is equal to n minus k, because it's the number of elements of the universal set, which is understood to be 1 to n in this case, minus the number of elements of A. So I think we saw this in a previous video, or this kind of formula in a previous video. So we have n minus k. So that defines a unique pairing. So I'll write this down. So we have a unique pairing of sets A with their complement A complement. Which means if there's a certain number of possible sets of the form A, then there are a certain number of possible sets of the form A complement. So how many sets are there of the form A? Well, the only thing restricting A is that it must have k elements. So that means the possible types of sets A here are n choose k. But then, how many possible sets are there like A complement? Well, the only thing governing A complement is that it has n minus k elements. So how many sets are there with n minus k elements? Well, there are n choose n minus k. And again, since this pairing is unique, we must have equality between these two choices of types of sets. Okay, we're going to do one more. So for our final example, we'll look at a nice combinatorial proof of a fairly famous sum identity. And that says the sum as k goes from 0 to n of n choose k squared is 2n choose n. Sometimes this is known as a central binomial coefficient, just by the way. So let's maybe look at a little example of this real quick, although we won't work out all of the details. Let's say we have n equals 4. So that means we'll have 4 choose 0 squared plus 4 choose 1 squared plus up to 4 choose 4 squared must be equal to 8 choose 4. Now, you can check that that works out if you'd like to, but really there's kind of no point because we're about to prove it in general. So I think a good first strategy is to look at one side of the equation, which we can easily write down what it means combinatorially, and show that the other side of the equation also counts that type of object. Okay, so let's do that as follows. So let's note that 2n choose n equals the number of n element subsets of a 2n element set, which I'll call 1, 2, up to 2n. Okay, so that's a good first observation to make. Then let's notice that the parts of this sum are counting the number of k element subsets of an n element set. And we're squaring them, so I think that motivates us to split this 2n element set into 2 n element sets. So let's maybe do that with the following observation. So if x is a subset of 1, 2, up to 2n, with the number of elements in x is equal to n, then we can write x as the disjoint union of a, b. So I'm using that notation again, where a is a subset of 1 up to n, where the number of elements in a is k, and b is a subset of n plus 1 up to 2n, where again b has n minus k elements. Okay, so I think this is looking good, and I think that motivates our final, what I'll call calculation. So let's do it here. We have 2n choose n is equal to number of n element subsets of 1 up to n. Okay, let's maybe put a yellow box around that. But that'll be equal to the sum as k goes from 0 to n of the number of k element subsets of 1 to n. That's like deciding the number of ways to choose this subset A.
Of course it is, of course.
Times the number of n minus k element subsets of n plus 1 to 2n. That's like choosing the number of ways that we can pick this subset B. Great, and then of course we're taking a sum here by the sum principle. So we would sum over where we had a 0 element subset A and an n element subset B, all the way up to having an n element subset A and a 0 element subset B. Okay, but now we can count each of these orange and red boxes using like the definition of the binomial coefficient. This gives us the sum as k goes from 0 up to n of n choose k times n choose n minus k. But by our
He's so small, man. He a midget.
we know that n choose n minus k is the same thing as n choose k. So in the end, we get n choose k times itself, or n choose k squared. Okay, that's good. Now I'm going to leave you with some warm-ups. So now I've got 2 warm-up problems for you.
Okay.
So the first is to, well, suppose you're in a class of 17 students. So that includes yourself. Then you'd like to show that at least 3 of you were born on the same day of the week. So this is like a pigeonhole principle problem. And then next, let's find a combinatorial proof of the famous identity for triangular numbers. That says 1 plus 2 plus 3 ending at n is n plus 1 choose 2. So there are many different ways to prove this, but here we want to look for a combinatorial proof. And that's a good place to stop. This is the 10th video in a series devoted to introductory proof writing.
We are still going right.
And today we're going to talk about
absolutely.
mathematical results, kind of the terminology behind mathematical results. And then we're going to start learning how to prove conditional statements. Okay, so there are lots of different names for mathematical results. And in fact, there's a bit of a hierarchy to these results that it's useful to know a little bit about. Although just be aware that this isn't really a strict hierarchy. So a lemma can be thought of as a very, very small result, but not really a small result that stands on its own, but it's generally thought of as a building block for a theorem, or a building block for a step in a proof of a theorem. And then often theorems are such big results that you'd like to look at some very special cases of a theorem, or look at something that follows very quickly from a theorem, and that's called a corollary. And then furthermore, if you have a result that's not quite as big as a theorem, whatever that means, you might call it a proposition. Now, kind of on the level of proposition, you have these other names of results, claim or observation. Often a claim is something inside of a proof, but it doesn't have to be. In fact, when I was in grad school, I had a professor use the name meditation for a result in class once. I thought that was pretty funny. And now a result that we don't know if it's true or false is called a conjecture. So all of these are known to be true. So there are proofs of every theorem, proposition, lemma, corollary, and so on and so forth. So if we, as the mathematical community, are calling a result a theorem, proposition, lemma, so on and so forth, then it has a proof and it is known to be true. So something that does not have a proof is called a conjecture. But often some of this stuff has historical naming to it. Like, for example, Zorn's lemma is equivalent to the axiom of choice. But that kind of makes it a fairly large result, but it's called Zorn's lemma. And I'm sure there are other examples of things like that that have historical names, even though the size of the result maybe doesn't match the naming convention. So here are some examples of results. So the first
all
one
this
says,
maths is making the blood flow out of my brain, which is causing me to fucking freeze everywhere else. That's definitely what's going on here.
Of a sub n is equal to 0. So if a series converges, then its terms go to 0. So this is an example of a conditional statement. So it's of the form P implies Q. So the statement P would be the series converges, and that implies the statement Q, which is that this limit is equal to 0.
Yeah.
Let's look at another example. So you probably learned this other example in a linear algebra class. It says an n by n matrix A is invertible if and only if its null space contains only the 0 vector. So this is an example of a biconditional statement. We would read this as P if and only if Q. And then there are also non-conditional statements, such as the harmonic series, which is the sum as n goes from 1 to infinity of 1 over n diverges. Notice this isn't of the form if P then Q. That's a non-conditional statement. So we'll learn how to prove conditional, biconditional, and non-conditional statements in this course. But that being said, we will start with conditional statements. But before we can get off the ground, we really need an explosion of very basic definitions to work off of. And so let's get those on the board. Okay, now we've got a boatload of basic definitions which we'll use in order to start our very basic proofs. And I don't think it's reasonable to memorize all these definitions right now. You'd probably just like to keep them written down somewhere near you or kind of at the ready to use whenever you see them within some sort of result that we're trying to prove.
Okay, there we go.
Okay, so let's maybe just go through them one by... Okay, so let's go through them one at a time. So an integer n is even if n is equal to 2k for some k which is an integer. So it's a multiple of 2. An integer n is odd if it's of the form 2k plus 1 for some k in the integers. The parity of an integer is its evenness or its oddness. So we would say that the parity of 5 is odd. Or maybe we would say the parity of 5 is 1, but that's kind of getting ahead of ourselves. So m and n have the same parity if they're both even or they are both odd. So 3 and 5 have the same parity. M and n have opposite parity if one is even and the other is odd. For example, 19 and 100 have opposite parity. Next, if we've got two integers a and b, we say that a divides b, and we write, well, I'm going to read this a divides b, but it's a and a vertical line b, if there is a d such that b is equal to a times d. So there's some dual way of saying this. So if a divides b, then b is a multiple of a. So sometimes we'll be saying b is a multiple of a, and sometimes we'll be saying a divides b, but those have the same meaning. Next, we say a natural number p, which is not equal to 1, is prime if its only divisors are 1 and p. So like, for example, 17 is prime. Yeah. Next, we say a natural number which is not equal to 1 is composite if it's not prime. And in fact, all composites can be written of the form a times b, where a and b are strictly between 1 and n, where n is that composite number. Yeah. You might notice that neither of these definitions say anything about, well, what happens if we're talking about the number 1 itself? That's because it plays a special role. 1 is called the unit of the natural numbers. So I didn't write that down here, but I'll just say it out loud. 1 is the unit of the natural numbers. So in general, in larger number systems, if you will, there are units, composites, and primes, or sometimes those primes become irreducibles. So those are your 3 types of numbers in larger number systems. So it's just kind of a bummer that within the natural numbers there's only 1 unit, so it seems to be playing this unique role, whereas in other number systems more objects are units. Okay, so moving on to the next 2 definitions. So given 2 integers a and b, we say that d is the greatest common divisor of a and b, and we write it as d equals GCD AB. Okay. If d divides a and d divides b, so it's a common divisor, and then it's got to be the biggest common divisor, but we encode that using divisibility. So if we have another common divisor c, so c divides a and c divides b, then c divides d. So that ensures that d is the largest such common divisor. Then, what about the least common multiple? That's like dual to the notion of the greatest common divisor. So we'll say that L is the least common multiple, and we'll write L equals LCM AB. If A divides L, B divides L. And if A divides M and B divides M, then L divides M. So this condition over here ensures that L is both a multiple of A and B. But then this condition here ensures that if we have another multiple, it is larger. Okay, so like I said, we probably don't need to memorize these just yet, although after doing lots of examples, you'll hopefully internalize all of these definitions. But we'd like to be able to unpack and repack these definitions as needed for our basic. Now we're ready to start writing down some very, very basic proofs. We're going to start with what's called the method of direct proof, which is used to prove conditional statements like if P then Q, or P implies Q symbolically. And so in fact, I think there's this nice outline that we can use for inspiration of how to write this proof in the first place. My suggestion would be to essentially follow this outline for your first several proofs, and then you can start maybe adding your own creative flavor to them. Okay. So let's say we've got this proposition, if P, then Q. And P and Q can both be really, really complicated mathematical statements. But our goal is to show that one implies the other. So how does the proof go? So based off the truth table of the implication statement, P implies Q, which I'll let you review if you need to, what we'd like to do is suppose that P is a true statement and show that that leads to the truth of Q as a statement. So we'll just say right here, suppose P, and what the undertext there is we're supposing P is true. And then we end with thus Q. And the undertext there is thus Q is true.
Thus Q.
And in the middle, you know, it's going to vary from proof to proof, but the general strategy will be to unpack the statement P via definitions. Probably since we're just starting it out, it'll be one of those definitions that we just saw on the board. So what I mean by unpack with definitions, I mean rewrite what it means for P to be whatever we're saying it is into like some equations or something.
Okay.
And then we'll make the appropriate calculations and logical arguments to get to a point where we can repack into Q via definitions. Okay, so this is all well and good, but I think it's better just to look at some examples. Actually, it's probably best to look at a ton of examples and try examples on your own, and then revisit this outline so that you have a more holistic view on it. So that, in fact, would be my suggestion.
Of course.
Okay, so let's do this first example. We'll prove this simple proposition. If n is odd, then n squared is odd. So just going through some typical examples of odd numbers, this seems very true. So 5 is an odd number. 5 times 5 is 25, which is an odd number. 11 is an odd number. 11 squared is 121, which is also an odd number.
That's crazy.
So it seems like we're good to go here. But let's write this proof down. So let's suppose that n is an integer and n is odd. Okay, so I filled in a little bit of the detail there. I said that it was an integer. That's kind of subtext of this statement, but that's okay. Now we'd like to unpack what it means to be odd via definitions. Well, we had a definition of that on the previous board. So that means, we have a k, which is an integer, such that n is equal to 2 times k plus 1. That was our definition of oddness. But now we've written oddness as some sort of equation. And since we need to square n, that gives us something like meaty to like do some calculations.
Yo, I did this in class.
Okay, so now let's go from there. Now we've kind of unpacked the left-hand side, the P statement totally. And we can see what the right-hand side is saying. It's motivating us to square this thing.
That's crazy.
So let's do that. So I'll write it like this. So let's notice that n squared is equal to 2 times k plus 1 squared. That's because n is 2k plus 1. Then we can multiply this out to 4k squared plus 4k plus 1. But then notice that we've got something times 4 plus 1. But 4 is an even number itself, so we can factor 2 out of each of those. So we can factor a 2 out of these first two, and that leaves us with 2k squared plus 2k plus 1. Okay, so let's see what we have. We have n squared is equal to 2 times something plus 1. So if we wanted to be super clear here, we could do that. And maybe we would use some language like observe that n squared equals 2 times a plus 1, where a is equal to 2k plus 2. Sorry, that should be 2k squared plus 2. And then we can repack this expression for n squared into the oddness of n squared. So we would end with thus, n squared is odd. Because recall, by our definition, if a number can be written as 2 times something plus 1, it is odd. Okay, let's do another. For our next example, we'll prove that if n is a natural number, then the expression 1 plus negative 1 to the n times 2n minus 1 is a multiple of 4.
Yo.
Okay, well, this is not quite the same sort of conditional statement because there's nothing really to unpack of our hypothesis here. So our hypothesis is just that n is a natural number. Like I said, there's nothing to unpack there. But there is a little bit of motivation for how to proceed by the shape of this object that we have in the conclusion. Notice we have -1 to the n power. And let's recall that -1 to an even power is positive, whereas -1 to an odd power is negative. So this object seems to behave differently depending on the parity of n, the evenness or oddness of n. So that motivates us to look at those two cases separately. So let's do that. So we're still going to start the same way. So we'll suppose that our hypothesis is satisfied. So we'll suppose that n is a natural number. And then we'll notice that this tells us that n is even or odd. So thus, n is even or n is odd. Because every natural number, in fact, every integer is either even or odd. And now we're going to split this into two cases. It's pretty typical to explicitly write down that we're splitting into cases like this. So case 1 will be maybe n is even. Whereas case 2, I'll put it down here, I think that'll give me enough room, will be the case when n is odd. Now we want to decompose what it means to be even or odd. Okay, so let's do it. So in this case, we have n equals 2k for some natural number k. And we know it's a natural number because we're starting within the natural numbers. So now let's plug that version of n into our expression, this being our expression. So maybe we'll use this language again. Notice that 1 plus -1 to the n times 2n minus 1 now has the form 1 plus -1 to the 2k times 4k minus 1. It's 4k minus 1 because we have a 2 times n right here. Okay, but now let's notice that -1 to the 2k is definitely +1, given that 2k is even. So this simplifies down to 1 plus 4k minus 1, which is equal to 4 times k, which is a multiple of 4. So we would maybe put a comment here and then note at the end a multiple of 4. So at least in this case, when n is even, we have achieved that our expression is a multiple of 4. Now let's do it in the case that n is odd. Okay, but notice that since we don't have all integers here, we'll need to use a slightly different expression for n being odd, and that will be of the form 2k minus 1. That's because if we use 2k plus 1, we can't achieve the odd natural number 1. I'll let you think about that, but in the end, it's not that huge of a deal. Okay, so the case when n is odd. So in this case, we have n is equal to 2k minus 1 for, like I said, some natural number k. And now we'll essentially do the same thing, but just with this value of n instead of the 2k value of n. So I'll use the same language. Notice that 1 plus -1 to the n times 2n minus 1 in this case is equal to 1 plus -1 to the 2k minus 1 times, so this is going to end up being 4k minus 2 minus 1. Right, so it's 4k minus 2 because if we multiply this thing by 2, we get 4k minus 2. Okay, but now let's do our calculation. This ends up being 1 minus 4k plus 2 plus 1. That's because this object, minus 1 to the 2k minus 1, is a -1 given that we have an odd exponent. But now putting this all together, we have 4 minus 4k, which is the same thing as 4 times 1 minus k. But that's also a multiple of 4. So either way we look at it, if n is even, we get a multiple of 4, and if n is odd, we also get a multiple of 4. So that's the end of this proof. Let's do another. For our next result, we'll prove that if m and n, which are integers, have the same parity, then their sum is always even. So this is going to, again, break down into two cases. So, and those cases are based off both being even or both being odd. But let's write that out. So let's suppose that m and n are both integers with the same parity. So we're assuming that the hypothesis is true, and just like we've been doing this whole time, we want to prove that that will imply the conclusion is true. Okay, so M and N are both even or both odd. That's exactly what it means for them to have the same parity. Now we'll split into cases. So case number 1 again, let's say M and N are both odd. So let's work through this. So what does this tell us? This tells us we can write M as 2A plus 1 and N as 2B plus 1, where A and B are integers. That's the definition of them each being odd. And now we'll notice that their sum will end up being even. So let's notice that M plus N is in this case 2A plus 1 plus 2B plus 1. But now we can put this all together and get 2 times A plus 2 times B plus 2. Factor a 2 out, we get 2 times A plus B plus 1, which is even. Great. So we showed that if we started with 2 odd numbers and we took their sum, we got an even number. And actually, I'll leave case 2 as a little bit of a homework exercise, but it should follow fairly similarly. Okay, so now we're going to look at something called a contrapositive. For our next set of examples, we're going to look at something known as a contrapositive proof. So let's recall that a conditional statement is logically equivalent to its contrapositive. So that means if we can prove that the contrapositive of a statement is true, that means that the original statement is also true. Well, let's recall what the contrapositive is in the first place. So if we have a conditional statement, P implies Q, its contrapositive is the statement not Q implies not P. And like I said, those are logically equivalent, which you can show with a truth table if you'd like to, but likely you did on your homework already. So what's the outline for a contrapositive proof? Well, it's just essentially a direct proof of the contrapositive of the statement. So there's nothing really there. Let's say we've got the statement, if P then Q, and so you would suppose not Q, and then do calculations and whatever, just like we had talked about before, and end up with thus not P. And so this proof has shown not Q implies not P, which, like we've been saying, is logically equivalent to the original statement. But I think maybe the really important question here is, how do you know whether to use a contrapositive proof or use just direct proof? And while there's no like tried and true method, the way that I think about it is the simplicity of the statements. So generally, it's easier to prove a statement if it starts with something simple in the hypothesis and you have something a little bit more complicated in the conclusion. So in other words, you're taking a simple statement implies a complicated statement. Okay. So if P is a simple statement and Q is a more complicated statement, you probably want to use the method of direct proof. Got it. Whereas if P is a complicated statement and Q is a simple statement, then you probably want to use the method of contrapositive proof. And that's because it essentially like changes the direction of this arrow. Of course, there's some negation there, but it takes you from simple to complicated when you weren't originally set up to do it that way. Okay, so we're going to do a couple of examples starting with this one. So let's suppose that we have real numbers x and y, and now we want to show that y cubed plus x squared y is less than or equal to x cubed plus xy squared implies that y is less than or equal to x. Oh my god. So this is a classic example of this thing that I was telling you down here. We've got a fairly complicated hypothesis and a very simple conclusion, which is kind of like backwards of what you would like. So we'll look at the contrapositive. Maybe let's write it out for this first one. We generally won't write it out, at least in the final proof. You might want to write it out on your scratch paper. So what does the contrapositive say? It says if y is not less than or equal to x, in other words, y is strictly bigger than x, then y cubed plus x squared y is strictly bigger than x cubed plus xy squared. So those non-strict inequalities changed directions and turned into strict inequalities. So this is the statement that we will prove. And often, at least when we're starting out, we'll indicate that we're proving something by contrapositive at the beginning of the proof. I'll just put it in parentheses. So contrapositive. Great. And that's mostly for the reader, but generally in higher level math classes, you wouldn't write that you were doing it by contrapositive.
Yep, okay. We're still going.
So now let's suppose that we have y bigger than x. So that's like supposing not q in this case. And now we want to work towards this inequality right here. But notice if y is bigger than x, we can immediately see that y minus x is bigger than 0. And x and y are both not 0. It's clear that they're both not 0 or not both 0 because if they were both 0, if we took their difference, we would get something that's 0. Okay, but if they're both not 0, then if you square them and add them together, you get a strictly positive number. So let's write that down.
Yeah.
So thus, x squared plus y squared is a strictly positive number. Why do we want to look at x squared plus y squared? Well, the stuff over here on the right-hand side seems like it looks like the stuff over here where we've multiplied by x squared plus y squared. Okay, so that motivates the following calculation. So I'll just write, notice that we have y minus x times x squared plus y squared is bigger than 0 times x squared plus y squared. So the inequality is inherited from this inequality right here, y minus x is bigger than 0, and the fact that we're multiplying by something positive. So that does not change the direction of the inequality. Okay. So after expanding out the left-hand side, hopefully we have something nice. So let's see what we have after expanding out the left-hand side. We'll have x squared y plus y cubed minus x cubed minus xy squared. And then over there on the right-hand side, we'll have 0 because 0 times anything is 0. But look at what we have. Everything which is a positive term is this stuff over here, and everything that's attached to a negative is this stuff on the right-hand side of the inequality. So when we move when we move everything with a minus sign over, we get exactly our inequality, our not p statement.
Okay.
So we can just finish this off by saying thus x squared y plus y cubed is strictly bigger than x cubed minus xy squared. Sorry, that should be plus xy squared. But that's what we wanted to show.
Got it.
That finishes the proof of this statement by contrapositive. Let's do another. So for our next result, we'll start off with two integers m and n. And we'll prove that if 3 does not divide m times n, then 3 does not divide m and 3 does not divide n. And we're going to use the contrapositive again here. But the interesting thing about this is that our conclusion, which maybe I'll put in these orange brackets, this conclusion is an and statement.
It's an and statement.
So that's pretty cool because we have to negate an and statement, which will turn into an or statement.
Yeah.
Okay, so now let's suppose not q, which in this case would be not this and statement. So suppose that 3 divides m or 3 divides n. So that's by one of
and 3 would divide
laws,
both.
Right? And so
m times
saying
n.
3 does not divide m is the same thing as 3 divides m. Same thing for 3 and n. And then, like I said, and turns to an or. Okay, but now let's notice that in our entire setup right here, m and n are playing in symmetric roles. But since they're playing in symmetric roles, it doesn't matter whether or not we decide that 3 divides m or 3 divides n. But there's a careful way of writing that down, and that's using the phrase without loss of generality. So without loss of generality, we will assume that 3 divides m, and then that's the same thing as saying that m is equal to 3 times k, where k is some integer. That's what it means to be divisible by 3. So you have to be careful with this phrase without loss of generality, or also the tool which we'll learn later, similarly, because they're not always applicable. You have to be really sure that it's the same calculation if you choose m to be a multiple of 3 or n to be a multiple of 3, or that m and n are playing symmetric roles in your setup. So here we're okay. Okay, so now we have everything that we need to work towards the conclusion of the contrapositive statement, which should be the negation of 3 does not divide mn. So that means we're trying to get to 3 divides mn. In other words, mn is a multiple of 3. Okay, so let's look at mn. So maybe we'll just say observe that. So m times n is now equal to 3 times k times n by replacing m with 3k by our setup. But that's equal to 3 times nk. But since mn is a multiple of 3, we can say that 3 divides mn as needed. And that finishes this proof off. Okay, we're going to look at one more basic definition.
One more basic thing.
To put in that big list at the beginning. And then we'll do a proof with that definition, and then we'll end with some warm-up exercises. So this next example plays a very important role in elementary number theory, and it's another useful thing to have under our belts for doing basic proofs. So given integers a and b, and then a natural number n, we'll say that a and b are congruent modulo n if n divides a minus b. So in other words, a minus b is a multiple of n.
Sure thing.
Later, we'll see that that's equivalent to a and b having the same remainder when dividing by n. That'll be a nice homework exercise. And then in this case, we'll write, well, I'm going to read this as a is congruent to b mod n, but this is the notation here. We have this triple equal sign here, and then in parentheses, mod n. So let's look at some quick examples. So 12 is congruent to 2 mod 5. That's because 5 divides 12 minus 2. Of course, 12 minus 2 is equal to 10. 34 is congruent to negative 2 mod 9. It's really important to consider negative numbers mod n as well. Sometimes that'll be super helpful. And that's because 9 divides 34 minus negative 2. 34 minus negative 2 is, of course, 34 plus 2, which is 36. That's a multiple of 9. Then 57 is congruent to 0 mod 3. So notice 3 times 10 is equal to 30. 3 times 9 is equal to 27. That means 3 times 19 is equal to 57. Notice 57 would also be 0 mod 19. Finally, if we have two numbers that are incongruent mod n, we say, well, like I said, we say they are incongruent or not congruent mod n. And we would write it like this. So with this slash through the triple equal sign. So we would read that as 13 is not congruent to 5 mod 3. Okay, so here's a nice first example of calculations that you might do with congruence mod n. So let's suppose that a and b are congruent mod n. Then we want to show that a squared and b squared are congruent mod n. Okay, so this is a conditional, P implies Q statement. Let's suppose that the hypothesis is true. So let's suppose that A is congruent to B modulo n. And now we're going to unpack this
Live,
all
laugh,
the way
love.
to an equation. So this will take a couple of steps.
This is me when A.
Thus, n divides A minus B. And what I really mean by that is that A minus B is equal to n times k for some integer k. So let's see, we did a stepwise unpacking of this definition. So we started with A is congruent to B mod n. We moved that to n divides A minus B. But if n divides A minus B is a multiple of n, so we can write A minus B as n times something. Okay, great. But now we'd like to get at A squared and B squared. But since these are on opposite sides of the congruence and these are on the same side of the equation, perhaps we'd like to move some things around. So maybe we would rewrite this as A equals B plus nk. But then how would we write that in language? Well, maybe we'll just say that we will
Language? Oh, I hate language,
B
man.
plus n times k, and then we'll say observe or notice or something that this calculation will finish us off. So we've got A squared is the same thing as B plus n times k squared, but multiplying that out gives us b squared plus 2 times b times n times k plus n squared k squared. But the important thing is that all of this stuff here is a multiple of n. So that means we can write the following. A squared minus b squared is equal to n times, it'll be 2 times b times k, and then plus n times k squared. But that's the same thing as saying n divides a squared minus b squared. We have a squared minus b squared as a multiple of n. But n dividing a squared minus b squared is the same thing as saying a squared is congruent to b squared modulo n, which is exactly where we wanted to end up. Okay, so that's good. Now I'll leave you with some warm-up exercises. So I've got 4 warm-up exercises for you. So the first is to read section 5.3 of the Book of Proof. Ooh. So the class that I'm teaching based around this material is using the Book of Proof. I think section 5.3 is a really nice take on the style of mathematical writing. Then for number 2, let's show that if we've got integers m and n that are the same parity, then 5m minus 1 and n plus 10 do not have the same parity. Next, let's show that if we have integers x and y, if x squared plus 2 times y minus 1 is even, then x is even and y is odd. And finally, show that if we've got integers a and b, then a plus b cubed is congruent to a cubed plus b cubed mod 3. Now, I'll just say that we have the methods of direct proof and contrapositive proof to work with.
Still going strong, 5 hours in.
This is the 11th video in a series devoted to conceptual proof writing. In the previous video, we looked at proving conditional and non-conditional statements. And when proving conditional statements,
5 hours strong, baby.
Direct proof method as well as proof by contrapositive. Today, we're going to look at proving conditional and non-conditional statements via contradiction. So let's look at a quick outline of a proof by contradiction, and then we're going to do a bunch of examples. So let's say we want to prove a proposition P. So P is some mathematical statement. It might be a conditional statement, it might be an existential statement, it might be something else.
I got it.
So what we'll initially do is suppose that P is not true. So this seems like we're kind of giving up the game. If we want to prove that something is true, why would we start our proof by supposing that it's false?
That's so silly.
Well, that's where the big trick is. What we'll do after supposing that it's false is follow that line of logic until we come up with a contradiction. So this should actually read not C and C. And that's obviously a contradiction. It's impossible for a statement C to be both false and true at the same time. But if we got a contradiction from assuming that P is false, then that means it's impossible for it to be false. In other words, it must be true. So that's how this whole thing works. Okay, so that being said, I think really we need to look at several examples, and then after which you need to get your hands dirty with some of your own proofs by contradiction. So we're going to start with a very classic one, and that is the square root of 2 is irrational. So let's see how we can do this. Obviously, we're going to use a proof by contradiction because that's the whole game today. Okay, so I like to use the following kind of language when doing a proof by contradiction, although you can come up with your own language. I like to say something like, towards a contradiction, we assume that the square root of 2 is rational. That means we can write it as a over b, where a and b are integers, and we might as well assume that this is a fraction in lowest terms. So that means that a and b share no factors, which is the same thing as saying that their GCD is equal to 1. So we'll say here the GCD of a and b is 1. So part of this equation right here is not the square root of 2 is irrational, because if we take the not of that statement, we see that the square root of 2 would be rational. But being rational means that you can be written as the ratio of integers. And then by the structure of the rational numbers, we know that we can always write a rational number in lowest terms. That's what this GCD of 1 stuff is. Okay, so now we want to take this assumption and then hopefully work it towards some sort of impossibility. Okay, so let's get started. So if the square root of 2 equals ab, then we see that 2 times b squared is equal to a squared. So we can get that by multiplying both sides by b and then squaring both sides. Okay, but look at this. We have 2 times b squared equals a squared. That means a squared is even, but if a squared is even, then a is even. So let's write this down. So a squared is even, and thus a is even. So you probably established that result in your homework exercises or something. Okay, so we know that a is even, but now we can decode a being even into an equation. So let's do that. So now let's write a as 2 times c, where c is some integer. Right? So that's the definition of evenness. And then plugging this expression for a into our equation right here will actually bring us to an immediate problem. So maybe I'll extend this sentence and say leading to 2b squared equals a squared, but that's equal to 2 times c, quantity squared, but that's equal to 4 times c squared. But notice that we can divide both sides by 2, and that leaves us with b squared is equal to 2c squared. But that means b squared is even, and thus b is even. So maybe let's just write and, so b is even. But let's see, what do we have? We have a is even and b is also even. But since a and b are both even, they're both divisible by 2. But if they're both divisible by 2, their GCD is at least 2. So we can say, so since 2 divides a and 2 divides b, we have 2 divides the GCD of a and b. Right? So that's kind of the definition of the GCD. But let's recall that we started with the GCD of A and B is 1. So this ends with the statement 2 divides 1, because 1 is the GCD of A and B, but that's a contradiction. Because 2 clearly does not divide 1. 1 itself is not an even number. So we got ourselves to a contradiction, but that finishes everything off, because what did we contradict? We contradicted our original assumption way up here that the square root of 2 was rational. So if the square root of 2 cannot be rational, it must be irrational. All right, let's do another. For our second example, we've got another very classic result, and that's on the infinitude of primes. This is based off of Euclid's original proof of this statement. So let's see, our proposition is that there are infinitely many primes. So again, we're going to work towards a contradiction. Here maybe we'll use a little bit different language by way of contradiction. And I'd like to point out while we're at it that often if you're making notes or if you're doing a rough draft of a proof, you might shorten by way of contradiction to BWOC. So often when I'm writing things on the chalkboard and not writing things out in their final draft, I'll use BWOC for by way of contradiction. Okay, so anyway, so by way of contradiction, let's assume that the set of all primes is the set P1, P2, all the way up to Pn. Okay, so let's talk our way through this. So if we're assuming that there are not infinitely many primes, then that means that there are finitely many primes. But if there are finitely many primes, then we can put them all together into a finite set and index them as such. So that's exactly what we've done here. So now from this set, we're going to consider a special number. And there are lots of different proofs for infinitely many primes of different types. 4k plus 1, 4k plus 3, 5k plus 4, 5k plus 1, so on and so forth. And lots of them use a similar strategy to this. In fact, there are two main strategies for proving the infinitude of prime in special cases. And One of them is using this kind of method right here. Okay, so anyway, let's get to it. So let's consider the following number. And this number is going to cause all the problems towards our assumption of the finiteness of the set of primes. Okay, so we'll call it n, and it'll be the product of all of these primes, p1, p2, up to p little n, plus the number 1. But now, that's a natural number. And every natural number is divisible by a prime. Well, I guess we should say that's a natural number bigger than 1, and thus it's divisible by a prime. So let's find a prime dividing n. Okay, but since this set right here is the set of all primes, it must be in this set. So maybe we'll write that as which must be p sub k for some k between 1 and n. Okay, so first of all, n must be divisible by a prime, but then it must be divisible by one of these primes because this is the set of all primes. So now that we said n is divisible by pk, that means n is a multiple of pk, which means we can write n as a times pk for some a, and then we'll do kind of the calculation that finishes this thing off. So let's observe that we can take the number 1 and we can write it as capital N minus the product P1 up to Pn. That's just by solving this equation right here for the number 1. But now capital N is a multiple of pk, so we can write it as a times pk. But then this P1 to Pn is also a multiple of pk. That's because it's the product of all of the primes, including this pk. So I'll write this as minus b times pk. And then maybe over here I'll say that b is equal to the product P1 up to pk minus 1, pk plus 1, all the way up to Pn. So it's going to be the product of all of those primes except for pk. But now we can factor a pk out, and we'll see that we have pk times a minus b. But that leads us to a problem. We have 1 is a multiple of pk. So that means pk divides the number 1. But the only natural number divisor of 1 is the number 1. So here we have thus pk is equal to 1. But 1 is not a prime. So we then ended up with pk is in this list, thus it's a prime.
That's crazy.
And it's equal to 1, so it's not a prime, but that's our contradiction. So we'll write down here a contradiction. But what was the source of this contradiction? It was way up here where we assumed that there were only finitely many primes. So thus it must be false that there are finitely many primes, and thus there are infinitely. I
just left because I kind of knew.
So now let's notice that neither of these were conditional statements. Let's now look at some examples of conditional statements that can be proven with a proof by contradiction. Now let's look at proofs by contradiction for conditional statements.
Okay, let's go.
But in order to do that, let's recall what the negation of a conditional statement
Roblox.
is. So not P implies Q is the same thing as P and not Q. So we made a truth table earlier to establish that logical equivalence. Okay, so now let's say we want to prove the proposition
truth table
Q, which is the same thing as this conditional right here. So if we want to do it via contradiction, we'll suppose that this conditional is not true. So in other words, we will suppose that P is true and Q is false. And then we'll do calculations with that setup. That's what happens in this box, which will lead us towards a contradiction just like we had before. So we'll have some statement is true and some statement is not true. So let's recall earlier we had contradictions like 2 divided 1. So 2 clearly does not divide 1. And we had another contradiction where some number was simultaneously a prime and it was equal to 1, but that's not possible. So I'd just like to do a little bit of a remark down here. So if C looks like P or Q, then maybe this proof could have really been done with a proof by contrapositive. Now, some instructors are really strict about only making a contradictory proof when a contrapositive proof is impossible. I'm not that picky, but just be aware of the instructor that you have. I guess the best case is that C is unrelated to P and Q. That's really the mark of a contradictory proof that was not a contrapositive proof in design.
good. Oh, good.
Okay, so let's look at an example. So let's prove the following conditional statement. If A and B are integers and A is bigger than or equal to 2, then A does not divide B, or A does not divide B plus 1.
Wow.
Okay, so just to maybe write this out,
that's a crazy predicament.
Underlining would be our statement P. This statement here, which I'm now underlining, would be our statement Q. So we want to initially assume P is true and Q is false. So let's do that. So let's first notice that we're working towards a contradiction. So I'll put BWOC by way of contradiction.
What?
Now in your final write-up of a problem like this, you'd want to write those words out. Okay, so by way of contradiction, let's suppose that A and B are integers, where A is bigger than 2 or equal to 2, and A divides B, and A divides B plus 1. So let's recall that when negating Q, which is an OR statement, that's going to turn the OR statement into an AND statement.
Oh yeah, of course it will.
Okay,
OR and AND, 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 OR. So
thus, we have B is equal to A times M, and B plus 1 is equal to A times N. And that's going to be for some M and N, which are integers.
I agree.
Now here's where we cause the problem. So let's do our subtraction of B plus 1 and B. So we have 1 is the same thing as B plus 1 minus B.
Oh, that is so true.
That's going to be the same thing as AN minus AM, but that's going to be the same thing as A times N minus M.
Wow.
But that means we've got an integer A which divides 1. But there are exactly 2 integers A that divide 1, and that's plus 1 and minus 1.
No way.
So thus, we have A equals plus or minus 1. So let's see what we have. We have A is plus or minus 1, 2. And A is bigger than or equal to 2 up here.
No!
But that's a contradiction.
No!
So these 2 arrows going towards each other, that would be read as that is a contradiction. And that finishes this proof. And now we'd probably like to do a little bit of a review of this proof to make sure that we couldn't do a proof by contrapositive. And in fact, this one is a little bit on the edge. I'll let you check if you can do a proof by contrapositive, but I think a proof by contrapositive would not lead to A being bigger than or equal to 2. It would in fact lead to A being bigger than or equal to 2, or A being less than or equal to -2. So I would say this problem lies somewhere in the middle right now. So C does look like P or Q, but if we try to do the proof by contrapositive, which like I said, I'll let you do, we don't end up proving not the original statement. We end up proving like something similar to it, but that's a little bit weaker. So that being said, it's also not one of these best cases, which is to be expected because not every proposition that you try to prove will fall perfectly into one of these 2 cases. And that's just something that you have to work with. Okay, now let's move on to biconditional statements. Now we're going to look at biconditional statements. But luckily, this is really just proving 2 conditional statements in a single proof. And we're armed with a couple of different strategies for proving conditional statements, so we should be good to go. But that being said, let's look at a quick outline just for good measure. So let's say we want to prove the biconditional statement P if and only if Q. That means we need to prove P implies Q using any method that we want, and we need to prove Q implies P using any method that we want. And that's really all there is to it. Okay, we're going to do 2 examples. The first one is actually something that we used previously in the video, but that being said, I think it's nice to see written out. So we'll prove that the integer n is even if and only if n squared is even. So I like to point out which direction I'm doing one at a time. And so I'll start by saying, okay, I'm going to go in this direction first. So I'll put the implication arrow and put a little box around it. Now, keeping in mind good proofwriting etiquette, which you were assigned to read at the end of the last video, you would want to put this into a sentence in your final draft. And this is something really important to stress, is that your first draft of a proof should not be the same as your final draft. And your chalkboard draft and your chalkboard notation needs to be translated into final draft notation. Okay, so that being said, let's do this forward direction first. And we're going to do this with the method of direct proof. So let's suppose that n is even. Okay, but what does that mean? So by definition of n being even, we have n is equal to 2k for some integer k. So that's the definition of evenness. But now, thus, n squared is equal to 2 times k quantity squared, which is the same thing as 4 times k squared, which is the same thing as 2 times the quantity 2k squared, which is even. And there we've done it. If n is even, then n squared is even. So now let's do the reverse direction. So I'll just put a little box and then the arrow going the other direction. And since we just talked about a proof by contradiction, let's do it that way. That being said, a proof by contrapositive is also a good choice. And actually, in the end, perhaps this proof by contradiction really could have been written as a proof by contrapositive, but we'll see that at the end. Okay, so for the reverse direction, what do we need to suppose? Let's suppose that n squared is even and n is odd. Right? So if we're going in the reverse direction, we want to prove that if n squared is even, then n is even. So recall that the negation of that implication would be this kind of setup right here. Okay, that's good. So now let's write n as 2k plus 1 for some integer k. And we'll simultaneously write n squared as 2 times maybe l for some integer l. Okay, so we're able to do that by the assumption that n squared is even and n is odd. So now from there, let's do our calculation. So let's put a heading on that like observe. So let's do 0 equals n squared minus n squared. But now let's use our two versions of n squared. So this is equal to 2k plus 1 quantity squared minus 2 times L, where the first version of n squared is taken from this expression, n is 2k plus 1, and the second is taken from our expression for n squared as an even number. Okay, so now let's do a bit of calculation. That's going to give us 4k squared plus 4k plus 1 minus 2l. But now notice that we've got 0 on the left-hand side, and we have even plus odd minus even. That's definitely an odd number on the right-hand side. That being said, in a previous video, we learned about congruence mod n. So let's maybe simplify this with the language of congruence mod 2. So this right-hand side is congruent to 1 modulo 2. So if you need to review that definition, now would be a good time to do that. So let's see what we ended up with. We have 0 is congruent to 1 mod 2, but that's a clear contradiction. So a contradiction. Recall that numbers are congruent mod 2 if and only if their difference is a multiple of 2. But the difference of 0 and 1 is not a multiple of 2. So that contradiction finishes off the proof of this backwards direction. Okay, so that being said, I think a proof by contrapositive is much better here, but I think doing this proof by contradiction is a nice illustration, especially going down here to the end and using this newer technology of congruence mod 2. Okay, so now let's do another. This next example will also use the notion of congruence mod n. And I'm also going to introduce a little bit of shorthand that perhaps you haven't seen yet. So we will start by supposing that we've got integers a and b. And then from there, we'd like to show that A is congruent to B mod 15 if and only if A is congruent to B mod 3 and A is congruent to B mod 5. And the shorthand that we're introducing is this IFF for if and only if. So again, this is something you would write in your notes or on the chalkboard, not in a final solution. Okay, so let's go and start maybe with the forward direction. So let's suppose that A is congruent to B mod 15. And we'll hopefully be able to prove is that A is congruent to B mod 3 and mod 5. Okay, so let's decompose this into a definition. So thus, 15 divides A minus B. That's the definition of congruence mod 15. So A minus B is equal to 15 times n for some integer n. Again, that's the definition of divisibility. So we had a twofold uncoupling of our definition. First, from congruence mod 15 to divisibility to this being a multiple. So that's cool. Okay, so now let's go from there, keeping in mind that we're trying to get to congruent to mod 3 and congruent mod 15. Okay, so let's see if we can do this all at once. So let's note that A minus B is equal to 3 times 5n, and A minus B is equal to 5 times 3n. So that's obviously the same thing because of commutativity and associativity of multiplication, but writing it in this first way, we see that A minus B is a multiple of 3, and writing it in the second way, we see that it's a multiple of 5. So now we would maybe say that 3 divides A minus B and 5 divides A minus B. Thus, A is congruent to B mod 3 and A is congruent to B mod 5. Again, note what we did here is we unpacked the definition, did a tiny bit of a calculation. It was really just the factoring of 15 into 3 times 5, and then repacked the definition. Okay, so that finishes the proof of this direction. So now let's do a proof of the other direction. Now let's look at the reverse direction. Now I think we can do this with a direct proof as well. So let's start by supposing that A is congruent to B mod 3 and A is congruent to B mod 5. So here I use this SPS as a shortening for suppose sometimes. Now let's unpack these definitions into equations. So thus, 3 divides A minus B and 5 divides A minus B. So A minus B is equal to 3m and A minus B is equal to 5n, where m and n are appropriate integers. Now, let's maybe cut out the A minus B bit and notice that this means that 5 times n is equal to 3 times m. But that means the left-hand side is a multiple of 5 and thus the right-hand side is also a multiple of 5. Now, technically we're using the fundamental theorem of arithmetic here, but I think that's kind of okay here. But 3 is most definitely not a multiple of 5, so that means that m is a multiple of 5. So via that, we can write m as 5 times k for some integer k. Great. And that's because 5 and 3 are both primes, and thus 1 is not a multiple of either. Okay, great. So we've got m is equal to 5k. Now we plug this version of m back up here. So I would maybe write that as, notice that a minus b is equal to 3 times m, which is now equal to 3 times 5k, which is equal to 15k, which leads to a congruent to b mod 15. So I skipped maybe an intermediate step where I said that 15 divides a minus b, but I think that's okay here. So that finishes this reverse direction, which finishes this proof. Okay, so now we're going to end with a few assorted results. Like I said, we're going to finish with a couple of assorted results.
Oh shit, I'm still muted.
And this first one is an
I don't know how the fuck how long I've been muted
so
for.
We'll prove that two numbers exist that satisfy
from the
some
way
rule. We
My
won't
stuff
show that
is.
they're unique though.
I cannot see that I'm muted until I fucking sit back.
And so this is a really
my
famous
microphone
formula
is just
called
like beep,
Bézou's
beep, beep,
formula
beep,
or
you know?
Bézou's lemma. So it says that if we've got natural numbers a and b, then there are integers
still going,
x
right?
and y.
Fuck yeah, we is. Fuck yeah, we is.
The GCD of a
We
and
is going.
So in other words, given
Jesus,
two natural numbers, you can always
Alright,
write
whatever.
their greatest common divisor as a linear combination of those natural numbers. Where you think about linear combination in terms of what you learned probably in a linear algebra class.
But oh well.
Okay, so the proof of this is super classic.
Let's keep it
so
going.
let's get going. So let's consider the following set. So I'll call that set S. And it'll be everything of the form AU plus BV, where U and V range over all integers. And then we'll take that and intersect it with the natural numbers. And so now let's note that the number A is in S. Well, so notice that we get the number A by taking U equal to 1 and V is equal to 0. And since A is a natural number, it's both in this set and that set over there. But what that really tells us is that S is non-empty. So we have a non-empty set of natural numbers.
Non-empty set.
So now let's recall earlier we talked about something called the well-ordering principle. And the well-ordering principle allowed us to take any non-empty set of natural numbers and choose a smallest element. And that's exactly what we're going to do here.
Oh yeah, I remember that.
So by well-ordering, S has a smallest element. And what will we call it? Well, based off of this up here, we'll call it D.
Call it proper
so
small.
D is equal to the minimum of S. But since S is everything of the form AU plus BV, that means D is of this form too. And so we'll take the numbers that produce D to be equal to X and Y. So we'll define integers X and Y such that D equals AX plus BY. So in other words, X is the U value that produces D, and Y is the V value that produces D. Okay, good. So now from here, what we'd like to do is show that D is in fact the GCD. So I think this is a perfect place for a subclaim. So let's put that here. So claim D in fact is equal to the GCD of A and B. So let's recall, in order to prove that, we need to show that it's a CD, in other words, a common divisor, and then we have to show that it's the largest such common divisor. So let's first show that it's a common divisor. And we'll do that by dividing A by D and show that we get a remainder of 0. And since A and B are applying symmetric roles here, we only need to check it for A. The B is similar, which we'll write at the end. So now let's use the division algorithm with D and A to write A equals D times Q plus R, where R is between 0 and, let's see, D. Great. So again, like I said, that's the division algorithm. And now let's notice if R is equal to 0, we are done, because that implies that D divides A. And then similarly, D divides B.
Finally, man.
So by way of contradiction, let's suppose that D is not 0. So by way of contradiction, suppose I meant R is not 0. But now let's solve this equation for R. So let's note now that R is equal to A minus D times Q, but that's equal to A minus AX plus BY times Q, where we wrote D using that linear combination of A and B. But now we can collect terms and then see that we get A times the quantity 1 minus QX, and then plus B times QY. But that's an element of S, because it's a linear combination of A and B, and that's what it takes to be an S. You have to be a linear combination of A and B, and you also have to be a natural number. But if R is not equal to 0, that means it's bigger than 0, which means it is a natural number. But that's a problem, because what do we have now? We have R is strictly less than D, and we have R is an element of S. So that means that R is in S, but it is smaller than the minimal element.
Okay.
But that's a contradiction.
Let's go.
You can't be smaller than the minimum of a set. So
that is so true.
We've reached a contradiction. And so that contradicts this possibility right here, the possibility that R is not equal to 0, which means that R really is equal to 0. But if R is equal to 0, then we have D is in fact a divisor of A. But then, like I said, D being a divisor of A and showing D being a divisor of B is really exactly the same proof. So that means we know that D is a divisor of both A and B, which is the first thing we need to prove when we show that D is the greatest common divisor. Okay, so now let's show the greatest part. So along the path of showing that D is the greatest common divisor of A and B, we've shown that D is a common divisor of A and B. So let's recall that we really only proved this case right here, that D is a divisor of A. But the case when D is a divisor of B is exactly the same. We could use our similarly approach in that case. Okay, so we have it's a common divisor. Now we need to show that it is in fact the greatest common divisor. So let's suppose that we have another common divisor. I'll call it C. So C divides A and C divides B. Okay, great. But what does that mean? That means that A is equal to C times some number. Maybe we'll use the number Z. And then B is equal to C times another number, which I'll call W, where Z and W are integers.
Bro, what the hell is what is the letter Z in number, bro? That doesn't make no sense. That don't make no sense, bro.
Plus BY from what we had up here. But now that'll be equal to C times XZ from this expression for A plus C times YW from this expression for B. But that's equal to C times some stuff. That stuff is xz plus yw. So we have D is equal to a multiple of C, which is the same thing as saying that C divides D. But that's exactly what we needed to prove the greatest part of the greatest common divisor. And that finishes off this proof. Okay, good. Let's do one more. So we're going to finish off with a really classic result. And that is there exist irrational numbers, x and y, such that x to the y is rational. So I think that's pretty cool. We're going to give two proofs here, a non-constructive proof and a constructive proof. And I guess like a non-constructive proof might have some logical issues depending on how you feel about the law of excluded middle. But that's some really kind of hardcore logic stuff that we're not going to worry about so much. Okay, so for our non-constructive proof first. So this is going to break down into two cases. And it's so quick. Notice I don't have much room here, and that's because I won't need much room. So our first case is, what happens if the square root of 2 to the power square root of 2 is rational?
Oh, that's crazy.
So perhaps that is a rational number.
Hey,
and
I don't know.
If it is, then we are done. Because we've got an example of an irrational to an irrational, which is rational. Okay, cool. So what about case 2? So case 2 is what happens if this number is not rational. So if this number is not rational, then in fact we can raise it to another number which is also irrational to produce something that's definitely rational. So let's do that. So let's note that if we take the square root of 2 to the square root of 2 and raise that to the square root of 2.
Boom, that's 2.
Then by our assumption, we have an irrational to an irrational. But by exponent rules, this simplifies to the square root of 2 to the 2 power, which is 2, which is rational. And we're done. So either way we have it, we have an example of an irrational to an irrational, which is rational. So here we're going to actually define numbers x and y. So let's set x equal to
how do they even make numbers
the square
that
root
crazy,
of 2.
bro?
Notice that is irrational by earlier in the video. And then we'll set y equal to the log base 2 of 25. And this is irrational by a homework exercise. And then from this setup, now let's observe that we can take x to the y, which is the square root of 2, all to the power log base 2 of 25. And we can write this as the square root of 2 to the power 2 log base 2 of 5. But then this 2 will cancel that square root of 2 down to a 2, and that leaves us with 2 to the power log base 2 of 5, which is clearly equal to 5, which is a rational number. So we've got an explicit example of an irrational to an irrational, which is a rational. Okay, so now I'm going to leave you with a couple of warm-ups. So I'm leaving you with 4 warm-up exercises. The first one is the gap in that proof that we just saw, and that is to show that the log base 2 of 25 is irrational. Next, show that there are no xy integers, such that 4x minus 6y is equal to 1. Next, suppose that a and b are natural numbers and show that a is equal to the GCD of a and b if and only if a divides b. And finally, say you've got an integer n, then you want to show that 2n squared plus n plus 5 is even if and only if n is odd. And that's a good place to stop. This is the 12th video in a series devoted to introductory proof writing. And today we're going to talk about proofs involving sets. So how do you show that something is an element of a set? How do you show that one set is a subset of another set? And how do you show 2 sets are equal? Those will be the main things that we cover. So let's start with how to show that something is an element of a set.
Honestly, Bossman, not a clue.
So let's say we've got a set written in set builder notation as follows. We'll call our set A. And it's built up of elements x satisfying some condition p, so p of x. So there's really not much to showing that a is an element of a. All you need to do is show that p evaluated at a is true. So recall p, when it's not being evaluated at anything, is an open sentence, but when you evaluate it at something, it becomes a mathematical statement which may be true and may be false. If it's true, then your element is in the set, and if it's false, then your element is not in the set. Okay, well, there's another way of writing down sets, which is also set builder notation, but adds a little bit of a different condition, and that's set builder notation of the following form. We have the set A is all x in S such that p of x. So p of x is still that mathematical statement, or that open sentence being evaluated at x. But we have this extra condition that x must come from some sort of universal set. And so the proof here really is essentially the same thing, except you also have to check that you're within that universal set first. So if you want to prove the claim that A is in A, then you would first show that A is an element from S, and then you would show that P of A is a true mathematical statement. Okay, so let's do a couple of examples before we move on to the meat of the video, which is showing one set as a subset of the other and then showing set equality. So let's consider the set, which I'll call A again, and it'll be all ordered pairs of integers such that their product is congruent to 0 mod 6. So let's look at some examples of things in A and things not in A. So let's notice that 2, 3 is in A, and that's because 2, 3 is in Z cross Z, and 2 times 3 is equal to 6, but 6 is congruent to 0 mod 6. Okay, so that's really all there is to it. Now let's look at another one. So the ordered pair 4, 9 is in A, and that's because 4, 9 is an element of Z cross Z, and 4 times 9 is equal to 36, but 36 is a multiple of 6, so it is congruent to 0 mod 6 as well. So in fact, we could find an infinite family of elements in this set. Let's note for all n in Z, the ordered pair n, 6 is in A. And that's because it starts off being inside of Z cross Z, so that's the first rule that it has to satisfy, and then the stricter rule that it has to satisfy is that 6 times n is congruent to 0 mod 6. So now let's look at a non-example. So let's notice that the ordered pair 2, 5 is not inside of A, and that's because 2, 5 is in Z cross Z, but 2 times 5 is equal to 10, which is not congruent to 0 mod 6. In fact, it's congruent to 4 mod 6. We could do another example. Notice 1/2 12 is not inside of A, and that's because 1/2 12 is not inside of Z cross Z. So it's not even within the universal set. But that being said, it does satisfy the condition, which is kind of interesting. I'll put that in quotes. We wouldn't actually check that because we don't get past the first door in this case. Notice that 1/2 times 12 is equal to 6, which is congruent to 0 mod 6. So it satisfies the stricter condition, but not the opening condition. Okay, so now let's talk about subsets. Now we're going to talk about proving how one subset is a subset of another. But let's note that that's really a conditional statement. Showing that A is a subset of B is equivalent to the conditional A is an element of A, so lowercase a is an element of A, implies lowercase a is an element of B. So we'll keep that in mind when we form our outline for our proof. And we'll have a direct and a contrapositive outline. Although I guess you could have a proof by contradiction outline if you wanted to as well, but I'll let you fill in those details. So if we want to prove that capital A is a subset of capital B, then the direct method would be to suppose we've got an element, lowercase a, of A, and then do some calculations with what it means to be inside of the set A. That's what this box is. And then you would end at the end with lowercase a is an element of B. And then likewise, if you want to do a contrapositive proof, you would start with lowercase a is not an element of B. That's like the not Q condition here. You would do some calculations and you would end with lowercase a is not a subset of capital A. Okay, good. So let's look at this first example, which I think we might do both ways. So we'll show that the set of all integers that are congruent to 1 mod 4 is a subset of the set of all integers which is congruent to 1 mod 2. Okay, so let's get to it. Now let's start by supposing that we've got an integer, I'll call it m, from this left-hand side. So in other words, it's of the form 1 mod 4. So being inside that set means that you're 1 mod 4. So thus we can say m is congruent to 1 mod 4 and then m equals 4k plus 1 for some integer k. Now we did this step from here to here in more than one step previously. We moved through divisibility, so we would say in the middle that 4 divides m minus 1, but I think this is okay just to jump all the way there from now on. Okay, so now looking ahead, we'd like m to be of the form 1 mod 2, but that means that m minus 1 is divisible by 2, but we can show that pretty easily. So now let's note that m is of the form 2 times 2k plus 1. But that means that 2 divides m minus 1. Pretty clearly, we can move that 1 over, and then we have m is an even number. Okay, so thus m is congruent to 1 mod 2. But that's exactly what we need for m to be in the set on the right. So maybe we finish it off with m is an element of the set of all integers that are congruent to 1 mod 2. Okay, so that would be this proof. Okay, so now as promised, let's also do the contrapositive. Now we will reprove this result using the contrapositive. So let's suppose we've got an integer which is not in the right-hand side. So in other words, m is an integer with m is not in this set of all integers such that it is congruent to 1 mod 2. Great. But what does that mean? That tells us that m itself is not congruent to 1 mod 2. That's what it takes to not be in that set. But if m is not congruent to 1 mod 2, it must be congruent to 0 mod 2. Because, well, there are only 2 possibilities when you're working mod 2. Only 2 remainders when dividing by 2, 0 and 1. So let's write that here. We have m is congruent to 0 mod 2. Okay, but if m is congruent to 0 mod 2, that means m is even. So let's write m as an even number. So we'll write m as 2 times k for some integer k as needed. And now let's break this down into two cases depending on the parity of k. So here's our case number 1, which is k is even, thus we can write k as 2 times, maybe I'll call it a, where a is some integer. So in this case, we have m is equal to 4 times a, which is congruent to 0 mod 4. But that means that m is not congruent to 1 mod 4. Great. And now let's look at case 2, which is the case where k is odd. But if k is odd, we can write k as 2 times b plus 1 for some integer b. But now plugging this version of k here, we see that m is equal to 2 times the quantity 2b plus 1, which is the form 4b plus 2, which is congruent to 2 mod 4. Yeah. But being congruent to 2 mod 4 means that you cannot be congruent to 1 mod 4. So that tells us that m is not congruent to 1 modulo 4. So either way you have it, through either of these cases, we have m is not an element of this left-hand set. So let's write out that left-hand set. It's all integers n, such that n is congruent to 1 modulo 4. So the direct way is definitely easier in this case, but I think it's nice practice to see both. So let's do another couple of these. So for our next one, we'll show that the intersection of the set of all integers that are divisible by 2 and the set of all integers that are divisible by 15 is a subset of the set of all integers divisible by 10. So let's get going. We'll do this with the direct method. So let's suppose that we have an element m from this left-hand side. So it's in the intersection of these two sets, the first of which is the set of all integers divisible by 2, and the second of which is the set of all integers divisible by 15. But what does that mean? Well, that means that m is in this set and m is in this other set. But we can quickly bring that down to m being even and m being a multiple of 15. So let's maybe take it all the way to that point. So m equals 2 times a and m equals 15 times b for some a and b which are integers. So this 2 times a is being in the first set, this 15 times b is being in the second set. So now let's note that since 2 times a equals 15 times b, so that's just setting both versions of m to each other, we know b is even. So I think that's pretty clear. The left-hand side is even. That means the right-hand side has to be even. 15 is non-even, which means all of the evenness on the right-hand side must be created by this number b. So now let's write b as 2 times c for some integer c. So now that we have this, let's plug this expression for b into this expression for m up here.
All right.
So I'll maybe write it like this. Observe that
I'm observing, brother.
m is now equal to
Big up Michael Penis, bro. I'm observing that shit.
Which is the same thing as 30 times c, which is the same thing as 10 times 3c.
We still recording?
10 times 3c is an
we are. What the
fuck
was that, bro?
Set. So we could say that this is in the set of all integers n, such that 10 divides n.
We are still good though.
Great. But that's what we needed to do to show this subset relationship. We started with an element of the left-hand side, and we showed that that element was also an element of the right-hand side. So that concludes this subset proof. So now let's do a couple more that are kind of a little bit more abstract. So for our next result, we'll show for all sets A and B, the union of the power set of A with the power set of B is a subset of the power set of the union of A and B. Let's recall, in order to be inside the power set of a set, you are a subset of that set. Okay, so let's get going. So let's take an element capital X from the power set of A.
Holy cow!
So
yo,
that means that X
I am currently reacting to a 12-hour video right now.
X is in the power
Hello.
set of B.
Are you doing what I think you're doing?
I'm
reacting to a 12-hour video.
Symmetric roles in this entire
yeah.
setup.
I also got the fucking
So
remix as well, which jump scared me like crazy.
X to be an element of the power
Wait,
set
is that a recording?
I got that on recording, yeah.
The same calculation would happen if we chose to
almost 6 hours in.
So that allows us to use our phrase without loss of generality. So let's do that. So without loss of generality,
I'm assuming you don't want to be watching this.
That X is an element of the power set of A.
You know.
Okay, now let's get down to what it means to be an element of the power set of A. Thus,
turn on the video twice.
X
Right.
is a subset of
Oh my
A.
days.
But notice that A
I get the
is a
secret cool thing all the
subset
time.
of
I have
A
a
union
plugin that
B.
gives me it
So
every
this
time.
is a subset itself of A.
That's the first time I've ever heard it.
But being a subset is a transitive property, so that means
That's
X
a rare
itself is a subset.
Yeah, and
of
they're like
A
1 in
union
1,000 or something.
So I'll just add that on, and
It's like 1 in 1,000 or 1 in
X
10,000. I can't remember,
itself is a
but yeah,
subset of
it's quite
A
rare.
Union B. But now we'll go back to this power set world. So if X is a
to be honest,
subset
mate,
of A union
I've
B,
lost.
it's an
I've lost
element
it.
of the power set of A.
I was able to follow this for about 4 hours, and then I
watched
six.
the power set of
Huh?
A
You started watching this at 6.
About half
so
6,
let's
yeah.
just check that we've done everything we need to do. We started
Bro,
with
I
an
want to
element
watch the
of
whole thing and then,
left-hand
you know, not
side,
go to bed
and we
as
showed
soon as
that
I'm
that was
done.
also an element of the right-hand side. That's exactly what we need to
You having a
do
good
to
time?
prove this subset
Yeah, I am
relationship.
actually.
Okay, let's do another.
Definitely.
So for our next result, we'll show that if
It's a math
the
video,
power
right?
set of A is
Yeah.
a subset of the power set of B.
Oh, you know,
then
they're cool.
A is a subset of
I mean,
let's really
when I
focus in on what we
finished.
want
Oh
to
wait,
prove.
did Oleki send you?
Our
No, she wouldn't have
goal
sent you
is
it.
to prove
But
this
basically, she
green
sent me
box thing over here,
reacting
that A
to
is a
all
subset
episodes of
B.
Skibbity Toilet.
But
But it was in Polish and by a furry. And then I finished it. I told her I finished it, and I said, "You will not find anything that I won't react to."
That's the conclusion.
And then she sent me
So
this.
keeping in mind that we want to prove the green
Oh,
thing,
I thought you got given it at school.
One of these over here.
No, that was the
Probably
Polish
a direct
Skibbity
proof
Toilet
is fine
video.
again. So
I got
let's
given this
take
video at like 5 p.m.
element A
What?
from
By Oleki?
And then
Yeah, hold
we'll
on, let me-
end
let
with
me go
that
back
element A
through our
is in
DMs real
fact
quick.
in B. Okay, so how do we do this? Well, we have
Yeah,
this stuff about
I
the power
finished
set.
I finished
But
the
what's
Skibbity Toilet video
closest
about
thing to a
4:45,
single element within the power set?
and then
Well, you guessed it, it is the
25
singleton.
past 5,
So if we
she
take
said,
A
"You're actually
and
good at this.
A,
What the fuck?"
let's
And then I just said, "There is no video I cannot react
the
to."
singleton A
And she sent me that
is a
video,
subset of
and then
A.
I just
But
told
being
her
a subset
that
of
I
A
can
means
do
you
it,
are an
and then she was like, "No,
element
you
of the
can't."
power set.
And I was like, "I simply
So we might
disagree,
say
and I have the
thus,
time."
The singleton A is
And then she tried to retract her
the power
suggestion.
set of A. But let's recall the power set of A
but, like,
as a given is a subset of
'Cause,
the
like,
power
I'm
set
streaming
of
a minute. I'll take a screenshot and just send it to her.
Oh yeah, sure. Oh fuck, I paused the video.
Singleton A
I don't have
is
much
an
time for
element
breaks because this
of
is
the
really
power
close to the
set of
upload
B.
limit.
But if the singleton A
Wait, no,
is
that's
There's an
element of
upload
the
limit?
power set
Yeah,
of
12
B,
hours. This is
that
11
means
hours,
that the
52
singleton
minutes.
A is a subset of B. And we'll add
I
that
will
on.
upload
The
24-hour-long
singleton
videos
A
then.
is a subset
Oh,
of
they did it before.
But if the singleton A is a subset of B, that means every element inside of that
You
singleton
got the screenshot?
is an element of B. But there's only one element, and that's
Alright.
little a.
You know what,
So
I'll
we
keep-
can
I'll
finish
keep
this
streaming,
off.
why not?
Finally, little a is an element of B.
But yeah, I
But
followed
that
this until like
finishes off what we
video
need to
8.
do. We started
And then I went to the toilet,
with
got a
is an
drink,
element of
came
A.
back,
We
and there
ended
was some
with
confusing
B. A is
stuff.
an element of B,
And I haven't been able to
and
follow
we
it
used the
since.
tool at this step right here. Okay, so now let's move on to showing set equality. Now we're going to show how to prove one set
But
is
yeah.
equal to another set. And this is technically a biconditional. So to show that capital A is equal to capital B, we would show little a as an
my
element of
fucking
capital
God.
A if and only if little a is an element of capital B. And so I've got this as an outline down here. So what
hold
you
on.
really need to do
I'll
is
send
show
you
these
I'll
two
send you a
subset
photo of
relations
like the
any
stuff
way
that
you
I've
want.
written down because
So that capital A
like
is a
she said
subset
it's
of
useful to
capital
know
B
some
and capital
stuff.
B is a
So
subset
I've
of
written down some
capital
stuff.
A. now
Oh
let's look at this
no.
example.
Yeah, I've
We want to
written down some
show that the
stuff.
set of all integers that are congruent to 0 mod 10 is equal to the intersection of the set of all integers that are 0 mod 2 and the set of all integers that are 0 mod 5.
Yeah.
So
And
how are we going to do this? Well,
once
we'll
I got
follow this
stuck after
outline.
video 8, I think I
And
wrote down
just to
like
say
2
which
or 3
direction we're doing
lines for
first,
9 and
I'll
10 and then
indicate
just gave
that
up in
with
writing.
a subset symbol in a box. So
But
this
yeah.
means we're going to start with an element of the left-hand side and show it's an element of the
These are all
right-hand
the
side, and
notes
then
that
we'll
I've got
reverse
from the
that.
video.
So let's
like,
suppose that
purely
M
from funny
is an
Michael
element
Man.
of the set of all integers that are congruent to 0 mod 10. Okay, great.
Why?
But what does that mean? That means that M is 0 mod
Yeah, so
10.
I've given up
but
trying to
being
follow the
0
video for
mod
about
10
1.5
means
hours.
that you're a multiple of 10. So
Have
we
you
can
been doing
write
other stuff,
M
or are you actually?
as
No, I have
10
been sat here for the last
times
6 hours.
for some
Well, not even on your phone or anything.
No,
But now
I
we
have
just
got on
factor
my phone.
10.
I have got on my phone.
So let's maybe put it as an observation or a note. We have M is equal to 2 times
like,
5k.
I've had this video
and
going the whole
M
time.
is equal to 5 times 2k.
I've had the mic unmuted the whole time, apart from when people come into my room.
M is congruent to 0
And yeah.
mod 2 and
also, the
M
funniest part is, right,
congruent to
my
0
mum thought I was in a
mod
live
5,
one-on-one session with this
respectively.
guy.
Finally, that tells us that
Oh,
M
yeah.
Which is
an
quite
element
funny.
of that intersection
it's
on
believable.
the right-hand side. So in other words, M is in the set of all integers that are
guess.
0 mod 2 intersect the set of all integers that are 0 mod
I can't wait for Oleki to call me an idiot.
And now we've done half the proof. We've shown that this set on the left is a subset of the set on the right. And now we'll do the other half. So now we'll do the other direction.
Well, I mean,
I'll
you know,
indicate with the subset
I've
symbol
got enough
going
free
the other
time.
way. So now we want to suppose that we have an element M from the
I literally
right-hand
set an alarm
side.
for 6
So that means
o'clock
it's in the
just so I could
intersection
wake up
of
and get
these
it done
two
before
sets.
like
So the
it
set
got
of all
too late in the
integers that
day.
are 0 mod 2 intersected with
I am
the set of
dedicated
all
to
integers
doing
that
dumb
are
shit.
0 modulo 5. But what does that mean? That tells us
what does that mean,
M
Michael?
itself
I'm not too
is
sure. I'm
0
too busy
mod
talking to Harrison,
2,
mate.
And
I'm just gonna
M
shut you up for a couple
itself
seconds.
is
Oh,
0
am I a distraction? Am
mod
I?
5.
I have to
No.
leave.
That's
No,
the
you don't have to
entropy
leave.
being
Please
each
don't
of those
leave.
sets.
Please don't leave.
But being 0 mod 2,
I can go
means
find
that
another
being
VC to join,
0 mod
Arch, it's
5
fine,
means
you
that
know.
they're a multiple of 5.
Please
So
don't
that means
leave.
we can write M as 2 times A and
You think I'm sitting here for another 6 hours with you? I'm gonna leave at some point.
Yeah, you can leave. You can leave at some point, but just please don't leave now.
Which are integers. Multiple of 2 from this, multiple of 5 from that. But now we can set those two expressions equal to each other. So we have 2
Oh
times
my
A
fucking
equals
God.
5 times B. Notice the left-hand side is even, which means the right-hand side also has to be even. The numbers 5 is odd. That means the number B has to be even.
Okay.
So we'll write that here. Thus, B is even, which means we can write B as
I'm
2
too
times
worried
C
that this guy's gonna make some
for
dumb mistakes.
some integer C.
Because he's done that already.
Now, putting this expression for B into this
Really?
expression for
Yeah, he said that
M,
81
we'll see
times
that
2
we're
is
essentially
186.
done. So let's
is.
observe that M is equal to 5 times B.
I'm
which
genuinely
is the
not
same
sure where he
as
got
5
81 times
times
2
which
is
is equal to
186.
10C.
Me.
But if M is
I wrote this video.
You're doing this video, yeah?
I wrote it.
Oh, you
scripted
the video, did you?
It's in
Yep.
the set on the left-hand side. So
He
that
did it
means
in his
that
head.
M is in fact an element of the set
what I
of
told him
all
to say.
integers that are congruent to 0 mod 10.
I'm pretty sure he
That
looked away
finishes
from
this
his
proof
notes
off.
and just
We
looked
started
up
with an
and
element of
tried
the
to do it in
right-hand
his
side and ended up
head.
with an element of the
What, you
left-hand
want a
side.
ceiling?
Now let's do
You want a
more
ceiling? You
abstract
cosplaying a
example.
Spider-Man
Now
on
we've
his
got a bit of a
ceiling.
more abstract example. So we'll
Nah,
start
he just has
with
notes.
any non-empty sets A, B, and C, and we'll show
The notes are in the
that
direction of
A
the camera. He looked
cross
perpendicular
B
to the
intersect
camera.
C is equal
Yeah.
to A cross B intersect A cross C. So in other words,
You
this
just got more
cross
notes, has he?
product has a nice distributive
I've put notes
property
everywhere,
over the
just to make it
intersection.
seem less,
Okay,
weird.
so since this is a set equality
Behind him
property,
is just
we need to show
words.
containment
He
in
is just,
both directions.
there's nothing
Let's
but
do
a
this
void
containment
and
first.
words around
So
him.
we'll start with an element of the left-hand side and show that it's in the right-hand side. Okay, so let's
hip,
do it.
hooray.
So let's suppose, like I said, we have an element of the left-hand side. But
He is
notice that
not a
elements
real
of the left-hand
person.
side
He
are
is.
ordered pairs, given that we have a cross
His
product.
existence is just
So that
reading
means we
words
have
I've
X,
written.
comma, Y is an
All
element of
Michael
A
is allowed to
cross
do is
B
read
intersect C.
Harrison's
like I said, it's best to work
words.
with ordered pairs. Okay, but now let's strip this
That is his
away
only
into what it
only
means
thing
for
he's
an
allowed to
ordered
do.
pair to be in a Cartesian product. And so that means that X is an element of A and
Got him crying on video once. Nearly
Y
shot
is
him.
an element of B intersect C. Great. So like I
yeah.
said, that's what it means.
I
I don't
also
think you're gonna abuse you.
But now we'll strip away what it means
I also
for
finished
Y
my
to be
first
in the
ever no clip run
intersection
of Tidal
B
Wave
and
without
C.
fucking it
So
up.
we have
Too
X
bad.
is in A,
Oh,
Y
GG. What was the accuracy?
and
Accuracy was like
Y is in
94%.
C. But now let's
Not
go
bad.
back to the cross
And the
product
depth was
rule.
like
So let's see.
290, I think.
Since X
Maybe
is in
280.
A and Y is in B, we know that the ordered pair X,
But
Y
I
is
think
in
at one
A
point I got to the
cross
drop with
B.
12 deaths, which is
And
quite
furthermore,
impressive,
since
to be
X
honest.
is in A and Y is in C, we know the ordered pair X, Y
Wait,
is in
the
A
wave with 12
cross
deaths,
I
or
got to the wave
But
in
if
12 deaths,
XY
yeah.
is in A cross B and XY is in A cross C,
I
then it's
don't
in their
quite know how.
intersection. So we can
Well, I
finish
kinda
that
just
off.
did.
We have XY is an element of A cross B intersect A cross C. But that finishes the proof of this first containment. Now
Okay.
let's do the reverse containment.
Reverse?
Now we're going to do the reverse containment.
Oh,
Notice
for
we're still
goodness
working with
sake.
cross products of sets. So when we start with our starting element, it makes sense to start with an ordered pair. So let's do that. Let's suppose.
So wait,
we have an
what is the
ordered
exact
pair.
time
I'll
I
call
will
it
finish?
XY again, which is in the intersection of A cross B.
I finish
and
in
A cross
22 minutes past 6, surely.
And I think this is going to be exactly the same.
No, 'cause I
steps
didn't-
that
I
we
don't
saw
think I started
before in
exactly at
reverse,
half six.
But that's okay. So
God.
let's see what we get immediately.
Okay.
We see that X, Y is in A cross B,
So,
and
it'll be
XY
5 hours, 48
is
minutes.
in A cross C.
Oh,
But
lucky
now
it's
let's
74
decode
DM.
each of those. So that means we have X is in A.
Is he understanding, and what does he
and
think of it?
Y is in B, and Y
Has
is
been
in
taking notes.
So that's what we
I've
decoding
stopped
this sentence
I've
right
stopped
here. So the
understanding
fact
for
that
about an hour and a
XY
half.
is in A cross B means X is in A, and it means Y is in B. And then the fact that XY is in A cross C again tells us that X is in A. That's not new information though, but it tells us that Y is also in
I've
C.
stopped paying attention to this
Okay,
for like the
good.
last hour and a
But
half
now
to 2
we'll put
hours.
these back together.
I just
So
I don't understand
we
this
might say
anymore.
something like, therefore, X is in A.
But I must keep going.
And Y is in B intersect C. So that's putting this and statement back into an intersection.
Get Olek in the corner, she'll
But then we can
explain everything to
finish
you.
it off. This means the ordered pair XY is in A cross B intersect C.
Oh,
But that finishes this direction off as
can't be asked, man.
Okay, so now we're going to look at an interesting application of set-based proofs to a very classic problem. Now we're going to look at a
Given
nice
off
little
on life, not
application of set
understanding.
theoretic proofs for studying a certain class of numbers. And so let's look at the definition of that class of numbers. So a natural number P is called perfect if it's the sum of its proper divisors. So here are the first three perfect numbers. There's 6, which is 1 plus 2 plus 3. Those are all of the proper divisors of 6. So when I say proper, I mean all the divisors that are not equal to the number itself. Then 28 is 1 plus 2 plus 4 plus 7 plus 14.
Oh shit,
And
adding. I know how to
496
add.
is this big sum right here.
I don't.
1
Oh
plus 2
shit, these are
plus 4 plus
perfect
8 plus
numbers.
16 plus
Okay.
62 plus
I know what a
124 plus
perfect number is.
8.
Okay, this is
And
good.
then they go on down the line. You can find big lists of them online if you'd
What
like
the
to.
bloody hell's a perfect
Then
number?
after that, we're going to define two sets which
All of its
seem
factors add
unrelated,
to
but they will
itself.
be very related. So
Or if you
let's take
include the
capital
number
P,
itself,
which is a
One.
set of
all of
perfect
its
numbers,
factors add to
and
itself.
let's set capital A
it
be
to
equal to
twice
all
itself.
numbers of the form
No,
2 to
not
the power
1.
n minus 1
Apart from 1.
times
2.
2 to the n minus
2 plus
1,
1
where n
is
a
not
natural
2,
number,
Harrison.
And then this 2 to the n minus 1 is a prime. So it doesn't run through all numbers of this form. It runs through only numbers of that form if this object is prime. And I'd
Okay,
like to point out
boss
that
man.
primes of this form are known as Mersenne primes.
Oh, I've heard of a Mersenne
and
prime.
what we'll prove
Hell
is
yeah.
that A is a subset of B. So, in other words, all of these Mersenne primes give rise to perfect numbers.
What?
And in fact, if we only looked at even perfect numbers instead of all perfect numbers, this would be equality right here. And an even more crazy fact is that it is not known whether or not there is an odd perfect number. So maybe there is, but we just haven't found it yet. Or perhaps there are no odd perfect numbers and we just don't know the proof yet. Okay, so anyway you have it, this is what we'll prove here, this subset relationship. And we'll do it by chasing elements through, just like we've been doing the entire video. Okay, so let's suppose that we have an element A from the left-hand side, so it's of this form. So we have a natural number n such that A takes this form here. So it's 2 to the n minus 1 times 2n minus 1, where 2n minus 1 is prime. But then the fact that that's prime really allows us to write down the factors of A quite easily. So now let's list the factors of A.
I know what a factor is.
I don't.
Like factor 50 sun cream.
So they break up naturally into two classes.
You should know what that is. You're not Ginger.
Of that prime number 2 to the n minus 1, or multiples of that prime number. So let's maybe break those into 1 and 2. So 1 will be not multiples of that, whereas 2 will be multiples of that.
Okay.
So if you're not a multiple of this part, which is prime, then you must be a power of 2, because that's all that's left over. So that gives you 2
I'm about to start a new video, Harrison. The next video, video 13 is about to begin.
So you have all of those
boy, I can't wait.
of A. But then you also have the factors of A that include that prime 2 to the n minus 1. But you have all of those factors multiplied
New
by
longest
all of these
Harrison and
factors
Tortoise
raised to the
clips
powers of
video
2.
coming soon.
So you would have 2 to the 0
We're not beating this one.
times 2 to the
No,
n
we're
minus 1,
not.
2 to
We're
the
not even
1
going to get
times 2
close.
to the n minus 1.
Unless
all
we
the way up,
stream.
2 to the n minus 2 times 2 to the n minus 1. And
Reacting to my
finally,
sleep.
2 to the n minus 1 times 2 to the n minus 1. But now let's underline all the ones that are proper divisors. So these are all proper divisors, and these are also all proper divisors. This number right here is A itself, so we won't include that in the sum. So now let's sum the divisors and see that we get A back. So let's maybe note that we're doing that here. So summing the divisors gives us 2 to the 0 plus 2 to the 1, all the way up to 2 to the n minus 1.
I mean, I'm going to be honest, no one's actually going to watch like all of this, so I don't know why I'm still talking and shit.
So we'll have 2 to the n minus 1.
I may as well just like
2
leave.
to the 0 added all the way up to 2 to the n minus 2. But now
that's
these are
not in the
finite
spirit of the
geometric
channel.
series. So those have a well-known closed form that I bet you learned in an integral calculus class or a second semester calculus class. So let's sum those up. So this
I told him not to do it yesterday. There is nothing he won't react to. I'll say there's nothing we won't react to, because I will probably do this one on this at some point as well.
Yeah.
Well, you got 12 hours. You're gonna watch the Utopia video.
Minus 1 that comes down here. Then we'll have this, which is coming from this brown underline.
I'm still planning on watching the cruelty score video, so I might do that.
Minus 1 minus 1. But now we can add those two together, and we'll see that we get 2 to the n minus 1 times 2 to the n minus 1. But that's exactly equal to our starting number A.
He said, I really get that now.
We started with a number A from capital A.
Don't doubt us.
And then by showing that the sum of all its divisors equals
I feel like Oleki's just gonna fucking send, after this, either going to send me 12-hour videos every day, or just give up.
But that's exactly what we needed in order to show that subset relationship.
Oh, she's probably going to find like a 12-hour Polish video or some ridiculous shit like that. And that will drive me insane.
First is to show the set of all integers that are 0 mod mn.
Like, that might be the one thing that could break me, just 12 hours of a foreign language.
Intersected with the set of all integers that is 0 mod n. Then furthermore, sometimes
because I'm not gonna lie, 45 minutes was too much.
I think it's a nice
so I don't know how I'll do with 12 hours.
Example where you have equality and where
see, if I was going to do a 12-hour long one, I would do it from midnight until 12
so the next one is
noon.
to prove that A is a subset of B if and only if A union B is equal to B. And then next, you'll need to show
I don't think I could do that, though, which is why I got up at 6 to do
open
this.
Interval from -1/n to n+1/n.
I would just put an all-nighter.
Closed interval from 0 to 1. And then prove the union from n = 2 to infinity of the closed
Anything for the
interval,
channel. Anything for the channel.
Anything for the channel.
n is equal to the open interval from 0 to 1. And that's a good place to stop. This is the
video 13. We're here. Disproof. Oh my god, this is a short one as well.
About how to disprove statements.
It's only 15 minutes.
I'd like to look at a chart of mathematical statements. Be they
This
true,
is the
false,
shortest
or
video.
unknown. So generally, if a mathematical statement is true, we call it a theorem or a proposition or a lemma, but I'll just put this all under the larger heading of theorem. So in other words, these are true.
Yeah, I know all about that Pythagorean
if we have a false
thing.
mathematical statement, well, we just call that a false statement. I'm not sure there's a really decided upon word for that. But something whose truth is unknown is generally called a conjecture. So we have things that are true, things whose truth or falsehood is unknown.
You asked me saying what Pythagoras theorem is, I wouldn't be able to tell you.
So let's look at some examples of things from each of these categories. So the Pythagorean theorem is something which we know is true. So of course we know that says that the sum of the squares of the lengths of the legs of a right triangle equals the square of the length of the hypotenuse. And so this theorem was discovered.
Hey man, we were given it on a sheet in the exam, right? I don't need to know what it was.
Interesting. Then also Fermat's last theorem is known to be true. So that's fairly recently in the grand scheme of things. It's also known that there are infinitely many primes. In fact, we proved that in a previous video. Some things that are known to be false are this statement right here. So there exist natural numbers a, b, and c, such that a cubed plus b cubed equals c cubed. So that would contradict the truth of Fermat's last theorem. Another statement which we know to be false is that all continuous functions are differentiable somewhere. And this is maybe not known to students taking a class like this, but once you take an analysis class, you'll learn about a function that is continuous everywhere but nowhere differentiable. So it's one of these crazy analysis.
Oh yeah, I heard that one.
Then what about some conjectures? Some things that we don't know if they're true or false. Well, we don't know if all perfect numbers are even or not. So the existence of an odd perfect number is not known. Also, we don't know something called Goldbach's conjecture, which says any even number bigger than or equal to 4 is the sum of 2 primes. So we don't know if that's true or not.
That is so on God.
Also, we don't know if there are infinitely many primes of the form n factorial minus 1. These are unknown. Okay, so now that we've got these three categories like described, let's talk about what a mathematician does. So mathematicians are generally interested in taking things from this category, so the category of conjectures, their truth is not known, and transporting them into the category of theorems or to the category of false statements. So we've been working on proving things. We'll talk about how to disprove things a little bit today. Then there's another really important thing that mathematicians do, and that is come up with conjectures in the first place. And so they go out here to the ether of mathematical results that are just floating around waiting to be discovered.
Oh my fucking god.
And then they find one and put it in this category of conjectures. And then it either sits there if it's really hard, or if it's not really hard, it probably gets proven immediately to be a theorem or a false statement. Now I'd like to tell you a little bit of a story about this process of going to the ether to find a conjecture. And in
going
fact,
to the ether, what the fuck?
Who did
Hold
number theory. So this is
you're losing your mind, you're losing your mind, you're losing your mind.
I'm pretty sure he said go to the ether to find a conjecture.
To visit with a professor.
I don't know where that came from.
She told a story that there would be a very large line of junior faculty from all over the region outside this senior professor's door, just asking for conjectures to work on.
I have such incredible mental strength.
This ether might just be the outside of some professor's door who's more senior than you are. Okay, so now back to how to disprove statements. So let's just say, in short, how do you disprove a statement P?
I'm going to place it. City Skyline.
That statement is true. So to show that P is false, you would show that not P is true. But just to have some very simple outlines down on the board, what if we've got a universal statement?
Here we go.
Let's say we want to disprove the universal statement for all x in S, P of x.
Yeah.
Then you would want to show that its negation is true. But what that boils down to is finding an x in S such that not P of x.
Oh,
so
okay.
that for all
Yeah.
turn into an existential statement. Then if we'd like to disprove this conditional statement, P implies Q, you would find some x, I'm missing an x here.
Oh my god, he's missing an x.
Is true and
no, that's going to ruin his proof.
False. So that's the negation of the conditional. What about disproving an existential statement? Well, that's going to turn into a universal statement.
So existential.
There exists x in S such that P of x, you would show for
I don't know what's going on
in
anymore.
S, not P of x. Okay, so let's get down to some examples. So now let's look at our first two examples of things to disprove. So we'll show that these are false. The first one is that for every natural number n, f of n equals n squared minus n plus 11 is prime. Now let's say we were not told that this was false. So if we were not told that this was false, we would guess that it's false.
I'm gonna go toilet and figure out what the fuck is going on.
There's no like simple closed formula for a prime. So there's no polynomial expression that always outputs a prime. That's kind of a well-known fact. So we know that this must not always be prime by that well-known fact. But now what we need to do is find a particular n so that when we plug that value of n in there, we get something that's most definitely composite. But it's not so hard to find one. In this case, 11 works. So let's note that f of 11 equals 11 squared minus 11 plus 11, but that's equal to 11 squared, which is not prime. So this was a for all statement that we disproved by finding a particular x, that x was equal to 11. Now let's look at another for all statement that we'll disprove. And that is for all sets A, B, and C, we have A set minus B intersect C equals A set minus B intersect A set minus C. So this one's maybe a little bit trickier to get some intuition behind, but this is false as well. And we'll show that it's false by making a particular example where this fails. So let's maybe look at the following sets. Let's take A to be the set containing 1, 2, 3. We'll take B to be the set containing 1, 2. And we'll take C to be the set containing 2, 3. Great. And now let's look at either side of this would-be equation, this would-be identity. So let's start with the left-hand side. So we have A set minus B intersect C. Okay, but that's going to be the set containing 1, 2, 3, set minus the intersection of B and C. But what's the intersection of B and C? It's exactly this number 2. Great. So just to be very clear here, this B intersect C became this singleton 2. But now if we do that set difference, we'll get the set 1, 3. So here we get 1, 3. Okay, good. So that would be the left-hand side. Now let's look at the right-hand side. So let's do A set minus B intersect A
we are
set
so
minus
back.
C. So that'll be 1, 2, 3.
Oh my god, I understand everything now.
Minus 1, 2. And then intersected with 1,
oh my
2,
days.
3, set minus 2.
Zoe has messaged me.
Okay, good. But now let's do that simplification. So if we
saying,
take
I don't think
1,
it's healthy to
2
play with
away
your
from
penis
1, 2,
for that
3,
long.
We're just left with the singleton 3. So this turns into the singleton 3, and then we need to intersect that with what's left over after doing that set difference. But that's pretty clearly the singleton 1.
Well, he's going to be surprised in 6 hours when I've been playing with my penis for 12.
We get the empty set. So let's see what
he
we
ain't
have.
ready.
We have the empty set
He ain't
from
ready
one
for a
direction,
12-hour
and
gooning.
this
No, that
double
sounds
from
wrong.
3 from this other direction. These are clearly not equal to each other, which means we
He ain't ready
found
for a
an example
12-hour
where this
gooning
fails,
session.
But that disproves this statement. Okay, let's do another. So for our next example, we'll look at the following statement. So we will disprove this. So this statement is false. And the statement says there is a real number x such that x to the fourth is less than x, which is less than x squared. So let's maybe get started on this, and we'll disprove this by negating the statement and
Yeah,
show
you
that the
messaged me at
negated statement
9:15
is true.
talking about
So let's
how
say
I was
that this
playing
orange
with my
arrow
penis.
means
OMG.
to negate our statement. But perhaps to do that carefully, we should maybe write this into symbolic logic.
Well, I've
So
got a
notice
feeling
that
he doesn't
in
know that you can
symbolic
just
logic, this
rename
says
games
there exists an x
in your
R
registered game settings.
such that x to the fourth is less
So
than
I
x,
just renamed OBS
and
to with my penis
x
OMG.
is less than x squared. So what I did is I took this compound inequality and turned it into an
Because like
and
when I was
statement.
reacting to
I think
Skibbity
that's the
Toilet, I
best
renamed
way in
OBS to
order
Skibbity
to
Toilet,
negate this kind of
and
thing.
he was like, "Where do you
so
get those
now
games?"
negating it, what happens is the existential turns into a universal. So that'll turn into a for all.
I have my resources.
And then we negate this and statement into an
Yeah,
or statement.
like I told him I get him from Goople.
Substatements, if you will. So we'll have x to the fourth is bigger than or equal to
Goople,
x,
Goople.
or x is bigger than or equal to x squared.
You know?
Okay, so now let's write that in words. So for all x in R, x to the fourth is bigger than or equal to x, or x is bigger than or equal to x squared. So that's what we will indeed show. And we'll break this into a couple of cases. And these cases are maybe inspired by how we know the real numbers act from maybe a pre-calculus or a calculus class. So for my first case, I'll look at everything where x is less than or equal to 0. So in other words, x will come from the interval minus infinity up to 0, including 0. Okay, but if x is negative and we take the fourth power of x, then x is positive. But a positive number is always bigger than or equal to a non-negative number, so that actually takes it all the way home. I don't think much needs to be said about that. So we have x is less than or equal to 0 is less than or equal to x to the fourth. Again, because every even power of a real number is bigger than or equal to 0. But then pulling out the middle there, we get this part of our or statement. So I think we're good to go there. Okay, so now let's look at our second case.
Second
so for case number two, we'll take the case when x is between 0 and 1, but not including 0 and also not including 1. But then from there, I think we can just take the well-known behavior of the real numbers, that if you take a number between 0 and 1, not including 0 and not including 1, and you square it, you get something smaller. So for instance, if your number was 1/2 and you squared it, you would get 1/4. That is
so true.
If your number was 2/3
Oh
and
my
you
God.
squared it, you would get 4/9, which is smaller. So I think this like immediately leads you to see that x squared is strictly less than x as needed. Now this may seem a little bit like a cheat, but I think it's okay in our process. And in fact, for one of the upcoming cases, we'll do it a little bit more carefully. But that being said, I think this is okay for here. Okay, so now let's look at case number 3. Case number 3 is maybe the most boring case, which is x is equal to 1.
Oh
but if
my
x is
goodness
equal to
me.
1,
Oh,
we
so
have
boring,
x
man.
squared equals x to the fourth. But equality satisfies, well, really both of those. Okay, so now let's move on to case 4. And so case 4 will be x is bigger than 1. So it's on the interval from 1 to infinity.
Okay.
So if it's on the interval from 1 to infinity, then that means we can write x as 1 plus a, where a is on the interval from 0 to infinity. So I think that's pretty clear. And then from here, we're going to look at the fourth power, because if x is larger than 1, we expect it to satisfy this inequality here. So let's look at x to the fourth, which is equal to 1 plus a to the fourth. And then multiplying that out will give us 1 plus 4a plus 6a squared plus 4a cubed plus a to the fourth.
Now that's crazy.
And that's by a binomial expansion, which we learned about in a previous video.
That is so true,
notice
Michael.
that everything that I'm underlining in orange is strictly bigger than 0. So since all of that is strictly bigger than 0, I can drop it and I've made something smaller. So that means this object is bigger than 1 plus 4a. And then again, since a is bigger than 0, I can replace that 4a with an a, and I've created something smaller. So this is strictly bigger than 1 plus a, but that's equal to x. So now reading from here to here, we see that we have achieved this inequality right here, or a strict version of this inequality. Okay, so let's see. Have we covered all real numbers? We have. So we covered
That's a
non-positive
lot of real
numbers
numbers.
here, everything on the open intervals from 0 to 1 here, everything equal to 1 here, and everything on the open interval from 1 to infinity here. So that covers all real numbers, and in each of those cases, we either satisfied this inequality or this inequality. So that means we proved the negation of our starting statement, which means our starting statement was false. We're going to end the video by looking at a little bit of a conjecture, one that we can actually prove. So this conjecture says there are distinct x, y, z, which are integers, such that x to the y is the same thing as y to the z. And in order to approach our decision of whether or not this is true, we would really just play with some integers. I think that's the best way to go about this. But since this is an existential statement, all we have to do is find distinct integers satisfying this rule. So after playing around with it a little bit, we'd come up probably with the following example. And I actually think this is the only example, although you would have to check that. So let's notice that 2 to the 16 is the same thing as 2 to the 4 times 4, which is the same thing as 2 to the 4 raised to the 4 power. But 2 to the 4 is 16. That's 16 to the 4 power. So let's notice here we have 16 in the exponent. Here we have 16 in the base, which means we've done it. We have x equals 2,
nice one, buddy.
y equals 16,
You've done it.
and z equals 4 is a solution. And that's all we need to do to prove that this is true. Okay, now I'm going to leave you with some warm-ups. So for the warm-up exercises, your goal is to decide if they are true and then prove them if they are true or prove that they are
still
false
recording and it hasn't frozen.
Methods.
Thank God for that.
So this first one is f of n equals n squared plus n plus 41 is prime for all natural numbers n. So decide if that is true or false and then prove it accordingly. Next is if n is an integer and n cubed minus 3n squared is even, then n is even. And finally, if x and y are real numbers such that x cubed plus 4x is less than y cubed plus 4y, then x is less than y. So I guess I'll give you a hint here that 2 of these are false and 1 of these is true. And that's a good place to stop. This is the 14th video in a series devoted to introduction to proof writing. And today we're going to start talking about mathematical induction. So mathematical induction is a strategy for proving a family of mathematical statements is true, where that family is indexed by the natural numbers, or sometimes more generally the integers. Okay, so let's dive into an outline of a proof by mathematical induction, and then we'll kind of give some intuition for why it works. So let's suppose that you want to prove the following proposition. It says for all natural numbers n, P of n is true. Well, it just says P of n, but that's understood to mean P of n is true. So that means you've got a bunch of mathematical statements, P of 1, P of 2, P of 3, P of 4, so on and so forth. And they're all probably connected in some sort of way. And we'd like to prove that they're all true. Okay, so here's our strategy. We'll prove something called the base case. And the base case is the first case of this identity or statement or whatever it is. So we'll prove that the statement P of 1 is true. And I'd like to point that out that we could do this any way we want, with a proof by contrapositive, contradiction, a direct proof, whatever we need to do. And then after that, we'll do something called the induction step. And for the induction step, we'll say that we are given some arbitrary k bigger than or equal to 1, and we'll prove that the truth of pk implies the truth of pk plus 1. So I'd like to point out that assuming this pk is true is sometimes called the induction hypothesis, and then proving this conditional is known as the induction step. But I think we can all put it into an induction step. So I guess it's important to point out that this is a conditional, so you would prove this with methods for proving conditionals like we've done before. Okay, so the standard visualization of a proof by induction is with a set of dominoes. So let's say we've got infinitely many dominoes, and those dominoes are indexed by the natural numbers, and each of them is attached to a statement. So this is the domino P1, P2, P3, so on and so forth.
Dominoes.
So I like to think about the base case as pushing over domino P1. Okay, so we've pushed over domino P1. And then the induction step, which
we think about dominoes for, huh?
PK implies PK plus 1.
He's talking about dominoes for some reason.
Checking that the dominoes are close enough together.
But I don't actually know why he's talking about dominoes.
Sure, that isn't you.
If this induction step holds, then
I'm pretty sure.
We'll push over P2, which will push over P3, which will push over P4, and so on and so forth. But it's important to do both of these. If we check that the dominoes are close enough together without pushing over the first domino, then we haven't done anything. So that's why the base case is important. But if we've pushed over the first domino without checking that the dominoes are close enough together, then all we've done is pushed over the first domino. That's why this induction step is important. So these two together will prove this infinite family of mathematical statements. Okay, so for the remainder of the video, I essentially want to do just a bunch of examples of proof by induction. And then there'll be a follow-up example video with even more of these. And if you're in the class I'm teaching, you're going to do a ton of these in class. I think maybe we'll just use the method of greasing the groove to get the real feel for proofs by induction. Okay, so let's look at our first statement. We'd like to prove for all natural numbers n that the sum 1 plus 3 plus 5 plus 7 plus 9 plus 11 all the way up to 2n minus 1 is equal to n squared.
That is so true, bro.
So this is the sum of the first n odd natural numbers is equal to n squared. So that's pretty interesting. Okay, so let's prove this by induction. So I'm going to lay this out by stating that we're doing the base case first. But this is really a chalkboard way to write this down, or maybe a rough draft way to write this down. If you were to write this down as a final draft, it would be like in a paragraph form. So maybe look back at your rules for writing mathematically to see how you might want to edit it into a final version.
I can read
so our base case will be the
mathematically.
n equals 1 case here. And notice the n equals 1 case is simply 1 equals 1 squared. So that's okay. Notice that if we're just summing the first natural number, the first odd natural number, that's just 1. And the first square of the odd natural numbers is just 1 also, so 1 squared. So we're good to go there. Okay, so now let's make our induction hypothesis. So in other words, we will assume that PK is true. So again, I will just lay this out. So our induction hypothesis is, let's suppose for some k bigger than or equal to 1, we have 1 plus 3 plus 5 all the way ending at 2k minus 1 equals k squared. So if we're doing our conditional over here, if pk, then pk plus 1, this is like assuming that pk is true. Now we want to show that this leads to pk plus 1 being true. Okay, so let's see how we can do that.
Wow.
So now we'll consider the next case, but we'll only consider the left-hand side of this next case. So that'll be 1 plus 3 plus 5 plus 2k minus 1 plus 2k plus 1. So let's notice that's the next odd natural number. So if the kth odd natural number is 2k minus 1, then the k plus first is 2k plus 1. And I guess maybe we can notice that by seeing that this is equivalent to 2 times the quantity k plus 1
When
minus
is this going
1.
to end?
Okay, great. But now we can use our induction hypothesis to take this first bit and rewrite it as k squared. So this is equal to k squared plus 2k plus 1 by the induction hypothesis. So let's color code this. All of that stuff in the green underline is collapsing to this k squared by our induction hypothesis. And then we're simply bringing down this k plus 1, or 2k plus 1. But now that clearly factors as k plus 1 squared.
Yeah,
so we have this as k plus 1
of course, it
squared.
clearly does that, yeah.
But that's exactly what we wanted to do. The sum of the first k
Oh,
plus
that
1
is,
odd
yeah,
natural numbers is k plus
cool.
1 squared. So that finishes our proof by induction. So let's just reiterate what we've done here. Notice that at this step here, we supposed that pk was true, and down here we showed that that led to pk plus 1 being true. Okay, let's do another. So our next example will be an alternating version of our first example. So in particular, we'll show for all natural numbers n, this alternating sum, -1 plus 3, -5 plus 7, all the way up to
fucking absolutely, man.
1
you
to
know,
the n, 2n
I've only
plus
got a
1
cheeky
is equal to
5 hours
-1 to
and
the n
what's that?
times n.
4,
And we'll do this exactly
16
the
minutes, I
same
think.
way by proving
Only 5 hours and 16 minutes ago.
induction step.
Coming bad at maths.
So let's see our base case
Oh my
here.
god.
That is also
He's losing touch.
the n equals 1 case. So let's see
No,
what happens with the n
bro,
equals 1
no.
case. We have -1 is the same thing as -1 to the 1 times 1. So we're good to go there.
What
Notice
big
the
guy
base
think,
case
huh?
is generally
What's his
quite
name?
simple.
Mr. Murray. What, Mr.
So
Murray?
now let's make our induction
What would
hypothesis,
big
which is
guy
that the
think?
kth case is true. Okay, so let's suppose
Bro,
What would big guy think?
what
Some-
would big guy think?
k bigger than or equal to 1, we have
Oh my
our
fucking
statement
God,
is
Jesus
true.
Am I
So in other
wrong?
words, we have -1
Hey, what
plus
would big
3
guy
minus 5 plus 7 all the way up to plus
Hey, to be honest though,
-1 to the
what
k
would he think?
times 2k minus 1 equals
what
minus
would you
1
think big
to the
guy would
k
think?
times k. Okay.
His prize
Then
student
that's
is just
our
like,
eighth statement being true. We're assuming pk.
I'm
in
sorry
this
that I can't do 11
Now we'd
hours
like
and
to use
52
this to
minus
prove
6
PK
hours and
plus 1.
36, alright?
So let's consider the left-hand side of the k plus 1
everything I did
case.
for this kid.
So that will be -1.
Bro, he taught me how to do
minus
matrices,
5
not
plus
tell the
7
fucking time,
minus
alright?
All the way up to plus -1.
Excuses,
k
if you ask me.
times
Alright?
2k
Oh
minus
shit, my
1,
bad.
and
Do you
then
want to
plus
watch this video? Do you want to
-1
carry
times
on?
k plus 1
Exactly.
times
I'm right,
2k
actually.
plus
Yeah,
1.
exactly.
So here we have the first k terms alternating, and then we've got the k plus first term there. Okay, and now let's color code our simplification again.
Right, at least I'm not
this
as bad as
purple
some people on
underline
Twitter.
will collapse to something quite simple using our
What
induction
is
hypothesis.
Bidmuth?
In fact, it will
Nah, they were
collapse
like
to -1
absolutely
to
insane.
k
Someone do the math
times
for how many
k
people voted
using,
for X.
Like I said,
And it
our
was
induction
1% of
hypothesis.
something.
So let's
You just
underline that.
divide by
And then we'll
100
simply bring
or
this
get rid of the
term
last
down.
two
So
fucking
we'll have plus
numbers.
minus
Simple
1
as.
Do
to the
that.
k plus 1 times 2 to the k, or times 2k
I do that.
plus 1.
Alright.
Now what we'd like to do is factor -1 to the k plus 1 out and see what we're left with. So factoring a
I mean,
-1 to
I
the
could
k
literally
plus 1
just
out of this
mute
whole thing.
my microphone and just go
Let's
and have a
notice that
nap
this
right now.
k
No
will
one's
be
gonna know
attached to a
apart from you if you tell anyone.
-1, So we'll have a -k. So I think
They're
that's
gonna
pretty good
hear it in the
because we're
video, but
essentially
go
just
for it, mate.
dividing
No,
by
I'll just
1
mute my
there.
microphone.
And then we'll have plus 2k
Nah, I don't
plus
feel.
1
I don't feel
left
too
over from the
tired. I
second
definitely
term.
could if I wanted
But
to.
now that simplifies quite nicely to
But then I'd have
-1
to
the
set an
k
alarm
plus
for
1
like
times k
half 6
plus
to make
1,
sure that I get
which
up.
is exactly where we
So then
need
I
this
don't-
to end
I don't have to
finish this
upload the
proof by
video,
induction.
and then
let's do
cut it.
For our
Wait.
next example, we'll
No,
prove for
I'd
all
have to
natural
cut it
numbers
first,
n into
render the
fifth
video,
power is congruent
and
to
then
n mod
fucking
5.
upload it. Jesus
so this
Christ.
is indeed a special case of Fermat's little theorem, just for what it's worth.
That'd be a
Okay,
lot,
so
bro.
let's
That'd be a
get going.
lot.
So we'll do this by induction, like we said. So let's do our base case.
The base
So
case.
Our base case is the n
That's
equals
like
1 case.
base case
Well,
from
let's notice
Geometry
that 1
Dash.
to the 5
I
is
play that
equal
game.
to
Yourself.
1.
I play that
Well,
game.
Anything, well, 1 raised to any power is equal to 1, but 1 is
big
definitely
surprise.
congruent
You
to
turned out this
itself,
way.
mod 5. And that's because 5 divides 1 minus 1. 5 divides 0. 0 is clearly a multiple of 5. It's the trivial multiple of 5.
Oh,
Okay,
okay, I've
great.
got to
So now
extend
let's
this out
make
one
our
more.
induction hypothesis.
Rats.
So let's suppose for some k bigger than or equal to 1, we have the result. So in other words, k to the fifth is congruent to
Team
k modulo
10.
5.
Like that.
Great.
Team 10.
Now what we want to end up with is k plus
Why
1
is
to
it
the fifth
done
is
that,
congruent to
then?
k plus 1 mod 5. But we have to get there. And in order to get there, we need
Oh,
to
that's a
recall
bit of
what
a
it means for
slope,
numbers
that's
to be
why.
Congruent mod n or congruent mod 5. So let's recall that up here. So A
grab
is
that
congruent
height.
to B mod, I'll just say 5, if and only if
Congruent.
5 divides A minus B. So that's what we'll use. We will actually
Congregation.
show that 5 divides
No,
k plus 1 to the
congruent.
fifth minus k plus 1. Okay, so that means we need to look
Yeah,
at k plus
com
1
si,
to the
com
fifth
sa,
minus
mate,
k
same
plus
thing.
1. Okay,
Com
so
si,
anyway,
com
let's
sa.
consider that. So let's consider.
You heard me. Come see, come start. Same thing.
You do know what come see, come start means,
Again,
right?
motivated by the fact that we need to
Yes, that's why I said it.
I don't believe
Don't
that
be
for a second.
funny.
I don't believe that for a second, Harrison. I don't believe you know any French.
Some things out and see what we have. So we'll have.
Remember I did Duolingo for 80 days? Okay.
5k to the 4th.
Oh wait, did you actually keep an 80-day streak on French?
K cubed.
Yeah.
Plus
I was bored.
10k
Jesus
squared
Christ.
plus 5k.
Comsi Comsar was not one of those
So
thoughts,
that's what we
but
get
it
if we
means
take
so-so,
k plus
right?
to the 5th power.
Yeah.
We know how to do that quickly.
Yeah.
By binomial coefficients. So this is 5 choose 0, 5 choose 1, 5 choose 2,
I've
5 choose 3, 5 choose 4, and 5
I
choose
forgot. I did a
5.
fucking.
Okay.
I did a
So
Polish
from this
Duolingo
object, we
fucking
will
lesson
subtract
while I was
k
reacting to the
plus
Polish
1.
skibbity toilet
Okay,
video,
So let's see what that leaves us with.
and then I just
So
said,
that will
and
leave
I just
us
said
with
apple
k
in Polish
to
like
the
3 or 4
5th
times.
minus k, where I've put the k to the 5th here and this minus k together. You might say, well, why didn't I combine like terms with this 5k term? That's because I want to use my induction hypothesis. Okay, so anyway, I've got k to the 5th minus
fits
k,
in well, though. Okay.
and then everything left over will be a multiple of 5 because those ones cancel.
The ones
let's
cancel.
factor
Oh my
5
god.
out.
One cancel. Cancel
So we'll have
one.
plus 5,
What?
and then
The
k
one
to the
show.
4th plus 2 k cubed plus 2k squared plus k. Okay, great. So that's the simplification that we've done here. But let's notice that this is
Alright,
most
so
definitely a
big is
multiple
that?
of 5.
That's all the way
And this
down
is a
there,
multiple
okay.
of 5 as well by the induction hypothesis.
Yeah.
So in the end,
Multiple
we know
of
that this
5?
whole thing is a multiple of 5. So
Whoa,
this is
it's a
equal to
multiple of 5.
m for some m,
Hey, Harrison,
which
you're a
is
multiple of
an
5.
integer. Again, because
No.
we've got a multiple of 5 here by the induction hypothesis, and we have a multiple of 5 here like by construction. Okay, but now putting this together, we see that 5 divides k plus 1 to the 5th minus k plus 1. Just reading this from the extreme left to
Oh,
right
love your sweater.
But that's exactly the same thing.
I don't
as
mind
saying
if it's
k
not much
plus
to
1
see.
to the
I'm
5th
sorry.
Is congruent to k plus 1
Why are you sorry?
modulo
The singing.
5.
You usually
That's
don't
exactly
like
where we
it.
wanted to end this thing up. Okay, let's
I
do
mean,
another.
currently it's
Next up,
better
we've
than
got a nice
fucking
calculus problem. It's
congregation,
something
bro.
we
It's
learned in
not
calculus class, but I think it's
God
nice
is
to
far.
reinvestigate it
Outside
now
this
that we know a
place is
little bit
warm.
about induction.
Outside it starts to
So
pour.
let's assume the product rule and that the derivative.
Do you know
with
what
respect to
song
x
I'm
is
singing,
x
Archie?
1,
Absolutely
and
fucking
then our
not.
goal is to
Don't
show that
Sweater
the derivative
weather
with
by the
respect to x
neighborhood.
to the n is n
Oh yeah,
times
of
x to the
course.
n minus
That
1.
one.
So that's the power rule
I've
for
never
natural
fucking
number
heard of
exponents.
sweater weather or the neighborhood.
Okay,
I
so
think.
we'll do this just like we've done the others. Let's first look at the base case. Notice the base case
Well,
is
surely
done
you know
here
the song
by
Sweaters by
the
Ivan B, yeah?
I
So
don't
notice that
know.
it's given
I don't know if I
right
do.
here. We are
I don't listen to
assuming that the
music,
derivative with respect
Harrison.
to x of x to the 1 is
When will you
1
learn I
times
don't
x
listen
to
to
the 0.
music?
So this is done.
You should.
You know, and sometimes this will be the case. Okay, so now let's make our induction hypothesis.
I don't think I should.
So that will be for
You should.
some k
I don't
bigger
think so.
than or equal to 1.
Why?
We have the derivative with respect to x of
I don't
x
know.
to the k is k times x to the k minus 1. And then from here, let's consider the next case. So let's consider the
Exactly.
derivative with respect to x of x to the k plus 1.
I just feel like
Now
it'd be
we
really
can
annoying
use
trying to
exponent
find
rules
something
for
that I
multiplying
like.
powers of x to
That's why you
rewrite
should make a
this as
playlist
the
of a bunch
derivative
of
with
different
respect to
songs
x
and
of
go,
x
yep,
times
that'd
x
do.
to the k. And then from here, we'll use the product rule, which is sometimes more formally known as the Leibniz rule. So this will give us the derivative with respect to x
Yeah,
of
but
x
what if I don't like the
times
ones in the
x to the k
playlist?
plus
Then all it will do
You
is
get rid of them.
times the
all it will do
derivative
is
with
suggest me
respect to x
similar
of x to
songs.
the k. So the derivative with respect to x of x
Don't
is
use the song
1, so that
suggestions
leaves
then.
us with x to the k plus x
So true. So true.
times k times x to the k minus 1 using the induction hypothesis.
Just listen to EDM all the
Putting this
time, you
all
know?
Together and simplified, you'll see that we get exactly what we want. That we have k plus 1 times x to the k. Okay, let's do another. So our
EDM,
next
yeah?
example is a special case of something known
Your
as
favorite
Bernoulli's
electronic dance
inequality.
music.
So you can look up the general setting of
Where have
Bernoulli's
you heard that
inequality.
from then?
So what we'll
What?
show is that for all real numbers x bigger than or equal to negative 1
EDM, where'd you
and
get that
natural numbers
fucking
n,
idea from?
we have 1 plus
Geometry
x
Dash.
n is bigger than or equal to 1
Oh, yeah, hold
plus
up. Let me
n
just,
times x.
Let me just listen to some Creo real quick.
Binomial expansion. It'd be quite nice. But here we're allowing certain negative values of
Let me just put Thunderzone V2 on real quick.
So
Hold on. My favorite song
will be the n equals.
Imagine you're just doing your homework and Thunderzone V2 starts playing.
That would be really funny.
A time where we start at n equals 0 or
wait, hold on. Let me just put Club Step on real quick. It's my favorite song.
Have all of the statements. But for everything that we've seen, we've used.
You know what this moment calls for? Club Step.
Okay, so let's look at 1 plus x to the 1 power is equal to 1
I know what time it is. It's time.
X, but that is bigger than or equal
Clubbing
to
time.
plus 1
It's clubbing time.
So there, we've done it.
Oh, I know what time it is, Harrison.
So now let's make an induction hypothesis. So, following the same kind of strategy, let's
can't even say it, man.
For some k
it's time for isolation. That's what time it is.
True. So in other words, 1 plus
my
x
favorite artist, Nighthawk22.
is bigger than or equal to 1 plus k times x. And then next up, we'll consider the k plus first case.
So
1 plus x to the k plus
definitely.
1, which is the same thing as 1 plus x
Wouldn't surprise me.
1 plus x to the k.
Oh boy. I can't wait to listen to that lullaby from Arcturus. My favorite song.
Use the induction hypothesis. And that manipulation is usually quite simple. Just like here, we took 1 plus x to the k plus 1 and factored a 1 plus x out so that we had a 1 plus x to the k to work with. Okay, so now let's apply our induction hypothesis. So that makes this bigger than or equal to
lyric to the song, okay?
1 plus x times 1 plus k times x.
I do not have a thing for Ice
So
Spice.
again, that's our induction hypothesis.
Yeah, you do.
And then from there, we'll just multiply this out. So that will give us something like this. 1 plus k plus 1 times x plus k times x squared. So that's what we get when multiplying this out. But since
that is literally me when I have 100 bands in Chanelli.
We know that this is bigger than or equal to 0. So if we drop it, we get something less than or equal to what we started with. So we
ain't no one want to live in this town, bro. What the hell is this?
1 plus k plus 1 times x.
Damn.
But now reading from
I've got
here to here,
some ground laid out for an international airport. This town has 4,000 people living in it.
Or inequality to finish off this statement. Okay, let's move on to another example. Now we're going to look at a result related to the fundamental theorem of arithmetic. So let's suppose we have.
I spent so long building the worst interchange in the world yesterday.
So we have at least 2 integers.
God.
And then let's also suppose we've got a prime, which I'll call p.
Finally,
no,
let's get a thoughts review of this interchange that I built. Hold on.
A2 up to an. Then we'll show that it follows that.
Well, where the hell are you seeing this in real life? You know what I mean?
One of these i's between 1 and.
Let's find out.
So,
oh my fucking god!
Where are you seeing that to?
You ever heard of this place called Texas?
Based off the setup. So let's do our base case, which, like I said, is the n equals 2 case.
Yeah, do you like the bridges?
So let's
mate, you just need one more lane.
P divides A1 times
I don't know.
A2.
You just need another lane.
Let's break this down into cases.
Oh, damn it, you're right.
Case number 1 is that P divides A1.
You just need one more lane. Just one more lane.
Because it divides one of the terms of the product. But case 2.
Oh my god, I'm almost 7 hours in.
Not divide A1. Okay, so we've got
5 hours and 2 minutes left.
Or it must not divide A1. So that's pretty clear. But if it does not divide A1, then
I will finish the video.
Harrison Talks Clips fans, are you living here?
So that's by the definition.
I'm looking at this on my phone, by the way. Hold on.
Okay, but if
are you living here?
Let me pull it up.
Then that tells us there exists
are you living here?
Integers x and y.
Let us know in the comments below. Are you living here?
Times y equals 1. So
is this your house?
Yo, guys, check out this intersection. Are you driving here?
Integer linear combination of those natural numbers. So
oh yeah, Harrison, do you want to know something really funny?
Hey, you living the hardest.
Harrison, do you want to know something really funny? What? I think at like around the 3 hour mark, I just farted audibly into the microphone.
I'm going to use z for another integer.
Like I stood up, turned around, and just farted into the microphone.
I think we'd probably like to get an A1 times y built into this equation so that we can get the A1 out of there. notice that I can rewrite this linear combination equation as a1 times y equals 1 minus px. So if I can eliminate the a1-ness from this, that would be good.
Daddy, don't
So we can
mess
do that
around
by
and
multiplying this entire equation
Harrison and Toys
by
Clips fans.
y.
Are you
So that'll give me
listening?
A1 times y times a2.
You listening to Hey
is
Ya?
equal to p times
Hey, Harrison and
and then
Toys
from
Clips
there, I
fans.
can make
Do
my
you get this?
replacement.
I
I'll
don't.
replace a1 in this
Please let me know
equation
what the
with
fuck any of this
1
shit
minus
means.
px. So that means I have 1 minus p times x.
Oleki,
times a2
let me know
is
in the
equal to
comments
p
below what this
minus
means.
z.
I don't
But
quite
now
get
let's
it.
move some things around. I have a2 is the
Huh?
same thing as p
Nothing.
times z plus p times x times a2. So that's just from symbolic manipulation. But notice
fine,
that
she wouldn't know that
equals
what it means.
p times z plus a2.
Wait, what did you say?
But that means that
Slag.
a2 is a multiple of p. In other
What,
words,
you called
p
it our
divides
slag?
a2. Okay, so let's see what we have. Our first case was p divides a1, in which case we're done.
Hey, bro, no
Our
worries. You don't know what it
second case was
means.
p does not divide a1, but that led us to
Can you
p
just
must
DM us
divide
in your
a2.
slide?
So that means that we do have p divides a1 or a2 as needed. But that's just for our base case.
You let me-
Now let's move on to our induction hypothesis. So now let's make our induction hypothesis. So let's suppose that if p divides a1 up to ak, then p divides
Wow,
ai
wow,
for
wow.
some I.
So we're supposing
that a conditional statement is true. So that's important. Okay, so now let's suppose that p divides a1 up to ak plus 1. And then let's break this into two cases. So case number one is that p divides a k plus 1. But in this case, we're done because we have p divides one of the terms from that product. Then case number 2 will be p does not divide a k plus 1. But then by the n equals 2
That's an
case,
onion?
or by the base case, that means that p must divide the
Ice
product
cold.
a1 up to ak. Here we're thinking about
Ice
splitting
cold.
this product
Alright.
A1 ak plus 1 as a1
Alright.
Hey, now, ladies.
Yeah. So we can really apply the base case to that like larger problem. But now if p divides this product a1 up to ak, then by the induction hypothesis, so by the induction hypothesis, that means
shake
p
it,
divides ai for shake
it like a Polaroid picture.
So let's see it.
Alright.
Either p divides ak
Shake it,
plus 1
shake
or
it,
it
shake
must
it,
divide
shake it,
one of the
shake it
AIs
like a
between 1 and
Polaroid
ak.
picture.
That's exactly what we needed to finish the statement off. Okay, let's do one more example. For our last example, we'll use induction to
Shake it like a
prove
Polaroid.
And so that says
To
for
do.
all real numbers x, we have the sum 1 plus x
Shake
plus
it
x
like a
squared
Polaroid
into x
picture.
n equals 1 minus
Oh,
x
my
to the
days.
plus 1 over 1 minus x. Okay, so let's start with the base case. So notice our base case is the n equals 1 case. We'll have 1 plus x. But notice that's most definitely equal to 1 minus x times 1 plus x over 1 minus x. Just multiplying the numerator and the denominator by 1 minus x. And
I need to
then
move the stock
we can
exchange building.
multiply
It's
this
too
out, and
big.
it's 1 minus x squared over 1 minus x. And I guess I see a little bit of a problem with my statement.
X, I'll give it to you.
And that is I should
Yeah.
not allow x
Oh.
to be equal
Yeah.
to 1. So let's fix that there. So for all real numbers x that are not equal to 1. So anyway, we've done our base case. Now let's make our induction hypothesis. So let's suppose for some k bigger than or equal to 1, we have 1 plus x
Yo,
plus
Custard,
ending at
are
x
you
to the
bigger than
k
or equal to
is
1?
Equal to 1 minus x to the k plus 1 over 1
Oh,
minus
okay.
x. Okay, good. Now let's consider the next case. So our next case will be the sum 1 plus x plus up to x to the k plus x to the k plus 1. Good. Now we'll apply our induction hypothesis to the first k terms. And that will leave me with 1 minus x to the k plus 1 over 1 minus x. So let's just point out that that's coming from our induction hypothesis.
Oh
and
my
then we have this
god.
last term, which is x to the k plus 1. Now let's give ourselves a common denominator. This is going to be 1 minus x over 1 minus x to give myself a common denominator. And then let's multiply some things out. So we'll have
I'll give it to you.
I'll
give it to you.
X to the k plus 1 plus x to the k plus 1. So then we'll have x to the k plus 1 times minus x. That'll be minus x to the k plus 2. Then my denominator is still 1 minus x. But that's exactly where I needed to end to finish this proof by induction. Okay, now let's end with some warm-ups. So I've got 3
Oh my
warm-up
days, this
exercises
video
based
is
off what
ending.
we saw today. So the first
Video
is to show that
14
the
is
sum
over.
of the first n squared
The
is
final
equal to
10
n times n
are
plus 1 times
upon
2n
me.
plus 1 over 6. Next is this nice inequality.
We are
involving
still
powers
going
of
and it
2.
hasn't frozen
we have
yet.
2n plus 1, 2 to the power n
Thank
plus 1
God.
is bigger than or equal to 2 to the power n plus 2 to the n minus 1 plus 1. And then finally, a divisibility problem. Show for all natural numbers n that 3 divides 7 to the 2n minus 1.
I really hope
In other words,
Oleki
7 to
watches
2n minus
the
1 is
entire
a multiple of
Zoophile
3.
video after I do
Or,
this.
if you want to work with congruence mod 3, that's the same thing as saying 7 to the 2n is congruent to 1 mod 3. So there might be a really simple way to do this, but recall that our goal here is to prove this by induction for practice. And that's a good place to stop. This is the 15th video in a series devoted to introduction to proofwriting.
No
in the last video, we
way.
looked at induction and several examples. And today is going to be another day about induction, this time something called strong induction. And then we'll end with some nice examples involving the Fibonacci numbers. Okay, so let's look at the outline of how to prove a proposition using strong induction. So we have the same sort of setup as a proposition with normal induction. That is, we want to prove for all natural numbers n that some statement p of n is true. So that means p of 1 is true, p of 2, p of 3, p of 4,
Hey,
so on and
Harrison.
so forth.
Yeah.
Well, it's not
Did you know
always all
that
natural
the
numbers.
average
Generally, it's all
American
natural
thinks that
numbers after
92%
some
of people
point, but that's clear
either
by
live in
the
California,
function.
Texas, or New
Then
York City?
What's the outline? So you'll start by proving
Don't be
several
surprised.
of the first statements. Well, it might be 1, it might be 2. It's really
I
going
mean,
to
so you think
depend on the
100
problem.
million people
So I
live in
bring
New
it like
York?
this. We'll start with this larger base
New York
case
City
where
as
we
well,
prove
which is
P
quite
of 1,
funny.
P of 2 up to P of R. And this R, like I said, it depends on the statement. So sometimes you may only need to prove P of 1, sometimes P of 1 and P of 2, so on and so forth. And then comes for the strong induction.
Why
step.
is Zoe messaging
That's
me?
where we show that P1 and P2 and P3
You
up
just call me
to
Harry.
PK implies PK plus 1. So instead
Yeah.
of only relying on the previous step to prove the next
he
step,
just called you
we rely
Harry.
on all previous
Ugh.
steps. Okay, good. So let's look at our first example.
Deary
So
me.
our first example says that every natural number n bigger than or equal to 8 can be
How am I
written
today?
in the form
I was good
n
until about
equals
5
3x
seconds
plus
ago.
5y, where x and y
Nah, you gotta
are
tell them that your head still hurts a little bit.
non-negative integers, but they're not both 0.
Nah, bro, I forgot about that.
Well, I guess this would stand if they were both 0. Because
Yeah,
that's
that's
not
too right,
given
that's too
anything
right.
that
Yeah,
is
my
n
bad,
bigger
my
than or
bad.
equal to 8.
Oh, he's probably gonna
Okay,
message
so
me
anyway,
as
let's
well,
get at
asking,
it.
oh
In
yeah,
this
did you
case,
hear
there
about
will be
Harrison? He's forgotten he had a
3 base
concussion.
cases. So let's put here our base
Oh,
cases.
God.
And those base cases will
Ew.
be n equals 8, 9, and 10. And the reason it's 8, 9, and 10 because you need to cover 3 cases, and then you can just add on 3s afterwards to get everything else. Okay, so anyway, that's getting ahead of ourselves, so let's jump back a little bit. So the first base case is 8, which can be written as 3 plus 5. Then the next one would be 9, which can be written as 3 times 3. So I guess here x is equal to 1 and y is equal to 1. Here x is equal to 3 and y is equal to 0. And then next we'll have 10 is equal to, let's see, that will be 5
We having
times
trash
2.
problems.
So in this
Oh
case,
no.
x is equal to 0 and y is equal to 2. Okay, so those are our 3 base cases. And now let's make our strong induction hypothesis. So our induction hypothesis will be, suppose for all 10 less than or equal to m less than or equal to k, we have the result holding. So in other words, we have integers.
You flexing on me that you have food.
X and Y.
Meal number 2.
M equals 3x
I haven't eaten anything today.
5y. So you might say, well, where did this 10 come from? Well, notice
last night I was hungry. Looked at the stuff he had in the cupboard.
So it's true for 8.
And the first thing he doing, I want a mug cake. It's the only thing we can have that was dessert.
That's the only thing you can make.
Bigger than or equal to 10.
That with the stuff we had.
In line with this kind of thing over here. And now looking ahead, we're going to look at the k plus first case. But the k plus first case is 3 more than the k minus second case. So perhaps we need to look at that case on its own. So let's write that here. In particular, since we have 8 is less than or equal to k minus 2 is less than or equal to k.
Yes.
Then
all right, cool. It's on the microphone.
K minus 2 equals 3 times what I'll call x naught plus 5 times what I'll call
I need to have noise suppression to do that.
For x naught and y naught in non-negative integers. So what I essentially did here is I just applied my induction hypothesis to this k minus 2 term.
I was just teething at my mic.
For that is it's 3 less
How does
than
that
our
taste?
next case, our k plus 2.
Yummy.
Now we've used everything from the induction hypothesis and we're ready for the induction step. So let's
I also have a live oleki reaction in this video.
Term, and notice that we can write that as k minus 2 plus
and the
3,
Skibbity toilet video.
using elementary arithmetic. But that's
I've included oleki.
3x naught
Ain't no way.
plus 5y naught plus 3 by our induction hypothesis. But that's equal to 3 times x naught plus 1 plus 5 times y naught by simple arithmetic. So we've done it. Notice that we have k plus 1 written as a non-negative integer combination of 3 and 5, which is exactly what we needed to do to finish this thing off. Now let's move on to the next one. For our next result, we'll show for all natural numbers n, 12 divides into the 4th power minus n squared. And before I present the proof, I'd like to present a little bit of exploration, which I've already worked out. So in general, let's say that we suppose that we could do this without strong induction, and we had an induction hypothesis where k to the 4th minus k squared was a multiple of 12. So we have this as a multiple of 12. Then we would look at the next case, which is k plus 1 to the 4th minus k plus 1 squared, and we would expand it out. So expanding it out, we get this previous case, which, like I said, by our induction hypothesis is a multiple of 12. But then this leftover bit is not clearly a multiple of 12. I think there's probably a trick that you can play with that to show that it is a multiple of 12. But since we're really going for examples of strong induction here, I think it's maybe better for us not to play that trick. So that motivates us to go back further. Instead of going back from k plus 1 to k, maybe we go back even further. And the motivation is to go back 6 steps to k minus 5. So notice there's 6 steps between k minus 5 and k plus 1. And you might say, well, why 6 steps? Well, it's actually pretty simple. It's because 2 times 6 is 12. We're looking for things that are multiples of 12. And then 2 and 4 are even. So if we expand something using binomial coefficients with 2 and 4, we'll always end up with 2 times something. And then we'll have this 6 rolling around in here too because of this 6-step difference that we're doing. So that's just a hunch. We'll have to work that out as we're going through the proof. But I think this is a good, intuitive guess of how to approach this. Okay, now let's look at the proof. Now we're ready for our proof. And since we have 6 steps between k minus 5 and k plus 1 during that induction step, that tells us we should have 6 base cases. And so I've done the calculation on the base cases here. There's really not much to that. All we have to do is look at n to the 4th minus n squared for n 1 through 6. So for instance, for n equals 3, we get 81 minus 9, which is 72, which is 12 times 6. I'll let you check the rest of those. Like I said, those are pretty straightforward. Okay, so now let's get at it. So our induction hypothesis will be something like this. For 6 less than or equal to m less than or equal to k, suppose that 12 divides m to the 4th minus m squared. So that's our strong induction hypothesis. And look, I picked it up right at the end of my last base case, just as we did before. So now in particular, since we have 1 less than or equal to k minus 5 less than or equal to k, we know 12 divides that sort of combination with k minus 5. So in other words, 12 divides k minus 5 to the 4th minus k minus 5 squared. Great. Now that's like the induction hypothesis applied to our k minus 5 term, which we motivated the need for on the previous board. And now we're ready for our last calculation. So let's consider the k plus first case. So that means we need to look at k plus 1 to the 4th minus k plus 1 squared. But we'd like to put this in terms of k minus 5. So this is equal to k minus 5 plus 6 to the 4th minus k minus 5 plus 6 squared. And now let's introduce a little bit of notation. So this is equal to L plus 6 to the 4th. I love notation. Minus L plus 6 squared.
Notation?
Where L is equal to K minus 5. And now we'll expand that out. So this expands out as L to the 4th minus L.
You know what notation is,
like
right?
Moving things around as we
Acid
do this.
notation from Geometry Dash.
And then
that's just how you write stuff down.
We'll have plus 12 times
acid
the following
notation from
object.
Geometry Dash.
We'll have 2L cubed plus 18L squared. And then after that, plus 71L plus 105. The important thing is that we have a multiple of 12 right here. And then by our induction hypothesis, we have a multiple of 12 right here as well. So we could maybe put that in right here and note that we have k minus 5 to the 4th minus k minus 5 squared is equal to L to the 4th minus L squared, which is equal to maybe 12 times x. You know, by this 12 dividing this thing. Okay, but now grouping things together, we have this first green underline is 12x.
That's crazy.
The second green underline is 12y. But if you add two multiples of 12, you get a multiple of 12.
What?
So in the end,
No way.
we have 12 most definitely divides this k plus 1 to the 4th minus k plus 1 squared as needed. Okay, so now let's apply this idea of strong induction to the fundamental theorem of arithmetic. Now we'll prove the fundamental theorem of arithmetic, and that says that any integer that's bigger than 1 has a unique prime factorization. And this will involve an existence proof so that it has a prime factorization to start with, and then a uniqueness proof that shows that that prime factorization is indeed unique. Okay, so the existence proof will be using strong induction. So our base case here will be the n equals 2 case. But notice for the n equals 2 case, we're done, and that's because 2 is a prime number. It's the only even prime number. Okay, great.
2 is an even prime number. So
now let's move on to our induction hypothesis, which will be a strong induction hypothesis. So let's suppose for all,
you know what else is strong?
Less than or equal to m, less than or equal
my
to
good
k,
friend Eddie Hall.
The result holds. So in other words, m has
I get Eddie Hall in here reacting to mathematics.
Notice I'm not saying anything about a unique prime factorization because we're just doing existence here, not unique.
I think he's a bit busy right now, actually.
And now let's consider k plus 1. So consider k plus 1. And this breaks down into two cases. So case number 1 is k plus 1 is prime. So if it's prime, then we're done because k plus 1 itself is its own prime factorization. So that's maybe kind of the best case scenario, is that if k plus 1 is prime. But let's look at case number 2, which is k plus 1 is not prime. But let's recall, if it's not prime, it's either equal to the number 1 or it's composite. It's not equal to 1 because it's bigger than 1, so that means it must be composite.
Well, that's an airport
bill.
K plus
1 is, like I said, composite.
Wow.
But that means that k plus
1
What's
wrong with the garbage, man? I've got so many.
Where A and B lie between 2 and
I wish
K.
I had a second
Not
monitor.
K, though, but it could include 2. But now what we'll do is apply the induction hypothesis to both A and B. So apply induction hypothesis to A and B. So that allows us to write A as the product P1 up to PR and B as the product Q1 up to QS, where the PI and the QJ are all primes. So we've got this prime factorization for A and a prime factorization for B. But now we put that together with the fact that k plus 1 has the perhaps non-prime factorization of A times B, and we can write k plus 1 as A times B, but in turn, that's the product P1 up to PR times Q1 up to QS, a product of primes. Or in other words, a prime factorization. So assuming that every number between 2 and k had a prime factorization allowed us to prove that k plus 1 also has a prime factorization. Okay, and so that's our existence proof done. Now let's do our uniqueness proof. So for our uniqueness proof, we're going to use a contradiction. We're going to use a neat contradiction involving like something called the smallest possible counterexample. Okay, so by way of contradiction, suppose that not every n has a unique prime factorization. But that means that everything without a unique prime factorization forms a non-empty subset of the natural numbers. We can find the minimal element of that subset by the well-ordering principle, so let's call that m. So let's call the minimum such number m. So what is m?
Hey,
so
Custard, are you a natural number?
Prime factorization, but it's the smallest one without a unique prime factorization. Okay, so that means we can
words I say,
P1 up to PR. We can also write it as Q1 up to QS, where the list P1 to PR and Q1 to QS are not permutations of each other. Because of course this uniqueness is up to
I guess I'm copying the crematorium with this.
2 times 3 and then a factorization of 3 times 2 to be the same. But if we have a non-unique factorization,
rest in peace, crematorium.
That means the list P1
I'm deleting an important road right now. I need to uncul-de-sac this place.
Okay, so now we're good to go.
Hey guys, would you live here? Comment down below.
And we'll notice that P1 producted to PR is the same thing as Q1 multiplied up to QS. But then since PR divides the left-hand side, we know that PR also divides the right-hand side.
Relay highway, where the body is. I know it's called bloody highway, isn't it?
Q1 up to QS. But that means that PR divides one of the terms in that product by
Can't believe I've been playing with my penis for 7 hours.
So by last video,
okay, I have to try and
divide
fix
something I'll call
this.
QI for I between 1 and S.
And actually,
let's reorder the QI so that indeed we know that PR divides QS. So we can do that. Then next up, if PR divides QS and P and Q are both primes, then that means that PR must be equal to QS. Okay, but then that means we can cancel it from this equation right here. So cancel it from, so let's maybe put a green star next to this equation, and then we'll bring the green star down.
Green star?
And what does that give us? So that gives us the equation P1 up to PR minus 1 equals Q1 up to QS minus 1. But then if we set each of these maybe equal to M prime, we see that M prime is most definitely less than M, and it has a non-unique factorization. And so it inherits that non-unique factorization from the non-unique factorization of M. But what does that do? That contradicts the minimality of our original M. So that contradicts the minimality of M because we found a smaller number that also has a non-unique factorization. Okay, so where does this contradiction make everything blow up? Well, way up here, where we suppose that not everything had a unique factorization. So that must be a false statement, which means indeed everything does have a unique factorization. And that finishes this proof off. Okay, so now I'm going to do one example involving Fibonacci numbers. So a very nice source of exercises for induction problems are the Fibonacci numbers. So I thought I'd leave you with the definition of the Fibonacci numbers and then one such example. There'll be others.
Fibonacci numbers.
Okay, so the Fibonacci numbers are defined as a recursive sequence as follows. So the 0th Fibonacci number is the number 0. The first Fibonacci number is the number 1, and then the n plus second Fibonacci number, f sub n plus 2, is the sum of the previous two. So f sub n plus 1 plus f sub n. This is true for n bigger than or equal to 0. So for instance, f2 is f1 plus f0. f3 is f2 plus f1, and so on and so forth. So here are the first several Fibonacci numbers. So we've got 0, 1, 1. We add 1 and 1, we get 2. We add 1 and 2, we get 3. We add 2 and 3, we get 5. We add 3 and 5, we get 8. 8 and 5 get 13, so on and so forth. So you see it's quite nice and easy to generate more Fibonacci numbers. Okay, so there are tons of nice identities involving Fibonacci numbers, which, like I said, give nice practice for inductive proofs. Here's one that I thought I'd do. So we have fn plus 1 squared minus fn plus 1 times fn minus fn squared is equal to -1 to the n. So let's start with our base case. And for our base case, I'll take the n equals 0 case, because that's the first Fibonacci number, or really the 0th Fibonacci number. So let's see what our left-hand side collapses to here. We'll have f sub 1 squared, because it's 0 plus 1, minus f sub 1 times f sub 0, minus f sub 0 squared equals, well, f sub 0 is 0, so both of those cancel. F sub 1 is 1, so we get 1 squared. But 1 squared is 1, but that's the same thing as -1 to the 0 power. So it checks out. The base case works. So we can maybe check mark next to this saying that our equation holds for n equals 0. Now let's make an induction hypothesis. So let's suppose for some k bigger than or equal to 0, we have our result holding. So in other words, fk plus 1 squared minus fk plus 1 times fk minus fk squared equals -1 to the k. And now we'll consider the k plus first case. So let's consider the left-hand side where we replace k with k plus 1. So that'll give us fk plus 2 squared minus fk plus 2 times fk plus 1 minus fk plus 1.
Whoa,
squared.
that's
and then
just
let's
a
start
fuck
simplifying
word.
that. So we want to get that down so that it looks something like this.
Wait,
so we probably need to
you know
use
how
our
your
recursive
fingers are
definition of
playing
Fibonacci
with my
numbers for the
penis?
fk plus 2.
Yeah.
So we'll replace
It says
each fk
streaming
plus
with
2
my
using
penis.
this right here.
Oh, does
So
it
that'll
now?
leave us with fk plus 1 plus fk quantity squared. So
God.
let's just be really clear. That comes from this term right here. And then we'll
No
also
way.
be replacing this fk
It
plus
says
2.
playing with my penis
So
for
that would
me.
be minus fk plus 1 plus fk
Streaming with my
times
penis.
fk plus 1. So like I
Wow.
said,
I think
that
it's saying
comes from
playing with my
here,
penis
this
is funnier.
orange underline.
I might
And then
just stop streaming to
finally,
make it say playing with my penis.
fk plus 1.
It might only say
quantity
that
squared. I
for
might
me
leave
because it's
that
kind of
as
cool.
is.
Yeah.
Okay, so now let's multiply some things out. That
I
leaves
mean,
us with f
you weren't
plus
watching
1
that.
squared plus 2 fk.
I had the
fk
occasional
plus
glance
1,
over.
and then plus fk.
What, and then get confused on what the
squared.
fuck was going on?
Okay, good.
And I go back
then
to
we'll
building
have
my city, yeah.
minus fk plus 1 squared minus fk
Oh,
plus 1.
there's a hole in my
minus
wall. My
fk
monitor's
plus 1
falling off
squared.
my
So that's
desk.
just from
I realised yesterday my
everything
monitor's
out.
been like
And
slightly
now let's see what
tilted backwards for
simplifies.
ages because it's been like
Notice we
falling off the
have
back of my
fk
desk.
plus 1 squared here, which will cancel this fk plus 1 squared.
Okay, so the next video.
And then another thing, let's
is
notice that this
half an hour.
negative fk
Okay.
times fk plus 1 and this 2
Oh.
fk times fk plus 1 will cancel
Just another
this
half hour.
down to have a coefficient of
I can go another
2.
half hour. Easy.
And now we can bring a minus sign out of the whole
have
thing, which is
infinite
motivated
mental
by the fact
strength.
that we're really going for -1 to the k plus 1.
You see that
so
little
bringing
tear
a
in my
minus
wall?
sign out of the whole thing, we'll be left with fk plus 1 squared from this term, and then
Wait.
minus fk plus 1 times fk.
So what is
from
that? Is that
this
your
term,
monitor
and then
doing that?
minus
my monitor
fk
stand, yeah.
squared from this remaining term right here. But then by our induction hypothesis, that's minus
crazy.
1 to the k. So multiplying -1 to -1 to the k obviously gives us -1 to the k plus 1. But that's exactly where we wanted to end up. Okay, so now I'm going to leave you with some warm-ups. Okay, so here
The
are 3
warm-ups.
warm-up exercises based off
No
of what we
way.
saw. The first is to prove for all natural
Oh
numbers
my
bigger
God.
than or equal to 12, we can write them in the form 4x plus 5y, where x and y are non-negative integers. Next, if we've got this recursively defined sequence where a0 is 1 and a sub n is 1 plus a0 plus a1 up to an minus 1, then show that an is equal to 2 to the n. Then finally show that the sum of the even Fibonacci numbers has this nice identity. So f0 plus f2 plus f4 all the way up to f2n is equal to f2n plus 1 minus 1. And that's a good place to stop. This is the 16th video in a series devoted to proofwriting. And today we're going to talk about relations. So let's just jump into the definition.
Relations?
So a relation on a set A
I'm not good at those.
is merely a subset of the cross product of A with itself. And so this subset could really be anything. So in fact, the empty set is a subset of A cross A. That means the empty set is technically a relation on A. But this is not a super interesting relation. This says that nothing is related to each other. So an element
nothing is related to
isn't
each other.
even related to itself.
Whoa.
Whereas at the other end of the spectrum, A cross A is a subset of itself. And that's almost like too much. That says that everything is related.
Everything
So,
is related.
To have meaningful relations,
Harrison, are we
you probably
related?
need something in between here.
Yeah.
That would be most
What?
interesting. And also,
Ain't no
we
way.
probably like those relations to have certain conditions. And we'll introduce
How
those
are we
conditions
related?
as we move through this video.
Are,
And
innit?
we'll study them more in upcoming videos.
Leaked.
Okay, now I'd
Me
like
and
to
Harrison
say a
are
little bit about
related.
notation. So often, if an ordered pair x comma y is an element of R, then we say that x and y are related via R. And often we write x, r, y. Okay, so let's look at an example. So let's say we've got this set A, and it's the three element set A, B, C. And let's say we've got a couple of relations. So let's say we have R1, which has A comma A in it, A comma B, and then maybe A comma C and C comma A. And then let's maybe also say that we have R2, and maybe R2 is equal to A comma B, B comma C, and then maybe C comma A. Okay, nice. And so those are definitely relations, and we know they're relations because they're both subsets of the cross product of A with itself, and that's all it takes to be a relation. But that being said,
Whoa.
let's practice with some of the notation just really quick.
This guy's in
So let's
McDonald's
take
merch.
this
Oh my
R1
goodness
and
me.
make the following observation. So notice that A is related to itself via R1, so A, R1A, and that's because A comma A is an element of R1. Whereas B is not related to A via R1, and that's because B comma A is not an element of R1. Notice that A comma B is, but B comma A is not. And so that's just an example of how this notation might work. But there's also a really nice way to look at these things via a visual representation.
Okay.
So what you do is you think about every element of your set as being a vertex of a graph or a point in the plane. So let's do an example right here. Let's say this is our point A, this is our point B, and over here is our point C. And then if something is related to something else, then that gives us an arrow from the starting position to the ending position. So let's just talk our way through it.
Okay.
So this fact that A comma A is in R1, in other words, A is related to itself, says that there's a loop from A back to itself.
Okay.
So this loop is playing the role of this A comma A here. And then what about A comma B? So A comma B would be an arrow from A to B. So an arrow from A to B, so something like that. So that arrow from A to B, just to reiterate, that's like from this ordered pair here. So the left term in the ordered pair is the initial point of the arrow, and the right term in the ordered pair is the terminal point of the arrow. Now let's notice that B comma A is not in R1. That means there's no arrow going back from B to A. So there's just a one direction
Ain't
arrow.
no way.
Okay, so now let's look at A comma C and C comma A. So A comma C will be a path from A to C like that, and then C comma A will be a path back from C to A. So this would be a picture of R1. So maybe we would put R1 over here to say that that's a picture of R1. Okay, so while we're at it, let's maybe make a picture of R2 as well. So R2, so I'll still need my points A, B, and C, but this one has less arrows because there are less elements. Notice that each element in the relation corresponds to an arrow between points in this graph. So we have A comma B, so that gives us an arrow from A to B. We have B comma C, that gives us an arrow from B to C. And then we have C comma A, that gives us an arrow back from C to A. And that's all we have. We don't have any reversals of these arrows. And we also don't have any loops like we did right here. So let's maybe put a box around this. Now notice that since R1 and R2 are simply subsets of A cross A, that means we can take their union and intersection, and that will also give a subset of A cross A. So R1 union R2 and R1 intersect R2 will also be relations. So let's look at each of those. Maybe let's look at R1 intersect R2 first.
Okay.
So which elements do these have in common? Well, we have A comma
R1
B,
and R2.
and we also have C comma A, and that's it. So those are the only elements in common. So if we were to draw our picture again, so again, label these A, B, C, then we would have an arrow from A to B, like this. And then we would have an arrow from C to A, and that's all we would have for R1 intersect R2. And then I'll let you look at R1 union R2, but what you'll get is just exactly this graph right here.
Why is he drawing a
R1
penis? Hold on.
with the inclusion of an edge between B and C, like this. Okay, so let's do some more examples. So this whole notion of a relation is really just an abstraction of things that we've seen before, that we actually called relations between numbers. And so often we'll like to go back to previously known relations that we've seen in other classes in order to further motivate this study. So in fact, we could just take our relation to be the relation less than, and that's what we'll do in this example. So let's say we've got a set A, which is the set containing 1, 2, 3, 4, and we say that X is related to Y if and only if X is less than Y. So let's start by writing this relation down as a set of points. So let's notice that 1 is related to 2, so that means we have 1 comma 2 in this set. That's because 1 is less than 2. And then we also have 1 being related to 3 and 1 being related to 4. Again, because 1 is less than 3 and 1 is less than 4. Next, we have 2 is related to 3 and 2 is related to 4, and finally 3 is related to 4. And that would be all of the entries from this set R. Okay, so now let's maybe make a picture of this. So I'll just put my numbers in a string. So let's say 1 is here, let's say 2 is here, let's say 3 is here, and maybe let's say 4 is here.
Okay, you got some numbers?
So we need an arrow from 1 to 2. We also need an arrow from 1 to 3, and finally we need an arrow from 1 to 4. And that's because 1 is smaller than 2, 3, and 4. And then we need an arrow from 2 to 3, and we need an arrow from 2 to 4. And that's because 2 is smaller than 3 and 4. And then finally we need an arrow from 3 to 4. And that would finish off our picture. Okay, so now we're going to look at one more set of examples before we look at some characteristics that relations can have. Now let's look at two related relations. So let's say R sub 1 is the set of all points x comma x squared where x is a real number. Let's notice that this is naturally a subset of R cross R. That means it is a relation on the set of real numbers R. Okay, so let's maybe graph this one first to get started.
Oh,
so notice that this is
my
exactly
goodness me,
the graph
he's
of our favorite parabola
graphing.
y equals x
He's made a
squared.
graph.
That's because x is like a free variable, but then the y
No
variable
way,
depends
he made
on
a
x. So let's
graph.
color code this. Let's say here we will graph this relation in yellow. So that means we simply need the graph of a parabola. So we need something like that. Great. And then let's look at our second relation, which I'm actually going to change for no reason then it makes a nicer picture. And so this is going to be the set of all points x comma y in R2, where y is bigger than x squared. Let's also notice that this is a relation on R cross R. Great, which means we can graph it the same way. But what's that? That's the set of all points that lie above this parabola.
Whoa,
So let's maybe color
no way.
code this in blue. So if we were to graph all of these points, we would graph every y value which is above its corresponding
That's a lot
x
of
value
points,
on the
though.
parabola.
How is he going to graph all of
So we would
those?
graph everything inside the parabola. And notice we do not
Whoa!
graph the parabola itself. I think that's a good variety of basic relations. Now let's look at some properties that relations can have.
Bro,
So
that's
there are
crazy.
3 very important properties that a relation
way.
might have. And if it has all 3 of those properties,
God.
it's super special. And it's the type of relation that we'll talk about next time. So let's suppose we have a relation, we'll call it R. So let's just recall again that that just means that it's a subset of A cross A. Then we say R is reflexive if for all x in A, x is related to itself. So if you're talking about a relation, it often kind of makes sense for something to be related to itself. Then we say R is symmetric if when x is related to y, we know that y is related to x. But we can put this symbolically into the conditional, x related to y implies y related to x. So that's how we would prove this type of thing. And then finally, we say R is transitive.
It costed me. You got conditioner?
X is related to Y
not?
and Y is related to Z.
What?
We
Ain't
know
no
that
way.
X is related to Z. So again, you could put that into a conditional with an and statement.
New Harrison Toys clips
So
video.
X related to Y and Y related to Z implies X is related to Z. Okay, so let's look at a chart of standard relations on the integers, and we'll prove some things about some of these relations, and then just argue the properties of the rest. So I have the properties here: reflexive, symmetric, transitive, and then I've got my relations: less than or equal to, divides, does not divide, and
That's a good one.
equal to. So I don't have greater than or equal to.
We start to lose it after that one.
A reflected version of less than or equal.
Good night, love you.
I just love how you ended it with a good night, love you.
Down here, we're going to start looking at the less than relation.
Good night,
So
love
let's notice
you.
it's not reflexive. And we can see that via example.
Wait, what's coming out tomorrow?
2 is not less than 2. 2 is equal to 2. It's not strictly less than 2. So maybe we would say here, no, it is not reflexive.
Tomorrow we have got.
No, it's not symmetric. And we can check that it's
Oh,
not symmetric.
the Tommy
by
in it
noticing
video.
That 2 is most definitely less
Let's
than
go!
3.
More views!
3 is
More
not
views!
less than 2. So again, it is
Why
not
does
symmetric.
Skibbity Friend
But it is
20 have no
transitive.
likes?
So let's note that if
Why would it have likes?
Oh, Ryoyo has
L is
commented,
less than
expecting a
N,
reaction to the
and
previous 19 by
N
yesterday.
is less than N, then L is less than N. So that would be the transitivity
Well,
property
Harrison,
for less
we have
than.
to react to
So I'll go over
Skibbity
here and
Friend
I'll put
1
yes,
through
it
19.
is transitive. Now it looks like we didn't prove anything here, and in fact,
If we
didn't.
do, it'd be
And
one
that's
video.
because in order to really
exactly.
check this thing about less than, you need something about the integers at a more base level, but we're not going that deep here.
Wait,
okay. Now
why
what
is
about
it-
less than or equal to? So notice that it's not
Oh, there's 2 more
symmetric,
oleki
so let's
reactions. I
start
didn't
with
even
that.
fucking
It's
realize.
not symmetric. That's because 2
Is
is
that-
most definitely less
Top
than or
10
equal to
beta
3.
loose Fortnite
3
skins in
is
Fortnite,
not less
and the
than or equal
greatest
to 3.
Fortnite clip of all time.
It is reflexive.
Oh.
That's because any number
Just
is
her watching
less than or equal to
shorts.
itself, because we allow that equality. And then it's also transitive. So I'll put a yes here for transitive for the same sort of reason as this down here. Now, and then maybe we would finish this off by saying that m is less than or equal to m.
Wait, why is it
for
doing it
all
like that?
integers m.
Oh.
That's because m is in fact equal to.
That is
so there's not
shit.
really anything going on there. Okay, now what about equality? Well, I remember learning in grade school that equality was reflexive, symmetric, and transitive, and we even use those words. So perhaps you've seen that before, but that's really one of the defining properties of equality. So I'll just put yes for all of these. And now let's move on to divisibility. So looking at divisibility, is it reflexive? Yes, it is reflexive. That's because for all integers n, we can write n as 1 times n, but writing it as something times n means n divides n. So notice, to prove that it's reflexive, we had to prove this universal statement. We had to do something. Whereas to prove that it is not symmetric, which we're about to do, all we have to do is give a counterexample. So that's important to notice.
Counterexample.
So we can go over here and put
Got
yes, it is reflexive. And shortly, that's just because everything divides itself. but it is not symmetric. And that's because, for example, 2 divides 4. So 2 most definitely divides 4 because 4 is 2 times 2. But 4 does not divide 2. But in order for it to be symmetric, 4 would have to divide 2. So anyway, that's our counterexample for symmetry. So it is not symmetric. But it is transitive. And I think that was maybe a homework exercise, but let's work through it just
Homework exercise?
So let's suppose...
I forgot this guy was like an actual teacher for a moment.
I've got homework, I just remember. I've got an assignment.
This language over here. So let's notice that
what have you got to do, mate? What have you got to do?
A times X
why?
And
I think it's ways businesses can use social media.
Times Y for some integers A and B.
It's like 300 words just to pass it, or 500 if I get a better grade. So
this version of Y and
that's not that many words.
So let's see what that leaves us with. We'll have
and we've been given a help sheet.
To B times AX. In other words, it's equal to AB times X.
Bro, you get it so easy, man.
But having Z.
How the bloody hell did I rotate the high school into the road? When did I do that?
That's exactly what we needed to end to show that this is transitive. So I'll put yes, this is transitive. Now,
I realized it's a bit wonky. I'm like, what? When that happen?
Does not divide. Well, in fact, that's neither reflexive, symmetric, or transitive. Now I'll let you check that one on your own. But that's essentially because if you negate does not divide, you get does divide. Okay, so now let's move on to inequality. Okay, so looking at inequality, it is not reflexive. And we can see that because 3 is equal to itself. It's not equal to itself.
Yeah, 10,000 people now live here.
Reflexive. But you can say that every number is equal to itself. But that means
it's had a bit of
every number is not
extension since last time. So
anyway, it's pretty clear that
Harrison and Daughters Clips fans.
But is it symmetric?
Are you living here?
Harrison and Tortoise Clips fans, are you living here?
Definitely not.
Do let us know in the comment section below.
That it's symmetric. So we have yes.
You live in there, Archie. You live in there.
I would so live there.
Well, in fact, it is not transitive, and we can do that via
the big blue hole on the right side.
So let's note that 2 is most definitely not
on the right side from the screenshot. There appears to be a big blue hole. I would live around there.
2 is equal
oh my
to 2.
days, you numpty.
For it to be transitive, we would need 2 to not.
I don't know what it is. It's like is it like a fountain or something?
That's a counterexample for it being transitive.
What, the red thing and then the blue inside?
Yeah.
Filled in charts.
That's them telling me I don't have enough workers.
Oh shit, is that what it is? I can't even make that shit out, man.
I think
put those together.
It just looks like you dumped a fountain in the middle of the road or something.
Let's find out.
Reflexive, symmetric, or transitive.
Not enough educated workers.
So it's reflexive if every point has a loop. So if you look at your graph of your relation, then you look at a point and that point should have a loop kind of around it. So where the terminal point and the initial point.
Where are you living the hardest?
Where you live, mate? If someone's watching this 7.5 hours in,
so what about symmetry? Well, so symmetry
says
that every arrow has an arrow back. So here we need 2 points. And let's say we've got 2 points and we've got an arrow from one to the other like this. So at the moment it is not symmetric, but if it were symmetric, we would also have
which building in that image is taller than the rest
of
them?
Having a two-way street instead of having a one-way street. And then what about transitivity? I like to think about transitivity as having a shortcut.
Hold on.
I'll just say there's always
this is so confusing because this guy's talking about one-way streets and two-way streets.
So there are 2 cases.
What did you say?
So
which building in that picture is the tallest out of all of them?
Let's say we have
it's pretty easy to tell.
This top left point to this bottom point, and then another arrow like that. So let's say that's what we.
It may be casting a shadow on the estate behind it.
So will tell us that there's a shortcut. So in other words, there's an arrow simply from this point to this point. And then there's one other way.
I think I found
transitivity, and that involves
stock exchange building.
So say we've got 2 points like this. And
the stock exchange building is just casting a shadow on the rest of it.
When you place it at level 1, before you make any investments, it's quite small. But you level it up to level 5 and suddenly it's that big.
That's important to notice as well. Okay, so now let's do some examples of checking.
I wonder if I can get the World Trade
So now we're going
Centers.
to show that the relation
I'm gonna
on the
fucking
integers
fly a
given
plane
by
into it or
congruence
something.
mod n
Whoa!
is
Put right next to the airport.
reflective, and
World Trade Center.
transitive. Okay, so let's do these one at a time.
Oh, Archie!
So
Oh,
look
no.
over here. In order to show it's reflexive, we need to take an
I've closed the
arbitrary
game now,
integer and show that it's related to itself.
Oh, World
So
Trade
let's
Center.
suppose we have an arbitrary integer,
God.
which I'll maybe call A, and observe that
Or I can do the
0
one World
times
Trade Center.
n is the same thing as A minus
Hmm.
A. Oh, that's because A minus A is 0, but 0 is the same thing as
You
0
living in the World Trade
But notice
Center.
that implies that n divides A minus A.
Yeah,
I
would
just
you?
put them, like,
Really
nowhere
fancy
near my
going on
city.
here.
Yeah, would you
But
live
notice
inside of
that
the World Trade
implies
Center?
that A is
God.
congruent to A mod n by the definition of congruence mod n. But then since we started with an arbitrary A and showed that it was congruent to itself, then we have indeed showed that this is.
Anyway, I think I might go for a bit. My
Now
shoulder
let's
is a lot
show
of
that
pain.
it is
Oh, you're gonna go for a
That
bit.
means we need to take two.
Yeah.
things that
Oh,
are
what a
congruent
shame.
and show that
Got
we
you
can
for an extra
reverse
2
that
hours of the
order.
video. You're welcome.
So
Oh,
let's
thank you, thank you.
suppose that A and
I've only
B
got-
are in Z.
How many's that?
Such
4
that
hours
A
to
is
go. I've only got
congruent
4 hours to go.
B
Ish.
mod
4 hours
n.
10.
Call me.
And where we'd like to
Call me
end
when you
up
have an hour
with
left,
is B is
alright?
congruent
An
to
hour
A
left,
mod
okay,
n.
okay.
So let's see how we can get
Bye
there.
bye.
What if you're in a
Notice
VC with
by
other
definition
people?
of congruence mod n
Should I just
I
join
wouldn't
the?
be.
n
Oh, you won't be.
divides
Okay.
Yeah,
A minus
I might.
B.
To be fair,
But that
I don't
means
know.
A minus
Okay.
B is equal to
Bye-bye.
n times k for some integer k. But now we can just take this equation and multiply it by -1. That will tell us that b minus a is equal to n times minus k. But since k is an integer, minus k is also
the
an
fuck?
integer. So this equation tells us that n divides b
Open
minus
Kevin's
a.
profile.
But n dividing b minus a is exactly the condition that we want to end this off, which says that b is
I'm gonna get more
congruent to
drink.
a mod n. So that's good. We have symmetry now at this point. Notice we took arbitrary a and b satisfying a congruent to b mod n, and we ended up with b congruent to a mod n, but that's exactly what we needed to do. Okay, good. So now let's work on transitivity. Okay, so for transitivity, we need to start with 3 things that are related in this sort of scenario. Maybe we'll use A, B, and C here. So we need A to be related to B and B related to C, and then we need to show that A is related to C. But remember, our relation here is congruence mod n. So let's suppose we have A, B, and C, which are integers, such that A is congruent to B mod n, and B is congruent to C modulo n. Okay, but then definition of congruence mod n will tell us that n divides A minus B and n divides B minus C. But then definition of divisibility says that A minus B is equal to n, maybe I'll call it times x, and B minus C is equal to n times y, and this is for integers x and y. So just to reiterate, that's by the definition of divisibility. But let's recall where we're trying to get. We're trying to get to A is congruent to C mod n, so we need something like A minus C. So how can we do that? Well, let's take these 2 equations and add them. Notice if we add these 2 equations, that gives us A minus C is equal to n times x plus y. But that equation tells us that n divides A minus C, but that's exactly the condition for A to be congruent to C mod n. So let's make sure
I
we've
wonder
done the
if he
right
has
thing.
already joined a
We assumed
VC.
that A was congruent to B mod n, and B was congruent to C mod n, and then we did some calculation, and we ended up with A is congruent to C mod n. But that's exactly what we need for transitivity. Okay, let's go.
Well, if he
So
has,
our next
it's not in a
relation will
server
be on
I'm
the
in,
integers
which
as
is quite
well.
likely, to be
And
honest.
let's say in this case
Oh, well.
that A is related to B if the absolute value of A minus B is less than or equal to 3. And then our goal is to show that R is reflexive and symmetric, but not transitive. Okay, so let's do this one at a time, just like we did before, starting with reflexivity. So reflexivity is really simple in this case. Let's notice that for all, maybe I'll call it a, which is an integer, the absolute value of a minus a is equal to 0, but 0 is most definitely less than or equal to 3.
That is so true.
So that means that, in fact, a is related to itself. And since a was chosen arbitrarily, that does it for this reflexivity. Okay, so now let's check symmetry. So let's suppose that a and b are integers such that a is related to b. But notice, putting it in terms of the definition of our relation, that means the absolute value of a minus b is less than or equal to 3. But we want b to be related to a, which would be the absolute value of b minus a. So let's note that the absolute value of b minus a is the same thing as the absolute value of -1 times a minus b. But the absolute value will cancel that -1 out, just leaving us with the absolute value of a minus b, which is most definitely less than or equal to 3 by our given. Wow. So that tells us that yes, b is related to a. So it is symmetric. So now let's move on to transitivity, and we'll show that it is not transitive. And we can find a pretty simple example of this. Notice that 6 is related to 3. That's because 6 minus 3 is equal to 3. That's less than or equal to 3. And 3 is related to 0 because 3 minus 0 is equal to 3, which is less than or equal to 3. But 6 is not related to 0. And that's because the absolute value of 6 minus 0 is equal to 6, which is strictly greater than 3. So here, this is reflexive, symmetric, but not transitive. Okay, let's do one more. So for this example, we'll consider a relation on the real numbers defined as follows. So x is related to y if and only if x squared plus y squared equals 1. Now let's check these properties. So starting with the reflexivity. Maybe before we start to check these properties, let's notice that all of the points that satisfy this rule lie on this circle of radius 1. So this is not reflexive. So here we'll say, no, it is not reflexive. And why is that? That's because 1 is not related to itself. And we can see that 1 is not related to itself because 1 squared plus 1 squared is equal to, let's see, the number 2, which is not equal to 1. Okay, is it symmetric? Well, yes, it is in fact symmetric, and we can prove this. So let's suppose that I'll call them a and b. So a is related to b. So that means that a squared plus b squared equals 1.
Whoa.
But then that means that b squared plus a squared equals 1 by the commutativity of addition. But that means that b is related to a. So it's quite simple to prove that this thing is symmetric. Now, is it transitive? Well, in fact, it is not transitive. And actually, if you have something that's always symmetric, but never reflexive, you can automatically know that it's not transitive because you'll never get those loops that we talked about with that picture before. But anyway, let's show that it's not transitive by an example. So let's note that 1 is most definitely related to 0. That's because 1 squared plus 0 squared equals 1. And 0 is related to 1 for the same reason, because 0 squared plus 1 squared is 1. But 1 is not related to itself by our previous calculation. So this is a counterexample for transitivity. So we're going to end by extending this definition of a relation to 2 different sets, but we're not really going to do much with that. And then we'll have some more. That's crazy, bro. So now we want to look at this very, very slight extension of our notion of a relation. But we won't do much with this. We'll just pick up on it later when we talk about functions. So there's a little bit of a spoiler. So a relation from a set A to a set B is simply a subset of A cross
as a human being.
But now notice if we're in 2 different sets here, A and B, the notions of reflexivity, symmetry, and transitivity don't make any sense. Notice that A comma A doesn't make any sense because every element of A may not be in B. That sort of helps us figure out why symmetry and transitivity may also not make any sense, because these could be wildly different sets. Okay, so let's look at a couple of examples. So let's say we've got a set A, which is 1, 2, 3, and our set B is A, B, C, D. So these are different sets. One is made of numbers and one is made of letters. And then let's say we've got a relation between these sets of 1 comma A, 1 comma B, and 2 comma C. So this is a fine relation. You might like light up and think, hey, this is not a function, but we're not there yet. We're not thinking about this type of stuff yet. This is a relation. And we could maybe make a picture of this relation as follows. Let's put A and B each in a line. So here we have 1, 2, 3, and here we have A, B, C, D. And then we could do our arrows for the things that are related. So 1 is related to A, so we've got an arrow from 1 to A. 1 is related to B, so we've got an arrow from 1 to B. And then 2 is related to C, so we have an arrow from 2 to C. And then that would be the whole picture of this. So let's look at another one, which is a little bit more interesting. Let's say we have our relation. It's a subset of Z cross the set containing 0, 1, and 2. And we say that A is related to B if and only if A is congruent to B mod 3. So I guess implicitly built into this is everything is related to either 0, 1, or 2 mod 3, but that's not too hard to show with the division algorithm. So maybe we could make a picture of this as well. So let's lay out all of the integers at the top. So 0, 1, 2, 3, 4, 5, 6. Then let's maybe go backwards, -1, -2, -3. Maybe that's enough integers. And then we'll have down at the bottom 0, 1, and 2. And then we'll put arrows if they're congruent mod 3. So notice -3 is congruent to 0 mod 3 because it's a multiple of 3. 0 is congruent to 0 mod 3, and 3 is also congruent to 0 mod 3, as well as 6 being congruent to 0 mod 3. So -3, 0, 3, and 6 all collapse down to 0. But then notice that 2 collapses to 1, 1 collapses to 1, and 4 also collapses to 1 mod 6. That's because they're all 1 more than a multiple of 3. And then we've got one more thing. So what about -1? -1 is 2 mod 3. It's 2 more than a multiple of 3. 2 is 2 mod 3, and 5 is 2 mod 3. So that would be our picture in this case. So it's a little bit messy. But that being said, I think we kind of get an idea of what's going on. Okay, so now I'm going to give you some warm-ups. So here's some nice warm-up exercises based on what we just saw. So let's consider the relation less than or equal to on the set 0, 1, 2, 3. So let's illustrate it with a graph and prove whether or not it is reflexive, symmetric, and or transitive. So next, let's consider the relation with the following graph. And then your goal is to translate this graph into a relation with sets. So what would the set A be? And then what would the set R, which is the subset of A cross A, be? Then, given a finite set A, how many relations are on A? So this may seem like difficult and tricky, but just go back to what you know about exactly what a relation is, and it shouldn't be too bad. And then finally, let's consider the set R, which is all ordered pairs of real numbers x, y, such that their difference is an integer. Now, your goal is to show that this is reflexive, symmetric, and transitive. And that's a good place to stop. This is the 17th video in a series devoted to introductory proofwriting.
Oh my fucking god.
In the previous video, we looked at relations on sets.
I mean, I am, but I'm not at the same time.
Certain characteristics that those relations can satisfy. And today we're going to look at a special type of relation known as an equivalence relation. So the definition goes like this. A relation R on a set A is an equivalence relation if it is reflexive, symmetric, and transitive. Recall, those were the properties that we studied last time. Then there's kind of an accompanying definition that goes along with this, which is the notion of an equivalence class. So given that R is an equivalence relation on A, and we have an element, little a, from A, the set, which we'll denote by bracket A, which is the set of all x in A that are related to A. So notice I've got x in A such that x are A. That's said to be an equivalence class with the equivalence class representative A. So I want to look at some basic examples first before we prove some properties, and then look at some more maybe classic examples. So let's take our first set to be -1, 0, 1, 2, and we'll look at the following 4 equivalence relations and kind of compare and contrast them. So let's say our first equivalence relation is just simply equality. So that means that things are equivalent or they are related if and only if they are equal to each other. So what does that mean? That means that we can write R as the following set. So it'll be -1, -1. So that means -1 is related to itself, 0, 0, 1, 1, and 2, 2. So recall that R was really a set of ordered pairs of elements from A to B. It was from the cross product of A with itself. And an ordered pair was in the relation if and only if they were related. That was sort of the idea here. So this says an element is only related to itself. Okay, so now let's look at the equivalence classes. Well, notice the equivalence class of -1 will simply be the singleton -1. That's the only thing that's related to -1. Furthermore, the equivalence class of 0 is just the singleton 0. The equivalence class of 1 is simply the singleton 1, and the equivalence class of 2 is simply the singleton 2. So we can definitely have equality be an equivalence relation, but I would say it's not super interesting. And that's because it doesn't really filter anything out. The whole idea behind an equivalence relation is you want something slightly weaker than equality, so that you can study a set without looking at maybe exactly the specifics. But equality is almost too strong to do that, because if we look at the set of equivalence classes, we've essentially just reproduced the original set. Okay, so let's look at our second equivalence relation, which is two elements are equivalent if they have the same parity. Let's recall that that's the same thing as them being congruent mod 2. So what things are in this set? So here we would have R is equal to -1, -1, and -1, 1. So -1 is related to itself because they have the same parity, and -1 is related to 1 because they have the same parity. And then furthermore, we would have 1, 1, and 1, -1 by reflexivity for 1 and then reflexivity for -1, 1. Okay, so that would be everything with an odd parity. And then we also have relations between 0 and 2. So 0 is related to 2, 2 is related to 0, 0 is related to itself, and 2 is related to 2. So that would be everything in that set.
Everything is fucking related
okay,
to
so
everything,
notice
bro.
that
They got
ordered pairs
incest on this
exist if
shit.
and only if the two entries have the same parity, which is exactly what we want. But now let's form the equivalence classes. So the equivalence class of -1 will be the set containing -1 and 1 because they have the same parity. Whereas the set containing, or the equivalence class of 0 will be the set containing 0 and 2, again, because they have the same parity. Let's also notice that this top one is the equivalence class of 1, and this bottom one is the equivalence class of 2. That's why I use this word equivalence class representative.
1, 2,
Notice
3,
this
4.
equivalence
I
class
declare
containing
a
-1 and 1 has
somewhat.
two representatives, -1 and 1. And likewise for this equivalence class containing 0 and 2. So here we have, given ourselves some simplification of the original set. So instead of looking at each element individually, we're looking at each element depending on its parity. Okay, so let's look at our next one, which
Parity.
is things are related if and only if they have the same sign. And here we'll consider negative numbers, positive numbers, and 0 to be three different signs. Okay, so what would our set for our relation look like? So -1 is related to itself, but -1 is not related to anything else because that's the only negative number. 0 is related to itself because 0 is not negative or positive. And then we have 1 is related to 1, 1 is related to 2, 2 is related to 1, and 2 is related to 2 because those are both positive. And then we have to have reflexivity and symmetry in there. Now we can build our equivalence classes. We've got an equivalence class for -1, which simply contains the singleton -1, equivalence class for 0, which is just the singleton 0, and then the equivalence class for 1, which is the set containing 1 and 2.
Of course.
So here we have three equivalence classes. We have filtered our original set slightly differently as to above, but we have given some simplification if we're interested in studying the sign of an element from our original set. So which one of these is better kind of depends on what exactly you're trying to do.
About two-thirds done
so
now.
now let's look no restriction. So by no restriction, I mean everything is equivalent to itself. which means R is simply equal to A cross A. So this will be quite big. Notice we'll have 4 times 4 entries here, so we'll have 16 total entries. So we'll have -1 with -1, -1 with 0, -1 with 1, and -1 with 2, and then so on and so forth. So everything is related to everything else. So in this case, you would have a single equivalence class, and you can take any of the numbers as the equivalence class representative. I'll take -1. So the equivalence class for -1, like I said, will be everything, -1, 0, 1, and 2. And now, whereas this original one was almost too restrictive, it didn't filter the original set in a way that we could study it more simply. This filtering down here is almost too generous. Notice it made everything equal to each other, so that doesn't help us studying anything either. So I think the takeaway here is an equivalence relation and the corresponding equivalence classes are ways to filter sets into smaller parts depending on the conditions that you're trying to study. So like in this case, we would want to study the parity. In this case, we would want to study the sign, and we have these nice simplifications for parity and sign. Okay, let's keep going. Okay, so let's look at another example. Let's define a relation R on R by x is related to y if and only if sine of x is equal to sine of y. Now, let's look at some equivalence classes. I won't check that this is an equivalence relation. I think it's pretty clear given that our relation is really defined out of this equality right here. Okay, so let's look at the equivalence class of 0. And this will be aided by the fact that sine of 0 is 0. So hopefully everyone remembers that from having taken a trigonometry class in the background. Okay, so this needs to be all numbers x such that sine of x equals 0. Well, really it's sine of x equals sine of 0 by this rule right here. But because sine of 0 is 0, we get just the solutions to the equation sine of x equals 0. But this is exactly the integer multiples of pi. We have -2 pi, -pi, 0, pi, 2 pi, and so on and so forth in both directions. Now there's a fancy way to write that if you're psyched, and that would be something like this. It would be pi times z. So that's a way of writing every integer multiple of pi. Okay, now let's look at pi over 2. And let's keep in mind that sine of pi
if you know me, I love me some good pie.
So it'll be useful to know that for this problem. Okay, so that's going to be all real numbers x such that sine of x equals sine of pi over 2, but sine of pi over 2 is 1. Okay, nice. So when is sine equal to 1? Well, it's pi over 2, and then it's pi over 2 plus 2 pi, which is 5 pi over 2. And it's also pi over 2 minus 2 pi. What we'll use there is the periodicity of sine. So in the end, you'll get the following set. So we have pi over 2 in the middle, 5 pi over 2 is next, and then before that is minus 3 pi over 2, and then you can get the rest of them on either side by adding or subtracting pi over 2 as needed.
Oh yeah.
Now we can write this in set builder notation if we want, like this. So maybe it would be everything of the form pi over 2 plus 2n pi, as n runs through all integers. I think that would be a good way to write it. And I guess likewise, you could write everything up here as 2n pi as n runs through all integers. Sorry, this should be just n pi as n runs through all integers. And taking inspiration from this sort of fancy algebraic way of writing this set, we could do the same thing down here. It would look like pi over 2 plus 2n times integers. Okay, nice. But we can actually make a picture of what's going on here. So let's recall the graph of the sine function. So obviously it's like periodic like this. And let's go to an arbitrary x. Let's say our arbitrary x is right here. Good. And now what we'd like to do from there is find everything else in the equivalence class of x. So that means we need sine of x to be sine of the other thing. Well, we can get that just by drawing a horizontal line at this point right here, which is sine x, and look at all the intersection points. So all of these things that are green dots, along with the original yellow dot, are the equivalence class of x. So let's maybe point that out. So this thing, all of these are in the equivalence class of x. Okay, let's do another. Next up, we're going to look at an interesting equivalence relation on the set z cross n. So in other words, we're comparing ordered pairs where the first entry is an integer and the second entry is a natural number with other such ordered pairs. So we'll say that a comma b is related to c comma d if and only if ad equals bc. So this has a really nice result. So I'll first show that this is reflexive. So let's notice that a comma b is related to a comma b because a times b is equal to a times b. That's really all there is to it. Next up, let's notice that if a comma b is related to c comma d, that tells us that AD equals BC. But now flipping that, we see that CD is equal to AB, which is the same thing as saying that C comma D is related to A comma B. So that gives us our symmetry. Now let's prove our transitivity. So let's suppose that A comma B is related to C comma D and C comma D is related to E comma F. So that gives us two facts. That tells us that AD equals BC, and it tells us that CF equals DE. Nice. Okay, so now let's take this one and multiply it by A. So let's see what that leaves us with. We'll have ADE is equal to A times C times F. But now we can write ADE as BCE. So let's do that. This is the same thing as BCE, given this fact right here. But now putting that together, we have ACF equals BCE. But now we can cancel C from both sides of this equation, and that gives us AF equals BE. But that's exactly the condition that we need for AB to be related to EF. And you might be worried right here at this step where we canceled C or divided by C.
Oh yeah, bro.
And you would be right to worry about that because C is allowed to be 0. So this step right here can only occur if C is not equal to 0. So in fact, you'd have to repeat this in the case that C was equal to 0 to finish the thing off. But I'll let you do that on your own. Okay, so that's a sketch of transitivity, and then we have reflexivity and symmetry. Okay, so now let's look at some equivalence classes. So let's look at the equivalence class of the ordered pair 1, 2. So that's going to be all ordered pairs AB such that AB is related to 1, 2. Yes. But let's recall, what does it mean for AB to be related to 1, 2 by our given? So that means that 2 times A is equal to B. So in the end, that'll give us everything of the form A comma 2A, as A runs through all natural numbers. So we get something like that. Okay, but that gives us a motivation of how this should be interpreted. So this equivalence class we can interpret as the number 1/2. And that motivation comes if we write out what this equivalence class looks like. So this looks like the set containing 1, 2, 2, 4, 3, 6, so on and so forth. But those are all, well, other than 1/2, those are all non-simplified versions of the fraction 1/2. So notice 2/4, that's the same thing as 1/2. 3/6 is the same thing as 1/2, and so on and so forth. So in fact, that's what you're getting for these equivalence classes. You're getting some notion of the fraction A over B. And we can see that by recalling the following rule about fractions. A over B equals C over D if and only if AD equals BC, which we can just get from cross multiplication. So really, this is a nice way of building the rational numbers out of the integers and this equivalence class, equivalence relation setup. Okay, let's move on. So our next little goal is to prove some of the standard general results involving equivalence relations and equivalence classes, starting with the following. So let's suppose that we have R, which is an equivalence relation on a set A. Then what we'll show is that the equivalence class with equivalence class representative A is equal to the equivalence class of B if and only if A is related to B. Okay, so let's get to it. So let's do this forward direction first. So let's suppose that the equivalence class of A is equal to the equivalence class of B. Okay, then let's note that A is related to itself by reflexivity, but that implies that A is an element of the equivalence class of itself, which is equal to the equivalence class of B. But then taking out the middle, that tells us that A is an element of the equivalence class of B.
Leave a like for reflexes.
By the definition of the equivalence class of B, that means that A must be related to B. And there we've done it. We've done the forward direction. Okay, so now let's do the reverse direction. So let's
okay, but like if anyone actually watches to this point,
related to B, and notice that we want to show a set equivalence here. So since we want to show a set equivalence, we need to show that equivalence class of A is a subset of equivalence class of B and vice versa. We'll only do one direction because this is a symmetric argument. But that being said, technically you need to do both. Okay, so we'll also suppose that X is
the current timestamp that you can see, the minutes that you could see.
And notice where we'd like to go
and I will send you a secret.
X is an element of the equivalence class of B. And that's because that will show us the equivalence class of A is a subset of the equivalence class of B, which is like 1/2 of the argument that we'll take to show they're equal. So if X is in the equivalence class of A, then that tells us that X is related to A. But then by transitivity, X is related to A and A is related to B, which means X is related to B. But if X is related to B, then that's exactly the condition for X to be in the equivalence class of B. Okay, so what did we do? We started with X's in the equivalence class of A. We ended with X's in the equivalence class of B. So that means the equivalence class of A is a subset of the equivalence class of B. And then maybe similarly, the equivalence class of B is a subset of the equivalence class of A, and thus they are equal as sets. Okay, so now let's introduce another definition which is going to be kind of dual to the notion of an equivalence relation and equivalence classes. So for our next definition, we're going to look at the notion of a partition of a set. So a partition of a set A is a collection of non-empty subsets of A. So there we've got a subset of A which is non-empty, such that if we take the union over this whole collection, we get the entire set. And if we take the intersection of non-equal sets, we get the empty set. So they're disjoint. Okay, so let's look at some examples, starting with a very simple one. So let's take A to be the set 1, 2, 3, 4, 5. So this would be an example of a partition of A. We could have the singleton 1, we could have 2, 3 together, and then we could have 4, 5 together. So that's an example of a partition. You could get another partition, maybe 1, 2, 3 is together, so 1, 2, 3. And then maybe 4 is by itself and 5 is also by itself. As you can imagine, there's probably a lot of partitions, and there are a lot of partitions. In fact, they're related to something called the Bell numbers, if you're interested in looking that up. Then we could take integers z and we could partition them a number of different ways. We could partition them into even numbers and odd numbers. So there's the set of all evens and the set of all odd numbers. You could also partition them into the set of all multiples of 3. So that would be 0 plus minus 3 plus minus 6. And then the set of all multiples of 3 plus 1. So that would be 1, and then 1 plus minus 3, and then 1 plus minus 6, so on and so forth. And then the set of all multiples of 3 plus 2. So that would be 2, and then 2 plus minus 3, so on and so forth. So that would be an appropriate partition. Okay, so now let's prove a nice result that fuses together these notions of partitions and equivalence relations. Now we're going to prove a really classic result. Actually, it's the first half of a classic result. The second half will be left as a homework problem. So let's suppose R is an equivalence relation on a set A. So what we'll show is that the set of equivalence classes of R is a partition of A. So that means by the definition of partition, there are two things to check. First, that these union to the entire set, and second is that equivalence classes are either equal to each other or disjoint. So let's prove this first part first, that they union to the whole set. So let's really spell out what we need to prove here. So what we'd like to prove is that the union over all A in A of the equivalence class of A is equal to A. So something like that. So I'd like to point out real quickly that the inclusion in this direction is totally trivial. And that's because each of these equivalence classes is a subset of A. So if we're taking the union of subsets of A, we get a subset of A. So that means all we'll focus on is the reverse inclusion. That is, we'll take an element from A and show that it's in this union. But that's also fairly quick. So let's suppose that we have an element, maybe I'll call it little x in A. Okay, but then by reflexivity, we know little x is related to itself, but being related to something is exactly what it takes to be in the equivalence class. So that means x is in the equivalence class of x. But now the equivalence class of x is most definitely part of this union since x is in A. So this is a subset of the union over all such equivalence classes. But let's see what we've done. We have started with x in A and we have ended with x as an element of this union. But that tells us that A is a subset of this union. But since this other direction was clear, this is all we needed to show to prove that these union to the whole set. Okay, so now let's move on to this second need, and that is to prove that these are either disjoint or they are equal to each other. And we'll do this by first supposing that we have two that are unequal. So let's suppose we have A and B in capital A such that the equivalence class of A is not equal to the equivalence class of B. And then we want to show that they're disjoint, and we'll do that kind of by a contradiction. So let's take an element x from their intersection. So this is how we're moving towards a contradiction. We'll show that no such x can exist. Okay, but notice that means that x is in the equivalence class of A and x is in the equivalence class of B. But that tells us that x is related to A and x is related to B. But then by the transitivity property of equivalence relations, that means that A is related to B. I guess we're using symmetry on this one first to get A to the left. But now if A is related to B, that means that the equivalence class of A is equal to the equivalence class of B. But that's a contradiction. So that contradicted our assumption right here. So that means that it must in fact be impossible to choose such an x. So let's point that out here. No such x exists. But the only rule that x satisfies is it's in this intersection. But if there's no such x in the intersection, then that means that this intersection is indeed empty. But that's exactly what we needed to do. Okay, so let's finish with one more thing. Now we're going to look at the integers modulo n. And so what is that? Well, we'll denote it by z subscript n. Read that zn. And that's the equivalence classes of z, where our equivalence relation is congruence mod n. So in the previous video, we showed that congruence mod n satisfied all the properties of an equivalence relation. So that means it gives us equivalence classes. And in fact, there are obvious equivalence classes here. We get the equivalence class of 0. So that's everything that's a multiple of n. we get the equivalence class of 1. That's everything that has a remainder of 1 when divided by n. The equivalence class of 2, that's everything with a remainder of 2 when divided by n. Ending at the equivalence class of n minus 1. That's everything with a remainder of n minus 1 when divided by n. Let's recall that those are the only possible remainders when dividing by n. Okay, so we've got n numbers here between 0 and n minus. Well, they're really n equivalence classes. And now there are some obvious operations that you can define on this. You just have to check that they're well defined. So let's define the following observation or operation on the equivalence class A and B. So A plus B will be the equivalence class of A plus B. So since we're working with equivalence classes, we have to check that this makes sense. In other words, it's well defined. And when you take an abstract algebra class, you'll see the need to do this even more and more and more. Okay, so how can we do that? So let's suppose that the equivalence class of A is equal to the equivalence class of A prime, and the equivalence class of B is equal to the equivalence class of B prime. And where we want to end, so we want to show that the equivalence class of A plus B is the same thing as the equivalence class of A prime plus B prime. So what that means is that this addition does not depend on your equivalence class representative. But let's notice if A is equal to A prime, that means that A is congruent to A prime modulo n. And then if equivalence class B equals equivalence class B prime, then likewise B is equivalent to B prime modulo n. But let's recall that means that A is equal to A prime plus n times, I'll maybe call it K, where K is an integer. That's because n divides A minus A prime by the definition of congruence mod n. And then likewise, B is equal to B prime plus n times L for an integer. Same sort of thing, n divides B minus B prime by the definition of congruence mod n. But now let's note that we can add these and we'll get A plus B is equal to A prime plus B prime plus n times K plus L. But that means that A plus B is congruent to A prime plus B prime modulo n. But that's exactly what we needed to do to show that the equivalence class of A plus B is the same thing as the equivalence class of A prime plus B prime. So in other words, this is a well-defined operation. Now we could go over here and define another operation, which is like multiplication, which would be equivalence class A times equivalence class B equals equivalence class of A times B. But we would have to check that that is well defined as well. But in fact, there's not really anything to that. It starts all the same until this step, but now you just multiply both sides of the equation instead of adding both sides of the equation. So that'll give us that A times B is equal to A prime times B prime plus n times something. And that something is a little bit complicated, and it comes from foiling out these things that I'm writing in red parentheses. But let's notice that everything other than A prime and B prime will be multiplied by n. Okay, but from there we see that A times B is congruent to A prime times B prime mod n, but that's exactly what we need for the equivalence class of AB to be the equivalence class of A prime B prime, which proves that this is a well-defined multiplicative operation. So we're going to finish off investigating some arithmetic properties of Zn. Now we're going to make an addition and a multiplication table in Z4. So that means all we need to look at is 0, 1, 2, and 3. And I'm going to use a simplified notation here, which is quite standard when working with Zn, and that's we're going to drop the brackets. Because if we know what setting we're working in, we can always think that these really mean the equivalence classes. Okay, so let's add 0 and 0. So 0 plus 0 will be 0. 0 plus 1 will be 1. 0 plus 2 is 2, and 3 is 3. And then down this line as well. Now let's do 1 plus 1, that is 2. 1 plus 2 is 3. 1 plus 3 is 4. But 4, the equivalence class of 4 is the same thing as the equivalence class of 0 modulo 4, because 4 doesn't have a remainder when divided by 4. Likewise, we can finish out this column the same way. Now 2 plus 2 is 4, but that's 0 mod 4 again because it's a multiple of 4. 2 plus 3 is 5, but 5 has a multiple of 1 when dividing by 4, so we get a 1 there. Likewise, we get a 1 here, then 3 plus 3 is 6, so we get a 2 here because that has a remainder of 2 when divided by 4. So we get this interesting addition table when we're working in Z4. Now let's look at the multiplication table. So 0 times anything will be 0. Okay, so that's not really surprising. 1 times anything will be itself, so that's the multiplicative identity still. Now let's look at 2 times 2. So 2 times 2 is 4, which is 0. So that's actually quite interesting, maybe more interesting than you may realize at the moment, because we've just multiplied 2 non-zero objects and gotten an object which is 0. Now let's do 2 times 3. So 2 times 3 is 6, which has a remainder of 2 when divided by 4. So 2 times 3 is 2. So that's also kind of interesting. But then 3 times 3 is 9. That has a remainder of 1 when divided by 4. So 3 times 3 is actually equal to 1. So 3 is its own multiplicative identity when working in Z4. Okay, so I'm going to leave you with some warm-ups. I'm going to leave you with 3 warm-up exercises. So first, define a relation R on the integers by x is related to y if and only if x plus 7y is even. Next, prove this is an equivalence relation and describe its equivalence classes. Next, let's set A equal to the set A, B, C, D, E, and let R be an equivalence relation with 3 equivalence classes such that A is related to D and B is related to C, and then your goal is to use the properties of an equivalence relation to write R out as a set. So these 2 facts, that A is related to D and B is related to C, together with the fact that there are 3 classes, really restricts this down to a single type of relation. Okay, next let's make an addition and multiplication table for Z6, and that's a good place to stop. This is the 18th video in a series devoted to introductory proofwriting. In the previous couple videos, we looked at relations on sets. And for a brief minute, we looked at a relation between 2 sets. And today we want to look at functions, which is really a very special type of relation between 2 sets. So let's look at our proper definition. So we'll suppose that A and B are sets, and then a function f from A to B, which we'll denote with the following notation. So read this as f is a function from A to B, is a relation, so that means it's a subset of A cross B, such that for every A in A, there is exactly one B in B, so that should be a lowercase b, such that the ordered pair A comma B is an element of F. Remember that F is really just a subset of A cross B, so at its heart. And so generally we'll write F of A equals B. And so that's like proper, maybe very common function notation that you know from pre-calculus or calculus class. But another notation we could use is this A gets sent to B, or A is mapped to B. So notice it's this arrow with this little vertical line here. And then if we're working with more than one function, we might put a little f over this to say that that mapping is done via f. Now there are things associated to functions like the domain, and so the set A is known as the domain of f. Then B, which is the target, is called the codomain of f. Notice that's not the range of f. The range is only the points in B that get landed on. So in other words, it's everything of the form f of A as A runs through all capital A. So like I said, that's called the range of f, or sometimes the image of f. Okay, so now let's look at a very basic example and then non-example as well. So let's look at this function f. So it takes A to 1, B to 3, C to 4, and D to 3. I guess I should say that A is the set A, B, C, D, and B is the set 1, 2, 3, 4, 5. So we could maybe draw this in a picture like this. So we could have a bubble over here that's A, so it contains A, B, C, D. Then we could have a bubble over here that is B, so that's 1, 2, 3, 4, 5. And then we'll notate this as arrows. So A gets mapped to 1, so there's our arrow. B gets mapped to 3. C gets mapped to 4. And then D also gets mapped to 3. So we have something like this. You know, we could also write it as f of a equals 1, or as a gets sent to 1. We could also write f of b equals 3, or b gets sent to 3, and so on and so forth. So those are just different ways of writing the same kind of thing over and over. Let's compare that with this r over here, which is a relation but not a function. Let's draw a picture of that. So we'll have our set A, which is made up of little a, little b, little c, little d, and then our set B, which is the numbers 1, 2, 3, 4, 5. Now notice this tells us to take A to 1. Okay, that's cool. B to 2, so everything is still okay. But it also tells us to take A to 3. And that's where we have our problem. Notice over here that every A in A, there is exactly one B in B such that A comma B is an F. But this A is connected to two elements from B, 1 and 3. So that's how you can see it in the set. In the picture, we can see that as having two tails of arrows based at A. Okay, so now let's continue on. So C gets mapped to 4 under this relation, but notice D is not sent anywhere. And that breaks a rule as well. So notice for every A in A, there is exactly 1. Well, D has 0 elements that it's mapped to, so that is not exactly 1. So there are a couple of different reasons why this relation is not a function. So before moving away from this example, I'd like to do one more visualization. So I'd like to take one more visualization of our function, and I'll maybe leave the visualization of the relation as maybe a warm-up problem, or maybe an exercise for you to do on your own. So here's what I have. I have the set A cross B, so down here on a horizontal axis, if you will. It's not exactly an axis. We have our set A, and on the vertical, again, axis, we have the set B. Now what I'd like to do is graph this function. So this is like an interesting discrete function on two finite sets, so it's not like a graph like you might see in a calculus class. So notice it will contain this A comma 1 element. But then after that, we have to sneak up here, and then we contain this B comma 3 element. So that would be the next thing that it contains. Then let's see. Then we sneak up here, and it contains this C comma 4, and then we sneak down here, and it contains this D comma 3. So in the end, the graph would be this like blob that's going through A cross B, containing all of these ordered pairs. But notice this blob passes like some version of the vertical line test, which is the test that you might have used in calculus or pre-calculus to determine if something was a function. Now, like I said, I'll leave it to you as an exercise to graph this relation and see that it's not quite as nice. Or you can see the visualization of the fact that this is not a function. Okay, so let's move on. For our next example, let's consider the function f. Its domain is the integers, and its codomain is the natural numbers. And we'll define it via this rule here. So this is like a standard way of defining a function. So we have when f acts on n, it gives us the absolute value of n plus 1. Or we could also similarly or equivalently define it by this arrow rule. So we have n is mapped to the absolute value of n plus 1. Now let's look at a couple of examples of evaluations, although this is quite simple. Notice f of 3 will turn into the absolute value of 3 plus 1, which is 4. F of negative 2 will turn into the absolute value of negative 2 plus 1, which is 3, and so on and so forth. So in fact, we could graph this if we wanted to, and I would say that'd probably be something nice to do. So notice the number 0, so f of 0 will give us 1, so that would be this point right here. F of 1 will give us 2, so that would be this point that's about right here. F of negative 1 will give us 2 as well. F of 2 will give us 3. F of negative 2 will give us positive 3, just like we saw before. And as you can see, we will essentially get this shape, which is a bunch of dots in a V. And those dots all lie on this like lattice of the integers and the natural numbers. So something like this. So you can imagine this as being the lattice of the integers and the natural numbers. Okay, let's do another one. So for our next function, let's look at phi, which goes from z squared. In other words, z cross z
I am
to
back.
z. So it
Let me
has
know
an
what I
input
missed
of
in the
2
comments
integers
below.
and an output of 1 integer. And it's defined by the following rule. Phi evaluated at mn is 14m minus 8n. Now I think maybe something good to do with this function is to determine its range. So let's get a good guess for its range by evaluating this at some points just to see what we get. So let's notice that phi evaluated at 0, 1 will be equal to -8, just based off of that rule. Phi evaluated at 1, 0 will be equal to 14 based off of that rule. Notice that phi evaluated at 1, 1 is 14 minus 8. That's equal to 6. What about phi evaluated at 1, 2? So that'll be 14 minus 16. That is -2. Oh, but what about this? What about phi evaluated at -1, -2? So that'll be -14 plus 16, which is 2. Okay, well, what do we notice about all of these numbers? Well, in fact, they're all even. And this is the smallest positive even number, and this is the smallest negative even number. So it seems like we're just getting all of the even integers. And that'll be what our claim is. And we will prove this claim. So here's our claim, that the range of phi, let's maybe write it like that, the range of phi is equal to all even integers. So we could write this as 2 times k, such that k runs through all integers. But let's recall using some notation similar to what we had in a previous video. That could be 2z. That says we're scaling every integer by 2. Okay, so let's see how this proof goes. Our goal is to show that 2 sets are the same, which means we need to do this with double inclusion. So let's do that. So we'll start with the inclusion going this way. So let's suppose that we have a number L, which is in the range of phi. But what does that mean? That means that L equals phi of mn, which equals, let's see, 14m minus 8n for some m and n, which are integers. That's what it takes to be in the range. Okay. But now let's notice this. Note that we have L equals, well, 14m minus 8n, but we can factor a 2 out of that, leaving us with 7m minus 4n. But that's very clearly in this set of even integers because it's multiplied by 2, and then 7m minus 4n is an integer. So let's just write this is in 2z, since that's some nice short notation. Okay, so that means we have proven the right inclusion, or the inclusion in that direction. So let's move on to the reverse inclusion. So let's suppose that we have a number, what should we use this time? Let's maybe use 2a, which is in 2z. Well, remember 2z, that's all even integers, so that means it's of the form 2 times a. And then let's observe the following calculation, which can be motivated by this up here. This phi of -1, -2 is 2. So if we have phi of -a, -2a is equal to, let's see, this will be 14 times -a minus 8 times -2a. But after fairly simple calculation, we'll see that that is equal to 2a.
Good.
But this equation shows us that 2a is in the range of phi, because we wrote 2a as an output of phi. That's exactly what it means to be in the range. I left out an e there. But that's exactly what we need to finish off this reverse inclusion. So the forward inclusion and the reverse inclusion finish the proof that the range of this function, or the image of this function, is indeed all even integers. Okay, so now let's move on to some special types of functions. Now we want to look at some special classes of functions. So let's see the definition. Given a function f from a to b, we say that f is injective, or in other words, 1-to-1, if for all x and y in A, we have f of x equals f of y implies x equals y. Then we call it surjective, or onto, if for every b in, that should be b in b, we have an a in a such that f of a equals b. So this means everything is landed on. And then we say it's bijective if it's both injective and surjective. So let's look at some pictures of functions that are injective, not injective, and surjective and not surjective. Okay, so first for an injective function. Let's say we have the following action like this. So these 3 dots, notice they're all mapped to 3 different places in the codomain. That's exactly what we need for this to be injective. So everything from the domain is mapped to a new thing in the codomain. Let's compare that to something that is not injective. So let's say we have some action like this. So notice this second and third dot are both mapped to this second dot. So they're mapped to the same thing. That makes this thing not injective. Notice if this were x and this were y, here we have f of x equals f of y, but x is not equal to y. Okay, now let's go over and explore a surjective and a not surjective function. So a surjective function means everything in the codomain is landed on, and this would be an example. Notice every dot over here is mapped onto. Then something that's not surjective would be something like this. So notice that this dot over here is missed. So you can think about something that surjective doesn't miss anything in the codomain. Okay, so next I'd like to give some outlines for proving that functions are injective and surjective, and then do some examples. So now I'd like to look at some proof outlines for proving injectivity and surjectivity of a function f from a to b. So in order to prove that it's injective, you'll start by supposing you have x and y in A such that f of x equals f of y. And then you will decode that or unpack that using the definition of f and do some calculations here. That's what this purple box is, to finally end with x equals y. And so that'll complete this proof. And then showing that f is surjective is a little bit trickier. So in your scratch work, you will solve f of a equals b for a. And what you'll get is a is written in terms of b. Then you're ready to write down your final proof. So we'll suppose that little b is in b and consider a equals, well, this crazy thing that you found after solving this. And then next up, you say something like, now observe that f of a equals b, but this is going to involve essentially the reverse calculation of this over here. Okay, so I think it's best to look at some examples of this. So let's first consider the function f that goes from the real numbers minus 0 to the real numbers defined by f of x equals 2 over x minus 1. And we'll show that that is injective but not surjective. So let's start by showing that it's injective, and then we'll show that it's not surjective by finding someone who is missed. And then we'll redefine the codomain to make it surjective. Okay, so injective. So let's suppose that x and y are in the set of real numbers minus 0, where f of x equals f of y. And now let's unpack that and see that that means that 2 over x minus 1 equals 2 over y minus 1. But now essentially we just solve for y or solve for x. It's the same kind of thing. So we can add 1 to both sides to get 2 over x equals 2 over y. Then we can invert this and we'll see that x over 2 equals y over 2, which means that x equals y. But that's exactly where we needed to end up to show that this was injective. So now let's show that it is not surjective. And the way to do this is to think about the horizontal asymptote of this function. Notice the horizontal asymptote will be -1. If we let x approach infinity, this thing will disappear and we'll have -1, and that's going to be the thing that is missed. So here's our claim, and that is there is no x from the real numbers minus 0 such that f of x equals -1. And how can we see that? And we can see that because, so let's do a little proof of that. So let's set f of x equal to -1 and show that we get no solution. Notice this is the same thing as 2 over x minus 1 equals -1, which is the same as 2 over x equals 0 But let's notice that 2 over x equals 0 has no solution. But that's exactly what we needed. Okay, so now let's maybe fix this and change this codomain from the real numbers to the real numbers minus -1, and now we'll show that it is surjective. So let's put an and here and we'll show that it is surjective. Okay, so the first step to showing it's surjective is to do this scratch work. Remember that scratch work is where we solve. So let's solve the equation f of a equals b for a. So let's see, that means we have 2 over a minus 1 equals b. That's the same thing as saying 2 over a equals b plus 1. But then that's the same thing as saying that a is 2 over b plus 1. Now we can see why b is not allowed to be 1. Also, that gives us a 0 in the denominator of this expression. So that would be our a. Now we're ready to show that this is surjective under these new conditions. So let's suppose that b is from the set r minus -1, and then let's set a equal to 2 over b plus 1, based off of that side calculation. Okay, now from here, let's do our final calculation. So we have f of a, so that's going to be equal to, let's see, 2 over a, but that's going to be 2 over b plus 1 minus 1. Great. But now you can simplify this. Maybe I won't go through all the details, but if you simplify all this, you'll see that you get b, but that's exactly what you need to get for surjectivity. Okay, let's do another. For our next example, we're going to consider the function which I'll call g. It goes from z2 to z2. So in other words, from 2 copies of the integers to 2 copies of the integers, z cross z. And it's defined by g evaluated at m comma n is 2m plus 3n comma m plus 2n. Now our goal is to show that this is bijective. So let's start by showing that it's injective. So let's suppose that we have m comma n, and maybe what I'll call m prime comma n prime in z2, such that g of m comma n equals g of m prime comma n prime. And what we want is for these two ordered pairs to be equal, which means both of their entries are equal to each other. In other words, m is m prime and n is n prime. Okay, so let's notice that this equation right here turns into the equation involving the outputs. So we have 2m plus 3n comma m plus 2n is equal to 2m prime plus 3n prime, and then m prime plus 2n prime. Okay, but what does it mean for ordered pairs to be equal? Well, ordered pairs are equal if and only if both entries are equal. So that means we need this entry here to be equal to this entry here. We also need this second entry to be equal to this second entry. So let's bring that down. We have 2m plus 3n must be equal to 2m prime plus 3n prime. And furthermore, m plus 2n must be equal to m prime plus 2n prime. Okay, great. But now, where would we like to go from here? Well, something that I would like to do is perhaps add these two equations with some scaling. So I think maybe our best bet is to take this second equation, multiply it by -2, and then add these two equations. Why? Because that'll cancel the m's here and the m primes here. So let's see, we'll have 2m minus 2m, that's 0. We have 3n minus 4n, so that's -n. Then the m primes cancel similarly, and then we'll have -n prime over here. But if -n equals -n prime, that means n equals n prime. Okay, great. But from here, it's a short trip to see that m and m prime are the same as well. We can perhaps take this and plug it into this first equation and do a very little bit of simplification to see that m is equal to m prime. Okay, But if m is equal to m prime and n is equal to n prime, then that means that m comma n is equal to m prime comma n prime, which is exactly what we needed to finish this proof of injectivity. Now let's show that it's surjective. Now we'll show that it's surjective. Recall that involves a little bit of a scratch calculation. So what we'd like to do is solve gm comma n equals maybe a comma b for the ordered pair m comma n. So notice that's the same thing as 2m plus 3n equals a, and then m plus 2n equals b. Just by using the definition of G, and then again the fact that ordered pairs are equal if and only if their entries are equal. Okay, but now we'll do essentially the same thing that we did before. So let's take this, multiply by -2 and add, or maybe multiply by 2 and subtract. It's the same kind of thing. So that's going to give us 2m minus 2m, which cancels, 3n minus 4n, so that's minus n, equals a minus 2b. But notice that means that n is equal to minus a plus 2b. Okay, good. And now let's swing that back into one of the earlier equations and see what that leaves us with. Perhaps we'll swing that back into this first equation. So that leaves us with 2m plus 3 times negative a plus 2b equals a. Okay, so that gives us 2m minus 3a plus 6b equals a. So we get 2m equals, let's see, moving that around, we'll have 4a and then minus 6b, which means m equals 2a minus 3b. So there we have it. We have values for m and n that will make this work. Okay, so now we're ready to write this up. So let's suppose that a comma b is in z cross z, in other words, z squared, and set m comma n equal to this thing that we calculated over here. So 2a minus 3b comma minus a plus 2b. And then observe that g evaluated at mn, well, that's going to be the same thing as g evaluated at this, so 2a minus 3b comma minus a plus 2b. But by the rule up here, we know that will be equal to 2 times 2a minus 3b plus 3 times negative a plus 2b. That's the first entry. And then the second entry is 2a minus 3b, and then plus 2 times negative a plus 2b. So that's the second entry. So just to reiterate what's going on here, because it's kind of messy, this is 2m plus 3n, and then here we have m plus 2n as needed. But now you can simplify this just doing standard calculation, and you'll see that you get AB in the end, which is exactly what we need. We found this, what's called a pre-image for the element AB. Okay, let's maybe do one more quick one and then I'll leave you with some warm-ups. For our last function, we'll call it h, and it goes from z cross z to q, and it's defined by h of mn equals m over the absolute value of n plus 1. And our goal is to show that this thing is surjective but not injective. Okay, let's show that it's surjective. These are actually pretty quick, and we don't actually need to do a bunch of side calculation here because we can kind of guess and check our way to it. So let's suppose that we have a over b in q. So we know that every element of the rational numbers can be written as a over b, where a and b are integers, but b is not equal to 0. And now let's observe that h evaluated at a comma, let's see, b minus 1 will give us a over the absolute value of b minus 1 plus 1. But that's going to end up giving us a over b. But notice this doesn't quite work if b is negative, so we might as well choose b to be bigger than or equal to 1. And you might say, well, how do we know we can do that? Well, every rational number can be written with a natural number denominator, so that's totally fine. And now everything works out perfectly. Okay, so now let's show that this thing is not injective, and we can do this by counterexample. So let's first note that h of, let's see, 2 comma 0 is equal to 2 over 0 plus 1, which is the number 2. But I think we can maybe hack this together. Notice that h of 4 comma 1 is equal to 4 over 1 plus 1, which is also equal to the number 2. So we have two elements that are not the same. 2 comma 0 is not equal to 4 comma 1, but they evaluate to the same number via the function. So this means it is not injective. Okay, let's leave you with some warm-ups. So here are 3 nice problems to practice what we've seen today. So let's consider the function f from z to z squared, or z cross z. Let's define it by f of n equals n minus 3 comma 3n plus 2. Notice the output needs to be in z cross z, so it has 2 components. Then next, with proof, decide if f is injective and or surjective. So for our next one, let's consider the function g. It goes from r minus 3 to r minus 2, and it's defined by g of x equals 2x plus 1 over x plus 3. Let's show that is indeed bijective. And finally, let's define a function h from z cross z, in other words, z squared to z, defined by h of mn equals 3m plus 5n. And you can show that that is surjective but not injective. And that's a good place to stop. This is the 19th video in a series devoted to introductory proofwriting. In the last video, we looked at the basics of functions, including injective and surjective functions.
We going strong.
And now we want to look at compositions of functions, inverse functions, and some other things. Okay, so let's get started. So let's say we're given functions f, which goes from a to b, and g, which goes from b to c. Then we can define a new function, which is called g composed with f, and this is the notation. And it goes from a to c, and it's defined as follows. So g composed with f of x is the same thing as g of f of x. So in other words, we apply the function f to x, and then that result is applied by the function g. So notice x is an element of a. When we plug it into f, we get an element of b. And then when we plug that into g, we get an element of c. So that's how this works. Here's also a nice diagram. So f is like an arrow going from a to b. G is like an arrow going from b to c. And then the composition is like your shortcut. So it's an arrow from a all the way to c. Okay, let's look at a really basic example that comes from like the definition of a function as a subset of the cross product. So let's consider the set A, which has lowercase a, b, c, d, the set B, which has the numbers 1, 2, 3, 4, 5, and the set C, which has w, x, y, and z. And then we'll define a function f. Notice that under this setup, f goes from a to b, and it's the following ordered pairs. So a comma 3, b comma 2, c comma 1, and d comma 3.
That's crazy, bro.
And then we've got a function g, and notice that by the way we have this set up, it's a function from b to c. So it has 1w, 2x, 3z, 4z, and then 5w. Okay, and now we'd like to write the composition as a set. So let's get to it. So let's say we have our set A here, so we can put it out as a diagram as these points A, B, C, and D. Then we have our set B here, which is like just the points 1, 2, 3, 4, 5. And then finally our set C, which is W, X, Y, and Z. Okay, and now maybe this blue arrow will be what F does to assign elements of A to elements of B. So notice it takes A to 3, so that gives us this sort of assignment here. It takes B to the number 2, so that would be that sort of arrow. It takes C to the number 1, so that would be an arrow like that. And then finally it takes D to 3. So let's notice it misses 4 and 5, but that's totally okay. And then let's say in this magenta color, we'll outline the action of G. So G takes 1 to W, so that would be like an arrow right across. It takes 2 to X, 3 to Z, 4 also to Z, and then 5 up to Y. So it does that sort of action. And now let's take this and write down G composed with F as a set. So hopefully this shouldn't be too bad. Maybe we'll cut out the middle on these in green and trace what happens to the elements of A, B, and C. So notice that this element of A goes to
9
3,
hours, Jesus
and then
Christ.
all the way down to Z. So what that tells us is that G composed with F of A is Z, which means we have the ordered pair A, comma, Z in this set. Okay, now what about B? So B is going to loop up here through 2 and then straight across to Z. So we start at B, we end at X. Sorry, I should have said X. So that tells us the ordered pair B, comma, X is an element of our function. Okay, then what about C? Well, C loops up here to 1 and then straight across to W. So that tells us that in the end, under this composition, C is sent to W. That gives us the ordered pair C, comma, W in this composition. Then we have one more to check, and notice that takes D up to 3, but then 3 branches down back to Z. So that means D gets sent to Z in the end. So we have D, comma, Z is our last ordered pair. And that would be a full set description of this composition of functions. Okay, so now let's do some more familiar examples. So our next example will involve some functions that are familiar from calculus class. So they're both functions of real numbers to real numbers. The first one, which we'll call f, sends x to x times e to the x. So let's notice that under the notation that we used last time, that would be equivalent to writing it as x gets mapped to x e to the x, and we could put an f up here, just to be familiar with all of the different notations of how to describe assignment. And then g takes x to x squared plus 3x. So we could write that as x gets sent to x squared plus 3x via the function g. And now since the domain and the codomain are the same, we can compose these in any order we want. So let's do that. So let's first calculate g composed with f. So that will be g of f of x, but that will be g with f of x inside, so that's x times e to the x. But g is telling us to square something, multiply it by 3, and then add those together. So that gives us x squared e to the 2x. That's what we get for squaring it. Of course, we're using standard exponential rules there. And then plus 3x e to the x. Okay, nice. And now let's do the composition in the other order. We have f composed with g of x. So that's f of g of x. So that'll be what? F evaluated at x squared plus 3x, but that ends up being x squared plus 3x times e to the x squared plus 3x. But I guess maybe the quickest takeaway here is that these are not equal. So notice that f composed with g and g composed with f are not equal to each other. And that is hopefully fairly familiar from like a calculus class. But what we get here is that the composition of functions is not commutative. Well, in fact, if we don't have the right sets chosen, then one direction doesn't even make any sense. Okay, another thing that I'll just state right now, but I won't prove, you can find the proof in the book of proof, which I'm using as a textbook for this course, is that the composition of functions is associative. The proof is pretty straightforward, and I don't think it's really illuminating in any way. So now let's move on to how injective and surjective functions behave under this composition. So for this theorem, we want to suppose that f is a function from a to b and g is a function from b to c, just like our setup over here for defining composition. Furthermore, we'll assume that they are both injective, and then we'll show that their composition is injective. But we'll also show that if they are both surjective, then their composition is also surjective. So this is really two proofs in one. So let's prove the injectivity proof. So let's suppose that f and g are injective, and that we have x and y in the domain of g composed with f, so that will be in A, such that when we apply g composed with f to x, we get the same thing as applying g composed with f to y. And what we'd like to do is see that this leads to having x equals y. Recall that that was our standard outline for proving something was injective. Okay, so let's see how we can do that. So notice that this tells us via the definition of composition that g of f of x is equal to g of f of y. But now we'll use the fact that g is injective to say that f of x is equal to f of y. Remember, that's the definition of injectivity. So let's write that down. So since g is injective, we have f of x equals f of y. Great. But now we'll just do the same thing with f. So now since f is injective, we have x equals y. But that's exactly all we needed to do to show that the composition was injective. So let's maybe look at our beginning step and our ending step. So we had an x and a y in A, such that g of f of x was equal to g of f of y. And then we did a calculation, including using the fact that g and f were both injective, and we landed at x equals y. And recall that that was exactly the way to prove something was injective. Okay, so now let's flip this around and show the surjectivity statement is also true. So in other words, what we'd like to do is suppose that f and g are surjective, and somehow get that f composed with g, or g composed with f, I should say, is also surjective. But remember, that means we need to take something in the codomain of g composed with f and find a preimage for it. Okay, so let's do that. So let's suppose f and g are surjective, and little c is an element of capital C. So we need to take something from capital C because g composed with f goes from A to C. So our end game will be to find a lowercase a in A that gets mapped to C under this composition. Okay, so now let's apply the surjectivity of our component functions. Okay, so since g is surjective, we have some little b in B such that g of little b equals C. So that's exactly the definition of surjectivity applied to g, which we are assuming is surjective. And now we'll do that again, applying the definition of surjectivity of f. So since f is surjective, we have a little a in A such that f of little a is equal to b. And now we're essentially home free. We can just make the following observation, that g composed with f evaluated at this little a is exactly equal to g of f of a, but that's g of b. But remember that b was chosen just so that it gets mapped to C under g. So that's exactly what we needed to do. So what did we do? We took an arbitrary C in the codomain, and via the definition of surjectivity and the properties of the given functions, we found an A in the domain such that that A gets mapped to that C under our composition of functions. But that's exactly what we need in order for this composition to be surjective. Okay, so now that we've done this, let's look at inverse functions. So hand in hand with the notion of a composition of functions is the notion of an inverse function. So let's build up towards that definition. We'll need something called the identity function first. So given any set x, so that's a capital X, the identity function, which we'll write as I sub x, goes from x to x. And what does it do? Well, essentially it doesn't do anything. So it takes every element to itself. So this is a lowercase x here being mapped to itself. And that's true for all little x in x. Okay, that's cool. Then, given a bijective function f going from a to b, we say that this function g going from b to a is its inverse if two things are satisfied. G composed with f is the identity on a. So notice if we compose it in that order, we'll go from a to a.
A to A.
And then F composed with G is the identity on B. So if we compose it in that order, we go from B to B. And then I should point out here that under this setting, we have a special name for G, and that is the inverse of F. So we'll write it as F inverse like this. And there's a bit of stuff that we're skipping here, like how do we know that having a bijective function means that we have an inverse and stuff like that, but I think that's okay for now. Okay, so now let's look at the following example. So we've got F, which goes from the real numbers -1 to the real numbers -2. And it takes x to 2x plus 1 over x minus 1. So I won't check this as bijective. We checked that a function very similar to this was bijective earlier. So what we'll just do is find its inverse. And we're going to find its inverse using the standard like pre-calculus method. Okay, so let's set y equal to 2x plus 1 over x minus 1, and then we'll swap x and y, so that'll give us x equals 2y plus 1 over over y minus 1, and now we'll solve for y. So let's see, that's going to give us x times y minus x equals 2y plus 1. Now we'd like to gather all the y's on one side of the equation. That gives us xy minus 2y equals x plus 1. Now we can factor a y out of the left-hand side. That leaves us with y times the quantity x minus 2 equals x plus 1, which tells us that y equals x plus 1 over x minus 2. And then finally, that's what we assign to F inverse. So F inverse of x is equal to x plus 1 over x minus 2. And notice it has the correct domain and codomain.
Okay,
its domain is definitely all real numbers except for 2, and then its codomain is definitely all real numbers except for 1. And in fact, that's its range as well.
So true, so true.
And then you can check here that if you compose f with f inverse, you get the identity function.
Okay.
So that's good. Let's look at another example. For our next example, we'll take the function g from z squared to z squared. So that's z cross z to itself. And we'll say that it takes an ordered pair m comma n to the ordered pair 2m plus n comma 5m plus 3n. We could do this by brute force, but I think we're going to assume that most people have seen linear algebra and use a trick here. It's not really much of a trick. So what we'll do is change our notation. And instead of writing these as ordered pairs, we'll write them as two-dimensional vectors. So that means we have g evaluated at the vector mn gives us the vector 2m plus n, 5m plus 3n. But this action over here looks exactly like multiplication by a 2 by 2 matrix. And what is that 2 by 2 matrix? Well, we can deconstruct it fairly easily. So this 2m plus n tells us that we should have a 2 here and a 1 here. And then this 5m plus 3n tells us we should have a 5 here and a 3 here. Now, if you want to, we can check that everything works, but as you'll see, it will work. And by check, I mean we're going to multiply this matrix that we found, 2, 1, 5, 3, into mn and make sure we get the right output.
I can do that.
But let's see, swiveling this 2, 1 into mn gives us 2m plus n. Here using like standard matrix vector multiplication, then swiveling this 5, 3 into the mn gives us 5m plus 3n as needed. So this all checks out. So now in order to find the inverse of this function, all we have to do is find the inverse matrix. So let's do that.
Okay.
So we want 2, 1, 5, 3 inverse. So how do we do that? Well, it's 1 over the determinant, so 1 over AD minus BC. So 2 times 3 minus 5 times 1. And then we'll swap the diagonals, 3, 2. And then we'll negate the off diagonal, so -1, -5. So something like that. But now let's notice that this number right here is exactly 1 over 1, which is the number 1, which tells us that our inverse is simply this matrix 3, -1, -5, 2. And I actually chose those numbers nicely because if we had gotten a fraction here, then this would not have been bijective in the integers, and we would not have been able to invert this in the integers. So it's important that we got integer entries this whole way. Okay, so now we could like put this back into our original notation and say that gm inverse of mn is equal to, let's see, it'll be 3m minus n, comma, minus 5m plus 2n.
Okay.
Just putting everything back in order. And this will be the inverse. And now you can check that these are inverses, but I'll leave that to you. Okay, now we're gonna look at the notion of an image and a pre-image. So let's suppose we have a function f which goes from a set A to a set B. Then if we have a subset X of A, the image of X under A, but generally we don't write that if the context is known. So the image of X is, well, we'll denote it by f evaluated at the whole set. So we read that as f of X, or the image of X. So it's going to be everything of the form f of little x as X goes through all of capital X. Now let's quickly notice that the image of X is a subset of the codomain B. In fact, it's a subset of the range. Next, if we take Y to be an element of the codomain B, the pre-image of Y, which we'll denote by f inverse of Y, or just say the words pre-image of Y, it'll be the set of all X in A such that f of X is an element of Y. Now let's notice that f inverse of Y, or the pre-image of Y, is a subset of A, so that's important. The image is a subset of the codomain, while as the pre-image is a subset of the domain. Okay, let's look at an example. Let's say we've got the set A, which contains lowercase a, b, c, d, e, and a set B, which contains the numbers 1, 2, 3, 4, 5. And then our function f is defined by the following ordered pairs: a, 1, b, 3, c, 1, d, 4, and e, 2. So let's find the image of a certain set. So let's find the image of the set containing a, b, and c. So that'll be 1 because f of a is 1, and then 3 because f of b is 3, but then f of c is also 1, but we already have that listed, so that doesn't add to our set. Okay, that's cool. Now what about f of the whole set A? So this would be like the image of the entire function, or the range of the entire function. So let's work through a, b, c, d, and e. So a gets sent to 1, let's see, b gets sent to 3, D gets sent to 4, and E gets sent to 2. So in the end, we get 1, 2, 3, 4. So that's not quite the whole codomain, but that is the range because it's the image of the domain. Okay, so now what about the pre-image of the set containing 1 and 2? So let's see what that'll leave us with. So we want to look for everything that gets mapped to 1. So A gets mapped to 1 and C also gets mapped to 1. So we get A, C. Those are the things that are mapped to 1. And then what is mapped to 2? Well, E is the only thing that's mapped to 2, so we get E. Okay, great. Now let's look at one more. Let's look at the pre-image of the singleton 5. But let's notice that nothing gets mapped to the number 5, so this just gives us the empty set. Okay, let's look at another example. For our next example, let's consider the function g. It goes from r to r, and it's defined to be the sine function. Okay, so let's see what we have. Let's do the image of the following set. Let's say it's everything of the form n times pi over 2 as n runs through all integers. Okay, so what do we know about this? Well, if n is an even integer, then we get a multiple of pi. But sine of a multiple of pi is 0. So we know that this set contains the number 0. But then if n is equal to 1, we get pi over 2. But sine of pi over 2 is 1, so we're good to go there. Then if n is equal to -1, we get sine of negative pi over 2. But sine of negative pi over 2 is -1. So those will be the 3 numbers that we get. And I guess maybe you could argue that those are the only 3 numbers, but I think we'll leave it at that. Now let's look at the pre-image of something. So let's take the pre-image of the set containing the square root of 2 over 2 and negative the square root of 2 over 2. So let's notice that this will be everything of the form pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4, so on and so forth. But let's notice that those are everything that is pi over 4 away from something that is n pi over 2. So we can actually write that set as follows. It's going to look like pi over 4 plus n times pi over 2 as n ranges through all integers. So we'll get something like that. Now we could do some other pre-images as well if we wanted to. Like what if we did the pre-image of the interval from 0 up to 1, maybe not including 0, but including 1. So this is a bit trickier, but notice that sine of 0 is 0, so we could include the point 0, or we'll start an interval at 0. And then sine of pi over 2 is 1, so this takes us up to pi over 2. So we'll have something like that. But then we'll union this with a bunch of other things that look fairly similar, and that's based off the periodicity of sine. So let's see, we'll union this with, maybe the next one will be 2 pi to 5 pi over 2. Notice that's 2 pi plus pi over 2. And then we'll get something back here as well, which is like negative 2 pi, and then negative 2 pi plus pi over 2, which I think is negative 3 pi over 2. So we get something of that form. And then we'll union those infinitely in both directions.
Wow.
But in fact, I think we could write that's a while.
That's
setup.
Quite far away, actually.
Maybe it would be the union as we work over all integers n of 2 times n times pi, and then 2 times n times pi plus pi over 2. I think that would be a nice way of writing that pre-image. And in fact, in order to make this a little bit more interesting, let's exchange this interval from 0 to 1 to the interval from 0 to infinity. And notice nothing changes. And that's because sine is never larger than 1. So adding all of those numbers larger than 1 doesn't allow you to get anything else out of the domain when taking this pre-image. So I'm going to end with the statement of a pretty important theorem, and we'll prove parts of it before leaving you with some warm-up. So the following is a classic theorem. We'll prove 2 parts of it, but it also makes for some really important classic
40
exercises
minutes.
that are somewhat of a rite of passage when going through a class like this. So let's say we've got a function f from a to b. We have 2 subsets of a, which are w and x, 2 subsets of b, which are y and z. Then the following 6 containments or equalities of sets hold. So the image of w intersect x is a subset of the image of w intersect the image of x. Then the image of the union of w and x is equal to the union of the images. Then next, x is a subset of the pre-image of the image of x. So that's how you would read that properly. Then notice the pre-image acts very nicely. In fact, the intersection and the union distribute with giving you equalities there. So in fact, with union and intersection, the pre-image is almost more natural than the image. And then we also have this statement. The image of the pre-image of y is a subset of y. Okay, so let's see which one of these we should do. So let's maybe do this one first, and then we'll do one more. So let's see, how do we want to do this? Well, with double set containment. So let's suppose that little x is an element of the pre-image of y intersect z. But what does it mean to be in the pre-image? Well, that means if you apply f to little x, you land in y intersect z. That's exactly what it means to be in the pre-image. But what does it mean to be in the intersection? It means that you're in both of those sets. So f of x must be in y, and f of x must be an element of z as well. But where do we go from there? Well, if f of x is in y, that means that x is in the pre-image of y. That's by the definition of the pre-image. And then if f of x is in z, that means that x is in the pre-image of z. So again, that's by the definition of the pre-image. So what have we shown so far? We've shown that the pre-image of y intersect z is a subset of the pre-image of y intersected with the pre-image of z. And what's left is to show the other containment. But I'm actually going to leave that as an exercise because it goes very, very similarly. Okay, let's do one more. So maybe for our next one, we'll prove this last statement here. So this is a single containment, so we only have to do one thing. So let's maybe suppose that little y is an element of f inverse, the image of the pre-image of y. Okay, so let's decompose this a little bit at a time. What does it mean to be in the image? Well, by the definition over here, that tells us that y equals f of little x for some little x in this inside set. But that inside set is inside f inverse of y, or the pre-image of y. But what does it mean to be in the pre-image of y? So being in the pre-image of y means f of x is in y. Again, that's what it means to be in the pre-image of y. But now we can just put these two equations together, so this equation and this equation, and we have it. So since f of x is equal to y, we have y is in y. But look at what we've done. We started here with y in the left-hand side, and we ended with y in the right-hand side. But that's exactly what it takes to prove this subset relationship. Okay, so now I've got some warm-ups for you. So here are 3 nice warm-up problems to practice what we've seen. So the first is to define 2 functions from integers to integers, which we'll call f and g by the following piecewise rules.
Sure,
so
mate.
f of n is 2n minus 1 if n
Totally
is
got
bigger
this.
than or equal to 0, and 2n if n is less than 0. And then g of n is n plus 1 if n is even, and 3n if n is odd. And then you'd like to determine the composition of f with g and g with f. So I know at least one of these can be simplified quite a bit into something nice. So for the second one, let's define this function f from r to the open interval from 0 to infinity by f of x equals e to the x cubed plus 1. So let's show that f is bijective and find its inverse. Finally, we've got a counting problem. So we'd like to determine how many functions we have from the set a, b, c, d, e, f to the set 1, 2, 3, 4, 5, 6 with the property that the cardinality of the pre-image of the singleton 5 is equal to 3. So that means there are 3 elements from the domain that get mapped to 5. And if you're not in the course that I'm teaching, then you might want to prove the rest of those statements from that theorem. If you are in the course that I'm teaching, well, you'll likely do those for part of your homework. And that's a good place to stop. This is the 20th video in a series devoted to introductory proofwriting. And today we're going to do proofs that might come from an advanced calculus class, or maybe the very beginning of a real analysis class. And I think this is kind of a new thing, introducing these types of proofs into introductory proofwriting classes. The standard for a long time was to focus on proofs that came from number theory or other types of discrete math, whereas these come from continuous math. So I think that's a really good idea because it gives you a more holistic view of the types of mathematical proofs that you are going to see in upcoming courses. Okay, so today we're going to be focusing on the precise definition of a limit. So it's possible you saw this in an introductory calculus class, maybe like differential calculus or calculus 1, but not everyone covers this in that sort of class. Okay, so let's suppose that f is a function from a subset x to r, where x is a subset of the real numbers, and a is an element of x, so a is a real number. Then we say that the limit as x approaches a of f of x equals L, and use this standard notation, if the following statement holds. So let's read this and then parse out what it means. So we have, for every epsilon bigger than 0, there is a delta bigger than 0, such that if x minus a is less than delta, then f of x minus L is less than epsilon. So some authors write this as sort of a challenge. So you challenge someone by giving them a very, very small number epsilon, and they stand up to that challenge and give you a number delta. So that
I'm not going to understand a single fucking thing for the next 40 minutes.
F of x is within epsilon of L. So in other words, this is kind of saying that if x is very, very close to a, then f of x is very, very close to L. But it's doing it in a more precise way. So here's a picture of what's going on. Let's say this green is the graph of a function. So it's like the graph y equals f of x. And then we have our point down here, a, and then our L here, which will be our eventual limit. So the given epsilon tells you to essentially make this epsilon band around this horizontal line L. So notice up here we have L plus epsilon, and down here we have L minus epsilon. And then this existence of a delta tells us that we can get close enough to A so that the graph is always within this epsilon band for the inputs that are, like I said, close enough to A. So notice that's what we have here detailed. So look at our little rectangle, which is from A minus delta to A plus delta, and then L minus epsilon to L plus epsilon. And our graph is totally within that rectangle. And so that would be like a graphical representation of this happening. So we could squeeze these two epsilon bands together, and that will cause these delta bands to squeeze closer to A. So that's the sequence of events. The epsilons get squeezed first, and they cause the deltas to squeeze. Okay, so we're going to need three like standard lemmas in order to look at some of the proofs that we'll look at eventually. And they're all versions of this triangle inequality. And so let's look at the most basic version first. So I'll call this a lemma. It's the triangle inequality. It says if x and y are real numbers, then the absolute value of x plus y is less than or equal to the absolute value of x plus the absolute value of y. In the real numbers, this is not so obvious why it's called the triangle inequality, but in R2 it is, because this is the difference between going along two legs of a triangle versus just taking the shortcut. Okay, so let's see how this might work. We'll start with the right-hand side. So we've got absolute value x plus absolute value y, and we will square it. So that'll give us the absolute value of x quantity squared plus 2 times the absolute value of x times the absolute value of y plus the absolute value of y squared. Okay, nice. But now notice that the absolute value of x squared and the absolute value of y squared is the same thing as just x squared and y squared, given that we're in the real numbers here.
Real numbers.
Also, the absolute value of x times the absolute value of y is bigger than or equal to x times y. So that's how we build in our inequality. This is bigger than or equal to x squared plus 2xy plus y squared. So again, we like make the inequality by dropping the absolute values. This to this is equality. This to this is equality, but here to here, these middle two terms are inequality. But now we can factor this. This will be x plus y squared. But squaring something and taking the absolute value and then squaring are the same thing in the real numbers. So this is equal to the absolute value of x plus y squared. But let's notice we've got a positive number squared, a positive number squared. That means we can take the square root and the order remains. So taking the square root, we have the absolute value of x plus y over here, and then bringing down the inequality in the correct direction, we'll have the absolute value of x plus the absolute value of y, but that's where we need it to end. Okay, so now let's look at our two other versions of the triangle inequality. So the next version of the triangle inequality we'll look at is sometimes known as the reverse triangle inequality. And it involves subtraction instead of addition. It says that if we have real numbers x and y, then the absolute value of the absolute value of x minus the absolute value of y is less than or equal to the absolute value of x minus y. So we'll start with our normal triangle inequality, so our initial triangle inequality. And I'm going to rewrite this with u and v. So we have the absolute value of u plus v is less than or equal to absolute value of u plus absolute value of v. And then what we'll do from here is evaluate this for different values of u and v to produce things that look like our goal inequality. Okay, so let's start with u equals x minus y, and then v equals y. Let's note that immediately that tells us that u plus v is equal to x, just by simple calculation. So plugging this into our triangle inequality, which we proved on the previous board, gives us the following inequality. So x plus y is x, like I said, and we have that's less than or equal to the absolute value of x minus y plus the absolute value of y. So we have something like that. Okay, good. Now let's move this around so it starts to look like what we have over here. So moving this absolute value of y to the other side of the inequality gives us absolute value of x minus absolute value of y is less than or equal to absolute value of x minus y. Okay, let's put a box around that because we will hold that for just a bit. Okay, now we'll take our original inequality and evaluate it somewhere else. Well, it's at a pretty similar place.
Yeah.
Let's take u to be equal to y minus x, and we'll take v to be equal to x. So immediately we see in this case, u plus v is equal to y. So what does that do for us? So we have u plus v in absolute values on the left-hand side. Like I said, that's y in absolute values. So we have absolute value of y is less than or equal to. So we'll have u, which is absolute value of y minus x, plus v, which was absolute value of x. So something like that. Okay. But now let's move some things around here and see what we get. So here we'll have absolute value of y minus absolute value of x is less than or equal to absolute value of x minus y, where I took the opportunity to change the order of subtraction from y minus x to x minus y, given that I'm inside of absolute values. So that's not really a problem. Now let's put the green and the blue box together and see what we have. So reading this green one off just as is, we won't change that, but we will change this blue box a little bit just to make it work a little bit better with our final goal. Notice that this is equivalent to saying negative absolute value of x minus absolute value of y is less than or equal to absolute value of x minus y. And now let's put a green box around this one because it's playing a similar role to the one above. But notice that these two inequalities are equivalent to the compound inequality that we want. So in other words, these two put together say that we have absolute value of x minus absolute value of y, all in absolute values, is less than or equal to absolute value of x minus y, which is where we wanted to end up with this reverse triangle inequality. Okay, now let's look at another version. Here we've got another version of the triangle inequality, which will follow very, very quickly from the original triangle inequality. So we have absolute value of x minus y is less than or equal to absolute value of x plus absolute value of y. Okay, so let's get going on this. Like I said, this will be very quick. We have absolute value of x minus y is equal to absolute value of x plus negative y. But now we'll apply the normal triangle inequality to that. That will be less than or equal to the absolute value of x plus the absolute value of negative y. But the absolute value of negative y is clearly just the absolute value of y, and that takes us home. Okay, so now let's do some examples of showing limits have certain values using our precise definition. Now we're going to do some examples where we show certain limits have certain values using our precise definition. And this is going to involve a scratch work. So we're going to do scratch work, and then during our actual proof, we'll essentially be writing our scratch work in reverse. So I think this is the standard way to approach this.
Definitely.
And this scratch work first method is fairly similar to what you did when you proved a function was surjective. Okay, so let's show that the limit as x goes to 2 of 3x minus 1 equals 5. So that value should be somewhat familiar from a calculus class. Yeah. Okay, so now let's do our scratch work, which means we're going to start at the end. We will start with this condition right here, f of x minus L is less than epsilon, and we'll work back towards this condition, x minus a is less than delta, and delta should depend on epsilon. Okay, so let's get to it. So we want the absolute value of 3x minus 1 minus 5, like I said, to be less than epsilon. Great. And then just looking ahead, down here at the end, we should have the absolute value of x minus 2 less than something. And that something is exactly what we will call delta. Great. And how do we know it's x minus 2? Well, because we're having x approach 2. And how do we know it's 3x minus 1 minus 5? Because 3x minus 1 is playing the role of f of x, and 5 is playing the role of L. So in this case, there's not much to it. This will be quite quick. Let's simplify this inequality right here, or maybe the interior of the absolute value, giving us the absolute value of 3x minus 6 is less than epsilon. But notice that we can factor a 3 out of that, leaving us with 3 times the absolute value of x minus 2 is less than epsilon. So clearly we use the fact there that the absolute value of 3 is 3. And then finally, we can divide 3 on both sides and we'll get epsilon over 3. And so that will be our choice of delta. And now we're ready for the proof of this limit value. So let's see it in action. So generally you start with the following language. Given epsilon bigger than 0, let's take delta to be equal to epsilon over 3. So this is the challenge. Given some arbitrary epsilon bigger than 0, we can find a delta situated in a way that will make everything work out. Okay, and then where do we go from here? So next up, let's notice that after we take this arbitrary epsilon and pick a delta, we have a conditional statement, an if-then statement. So that means we need to prove that using standard rules from proving conditional statements. So we will suppose that x minus a is less than delta and show that that leads to f of x minus l is less than epsilon. Okay, so let's do that. Let's suppose that absolute value of x minus 2 is less than delta, but delta is equal to epsilon over 3. But let's notice that that immediately leads to 3 times the absolute value of x minus 2 is less than epsilon, which immediately leads to the absolute value of 3x minus 6 is less than epsilon, which in turn leads to the absolute value of 3x minus 1 minus 5 is less than epsilon. And that's exactly where we needed to end up. Okay, so now let's do another example. For our next example, we'll show that the limit as x goes to 3 of 2x squared equals 18. So let's take our approach that we did before, starting with our scratch work. So we would like the absolute value of 2x squared minus 18 to be less than epsilon. And recall, we want to root this out until we have an x minus 3 term. So let's try to get there. So we can divide a 2 out of this, giving us 2 times the absolute value of x squared minus 9 is less than epsilon. Then maybe do a couple steps at once. This factors into x minus 3 times x plus 3. I can write both of those in absolute values. Okay, and then dividing by 2, we have that's less than epsilon over 2. But now we look at that and we see we have this extra term. And this extra term in this case is this x plus 3 term. So we'd like to somehow take care of that, like maybe bound that above and below by something. Okay, so how can we do that? Well, let's do like a little bit of wishful thinking. So if the absolute value of x minus 3 is less than 1, so in other words, if delta is at least 1 or smaller, which it probably is because we're taking an epsilon to be very small, then we have the following inequality. This will simplify down to -1 is less than x minus 3 is less than 1. That's how compound inequalities arise out of absolute value inequalities. But this is the same thing as what? 2 is less than x, which is less than 4, but we want x plus 3. Notice this means that 5 is less than x plus 3, which is less than, let's see, add 3, we have 7. But now taking the absolute value here doesn't really do anything. Notice this means that the absolute value of x plus 3 is less than 7. Okay, but now plugging this into our inequality that kind of gave us a little bit of pause and then bringing it down leaves us with the absolute value of x minus 3 times 7 is less than epsilon over 2, which means the absolute value of x minus 3 is less than epsilon over 14. So that tells us that should probably be our delta, but notice our delta should also be less than 1 based off of this. So the real problem is how to encode that in our solution. So let's maybe see how we might do that. So let's say we are given an epsilon bigger than 0. Let's take delta to be equal to the minimum of the following two numbers.
Sure.
Well, one number will be 1, and the other number will be epsilon over 14. So you could have a crazy person give you an epsilon of like 20, and then 1 will be smaller. But likely epsilon is super small, like 1 over a million or something. So the 1 doesn't really matter. But that being said, this is the precise way of going about this. Okay, so now where can we go from here? Well, keeping in mind what we did over here, we're going to need a bound for x plus 3. So let's get that bound for x plus 3 first. Now let's see that if we suppose that the absolute value of x minus 3 is less than delta, then that means, first of all, that the absolute value of x minus 3 is less than 1. But then bringing that all out, that tells us that x is between, like we saw over there, 2 and 4. But that means that x plus 3 is between 2 and 7, which means the absolute value of x plus 3 is less than 7. And now with this setup, we're ready to finish it off. So let's maybe put observe or something like that.
I am observing, Michael.
2x squared minus 18
I'm watching.
Is the same thing as 2 times the absolute value of x minus 3, and then times the absolute value of x plus 3. But now we can put in our inequality right here. And maybe we should change what we have up here to say, notice that x minus 3 is less than 1, and absolute value of x minus 3 is less than epsilon over 14. That's what we get out of this minimum statement, and we'll use each of those. So just to reiterate, we use this less than 1 to derive this inequality for absolute value x plus 3, and we're about to use the epsilon over 14 here. Okay, so now let's use our inequality. So now this is less than 2 times, so we already determined that absolute value of x minus 3 is less than epsilon over 14, so I can put an epsilon over 14 here. And then we know absolute value of x plus 3 is less than 7 from this line here, so times 7 here, but that all turns into epsilon. So in the end, we have absolute value of 2x squared minus 18 is less than epsilon, which was needed. Okay, let's do one more before we prove some standard results involving limits. So for our last example, before we prove some general results, we'll show that the limit as x goes to 9 of the square root of x equals 3. So again, let's do our scratch work first. Okay, so we will need the absolute value of the square root of x minus 3 to be less than epsilon. And let's look at where we should finish off. Well, we should finish off down here with the absolute value of x minus 9 is less than something. And that something is what we will eventually call delta. So now how can we build absolute value of square root of x minus 3 to absolute value of x minus 9?
Okay.
Well, in this case,
how do I do that?
Multiply by something.
Please tell me.
So what will we multiply by? Well, I think the square root of x plus 3 is a good choice, just based off of difference of squares factorization.
Yeah, that is so
true,
true,
And of course,
man.
we don't really need this
So
absolute
true,
value
man.
because that's always positive.
That
but
is
let's
so
just put them
true,
in there
man.
to
Oh
be
my
safe.
god.
Okay, so multiplying both sides of this inequality by this term
Okay.
will give us absolute value of x minus 9 on the left-hand side, because square root of x squared is x.
Yeah.
And then on the right-hand side, we will have
I know that one, mate.
times
Even I know
the
that
absolute
one.
value
Not
of
that-
square root
not
of
that
x
difficult, mate.
plus 3. And now we need to bound this square root of x plus 3. And I think we can do that the same way as we did before, but I'm going to need a little bit more room, so let's get rid of this, just keeping in mind that's where we're going. So let's play the game of wishful thinking, and let's say what would happen if the absolute value of x minus 9 was less than 1. Well, that means that x is between 8 and 10. But then if we take the square root of x, we'll see that the square root of x is between the square root of 8 and the square root of 10. But that's a little bit gnarly to work with. So perhaps we'll like round each of them to their closest like perfect square. So this is less than the square root of 16, which is 4, and this is larger than the square root of 4, which is 2. So deleting out the middle, we have 2 is less than the square root of x, which is less than 4. Now we can add 3 to all parts of this, and we'll see that 5 is less than the square root of x plus 3, which is less than 7. But in this case, since our absolute value of x plus 3 lives in the numerator of the calculation, we're actually going to need to bound it below. So let's take
Ay,
that.
caramba,
The absolute
man.
value of the square root of x plus 3 is bigger than 5. And that gives us motivation to take delta to be equal to 5 times
so
epsilon.
much motivation.
Not epsilon over 5. Again, because things are happening in the numerator instead of in the denominator like in the previous case.
Okay.
And now we're ready to write down our final solution. So let's say we are given epsilon bigger than 0. Let's take delta to be equal to the minimum of 1 and 5 times epsilon. And first, we will derive this inequality. First, if the absolute value of x minus 9 is less than delta, then in turn, it's less than or equal to 1, which leads to the absolute value of x plus 3 bigger than 5 by that calculation we did over there. And now we're ready to finish this thing off. So let's maybe write it in a slightly different order just for some variety. So let's maybe say, note the following calculation. We have 5 epsilon.
5 epsilon.
Is bigger than or equal to delta, since delta is the minimum of these two.
Isn't epsilon the other way?
Delta is bigger than the absolute value of x minus 9, but that's equal to the absolute value of the square root of x minus 3 times the absolute value of the square root of x plus 3 by factorization. But now that in turn is bigger than 5 times the absolute value of x minus 3 by this inequality right here, which we derived over on the scratch work. But now, I just had my epsilon backwards, but now reading this
I thought so.
and dividing by 5, we get exactly what we need. This leads to the absolute value of the square root of x minus 3 is less than epsilon, which is exactly what we need for this limit to have the following value. Okay, so now let's prove some more general results. For our main result, we'll prove standard limit rules that you learned in calculus. So let's suppose the limit as x goes to a of f of x is L, and the limit as x goes to a of g of x is M. So in other words, the two limits exist. Then we will show the following 4 statements hold. So first, the limit as x goes to a of c times f of x is c times L. So where c is a constant multiple. I haven't written that here, but let's assume c is a constant, so a real number. So in other words, we can essentially factor this c out. Then next, we'll show the sum rule. So the limit of the sum of two functions is equal to the sum of the limits. Next, the product rule. So the limit of the product of two functions is equal to the product of the limits. And finally, the quotient rule. The limit of the quotient of two functions is equal to the quotient of the limits. Of course, there, we need that bottom limit is not equal to 0. Okay, so let's get going with this first statement. So let's say we are given epsilon bigger than 0, and we'll first use this epsilon along with the fact that our limit of f of x is L in this case. So let's take delta bigger than 0.
Delta interface.
Delta minus a is less than delta.
Oh my god, that is a Geometry Dash reference. Oh my god.
But it's less than epsilon over c. So something like that.
Okay.
And now we're ready to essentially finish this thing off. So let's note
you so much, Michael.
that our final goal is the absolute value of c times f of x minus c times L, which we can factor a c out of, giving us f of x minus L. But recall that we built this to be less than epsilon over c, so this is less than c times epsilon over c, which is equal to epsilon. I guess I should state here that c is not just a constant, but it's a non-zero constant for this to work. I'll let you think about the case what happens when c is the 0 constant. Okay, so let's see, did we do it? Yes, given an epsilon bigger than 0, we found a delta out of our original assumption so that this difference here was less than epsilon as needed. Okay, let's move on to our second statement. Now for our second statement. So again, let's say we are given epsilon bigger than 0. Let's take delta 1 and delta 2 bigger than 0 such that if absolute value of x minus a is less than delta 1, then the absolute value of f of x minus L is less than epsilon over 2. Okay, so we can do that because of this limit which was given. And then also, absolute value of x minus a less than delta 2 should imply that the absolute value of g of x minus m is also less than epsilon over 2. Great. And now we're ready to finish this thing off. Well, we have to find our final delta. So let's take delta to be equal to the minimum of delta 1 and delta 2, and note the following calculation finishes it off. So the absolute value of f of x plus g of x minus L plus m by the triangle inequality separates out into the absolute value of f of x minus L plus the absolute value of g of x minus m. So just to reiterate, there we use the triangle inequality after moving some things around here, but we did use the triangle inequality there. But notice now we want to apply this rule up here, but we need to include a statement here, which I forgot. If absolute value of x minus a is less than delta. So if it's less than delta, then it's less than both delta 1 and delta 2, which means that this object right here is less than epsilon over 2 plus epsilon over 2, which is equal to epsilon. So that finishes this proof off. Okay, now let's do our product rule proof. Okay, so now for our product rule, which is a bit trickier. So let's see how that goes. So let's say we are given epsilon bigger than 0. Let's take the following 3 deltas. So let's look at these. So our first delta will be chosen as follows. So delta 1 bigger than 0 such that if x minus a is less than delta 1, then, which I'll write as an implication, we have absolute value of g of x minus m is less than 1. Okay, well that may not seem super helpful, but let's see where that leads us. So that'll lead us to m minus 1 is less than g of x, which is less than m plus 1. So that's pretty easy to unravel this absolute value inequality to this compound inequality. But retrieving an absolute value back into this, we'll see that this means the absolute value of g of x is less than the absolute value of m plus 1. Okay, great. So that's how we choose our delta 1 so that this occurs. But the real takeaway here is that we actually chose this delta 1 so that this inequality over here happened. Okay, now we'll choose our delta 2 and our delta 3 a little bit more like we did before. All right. So let's take delta 2 bigger than 0 such that x minus a less than delta 2 in absolute values implies f of x minus L less than not epsilon over 2, but epsilon over 2 times this object. So 2 times absolute value of m plus 1. And now we'll choose delta 3 kind of in concert with this, but with the function g of x. So delta 3 will be chosen such that the absolute value of x minus 3 less than delta 3 implies absolute value of g of x minus m is less than epsilon over 2 times the absolute value of L plus 1 in this case. And notice by our construction, those denominators are never 0, so that's okay. Now, finally, let's set our delta to be equal to the minimum of delta 1, delta 2, and delta 3. And then we're ready to finish this thing off. So if absolute value of x minus a is less than delta, then that means it's less than or equal to delta 1, delta 2, and delta 3. So that's good. And now we can see that in this case, the absolute value of f of x times g of x minus L times m simplifies as follows. So we'll start by adding a version of 0 in there. And that version of 0 will be L times g of x. So this is equal to the absolute value of f of x times g of x minus L times g of x plus L times g of x minus L times m, like that, in absolute values. But now we can see that we've got a common g of x factor here, and we have a common L factor here. And then we can use the triangle inequality to take those into 2 absolute values. So that's going to say that this is less than the absolute value of g of x times, let's see, the absolute value of f of x minus L
sure thing, man.
is
Sure
going to be
thing.
left over after pulling that g of x out.
None of this is real,
and then
man.
We'll have plus the absolute value of L after pulling that out, and then times the absolute value of g of x minus m is
I'm being 100% serious.
But now
None of
let's
this is
notice that
real.
the absolute value of g
You
of
cannot
x
convince me any of
less
this is real
than
anymore.
absolute value of m plus L. So that'll cancel this f of x minus L's denominator down to epsilon over 2. And then we'll have an L times epsilon, so plus absolute value of L times epsilon over 2 times absolute value of L plus 1.
Okay.
So that occurs from this last
Good
term.
things, good things.
But notice that this L plus 1 and this L will cancel that down to epsilon over 2 with the correct inequality, giving us this whole thing is less than epsilon over 2 plus epsilon over 2, which is epsilon. And that finishes this whole thing off. Okay, so now let's do our quotient rule. Now let's work on our quotient rule, the last thing that we need. But we're going to prove a specialized version of this. We'll prove the case when f of x is equal to 1. So we'll prove the limit as x goes to a of 1 over g of x is in fact equal to 1 over m if m is not equal to 0. But that combined with number 2 would give us, but that combined with the product rule would give us exactly what we wanted there. Okay, so let's do that. Well, maybe we'll put a box around this to show that this is actually what we are proving. So let's say we're given epsilon bigger than 0. Let's take the following deltas. So let's take delta 1 bigger than 0. That makes the following happen. And that is that if x minus a is less than delta 1, then we have absolute value of g of x minus m is less than the absolute value of m over 2. Okay, so again, that's possible. We're just taking our epsilon to be absolute value of m over 2 in that case. But now let's see where that takes us. So we have the absolute value of g of x minus m is, using one of those triangle inequalities, will be bigger than or equal to the absolute value of m minus the absolute value of g of x. But then this can be pinned on the left by absolute value of m over 2. So now putting those two things together, we'll see that the absolute value of g of x is bigger than the absolute value of m over 2. So again, that's from those two portions right there.
Most certainly.
But we're going to need something involving 1 over the absolute value of g of x. So let's notice that 1 over the absolute value of g of x is less than 2 over the absolute value of m. But we don't actually need it like this. We need it in one other version, which I'll summarize
of course
up
we
here.
do.
And
Of course we
is
do.
1 over
how would I be so silly to not spot that one?
Of g of x is less than 2 over absolute value of m quantity squared. Okay, good. Now I'm going to get rid of this, and then we'll talk about our delta 2 choice and finish this up. Okay, now we're ready to talk about our delta 2 choice. So we'll choose delta 2 bigger than 0 such that x minus a is less than delta 2 implies the following. And you'll see all of this come together. So we'll have absolute value of g of x minus m is less than epsilon times the absolute value of m squared over 2. And that's motivated by this inequality that we built before. Okay, so now we're ready to finish it off. So let's set delta equal to the minimum of these two, delta 1 and delta 2, and observe that if the absolute value of x minus a is less than delta, then the following calculation holds. So the absolute value of 1 over g of x minus 1 over m turns into
still going strong 10 hours later
minus m over m times g of x just by finding a common denominator. But then we can split these absolute values
1.1 will do.
We get the absolute
I don't
value
fucking
of g
come
of
up
x
too close and then
minus
just
m in the numerator over
it's not
the absolute
peaking at
value
all
of
somehow.
m times the absolute value of g of x in the
Peek,
denominator. But now we can apply our two deltas. So delta 1 will give us this inequality, and delta 2 will give us this inequality. So this is less than 2 times epsilon times absolute value of m squared over 2 times absolute value of m squared when putting it all together, but that's equal to epsilon. And that finishes off this last case. So now I'll leave you with some warm-up. So here are 3 nice warm-up problems based off the precise definition of the limit. So you'll use that precise definition to prove the limit as x goes to 4 of 2x plus 1 is 9, limit as x goes to -3 of x squared minus 2 is 7, and finally, limit as x goes to 2 of 2x minus 1 over 3x plus 4 is 3 over 10. And that's a good place to stop. This is the 21st video in a series on introductory proofwriting.
No.
And today we're going to look at basic
more
proofs involving sequences and
calculus.
series.
No
So
more
let's
proofs from
start with what it
calculus.
means for a sequence to converge. And so maybe before that, even
I'm
we
gonna
should
go
just recall that a
piss.
sequence is a list of numbers. So like 1, 3, 5, 7, 9, that's a sequence. And that's the list of all odd numbers. So that would be the sequence of all odd natural numbers. But we generally write sequences with indices. So like A1, A2, A3, A4, A5, so on and so forth. And then we package all that up into the following notation. So a sequence, which we'll write curly braces A sub n, converges to L, and in that case we will write the limit as n goes to infinity of A sub n equals L if for every epsilon bigger than 0 there is a natural number n such that if little n is larger than capital N, then the absolute value of A sub n minus L is less than epsilon. So what this means is that we can always make the terms of our sequence very, very close to the limit of the sequence if we look far enough into the sequence. So here's a picture of that happening. So let's say here's our limit L. I've put my epsilon bound around L, and I've put my n here. And notice my sequence is in this magenta chalk, and once we get past this capital N, we're always within our epsilon band. And the idea is that you can squeeze this epsilon band closer to L, and that will push this capital N further out. But you can always find a capital N where after that point, you're always within epsilon of your limit. Okay, so now that we've looked at that precise definition, let's show that a few sequences have certain limits using this precise definition. So let's maybe first consider the following
We are
sequence,
so
which is of
ready
the
to
form
finish this.
3n plus 1 over 2n plus 4. And then I'm going to introduce some more notation. Sometimes you write here that n goes from 0 or maybe 1 to infinity. There could be a different starting point though. Okay, so let's write the first couple of terms of this. So if we plug in n equals 1, we will have 3 plus 1, which is 4 in the numerator, and then in the denominator we'll have 2 plus 4, which is 6. So we have 4 over 6. So that can pretty
4 over
clearly
6, that's
be
2/3.
simplified, but we won't simplify it.
What?
If we plug in n equals 2, we will have 7 over, let's see, plugging 2 in here, we'll have 8. Good. Then if we plug in n equals 3, we'll have 9 plus 1, which is 10, over 6 plus 4, which is also 10. Okay.
What?
Then you can see this goes on and on and on. Great. And now probably from calculus, you know that the limit here should be the ratio of the leading coefficients. So it should be 3 over 2, and that's what we'll show.
Oh wait, hold on, yeah.
So let's maybe
yeah.
do that in the form of a claim.
I have actually
So let's make our
seen that
claim,
before.
which is the limit as n goes to infinity of 3n plus 1 over 2n plus 4 is in fact equal to 3 over 2. And if you recall how we proved certain limits had values in our previous video when we talked about functions, there was a bit of scratch work to do to get ourselves set up. And in fact, in this case, there's also a bit of scratch work to do in order to get ourselves set up. This is kind of like solving the problem in reverse and then rewriting it in the forward direction. Okay, so let's start with where we want to end up, which is 3n plus 1 over 2n plus 4 minus 3 halves is less than epsilon. Of course, that's within an absolute value. So that's the nth term of our sequence minus the would-be limit of our sequence. But now we probably want to simplify what's going on in the absolute value. We can do that by finding a common denominator. The denominator on this left-hand term is already even, so we only have to build up the denominator on the right-hand term. And we'll do that by multiplying by n plus 2 over n plus 2. That gives us 3n plus 1 over 2n plus 4, just bringing that down, minus 3n plus 6 over 2n plus 4, like that. We want that to be less than epsilon. But let's see, that's going to simplify to 5 over 2n plus 4 is less than epsilon. But now we can start doing a little bit of simplification, and notice that 5 over 2n plus 4 is itself less than 5 over 2 times 1 over n. And that's just from dropping the plus 4 in the denominator, which makes our whole thing larger. So if we can pin that smaller than epsilon, then we're good to go. But notice that means 1 over n is less than 2 over 5 epsilon. Maybe 2 epsilon over 5, which is the same thing as saying n is bigger than 5 over 2 epsilon. And this 5 over 2 epsilon is what we will take for our capital N. Okay, so now we're set up to write our proof in the proper order. Okay, so let's say we're given an epsilon bigger than 0. Let's take our capital N, which is a natural number, so that capital N is larger than 5 over 2 times epsilon. We can't really take it to be equal to 5 over 2 times epsilon because this may not be a natural number. But by the Archimedean principle, we know that for any real number, we can find a natural number larger than that real number. Okay, and now looking over here at the definition, we need to prove this conditional. So if little n is bigger than capital N, then a sub n minus L is less than epsilon. This is our a sub n minus L less than epsilon in our case. Okay, so let's get to it. So let's suppose that little n is bigger than capital N, and then make the following calculation. So we'll have the absolute value of 3n plus 1 over 2n plus 4 minus 3 over 2, which is equal to the absolute value of 5 over 2n plus 4 by the calculation that we did over there. But that is less than 5 halves times 1 over n. We can drop the absolute value because everything in there is positive at this point. And the inequality comes from the fact that we made the denominator smaller. But now since lowercase n is bigger than uppercase n, we know this whole thing is less than 5 over 2 times 1 over capital N. But since capital N is larger than 5 over 2 epsilon, it means 1 over capital N is smaller than 2 over 5 epsilon. So we have this is less than 5 over 2 times 2 over 5 epsilon.
Wow.
But now those two cancel, giving us epsilon. So let's see. Have we done it? Yes. We said if n is larger than this capital N, then our a sub n minus L is less than epsilon. So that means we've proven this claim. Okay, let's do another. For our next example, we'll show that the limit as n goes to infinity of n over n squared plus 1 is equal to 0. And we'll do this with our scratch calculation and then final draft approach. Okay, so for our scratch calculation, we'll look at our goal, which is to show the absolute value of n over n squared plus 1 is less than epsilon. But notice all of the terms here are bigger than 0, so this is equivalent to saying n over n squared plus 1 is less than epsilon. Notice it looks like I'm not subtracting the limit, but the limit is 0, so the minus L is just minus 0 in this case. Okay, now where can we go from here? Well, we'll do a similar trick as we did in the last board, and that is we'll drop this plus 1, creating something larger. So in other words, we'll look at n over n squared, which is larger than n over n squared plus 1. So we made the denominator smaller, which made the entire thing larger. But notice that is 1 over n, and if we can get this less than epsilon, then our thing is also less than epsilon. But in fact, we can make that less than epsilon fairly easily just by picking n to be bigger than 1 over epsilon. So that'll be our choice for capital N, or our choice that we want our capital N to be larger than. Okay, so now I think we're ready to write down this proof. So let's say we're given some epsilon bigger than 0. Let's take our natural number capital N so that capital N is larger than 1 over epsilon. But now that means that 1 over capital N is less than epsilon. Okay, now we're ready to finish this thing off. So let's suppose that little n is bigger than capital N and observe that the absolute value of n over n squared plus 1 is equal to n over n squared plus 1, because we don't really need the absolute value, but that is less than n over n squared, because we've made the denominator smaller, thus making the whole thing larger. But that's equal to 1 over n, but that is less than 1 over capital N, given that little n is bigger than capital N. But that is in turn less than epsilon by this observation that we made up here, which was born out of the way that we chose our capital N in the first place. So let's see. We started with an n larger than this capital N, and we ended with our term minus its limit is less than epsilon, which is exactly what we needed to prove that this limit was 0. Okay, let's look at a different type of limit. Now we'll look at a different type of a limit where the limit maybe does not converge, but it diverges to infinity. So let's say we're given a sequence a sub n. We say that the limit as n goes to infinity of a sub n equals infinity if for every real number capital M, there is a capital N, which is a natural number, such that if little n is bigger than n, then a sub n is bigger than m. So instead of trying to get the terms of the sequence close to some limiting value, we want to drive the terms of the sequence as large as we can. So you think about this capital M as a very large number, and we can always achieve a tail of this sequence, which is always over that large number. Okay, so let's look at a couple of examples. So let's maybe start with a fairly simple example, which is the sequence 2 to the n, so powers of 2. So let's notice that this is 2, 4, 8, 16, 32, so on and so forth.
Oh, yeah,
so that
those.
pretty clearly diverges to infinity, or it has a limit which is infinity. But let's maybe check that. So we'll do this with a scratch work and then forward direction proof, just like before. So let's lay out our scratch work. So what we want is for 2 to the little n to be bigger than some real number m. So I think one way to do this would to be as follows. Notice if we take capital N bigger than m, then 2 to the n is always bigger than n. So if you put something in an exponent, you'll always get something larger than what's in the base. But that is bigger than m. So maybe something like this works, but this is really just like some scratch work, right? And that really kind of tells us the need for the following lemma. So the lemma would be something like this.
Oh yeah, the lemma.
So maybe for all n, which are natural numbers, we have 2 to the n is larger than n. I think something like this might help us out. Okay, so now let's go over here and prove that lemma using induction, and then we can apply the proof of that lemma or apply the result of that lemma to our final goal. Okay, so let's say lemma for all natural numbers n, we have 2 to the n is larger than n. Okay, so like I said, we're gonna do this by induction, which means we'll first need our base case. So our base case is the n equals 1 case, that's the smallest natural number, and it holds pretty clearly in this case. So we have 2 to the 1 is equal to 2, which is bigger than 1. So we're good to go there. And now let's make an induction hypothesis. So let's suppose for some k bigger than or equal to 1, we have 2 to the k is bigger than k. So something like that. And then let's consider the next case. So we'll consider the 2 to the k plus 1 case. Okay, but now notice that 2 to the k plus 1 is equal to 2 times 2 to the k. But that is larger than 2 times k by the induction hypothesis. But 2 times k is equal to k plus k, just by the definition of multiplication. But then, since k is bigger than or equal to 1, we know this is bigger than or equal to k plus 1, just replacing one of those k's with 1. But now we have proved our induction step. Notice we have 2 to the k plus 1 is larger than k plus 1. So that finishes this proof. And now we're ready to prove that this sequence in fact diverges to infinity. But let's maybe do that in the place of this proof right here. Now that we've got our lemma, we're ready to prove our claim. So let's say we are given some real number, which we assume to be quite large, but it's not written that it's quite large. So we've got a real number m. Now let's take a natural number, which we'll call n, such that that natural number is bigger than our real number. So this is always possible by the Archimedean principle. And now suppose that our lowercase n is bigger than our uppercase n, and notice that 2 to the n is larger than n by the Archimedean principle.
Yeah.
But that's larger than our capital N by this assumption right here. But that's larger than our capital M by our setup here.
Yes.
So in the end, we've pushed 2 to the n larger than m, which, if you look carefully at the definition over here, is exactly what we need to do to show this limit is infinity. Okay, let's do a related problem. Next up, we'll look at the sequence 2 to the n over n. And probably from a calculus class, you know that this should also diverge to infinity. And that's because the denominator is acting like a polynomial, whereas the numerator is acting like an exponential function. And exponential functions always grow faster, or they always win. But how would we show this? I think maybe to show this super carefully using the tools that we have, we could start with the following lemma, which says for all n bigger than or equal to 2, 2 to the n is bigger than or equal to n squared. But if 2 to the n is bigger than or equal to n squared, then that'll nicely interact with the denominator that we have here. So that's a sketch of where we would go with this. Okay, now let's prove this with induction. Notice our base case will be the first case satisfied, which is n equals 2 here. So if we plug in n equals 2, we get 2 to the 2, which is equal to 2 to the 2. Great. So that's really all there is to that. Now let's make an induction hypothesis and then prove our induction step. So let's suppose for some k bigger than or equal to 2, we have 2 to the k is bigger than or equal to k squared. And then we'll consider the next case. So, and consider, like I said, the next case, which is 2 to the k plus 1. So let's notice that that is equal to 2 times 2 to the k. But now we can apply our induction hypothesis to take care of this 2 to the k. So this is bigger than or equal to 2 times k squared. Okay. But then we can rewrite this as k squared plus k squared. And then from here, you might need another little bit of an inequality, which I'll leave as a homework lemma. And that says that this is bigger than or equal to k squared plus 2k plus 1. And so let's just sketch out what's needed for that. And that is to show that k squared is bigger than or equal to 2k plus 1. Which is definitely true after a point. Okay, so that would maybe be something to add into this to like clear up all of the gaps. But now k squared plus 2k plus 1 is equal to k plus 1 squared. So we in fact have 2 to the k plus 1 is bigger than or equal to k plus 1 squared as needed to finish this induction proof. Okay, so now let's prove that this sequence in fact diverges infinitely. Now we're ready to finish this example off. So let's say we are given some m, which is a real number. Now let's take some natural number n such that capital N is larger than this real number m. So again, always possible by the Archimedean principle. And now we'll suppose that lowercase n is bigger than capital N and observe that this essentially takes us home. So we have 2 to the little n over n is bigger than or equal to little n squared over little n by our lemma, which is equal to little n, which is bigger than capital N, which is bigger than capital M, as needed. So that's what finishes this proof off. Okay, now let's look a bit at series. Now we're going to look a very little bit at series. So let's recall that the series, which can be written as the sum as n goes from 1 to infinity of a sub n, converges to s if the sequence of partial sums also converges to S. Let's recall the sequence of partial sums, which we'll denote by S sub n, is equal to A1 plus A2 all the way up to AN. So I think it's aptly named sequence of partial sums. Let's also recall that if the limit of the sequence of partial sums either does not exist or is plus or minus infinity, then we say that this series diverges. Okay, so let's look at a couple of examples, starting with the sum of 1 over 2 to the n. Okay, so let's look at a couple of cases of the sequence of partial sums to get an idea for what's going on here. So notice that S sub 1 is simply 1/2. That's the first
That's
term.
crazy, bro.
S2
Then we're going to have
is equal
a quarter.
to 1/2 plus 1/4, which is equal to 3/4. S3 is equal to 1/2 plus 1/4 plus 1/8.
7/8.
But that's 3/4 plus 1/8. But that's 6/8 plus 1/8, which is 7 over 8.
Brother.
And then maybe S4 you can calculate to be 15 over 16.
Just 2 to the n minus 1.
So notice the denominators are always powers of 2, and the numerators are 1 less than those powers of 2.
Yes, there you go.
So that maybe brings us to the following claim, which would be S sub n, which is equal to 1/2 plus 1/4 plus all the way up to 1 over 2 to the n is equal to 2 to the n minus 1 over 2 to the n. Okay.
There you go.
And now let's
figured it
prove
out.
this by induction.
Oh,
But if we can prove this by induction, then we're probably done, and that's because we can rewrite this as 1 minus 1 over 2 to the n, which has a limit which is equal to 1, which maybe we won't show, but you would show that exactly the same as we showed these other limits are equal to 1. So anyway, let's, like I said, prove this by induction. Notice the base case is done by our preparatory calculation. So let's make an induction hypothesis and prove the induction step. So let's suppose for k bigger than or equal to 1, we have S sub k is equal to 1 minus 1 over 2 to the k, as we've calculated up here and surmised. Okay, now next, let's consider the next partial sum, which is S sub k plus 1. But notice that's exactly equal to S sub k plus 1 over 2 to the k plus 1. And that's because in general, a sub k plus 1 is all that you need to add to the kth partial sum to get to the k plus first partial sum. Now we'll apply our induction hypothesis to get 1 minus 1 over 2 to the k plus 1 over 2 to the k plus 1. Okay, but now we can simplify this pretty easily by giving ourselves a common denominator. We can add 1 here if we multiply by 2 here. And then if we subtract those, we get 1 minus 1 over 2 to the k plus 1 just as needed. And that proves the closed form of the sequence of partial sums in order to prove that this is in fact equal to 1, because the limit of the partial sums is equal to 1. You would have to prove that carefully with the epsilon n definition of the limit of the sequence like we've been doing, but I'll maybe leave that as a little bit of a homework exercise. It follows very similarly to the other examples we did. Okay, let's do another. For our next example, we'll look at the sum as n goes from 1 to infinity of 1 over n squared plus n. And here we're going to take motivation from calculus, where we did partial fraction decomposition. And let's take this 1 over n squared plus n, and note that we can rewrite it 1 over n minus 1 over n plus 1. So if we give those things a common denominator, we'll see that that works exactly. And now let's write our nth partial sum. So notice S sub n will be the first term, so that'll be 1 minus 1/2 plus the second term, which is 1/2 minus 1/3, plus the third term, which is 1/3 minus 1/4, all the way up to the nth term, which by our decomposition is that thing over there. So this is 1 over n minus 1 over n plus 1. But notice there's a lot of cancellation here. We get this half cancels this half, this third cancels this third, this quarter will cancel this quarter, all the way down to this 1 over n will be canceled by something before it, leaving us with 1 minus 1 over n plus 1. But perhaps we would really want to prove this carefully with induction. So let's see how we would lay that out. So let's make our claim that S sub n is 1 minus 1 over n plus 1 in this case. So notice that our base case will be the n equals 1 case here, which will be just 1 over 2, which is equal to 1 minus 1/2. And now let's make an induction hypothesis. So let's suppose for some k bigger than or equal to 1, we have S sub k is equal to 1 minus 1 over k plus 1, and let's consider the next term. So S sub k plus 1 will be S sub k plus the k plus first term, but we'll take this format for the k plus first term.
Ain't no way.
So this will be 1 over
format?
k plus 1
What?
minus 1 over k plus 2. But now we can use our induction hypothesis to rewrite this S sub k as 1 minus 1 over k plus 1.
Oh, okay.
And we'll see that these 1 over k plus 1s cancel, and we're left with exactly what we need, which is 1 minus 1 over k plus 2. So that establishes this closed form here. But now all we have to do is take the limit of this sequence of partial sums. Again, proving that carefully using our epsilon n method, we'll see that this goes to the number 1. So that means the value of this series is 1. Okay, let's look at one more series. Now we're going to look at a famous series known as the harmonic series. So that's the sum of terms 1 over n, the sum of reciprocals of natural numbers. So in other words, this is like 1 plus half plus third plus quarter plus ... And maybe surprisingly, we'll show that this diverges, which you probably saw in a second semester calculus class already. Okay, so let's see how to do that. Instead of taking the nth partial sum, we'll take the 2 to the nth power partial sum. So let's see, S sub, like I said, 2 to the n. So that'll be 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6 plus 1/7 plus 1/8. And like I said, ending way out here at 1 over 2 to the n. Okay, nice. And now we're going to make some replacements. So let's maybe group 1/3 and 1/4 and we'll replace 1/3 with 1/4. We'll group a 5th through an 8th, and we'll replace a 5th, a 6th, and a 7th with an 8th. And then we'll continue to do that. But making those replacements means that we have something smaller, because a 1/4 is smaller than a 1/3, and an 1/8 is smaller than a 5th, and so on and so forth. So that means our starting thing is greater than 1 plus 1/2 plus a 1/4 plus a 1/4 is a half. An 1/8 plus an 1/8 plus an 1/8 plus an 1/8 is also a half. And you'll see that we have just a bunch of strings of 1/2. But how many strings of 1/2 do we have? Well, we have exactly n copies of 1/2, and that's because we went out here to 2 to the nth power.
That is so crazy,
that's pretty clear here, because this is 2 to the 3rd power, and after 1 over 8, so going out that far, we have 3 copies of 1/2. Okay, so notice that we can put all these together and we'll get 1 plus n over 2. But now that clearly goes to infinity as n goes to infinity, which again, you can check with an mn argument like we did before. But the important thing here is that we have shown that this harmonic series is in fact divergent. So we have a divergent series. Okay, so now let's prove a general result before I leave you with some warm-ups. Now we're going to prove a result whose contrapositive is known in a calculus class as the test for divergence.
Okay.
So in particular, we'll show that if the sum as n goes from 1 to infinity of a sub n converges, then the limit of the terms equals 0. Let's recall the contrapositive says that if the limit of the terms is not 0, then our series diverges. Okay, so let's get going with the proof. So let's suppose that the sum as n goes from 1 to infinity of a sub n has a value of
Oh my god,
s.
there's a new Mr. Beast video.
And then let's also set s sub n to be the nth partial sum. So a1 plus a2 all the way up to a sub n. So we know that s sub n converges to s. So let's use that via the definition of convergence for a sequence. So let's say we're given an epsilon bigger than 0. Let's take our capital N, which is a natural number, such that if little n is bigger than capital N, then the absolute value of s sub n minus s is less than epsilon over 2. Now we'll choose epsilon over 2 for a reason which will come up. And we're allowed to do all of this because we know something about the convergence of that sequence of partial sums. Okay, so now let's observe that if little n is bigger than capital N minus 1, so that's our new capital N in this case, it's just capital N minus 1, or capital N plus 1, I should say. And that's because that means n minus 1 is larger than n, just for what it's worth. We have the following result. So let's notice the absolute value of a sub n is the same thing as the absolute value of s sub n minus s sub n minus 1. The nth partial sum minus the n minus first partial sum. Notice that's just taking all of these terms and subtracting off all but one of them. But now we'll add a version of 0 in here. This is equal to the absolute value of s sub n minus s plus s minus s sub n minus 1. Like I said, just adding a version of 0 in there. But now we can apply the triangle inequality to see that this is less than or equal to the absolute value of s sub n minus s plus the absolute value of s sub n minus 1 minus s. But since n minus 1 is larger than n, and that means that n is also larger than n, we know that each of these is strictly less than epsilon over 2 by our setup right here. But that's equal to epsilon. But that means we have our a sub n term is less than epsilon, which is exactly what we need for its limit to be 0. Okay, so now I've got some warm-ups for you. Now I've got 3 warm-up problems for you. So the first is to show using the epsilon n definition of a limit of a sequence that the limit as n goes to infinity of n minus 3 over 2n plus 5 is 1/2.
No.
Next, show via partial sums and stuff like that, that the sum as n goes from 1 to infinity of 1 over 3 to the n is equal to 1/2.
No.
So at the end of this, you'll need an epsilon n proof that the limit of the sequence of partial sums is what you want it to be. And then finally, a little bit more general of a proof, which you can adapt something from what we did in a previous video, and that is show that the limit, if the limit as n goes to infinity of a sub n is L, and the limit as n goes to infinity of b sub n is m, then the limit of the sequence built out of the sum of the terms is L plus m. And that's a good place to stop. This is the 22nd video in a series devoted to introductory proof writing. And today we want to talk about what it means for sets to be the same size. And this is even if they're not finite sets. So let's jump right into a definition.
Still going
So
strong.
we'll say that sets
Making sure
A
this shit
and
doesn't
B
freeze,
have
man.
the same cardinality, or we may say they are equinumerous if there is a bijective map between them. So we might call that bijective map F. So we've got a bijection from A to B. And then in that setting, we'll write the following maybe bit of notation. We'll say the cardinality of A is equal to the cardinality of B, or really this set with like absolute value symbols around it, but it's not really absolute value symbols. Or we might say they have equal cardinality with this notation. So notice we've got A equals with a subscript CB. So that means they have equal cardinality or they are equinumerous.
Okay.
So what's the main idea here? Well, the main idea is to count things are the same without actually counting. And just imagine that you have 6 objects. Maybe you've got 6 blue objects.
6 blue objects.
And you also have 6 magenta objects.
6 magenta objects.
But you don't know how to count past 4.
Oh, fuck.
How might you know that there are the same number of blue objects as
I can't
magenta
count
objects?
past 4.
Well, you could know that just by matching every blue object with exactly 1 magenta object. So we'll match this blue dot with this magenta dot, and so on and so forth.
I'd know to do that, Michael.
And then we've shown that there are the same number of blue dots as there are magenta dots without actually counting them. Yeah, there are 6 blue dots and 6 magenta dots, but we didn't really need to count up to 6 to show that there were the same number. All we had to do was to show that there was a 1-to-1 correspondence or a bijection from the set of blue dots to the set of magenta dots. Okay, so let's look at a little bit more of a concrete example. Let's say we have the set A, which is the set containing 0, 1, 2, 3, 4, and 5. So it has 6 elements.
I don't know how to count past 4.
And let's say we have the set B, which is the set containing 3, 5, 7, 9, 11, and 13. So another 6 elements. Notice they both have 6 elements, which means there's probably a bijection between them. And in fact, we can exhibit this bijection by the following map, which I'll call F. So it'll take n and send it to 3 plus 2n. And so even though A has 6 elements and B has 6 elements, we can show they have the same number of elements without actually counting to 6 by checking that this is indeed a bijection. Okay, now let's look at some more interesting. Now let's look at a more interesting example. So I think we can all agree that the set of natural numbers and the set of integers both have infinitely many elements. But do they have the same infinity of elements? Well, this theorem will show that they do. So we'll show that the cardinality of natural numbers is equal to the cardinality of integers.
What?
So in other words, we can find a bijection from natural numbers to integers. Now, how might we do that? Well, let's do it with a schematic first. And after we do that, we'll write down maybe a formula for this map.
And then you have the negative natural
numbers. So let's define our function f from n to
like
z
1 from
by the following
n
diagram.
Compare with 1
so
from
I'll
z
put all
and
my
negative 1
natural
from
numbers
z.
on the first row. So 1, 2, 3,
Meaning
4,
it's
5, 6,
double,
7,
pretty much.
so on and so forth. And then I'll list my integers on the second row. And I'll list them in the following order.
How the fuck does that mean?
0, 1, negative 1, 2, negative 2, 3, negative 3, so on and so forth. So I think there's a pretty clear pattern of how we're listing the integers. And so the function that we're making will map 1 to 0, 2 to 1, 3 to negative 1, 4 to 2, 5 to negative 2, 6 to 3, 7 to negative 3, and so on and so forth. Now, I think this is pretty clearly a one-to-one and onto map, in other words, a bijective map, which indeed shows that the set of natural numbers and the set of integers are equinumerous. But since we can in this case, let's write down a formula for this function. Okay, so let's notice that f of n has the following behavior. So it's pretty easy to see what it does to even numbers. It just takes half of them. So 2 gets mapped to 1, 4 gets mapped to 2, 3 to 6, that's half of each of those. So this will go to n over 2 if n is even. Then we just have to decide what happens if n is odd. And looking at it for a little bit, we'll see that it sends n to 1 minus n over 2 if n is odd. And let's check that to make sure it makes sense. So notice 1 will be sent to 1 minus 1 over 2, that's 0. 3 gets sent to 1 minus 3 over 2, that's negative 2 over 2 or negative 1. And then you can check the rest of them seem to work out as well. So this is our map. And then we could check that this is bijective, like by hand if we wanted to. So let's maybe do that for practice. We'll first show that it's injective. So let's suppose that f evaluated at m is the same thing as f evaluated at n. And then we'll break this down into 2 cases. So the first case is that f evaluated at m and thus f evaluated at n are both less than or equal to 0. Well, they're equal, so they both have to be less than or equal to 0 if one of them is. But if they're both less than or equal to 0, they must be from this output. Notice that things of this form, 1 minus n over 2, where n is a natural number, are less than or equal to 0, whereas things of this form are always strictly bigger than 0. So what does that tell us? That tells us that 1 minus n over 2 is equal to 1 minus m over 2, which leads us to m equals n. Okay, then we would need to go on to our second case. So case 2 would be f of m equals f of n, which is strictly bigger than 0. So in that case, we know that we're coming from this setup right here. So we have m over 2 equals n over 2, which again leads us to m equals n. Okay, so either way we have it, we have f of m equals f of n leads to m equals n, which means we do have injectivity. Now let's prove surjectivity. So let's say that we've got an integer and find a pre-image for that integer. So if we've got an integer b, we'll split this into two cases. So our first case is what happens if b is bigger than or equal to 1. So if b is bigger than or equal to 1, then note that f evaluated at 2b is exactly equal to b. And that's pretty clear. That's how it's going to happen from our chart up here. Notice that all positive integers are landed on by the even integers. Okay, so now what about our second case? So case number 2 is what happens if b is less than or equal to 0. So here you can note that f evaluated at 1 minus 2b is equal to b. You might be worried because 1 minus 2b seems like it may not be a natural number, and our domain is all natural numbers. But if b is less than or equal to 0, then 1 minus 2b is most definitely a natural number just by construction. So anyway, either way we have it, we have found a pre-image for our integer b. So putting these two things together, we see that f is a bijection, which really finishes off this careful proof that the natural numbers and the integers are equinumerous. Okay, let's do another. So we just finished showing that the integers and the natural numbers are equinumerous.
I still don't get that.
But now we'll show that not all infinite sets are equinumerous with each other, and we'll do that via an example. We will show that the natural numbers and the real numbers are not equinumerous. So that means there are different cardinalities for infinite sets. Okay, so how might we do this? Well, we'll do this by way of contradiction. So by way of contradiction, let's suppose that the cardinality of the natural numbers is the same thing as the cardinality of the integers. And let's say that's via some bijection, which I'll call f. And so that goes from n to r. Great. And now let's consider the decimal expansion of everything in the image of f. So I could write f of 1 as a whole number part, which I'll just write as a star. We won't need the whole number part.
Okay.
And then decimal point A11, A12, A13, A14,
yes.
so on and so forth.
Of course, my friend.
So we've got these places on the decimal double subscripted. The first subscript is which natural number they come from, and the second is their position. Okay. So that means f of 2 will look like, well, a whole number part, which we don't care about, so I'll put a star there. And then A21, A22, A23, A24, so on and so forth. Maybe we'll write one more down. F of 3 will be star dot A31, A32, A33, A34, dot, dot, dot. Okay, great. But now we'll show that this function cannot be surjective, and we'll do that by constructing something which is not in this list. So notice this list goes on and on and on, and since we're towards a contradiction, supposing it's bijective, then every real number should be on this list. But like I said, we'll find a real number that's most definitely not on this list. Okay, so let's define a number which I'll call y, which is on the open interval between 0 to 1, by the following decimal expansion. So I'll say y is equal to 0.b1, b2, b3, b4, so on and so forth. And these bn's will be defined by the following kind of decision. They'll be equal to 0 if ANN is not 0, and they're equal to 1 if ANN is equal to 0. So we go on this diagonal right here, so let's highlight this diagonal. So A11 down to A12 down to A11 down to A22 down to A33 down to A44 and so on and so forth. And we look at A11 and we decide, is it 0 or is it not 0? If it's 0, then we set b1 equal to 1. If it's non-zero, we set b1 equal to 0. And then we continue doing that. But let's notice that by doing that, we'll have the nth decimal place of y is always different than the nth decimal place of f evaluated at n. But that means that y is not the output of anything here. So let's maybe summarize that here. We have y is not equal to f of n for all natural numbers n, which means that f of n does not contain y, so it cannot be all real numbers. But that means that it's not bijective, but it not being bijective is a contradiction, contradicting our original assumption that the natural numbers and the real numbers were equinumerous. So again, let's review how we know that y is not equal to f of n for all n, which are natural numbers. That's because the first decimal digit of y is different than the first decimal digit of f of 1. So that means it can't be f of 1. The second decimal digit is different than the second decimal digit of f of 2, so it can't be f of 2. The third decimal digit is different than the third decimal digit of f of 3, so it can't be f of 3, and so on and so forth. So wrapping that all together, we have y cannot be one of these f of n's, which means f cannot be bijective. Okay, let's maybe look at some sets that are equinumerous with R. Next up, we'll show that the open interval 0 to infinity is equinumerous or has equal cardinality with the open interval from 0 to 1. And we'll construct a function that does this, but we'll use a geometric argument to start that function. Okay, so let's start with our real number line here. Let's maybe put 0 on the real number line at that spot. Maybe back here we'll put -1. And then let's put a partial real number line. Maybe what I really mean is the interval between 0 and 1 going vertically right there. Great. And then next up, we're going to need this point up here, which is the point -1, 1. So let's put that in there, -1, 1. And then let's go over here to some arbitrary x, which is between 0 and infinity. So it's on that open interval. And then let's make a line segment from x to our point -1, 1. So the line segment will look something like that.
I'll ring him up now.
And then its intersection point with this interval will be called f of x. And now notice, as x moves towards 0, f of x will also move towards 0. And then as x gets bigger and bigger and bigger and bigger, f of x will move towards the number 1. Let's maybe point this as the number 1 here. And we can also get a nice formula for f of x using similar triangles. Okay,
there
so let's
is
drop a
an
vertical
hour,
right here.
1 minute, and
has
30
length
seconds
1,
left of this video.
And then this has length f of x, obviously, and length x.
Almost done.
But from x to -1, we have length x plus 1. So let's see. We can see that 1 over x plus 1 is equal to f of x over x. Again, by similar triangles. We've got the height of this triangle and the base, the height of the smaller triangle and the base. But putting this together, we see that f of x is equal to x over x
If you think it will take you less than an hour, you can just go now.
And then you can check that this is bijective.
I'm waiting for Lon to say if we need to or not.
Previously in the
today.
course. So I'll leave that as a little bit of a homework exercise. So check this is bijective.
Oleki said that if I ever want to like go through this and just figure out stuff that I don't understand, I can just DM her and she'll explain it.
But the appearance of that bijective function means that these have equal cardinality.
Okay then.
Okay, let's move on. Now we're going to prove a very important general result that says equality of cardinality is in fact
I'm going to need at least a week before I can,
in order for it to be considered
ask her anything about this.
It must be reflexive, symmetric, and transitive. So we'll check each of these, starting with reflexivity. So this is pretty quick. Let's notice that the identity map, which is generally called I sub A, which goes from A to A and is defined by I sub A evaluated at A equals A, is a bijection. There's not really much to that. I wouldn't check that's a bijection or anything. The
there is now officially 1 hour left
a bijection.
on this video.
But the fact that that's a bijection means the cardinality of A is equal to the cardinality of A, which is exactly reflexivity for this relation. Now let's look at symmetry. So let's suppose that the cardinality of A equals the cardinality of B, and let's say via a bijection from A to B, which I'll call F. Okay, but if F is a bijection, it has an inverse. So I'll write that as, since F is bijective, there exists a unique, so there's some notation, there exists a unique inverse, which I'll call F inverse from B to A, which is also a bijection. So I think earlier we proved that a function has an inverse if and only if it's a bijection.
That is so true.
Okay,
man.
so that means F inverse
I
is
do
a
not
bijection.
remember you talking about that
but
at all.
The fact that F inverse is a bijection means the cardinality of B equals the cardinality of A. But starting here at cardinality of A equals cardinality B and ending here at cardinality B equals cardinality of A is exactly the symmetry rule for equivalence relations or for relations. Okay, now let's look at transitivity. So let's suppose that cardinality of A equals cardinality of B and cardinality of B equals cardinality of C via bijections again. So bijections,
hell yeah.
which I'll call F going from A
Started
to
having a
B
great time.
and G going from B to C. And then previously we showed that composition of bijections was a bijection. So that tells
Introduction
us
to
that
proof
G
writing, full
composed with
course.
F, which goes from A to C, is also a bijection.
Oh yeah, I don't know if I told you, but I now have Skibbity Toilet reacting as well.
Follow the definitions
He's hiding behind your face.
Injectivity and surjectivity.
He's like just.
But that means we've got
I think it's your face.
from A to C,
Did I put it behind her?
which
No,
leads us to
he's
say the
just peeking
cardinality
above
of A
your
is
face
equal
right
to
now.
the cardinality of C. But starting with these two equalities and ending with this is exactly what we need for the transitivity of this relation. So putting these three things together, the equality of cardinalities is an equivalence relation. And you might say, well, equivalence relations always come with equivalence classes. So what are the equivalence classes in this case? Well, the equivalence classes are exactly what are known as the cardinal numbers. So that's more of an
cardinal
advanced set theory
numbers.
type thing.
Something
But
that I've
for
heard
instance,
of.
The equivalence class of the cardinality of the natural
This genuinely
numbers is given
feels like
by
I'm
the
watching another
cardinal
Polish
number, which
video.
is called Aleph
Holy fuck.
0. And then there's another one for the equivalence class of the cardinality of the real numbers, and so on and so forth. So again, we're not going to talk about that so much here, but a full course in set theory would study these things in depth. Okay, let's
No, thank you. I'm not doing a full course in set
Two
theory.
more kind of important examples. The first is that the cardinality of the real numbers is equal to the cardinality of the interval from 0 to infinity. But that seems like it should follow. Notice that this interval from 0 to infinity is essentially half the real numbers. And we know that's equinumerous with 0 to 1, which is much smaller. So it seems like it should also be equinumerous with r. And we can do this with a pretty simple function. Let's consider the function g going from r to this interval from 0 to infinity defined by g of x equals e to the x, like from calculus class. So it's well known that
I can
the
turn myself
values
back up
of
now. I
that
forgot.
function
I'm
are
on minus
all
10 decibels
non-negative,
right
or I
now.
guess I should say positive real numbers. And also it's a one.
My mum was hoovering and it was really loud, and you could I could see it. I could see it on OBS.
Equality of cardinality.
So I just turned myself down to minus
Now we've got
10.
one that's a little bit more interesting, and that is
Because
the
at that
interval
point,
from
well,
0
not
to 1,
minus 10, but
not
like
including 0
almost
and
minus
not
10.
including 1, has equal cardinality to
I think
the
it was minus 10 the
closed
first
interval from
time.
0 to 1.
Then
And
she
we
started
can do this
hoovering
kind
again,
of
so
with a
I turned myself
picture.
down to minus
So
7.
let's say we've got our open interval from 0 to 1 here. Then maybe underneath we'll have our closed interval from 0 to 1. And the idea is we want to take single points out of this open interval, map them onto the endpoints, and then kind of fill in the gaps afterwards. So there's a number of different ways to do this. Maybe here's how we'll do it. Let's take the point right here, which is 1/2, and we'll map 1/2 to the number 1. And then after that, we'll take the point right here, 1/3, and we'll map that to 0. And then after that, we'll take 1/4, and we'll map that to 1/2. And then we'll take 1/5, and we'll map that to 1/3. And then we'll take 1/6, and we'll map that to 1/4.
Oh, that was
and now
the
I
cool
think you can
Harrison
kind of
alarm.
See what we're doing. So we're taking a half and a third, and we're
in case I
filling
just
in
completely
those two
forgot to call you, I
open
set an
points
alarm
into
for
closed
5:30.
points. And then we're like just kind of cascading.
I forgot about the alarm.
Then what do we do with every
But
point
remember
that's
to
not
call
of this
you.
form? Well, those just get mapped to themselves. So we could put that together as follows.
Need name
Let's define
suggestions
f
for my baby.
from
What is
0, 1
that,
to
Georgia?
Closed 0, 1 by f of x equals. So this is going to be a big piecewise function.
Be
So it'll equal
real.
1 if x
I think you know
is
it's
equal to
Georgia I'm
1/2,
on about as well.
0 if x is equal
I think
to
so.
1/3. But
Yeah,
then
so
let's
Captain
notice
did
1
need
quarter
name
gets
suggestions
mapped
for
to
my
a
baby.
half. Then 1/5 gets mapped to a third. So it'll
Can
get
you
mapped
just-
to 1
can
over
you say
n minus
Harrison?
2 if x is equal to 1 over n and n is bigger than or equal to 4. So does that work out? Well, 1 over 4 gets mapped to 1 over
Harrison,
2,
if it's a
1 over 5 gets
boy.
mapped to 1 over 3, and so on and so forth.
And
And if we're not one of those
Harrison
numbers,
at if
then it
it's a
gets mapped to
girl.
itself. So f of x is equal to x.
Actually, I'm terribly
otherwise.
sorry, but I have to
And you can
go.
check that this is
Oh,
1
for
to 1
fuck's
and onto, but by
sake.
construction, it's
do you reckon
very
you'll be
clearly
back
1 to 1
within
onto. So that shows
within
us
about
that open
50
intervals
minutes?
and corresponding
Don't know, we'll
closed
find
intervals
out.
have
Oh,
the
fuck
same
me.
cardinality.
Bye-bye.
But now
Bye-bye.
putting this together with
Fuck's
the
sake.
fact that cardinality makes an equivalence
Cheeky
relation
bastard.
tells us that all of these sets are
We still good?
the open interval
Oh,
from
yeah,
0
we're still
to
good.
infinity, the open interval from
course we're
0
still
to
good.
1,
Why would we
the
not be good?
closed interval from 0 to
Oh, yeah.
1, the
We are so
half
good.
open interval, etc. have the same
Oh my god, there's so many
So of course, we
intervals
only
and stuff.
checked some of those. We didn't check this one with the half open interval, but you could imagine that it has a pretty similar to proof to what we saw right here. You might say, well, why are we dealing with the open interval between 0 and 1? What about more generally the open interval from A to B? Well, just by scaling, you can also check that that has the same cardinality. But we'll leave that for a homework exercise. So here I've got 3 nice warm-up exercises based off what we saw. So the first is to show that the cardinality of the set of even integers is the same thing as the cardinality of the set of odd integers. Next, show that the cardinality of the set of 0, 1 cross n is the same thing as the cardinality of n.
Oh my god.
So there, that's just
Oh my
a
god.
finite set containing 2 elements, 0, 1.
Right, what's this?
And then finally
What's
show
this
the
bitch boy
cardinality of the
saying?
real numbers is the same thing as the cardinality of the set from 3 to 19. So you might actually want to use transitivity here by showing that 3 to 19 is equal in cardinality to 0, 1, and then apply a result from the video. But you could do this
Can't
in a
believe
number of different
Harrison is
ways.
gone.
And that's a good place to stop.
Oh, it's been 11 hours. Oh,
This is
No.
the 23rd
Oh,
video in
phew.
a series devoted to introductory proofwriting. And today we're going to talk about
thought
what
you-
it
I
means
thought you
for
would just
a
leave
set
me.
to be countable and
I thought Michael would
uncountable.
leave me.
Let's jump right into a definition. So we say a set A is countable if it's either
I really thought he would
finite
leave me.
or it's equinumerous with the natural numbers. That is, it has the same cardinality of the natural numbers.
It's about half and half,
If you recall
okay.
from last time, that was
I do in fact
equivalent to
recall from
having
last
a
time, of
bijection
course.
between the natural numbers and that set. Okay, and then we say that A is uncountable otherwise. In other words, there is no bijection between n, the natural numbers, and the set A, or their cardinality is not the same. Now, the cardinality of the natural numbers is an important cardinal number, if you will, and so we generally give it a name, and that name is Aleph 0. So I think my
Aleph
live
zero.
handwriting for this is not great, but it generally looks like this shape. You can Google it and get an idea for different ways of writing this down. It's the first letter of the Hebrew alphabet. And so, like I said, the cardinality of the natural numbers is Aleph 0, but we could write that as an equation as follows. Okay, so let's move on to our first big result of the day, which will help us prove a lot of associated results. And that is, a set is countable if and only if its elements can be arranged into a list. Okay, so this is an if and only if statement, which means we have 2 directions to prove. Let's prove the forward direction first. So we'll start by supposing that A is countable. But notice that breaks into 2 cases immediately. So either A is finite, so let's write that as case 1. A is finite, but in that case we can write A as its elements.
Wow.
So in other words, we have A as A1, A2, A3, all the way up to AN, where n is the cardinality of A in this case. But clearly that's a list. So we've listed the elements of A. So if A is finite, this is pretty straightforward. And so let's look at case 2, which is A is infinite, and thus the natural numbers have equal cardinality to A, and let's say that's via a bijection which I'll call F, which goes from N to A. But notice that this bijection can easily be used to build a list of the elements of A. So notice we have a list with every element from A, and that list goes like this: F evaluated at 1, F evaluated at 2, F evaluated at 3, F evaluated at 4, and so on and so forth.
Of course, my brother.
Okay, so either way we have it, via these two conditions that give us countability, either finiteness or infinitely countable, we can build a list that contains all of the elements from A. So that finishes the proof of this forward direction. And now we'll move on to the proof of the reverse direction. So let's suppose the elements of A are arranged in a list. And that list is A1, A2, all the way up to AN, and then let's keep going. So maybe I won't look at the case when this list is finite. If this list is finite, then A is clearly a finite set. But then if A is a finite set, then it's countable. So let's only look at the case where A is infinite and all of its elements are on this list. But the fact that we've got a list of all of these elements gives us a really easy way of creating a bijection between the natural numbers and the elements on our list. And the natural numbers is just defined by the order of our list.
That is so true,
So
boss
we
man.
could send the natural number 1 to A1, we could send the natural number 2 to A2, and in general, we could send the natural number n to AN. So in other words, this defines a bijection, which we'll call F, going from N to A by F evaluated at N is A sub N. But the fact that we've got a bijection from N to A is exactly what we need to have the cardinality of N equal to the cardinality of A, finishing the proof of this result. Okay, so now let's apply this result a few times. Our first main result will be to prove that the rational numbers are countable. That is, the cardinality of the natural numbers is the same as the cardinality of the rational numbers, which may seem a little bit surprising because the rational numbers seem so much bigger than the natural numbers. In fact, it seems like they should be closer to the real numbers, but they're not. They're not closer to the real numbers. In fact, they are equinumerous with the naturals, and we'll prove that here. Okay. So our strategy will be to list or create a list which contains all of the rational numbers. And then since we have that list can be used to find a bijection, which will finish it off via the result of the previous theorem. So I've started a chart here that will help us form our list. And along this first row, we'll write what will eventually become the numerator of a certain rational number. And then along the column, we'll write what will eventually become the denominator of a certain rational number. Then in the numerator, we're going to list all integers. So I'll list 0, 1, -1, 2, -2, 3, -3, so on and so forth. So I think we can all agree that that will be a list of all of the integers, kind of as we saw previously. And then down the column, I'll list all of the natural numbers. And that's because if I take the numerators to be any integer, I only need the natural numbers as denominators in order to get all of the rational numbers. Okay, so here we'll have 1, 2, 3, 4, and then so on and so forth. I think that's far enough to get an idea of what's going on. And then at the intersection of the rows and the columns, we'll form a fraction with the denominator given by whichever column we're in, or the numerator given by whichever column we're in, and the denominator given by whichever row we're in. So let's see. This will be 0 over 1, here we'll have 0 over 2, 0 over 3, 0 over 4, and so on and so forth down. So notice those are all equal to 0, which is not super interesting, but we will definitely have repeats here, which we'll take care of in the end. And then here we'll have 1 over 1, 1 over 2, 1 over 3, 1 over 4, so on and so forth. So those are all new. And then next we'll have negative 1 over 1, negative 1 over 2, negative third, negative fourth, so on and so forth. Here we have 2 over 1, 2 over 2, 2 over 3, 2 over 4, so on and so forth. Negative 2 over 1, negative 2 over 2, negative 2 over 3, negative 2 over 4, and then continuing in that direction to the right and down. Notice that we've listed some of the numbers more than once. We have 1/2 here, and we have 2 over 4 here, which is equal to 1/2. We have 1 here, and then we have 2 over 2, which is also 1 here. So once we make our list, we'll have to like exclude repeats. Now, how will we make our list? Well, the trick is to count along a diagonal. We can't count along all of the rows because we've got an infinite list here, an infinite list here. There's nowhere to stop going out that way.
That's so true.
But if we count along diagonals like this, we can make a list. So let's do that. So we'll count like this first, okay? And then after that, we'll count like this. So maybe I'll put a circle around what we keep, and then I'll go straight through what we don't keep. So we will not keep this 0 over 2 because we've already counted it. Then we won't keep this 0 over 3 because we've already counted it, but we will keep the 1 over 2 and the negative 1 over 1. So just to like be clear, this is the order that we're making our list in. So this will be the first element, the second element, the third, the fourth element, and then the fifth, sixth, and so on will come from here, here, and then trending down and right. So let's draw what's going on in this next diagonal. So we'll get a third, we'll get negative half, we'll get 2 over 1. So we'll get all of those numbers. So this will be the fifth element of the list, the sixth, and the seventh. And then let's keep going. So we'll skip the 0 over 5, which is right here. We'll get the 1 over 4. We'll get the negative 1 over 3. We will skip the 2 over 2, but we will take the negative 2 over 1.
Okay.
And that'll be the 8th, 9th, and 10th elements of our list.
Okay.
So now putting this all together, we'll see that we will form a list. And that list goes like this: 0, then the next element is 1, and then 1/2, and then negative 1, and then 1/3, and then negative half, and then 2, and then a quarter after that.
A quarter after that.
And then negative 1/3 after that,
All right.
and then negative 2 after that, and so on and so forth. So we've made a list that definitely contains rational numbers. Will it contain all rational numbers? Well, it will, because somewhere on this table is every rational number. And since we're counting through every element of this table and either keeping it or throwing it away, we'll eventually count every rational number. And that's essentially the idea of this proof that the rational numbers are countable. We do that by making a list. Notice that it would be extremely difficult to write down a formula that defines a bijection between N and Q. In fact, it's not really worth it, given that this description here without a formula is pretty clearly a bijective correspondence. And it's
very clear, man. That is
okay. So let's do another related result. Now we're going to prove a related result. And that says if A and B are both countable, then so are the sets A cross B, their Cartesian product, and A union B, their union. Okay, so let's get off the ground. So the first thing that we'll do is write A and B as lists. So we'll write A as A1, A2, A3, dot, dot, dot. So there we have a potentially infinite list there. And then we have B is the set B1, B2, B3, dot, dot, dot. So we know that we can write A and B as lists by that theorem that we started the video off with. Now that we've done that, we want to focus on the case when we're looking at A cross B, and then we'll swing around to A union B afterwards. And the case when we're looking at A cross B is very, very similar to what we did with the rational numbers. You can maybe even guess what it's going to look like by what we did with the rational numbers. So let's list everything in A along this first row and everything in B along this first column, and then we'll make diagonals just like we did before. So here's A1, A2, A3, A4, so on and so forth, going infinitely in that direction.
Wow.
And here we'll have B1, B2, B3, B4, and then infinitely down as well. And then at the intersection of the rows and the columns, we'll put our ordered pairs. So here we have A1, B1. Here we have A2, B1, A3, B1, finally A4, B1, and so on and so forth. That's what's happening in the first row. And then in the first column going down, we'll have A1, B2, then A1, B3, A1, B4, and then down with entries A1. Then we can fill out the rest similarly. So here we'll have A2, B2, and then A3, B2. And here we'll have A2, B3, and then A3, B3, and then I'll let you fill in more.
Of course, my brother.
Too.
Oh, for goodness
And now
sake.
we're going to play this same game that we did with the rational numbers to create a list. So let's go across the diagonal here to make our first entry in our list. So there's our first entry. And then we'll go across this next diagonal here to create our second and third entries in the list.
Oh yeah,
And
we
then we'll
will.
go across this diagonal here, which is right below it, to make our fourth, fifth, and sixth entries in the list. And then we'll just keep going down and down and down and down. And since every element of A cross B is in this array somewhere, and we're going through every element of A cross B and like listing them in this certain order, that means we have actually formed a list of all of the elements of A cross B.
Hell yeah, we have.
But forming a list of the elements of A cross B means that A cross B is countable. In other words, the cardinality of A cross B is the same thing as the cardinality of the natural numbers.
Okay.
Okay, so now let's look at the case when we're taking A union B. So the case for A union B is a little bit shorter. We'll just make a single list. We don't have to make an array or anything. It's just what we'll think about is shuffling the elements of A and the elements of B together. So I'll write A union B with the following notation. So we'll take A1, B1, A2, B2, A3, B3, and so on and so forth. So we alternate elements of A and elements of B. And then, well, since the union throws out duplicates, we'll just throw out duplicates whenever we need to. But the end result is that we've created a list of all of the elements of A union B, but that's exactly what was needed to show that the cardinality of A union B is the same thing as the cardinality of the natural numbers. We've found a list of the elements of A union B. Okay, so now I'd like to introduce a couple of more definitions having to do with unequal cardinalities. Now we somehow want to classify sets that do not have equal cardinality by size, and we'll do that with the following definition. So let's suppose that A and B are sets, then we define the following three notions, one of which we've defined before. So the cardinality of A equals B if and only if there's a bijection from A to B. Let's recall we also had this notation here with a equal sign and a subscript C. I'll remind you of that notation as well for these other two definitions. So we say the cardinality of A is less than or equal to the cardinality of B if and only if there is an injective map from A to B. And we have similar notation for that as well. And then we say the cardinality of A is strictly less than the cardinality of B if and only if there is an injection from A to B, but no bijection from A to B. And again, we've got like that similar notation for that notion as well. Okay, so now we're going to prove a really important theorem, and it's like a real classic one as well. And it says that if you have any set A, then the cardinality of A is strictly less than the cardinality of the power set of A.
Bigger weapons, I need more
Taking a
bullets.
power set always builds something which has a larger size. And let's see the motivation for this. Let's say that if A is finite, we know the following fact. The cardinality of the power set of it, or the cardinality of A, is most definitely less than 2 to the power cardinality of A. That's because like x is always less than 2 to the power x. But
No
that's
way.
equal to the
Real?
cardinality of the power set of A in this finite case. So
Oh,
there
that
we've
is
like
true,
made
actually.
the inequality.
Yeah, I
But
do
of
actually
course,
remember
the
that one.
finite case is not every case. We definitely have infinite sets, and that's what we want to prove here. A general proof that will include infinite sets. So the first thing that we'll do is construct an injection from A to power set of A, but then show that there is no bijection. So let's first consider the map, which I'll call G, going from A to power set of A. And what it does is it takes an element A and it sends it to the singleton A. So the singleton subset A.
Of course.
Okay, well, let's notice that this map is injective. So I won't check that. That's pretty clear that this map is injective. But the fact that this map is injective tells us that the cardinality of A is less than or equal to the cardinality of the power set of A. We just have to show that there's no bijection to finish this thing off. So now let's show that there is no bijection, and we'll do this by way of contradiction. So by way of contradiction, let's suppose that f going from A to the power set of A is a bijection. But since it's a bijection, that means it is surjective. So that's important. The real thing here is that it will fail surjectivity. Now we'd like to consider a very carefully constructed set. So let's consider this set, which I'll call B, and it's made up of all elements from A, so it's a subset of A, and those elements of A satisfy the following rule. A is not an element of f of A. So this may seem kind of crazy, but notice that what does f do? It takes elements of A and sends them to elements of the power set. But what are elements of the power set?
All of them.
They're subsets. So what f really does is it takes elements of A and it assigns them to subsets of A. But that means we can talk about an element of A being inside of its assigned subset or not. And this is how we'll define B. So it will be all A in A such that little a is an element of f of little a. Okay, so that's interesting.
Okay.
So let's note that this is most definitely a subset of A, which is the same thing as saying that B is an element of the power set of A. But now, since f is surjective, we can find a little b in A such that B equals f of little b. So it's a subset, which means it's in the power set, but this is an onto function, so we just find the pre-image of this subset. But now the real question is little b in B? And this is where we're going to
who the
run
fuck
into
knows if
a
little b's
really
in B?
interesting contradiction. So let's do this by cases. So case number 1, which is B is an element from B. If B is an element from B, by the definition of this capital B, that tells us that little b is not in f of little b. Oh, but that's a problem because f of little b equals capital B. So we have if b is in capital B, then b is not in capital B. But that's impossible. That's a contradiction. We have something happening and its negation happening at the same time. Okay, so now let's look at case number 2, which is B is not in B. Oh, but this capital B equals f of little b. So we really have B is not an element of f of little b. But that's exactly the condition to land in B, so that implies that little b is in the subset of B. But that's another contradiction. We said that B was not in capital B, and that implied that B was in capital B. So something is true and its negation is true at the same time, which is another contradiction. But those are the only two cases. Both lead to contradictions. So that means up here in our assumptions, we made an assumption that is false. And what is that assumption? Well, the assumption is the existence of this bijection from A to the power set of A.
Cool.
So that
my
means
brother.
no such bijection exists.
How dare I do such a thing?
But since no such bijection exists, we have satisfied the condition down here for the cardinality of A being strictly less than the cardinality of the power set of A. Okay, so I want to do two things before we leave. One is look at a result that's built off of this, and then also give you some warm-up exercises. So it follows from that last theorem that we proved that we have an infinite list of non-equal infinities. So we could start with the natural numbers, which is a countably infinite set, and then we could take the power set of natural numbers and create a set with cardinality, which is strictly bigger than the natural numbers. Then we could take the power set of that and create another set which is bigger than the cardinality of what we had in the previous step. Then we could continue taking the power set forever and ever and ever and create all of these infinite sets with unequal cardinalities, kind of increasing cardinalities, if you will. Now you might say, well, I know that the natural numbers lives right here. Well, is there anything maybe more common that has the cardinality of the power set of the natural numbers? And yes, in fact, the real numbers has the cardinality of the power set of the natural numbers. Then what about the power set of the power set of the natural numbers? Well, yeah, all functions from R to R, not continuous functions, but all functions from R to R has the cardinality of the power set of the natural numbers. Then you can keep going and these things get kind of more obscure. Maybe another question which is obvious to ask is, okay, I have an infinite set here, natural numbers. I have an infinite set here, which is either real numbers or power set of natural numbers. They are unequal. One is larger than the other. Is there any set in between them? In other words, can I find an infinite set whose cardinality is larger than natural numbers but smaller than real numbers? Well, that's actually unknown, and that's in fact known as the continuum hypothesis. And also, in fact, it's been proven that it's impossible to prove it true or false. And versions of set theory are consistent with it and without it. So I think that's pretty interesting in itself. Okay, so now that we've said all of this, I'll leave you with some warm-up exercises. So now I've got three nice warm-up problems based on what we saw today. The first is to consider the following set, which I'll call A. It will be all ordered pairs m comma n, where m and n are natural numbers, and m is less than or equal to n.
How we
so
doing?
let's show that's a countable
We still
set.
good. Oh my god.
Next, let's describe a partition of the integers into 5 countably infinite subsets. So you'll have to recall what a partition of a set is, but that might be a nice review. And then finally, let's prove that the set of all complex numbers is in fact uncountable. And that's a good place to stop. This is the 24th video in a series devoted to introductory proofwriting. And today we're going to look at a very powerful way to show that two sets have the same cardinality. But we need a bit of a setup first. So let's recall if we have sets A and B, we say the cardinality of A is less than or equal to the cardinality of B, if and only if there is an injective map from A to B.
Of course, brother.
So I'll use this hook arrow to mean that we have an injection from A to B. Furthermore, we would say that cardinality of B is less than or equal to cardinality of A, if and only if there was an injection from B to A. And so we know with numbers, if x is less than or equal to y and y is less than or equal to x, then x must be equal to y. So it would be nice if that were also true for cardinality. So in other words, it would be nice if the cardinality of A being less than or equal to the cardinality of B and the cardinality of B is less than or equal to the cardinality of A, then they have equal cardinality. In other words, A and B are equinumerous. But what does that really mean? That means we should be able to take an injection from A to B and another injection from B to A and construct a bijection from A to B. And that's exactly what we'll do today. And this is called the Schroeder-Bernstein theorem, or sometimes the Schroeder-Cantor-Bernstein theorem. Okay, so let's give a general idea of the construction before we look at the careful proof. So let's say this blue box over here is our set A, and it's being mapped to this red circle over here by our function f, and that is our set B. So notice all we have is that A gets mapped to B in a one-to-one method, so it's injective. So that means we may miss elements of B over here.
Ay caramba.
So we could maybe
Missing
see
elements.
the image of A inside of B like this. So this inside square right here would be f of A. Okay, nice. Then we could take the image of B inside of A under G and get a picture that's something like this. So we would have a circle in here. So remember that G is injective, it may be surjective, so it may miss things like this right here. But notice it's got this f of A inside of it. So let's draw this f of A inside right here. And let's get a handle on what these parts are. So notice that this outside bit right here is G of B. And then this inside bit right here is G of f of A. And then the idea is we keep doing this to build like this nested action.
What?
So let's maybe do one
way.
more. So applying f, that'll actually give you a copy of another red circle in here and another blue circle in here, or blue square in here. And what would those be?
No way.
So this would be f of G of B, and this right here would be f of G of f of A. And you can imagine this going on forever and ever and ever and ever and ever.
No way.
Now, what we'd like to do is somehow define this map from A to B so that it makes a choice as to which part of this like descending inclusion we are a part of. And maybe the easiest way to do that is to map all of the blue sets over here on the left to the blue sets on the right, and then map all of the red sets on the left to the red sets on the right. So let's just keep in mind that the blue set will be between this outer blue boundary and this red boundary. So this blue set that I'm shading right here should get mapped to this blue set over here that I'm shading. So for instance, a point right here would get mapped to a point right here. Okay, great. And then this red set right here should get mapped from this red set, which is right here. And you can imagine what's going on after that. So this blue square that's inside here should get mapped to this blue square inside here. And then what's going on here inside of this red circle, but outside of the blue square, will get mapped to a red circle that's inside this inner blue square. Okay, so anyway, what we'd like to do is somehow describe all of the blue sets and all of the red sets. But notice that the red sets are just a complement of the blue sets, so that shouldn't be too hard once we get the blues.
Not hard at all.
Let's notice that this outer blue set is just simply A minus G of B. Great. So that's this outer blue set. Okay, but then what's this inner blue set? Keeping in mind
brother. What is that inner blue set?
this red circle inside, and then what we get after doing this shading. So this blue set in here will be, let's see, G of f of A minus another G of B, because we have to take away what's going on right here, but what's going on right here is G of f of G of B. So let's write this down, G of f of G of B. Great. So just to reiterate, this is the outermost blue shading, and then this is the second level of blue shading. But of course we want to union them. And then we'll get another level of blue shading, which is inside of here, and that'll be constructed the same way, but we'll just have more compositions of this G of f of B. So let's see. Putting this all together, we'll get a set which I'll call U, which will be the union as n goes from 0 to infinity of the n-fold composition of G composed with F, evaluated at A minus G of B. Okay, and notice that if we set n equal to 0, we get this first set, which like I said is this outer blue region. If we set n equal to 1, we get this set here, which is maybe the next level of blue region, and then so on and so forth. Okay, so just to reiterate, those are all of the blue sets. And then after that, we'll have all of the red sets, are just simply their complement in A. So they'll be A minus U. Then we can figure out what happens to the elements by what we spoke about before. So this element right here, which I'll maybe call A, will get mapped to F of A. Okay, but then this element right here, which maybe we'll call X, will get mapped over here to the inverse image of X under G. But notice since G is injective, that's well defined, especially since X is inside the image of G in the first place. Okay, so it looks like when we're in a blue set, in other words, when we're in the set U, we will be traveling over to our set B using our function f, whereas if we're in a red set, and the red sets are labeled by V, we will be traveling from A to B with the inverse of G, which is well defined because we are inside the image of G, and G is injective. Okay, so now that we've got this kind of idea of what's going on here, let's look at the careful proof. Now we're ready to prove the main result for this video, which is, like I said, the Cantor-Schroeder-Bernstein theorem, which says if the cardinality of A is less than or equal to the cardinality of B, and the cardinality of B is less than or equal to the cardinality of A, then they have equal cardinalities. Okay, so let's do that. So let's suppose that we have our setup. So cardinality of A is less than or equal to cardinality of B. And let's say that is via an injection, which I'll call F. So I'll use this hook arrow to indicate that it's an injection. And then we'll also suppose that cardinality of B is less than or equal to cardinality of A, and that's via an injection which I'll call B, or G. And now we'll define those sets, which will be the blue and red sets that we saw on the previous board while we were getting some motivation for what's going on.
Fuck yeah, I am so motivated to be done.
Define our set U, which will be the union over all non-negative integers of the n-fold composition of G composed with F, and then evaluated at the set A minus G of the image of B. So something like that. Then we'll take V to be equal to A minus U. But that clearly sets up a disjoint union of A. So A is the disjoint union of U with V. And that's because V is defined to be the complement of U in A. Okay, now we have our sets defined. Now let's define our function. So we'll define our function h from A to B by h of x equals, so it'll be equal to f of x if x is in U, and it'll be equal to G inverse of x if x is in V. And maybe let's underscore that this is okay. And what I mean by okay, it's well defined because x is in the image of G. So that means we can apply G inverse, and G is 1-to-1. That means there's a clear single element for which this is. Okay. So now we'd like to show that H is 1-to-1 and onto. So let's first show that H is injective. Okay, so let's suppose that H of X equals H of Y. And this is going to break down into 3 cases depending on where X and Y come from.
That's crazy,
so the
bro.
first case is if X and Y are both from U. Okay, but h of x equals h of y when they both come from U boils down to f of x equals f of y, which boils down to x equals y, and that's because f itself is injective. So there's not much to do right there. Now the second case will be what happens if they both come from V. Okay, well, if they both come from V, then applying H is the same thing as applying G inverse, and we have G inverse of X equals G inverse of Y. But from here, we'll simply apply g to both sides of this equation, giving us x equals y. So we don't actually use the injectivity of y at this step, or of g at this step. What we've really done is use the injectivity of g way back here to have this function be well defined in the first place.
Okay.
Okay, so that brings us to our third case, which is what happens if x is in u and y is in v. So they come from different sets. Okay, well, that means that f of x equals g inverse of y. But now applying g to both sides, we'll get y equals g of f of x. But notice everything of the form g of f of x is inside of u by the definition of u.
Oh, it's inside
so
u.
This is in
of
u.
course
But let's
it
notice
is.
that's a contradiction.
How could I possibly be so silly and miss that one?
Simultaneously, y is in v
Ugh.
and y is in u, but those are disjoint sets, so that's impossible. So like I said, that gives us a contradiction. So based on the analysis of these three cases, H must be injective.
Cool.
Now let's move on to the surjectivity proof.
Goodbye.
We just finished showing that H is 1-to-1. In other words, H is injective. Now we'll show it's surjective. But then we'll have a bijection from A to B, which means the cardinality of A will be equal to the cardinality of B, finishing everything off.
Of course it will be.
So let's suppose we have something from the codomain. I'll call it little b. So like I said, that comes from capital B. But notice that means that g of little b must be inside of A, given the fact that G goes from B to A. But then let's recall that A is the disjoint union of U and V. So I'll put a little dot right there to show that or to indicate that we have a disjoint union. So that little dot sometimes means that U intersect V is the empty set. Again, a disjoint union. But the fact that we have a disjoint union there allows us to break ourselves into two cases. So the first case is what happens if G of B is inside of U. Okay, but that means that G of B is inside of one of the components that union up to U. So in other words, it's inside G of F composed with itself n times evaluated at A minus G of B for some n bigger than or equal to 0. So in other words, G of B equals G composed with F composed with itself n times evaluated at X for some X, which is inside of A minus G of B. And now I'd like to make a little subclaim over here that n is not allowed to be 0. So here's my subclaim that n is not allowed to be 0. Because if n is equal to 0, then that means G of B equals X. But notice that X is not inside of G of B by our assumption up here, but that's a clear contradiction because if you evaluate an element at a function, well, it will be in the image of that function. So that means that, in fact, yes, n cannot be 0. It has to be bigger than or equal to 1. But if it's bigger than or equal to 1, we can factor a copy of G composed with F off of it. So we have G composed with F composed with G composed with F to the n minus 1 evaluated at X. But now we can cancel a G from both sides, and we will have B equals F of G composed with F n minus 1 of X. Great. But now if we set this element right here equal to A, then what we have is B equals F of A for some A in A. It just turns out that the A has this complicated formula right here, which we got out of our argument above. Okay, so like I said, that's our first case when G of B is in U. Now let's look at the second, somewhat shorter case when G of B is in V. Now let's look at this second case where G of B is in V. But notice if g of b is in V, then applying h is the same thing as applying g inverse by our definition of h. So let's note that real quick. And this is going to fall out very quickly. So h of g of b is exactly equal to g inverse of g of b, which is equal to b. So there, we found a pre-image, g of little b, of our element b that we chose above, but that's exactly what we needed to do to finish this surjectivity proof. Okay, so that finishes the proof of this big theorem, and now we'll look at some example applications. So we just finished proving the Cantor-Schroeder-Bernstein theorem, which says that if you have cardinality of A is less than or equal to cardinality of B, and cardinality of B is less than or equal to cardinality of A, then the two cardinalities are equal. But in terms of functions, that means if we have an injection from A to B and an injection from B to A, then we have a bijection between these two sets.
Just look at it, bro.
And that's maybe how you want to think about it, because often it's most easy to find an injection between two sets and then not worry about finding a surjection. So like I said, injections are somewhat easier to construct than surjective maps.
5 is less than 5.
And so this Cantor-Schroeder-Bernstein theorem allows us to show two sets have equal cardinality, they're equinumerous, by just constructing injections, which, like I said, are easier to construct. Okay, so let's do an example that we have done before, and that is to show that the closed interval 0, 1 has equal cardinality with the open interval 0, 1. Okay, so let's first show that we have the inequality maybe in this direction. Open interval 0, 1 is less than or equal to in cardinality to closed interval 0, 1. And since open interval 0, 1 is a subset of closed interval 0, 1, this is quite easy. We can just use the inclusion map, which is generally written as an I, and this takes, like I said, open interval 0, 1 to closed interval 0, 1, and just it takes x to x. So this is clearly an injective map, but it being an injective map proves this cardinality condition. Okay, so now let's prove this second direction so that the cardinality of 0, 1 is less than or equal to the cardinality of open 0, 1. And maybe let's visualize what's going on with this over here. Okay, so let's look at open interval 0 to 1 on the bottom, and we'll look at closed interval 0 to 1 above. And what we'll essentially just do is we'll scale this closed interval 0, 1 until it fits inside of the open interval 0, 1. So let's scale it maybe until it moves between 1/4 and 3/4.
Wow, okay.
And that is most definitely not onto, but this example is not onto either, but it is definitely 1 to 1 if all we do is scale this a little bit. So now we've got to construct a function that does that, but that's not too difficult. So let's define f from closed 0, 1 into open 0, 1 by f of x equals, let's maybe take it equal to 1/4 plus 1/2 times x, and that'll do it exactly. So let's notice that takes the point 0 to 1/4, 1 to 3/4, and then scales everything in between, and that's clearly a 1 to 1 function, which I'll let you check. Okay, so now putting these two things together, we have our result up here that these two have equal cardinality. All right, let's now look at a little bit more of an interesting example. For our last result, we'll show that the cardinality of the real numbers is equal to the cardinality of the power set of the natural numbers. So we alluded to this result, I think, in the last video. Now we'll prove it. And we'll use the fact that the cardinality of the real numbers is the same as the cardinality of the half open interval from 0 to 1, where we include 0. And we'll do this by constructing injections. Okay. So an injection which I'll call f from 0, 1 to the power set, and then another injection which I'll call g from the power set to 0, 1. Okay, so let's see how we can construct f first. So the idea is to take an element from 0, 1 and then write it in its decimal expansion. So let's do that. So let's take x from 0 to 1 and, like I said, write it in its decimal expansion. So it can be written as 0.A1, A2, A3, A4, so on and so forth. So we have x is equal to that. And you might say, well, decimal expansion is non-unique. A trailing tail of 9s is the same thing as a trailing tail of 0s. But let's just always take a trailing tail of 0s instead of a trailing trail of 9s. So I'll maybe point that here. So we'll use 0.4 instead of 0.399 repeating. Great. So when we have a choice as to take a trailing 9s or trailing 0s, we'll take just the trailing 0s. Okay, now we'll define f evaluated at x as follows. So it'll be equal to 10 times a1, and then 100 times a2, and then 1,000 times a3, all the way up 10 to the n times a sub n, and so on and so forth. So let's look at a little bit of an example of what's going on here. So f evaluated at 0.231 will be equal to the subset 2300, 1000. And recall, we're getting subsets as outputs of f because f should take these numbers and output subsets.
So true.
So that's the right type here. And now we just need to finish this off with the claim that f is injective. But this is pretty straightforward. Let's suppose that f of 0.a1, a2, so on and so forth is equal to f of 0.b1, b2, so on and so forth.
It'd be the same.
But let's notice that this encodes the decimal points as like multiples of powers of 10, so it's really easy to see when two sets are equal. And in fact, what this means is that 10 to the n times a sub n is equal to 10 to the n times b sub n for all n. But that gives us that a sub n is equal to b sub n for all n. But that means that those two inputs were the same. So maybe if we called this input here x and this input here y, then that implies that x equals y. But that's what we need for our injectivity. Okay, so now let's construct our reverse map. Now let's construct our map G, which takes an element from a power set, in other words, a subset of natural numbers, and it gives us a number between 0 and 1. And this will kind of be in the same spirit. So let's say that G takes a subset A, and what it gives us is the numbers 0.A1, A2, A3, A4, so on and so forth, where we define A sub n to be 0 if n is not in A, and it's 1 if n is in A. So somehow we're like collecting some data on what natural numbers are inside of A. So let's look at some examples here. So let's notice that G of the empty set is equal to just the number 0. That's because nothing is in the empty set. And then what about G of the set of all natural numbers? That's a subset, so we have to know what G does to that as well. Well, that will be equal to 0.1111, so on and so forth. That is a repeating 1. That's because it includes all natural numbers. Let's look at a little different example. Let's say G evaluated at the set 1, 3, 4. So that'll be 0.1011. So it contains 0, does not contain 2, contains 3, contains 4, doesn't contain anything else. So that would be the image of G in this case. Okay, so now let's finish this off by proving that G is injective. And by the construction of G, this will be pretty straightforward. So let's suppose that G of A equals G of B. But then we need to show that A is equal to B. But A and B are subsets, so we need to do that with subset double inclusion. So let's suppose that little n is within A. Okay, but what that tells us is that G of A, if we set it equal to 0.A1, A2, AN, so on and so forth, this nth digit right here is equal to 1. But then if we set G of B equal to the expansion 0.B1, B2 up to Bn, so on and so forth, then this nth digit right here is also 1. That's because these outputs are the same. But if the nth digit of B is 1, that tells us that N is in fact inside of B as well. But that means that A is a subset of B. But then by a completely symmetric argument, we can show that B is a subset of A, so I won't write that down because it's completely symmetric. So in the end, we will have that A and B are equal as sets, which is what we need for G to be injective. And that finishes the proof of these equal cardinalities.
Wow.
Now let's finish this off with some warm-up exercises. So I've got 2 warm-up exercises for you. The first is to show that if A is a subset of B, and we have an injection from B to A, which we'll call G, then A and B have equal cardinalities. Then next, let's prove that n cross n, in other words, n squared, has equal cardinality with n using Cantor-Schroeder-Bernstein. So we did an alternative proof last time, but I think you could do a second kind of nice proof as well using this new theorem, and that would give you practice using this new theorem. And that's a good place to stop.
Oh my fucking god. Thank you so much for not watching this video. If you did, you're stupid.